Section 1. Astrophysics Fundamentals: Light, Stars, Galaxies, and the Expanding Universe. Chapter 1. What is astrophysics? Astrophysics is the branch of science that seeks to understand the fundamental workings of the universe by applying the principles of physics to celestial objects and cosmic phenomena. Unlike observational astronomy, which catalogs and maps what we see in the sky, astrophysics asks deeper questions. It wants to know what stars are made of, why galaxies form the way they do, and how black holes warp the very fabric of space and time. Through this exploration, astrophysics bridges the gap between what we observe and why it exists. At its heart, astrophysics unites the vast expanse of the cosmos with the smallest, most fundamental forces and particles that govern nature. It's an interdisciplinary field, combining insights from classical mechanics, electromagnetism, quantum physics, and relativity to explain everything from the faintest glimmer of a distant star to the immense energies released in supernova explosions. The term astrophysics itself emerged in the mid-19th century as astronomers began to use the tools of spectroscopy to analyze starlight. Before that, astronomy had been largely descriptive, concerned with recording the positions and motions of stars and planets. But when scientists discovered that the spectrum of light from the sun and stars revealed their composition, temperature, and motion, astronomy expanded into a more profound scientific endeavor. This shift marked the birth of astrophysics, the marriage of astronomy and physics into a single, powerful lens through which we explore the universe. One of the central principles in astrophysics is the universality of physical laws. This idea states that the laws we test and confirm on Earth also apply in the most distant reaches of space. When we see the same spectral lines of hydrogen in a distant quasar that we see in a laboratory on Earth, we're observing the same atoms obeying the same rules, despite being separated by billions of light years. This principle allows astrophysicists to make predictions and test theories about phenomena that are far beyond human reach. For instance, we cannot visit the core of a massive star, yet we can use the equations of nuclear fusion, verified in laboratories and particle accelerators, to model how stars burn hydrogen into helium and heavier elements. Similarly, we rely on the well-tested laws of gravity and general relativity to explain the motion of galaxies and the bending of light around massive objects. Another cornerstone of astrophysics is that the information we receive from the cosmos arrives as light in its broadest sense. From radio waves to gamma rays, the entire electromagnetic spectrum carries clues about the universe's history and composition. Optical light, which we see with our eyes, is just a small fraction of this spectrum. Astrophysicists use specialized instruments, telescopes that operate at different wavelengths, to collect and analyze this light. Radio telescopes map cold gas clouds that birth new stars. Infrared telescopes peer through dusty nebulae to glimpse star-forming regions. Ultraviolet and X-ray telescopes reveal the high-energy environments near black holes and neutron stars. Gamma-ray observatories catch brief, violet bursts from the deaths of massive stars or the merging of exotic stellar remnants. By combining these observations, astrophysicists piece together a multi-wavelength portrait of the cosmos. Each portion of the spectrum offers a different perspective, much like viewing a single scene under various lights. This comprehensive view allows scientists to understand the life cycles of stars, the dynamics of galaxies, and even the large-scale structure of the universe. To interpret these observations, astrophysics draws upon several key areas of physics that together form the theoretical backbone of the field. Classical mechanics describes the motion of objects, from orbiting planets to interacting galaxies. Newton's laws of motion and his law of universal gravitation provide the framework for understanding how objects attract and move in response to gravitational forces. Thermodynamics governs the transfer of energy in stars, explaining how heat and radiation flow within celestial bodies. The balance of energy transport determines a star's size, temperature, and lifespan. Electromagnetism, captured in Maxwell's equations, describes how electric and magnetic fields interact, essential for understanding how light propagates through space and how magnetic fields shape cosmic structures. Quantum mechanics explains the behavior of atoms and particles at the smallest scales, crucial for understanding atomic spectra, nuclear reactions in stars, and the behavior of matter under extreme densities. General relativity, developed by Albert Einstein, describes how mass and energy warp the fabric of spacetime itself. This becomes essential when studying massive objects like black holes and the expansion of the universe on cosmological scales. These pillars of physics allow astrophysicists to move beyond mere observation, enabling them to build theoretical models that can be tested against the data collected by telescopes and observatories. One of the remarkable features of astrophysics is its ability to connect the smallest and largest scales of nature. The nuclear reactions that power a star occur within atomic nuclei, while the same star's gravitational influence can shape the orbits of planets light years away. On a grand scale, astrophysics explains how clusters of galaxies, spanning millions of light years, form from tiny fluctuations in the density of matter just after the Big Bang. These fluctuations, imprinted in the cosmic microwave background, grew over billions of years under the pull of gravity to become the vast cosmic web of galaxies we see today. Astrophysical processes also reveal the interplay of the four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. In the cores of stars, the strong force binds protons and neutrons, allowing nuclear fusion to release tremendous energy. Gravity contains this energy, shaping the star's structure. The light emitted by fusion is carried outward by radiation and eventually escapes to space, where it travels for eons to reach our telescopes. A central method in astrophysics is the cycle of observation, theory, and prediction. Observations provide data, images, spectra, timing measurements that capture the state of celestial objects. Theories attempt to explain these observations using the laws of physics to build models that can account for what is seen. For example, the discovery of pulsars, rapidly rotating neutron stars that emit beams of radiation, challenged astrophysicists to develop theories of how magnetic fields and relativistic effects work in such extreme environments. The interplay of observation and theory sharpened our understanding of these dense, exotic objects. Similarly, observations of the motions of galaxies revealed that they rotate faster than visible matter alone would allow. This discrepancy led to the hypothesis of dark matter, an unseen substance that exerts gravitational influence, yet does not emit or absorb light. Decades of observations and theoretical work have confirmed dark matter's role as a dominant component of cosmic structure. Astrophysics remains a vibrant, evolving field. Questions that once seemed unanswerable, like the nature of black holes or the origins of elements, are now explored with precision instruments and powerful supercomputers. Yet new questions constantly emerge. What is the true nature of dark energy, the mysterious force causing the universe's expansion to accelerate? What happens to matter at the heart of a black hole, where gravity overwhelms all other forces? Are there other forms of life in the universe, hidden in the atmospheres of exoplanets or the icy oceans of moons? These mysteries drive the work of astrophysicists, inspiring the design of new observatories and the refinement of theories that seek to unify the known forces of nature. Beyond its scientific scope, astrophysics offers a profound perspective on humanity's place in the cosmos. It reminds us that the atoms in our bodies were forged in the hearts of ancient stars, stellar crucibles that lived and died long before Earth itself took shape. It shows us that we are part of a universe that is dynamic and evolving, governed by laws that link the flickering of a distant quasar to the glow of a candle's flame. This perspective can be both humbling and uplifting, revealing our connection to a vast, interconnected whole. As we gaze into the depths of space, measuring the light from galaxies billions of years old, we are not merely gathering data. We are witnessing a tapestry of existence woven over unimaginable spans of time. In every observation, we find echoes of the same forces that shape our own lives: gravity that binds us to Earth, light that warms our days, and the elements in our blood and bones that once shone in ancient stars. Astrophysics, then, is more than a scientific discipline. It is a gentle reminder that, in the vastness of the cosmos, we find both our origins and our destiny, forever intertwined in a universe that continues to reveal its secrets to those who seek with patience and wonder. Chapter 2: Tools of the Cosmos, Telescopes and Detectors. Astrophysics, like all scientific fields, relies on tools that allow us to observe, measure, and understand the universe. Chief among these are telescopes and detectors, instruments that transform the faintest glimmers of distant stars into data that can be analyzed and interpreted. These devices are the eyes of astrophysics, opening windows to the vastness of space that would otherwise remain forever beyond our reach. A telescope, at its most basic, is a device that collects light. Unlike the human eye, which has a limited aperture and can only gather so much light, telescopes have much larger apertures that collect far more light, revealing fainter and more distant objects. By capturing more light, a telescope can also reveal finer details, turning tiny points of light into complex structures: spiral galaxies, star clusters, nebulae. This ability to gather and focus light makes telescopes essential for studying the cosmos in all its rich complexity. The principle of focusing light can be achieved through two main designs: lenses and mirrors. Refracting telescopes use lenses to bend and concentrate light, much like a magnifying glass focuses sunlight to a point. Reflecting telescopes, on the other hand, use curved mirrors to gather and redirect light to a focal point. Both designs have their advantages and limitations, but mirrors tend to be favored for large telescopes because they can be made much larger and lighter than lenses. The most powerful ground-based telescopes today rely on mirrors that span many meters in diameter, carefully polished and precisely aligned to collect light from the farthest reaches of the universe. Detectors are the other half of the equation. While telescopes collect and focus light, detectors measure and record it. In the early days of astronomy, this role was filled by the human eye, or photographic plates that captured the light as chemical reactions on glass. Today, electronic detectors, such as charge-coupled devices, CCDs, are used to convert light into digital signals that can be analyzed with computers. These detectors are incredibly sensitive, able to detect single photons of light, and they provide a level of precision and consistency that was once unimaginable. Beyond visible light, telescopes and detectors are designed to capture the entire electromagnetic spectrum. Each region of the spectrum, radio, infrared, ultraviolet, X-ray, gamma ray, requires different materials and designs to collect and measure its unique properties. Radio telescopes, for example, use large parabolic dishes to gather long wavelength radio waves, while X-ray telescopes rely on special mirrors that can reflect high-energy photons at shallow angles. Each of these instruments reveals a different aspect of the cosmos, offering insights that would be hidden if we relied solely on the light our eyes can see. Ground-based observatories are often built in remote, high-altitude locations to minimize the blurring effects of Earth's atmosphere. The thin, dry air reduces the distortion of starlight and allows for clearer, sharper images. In some cases, astronomers use adaptive optics, systems that adjust the telescope's optics in real time to correct for atmospheric turbulence. These corrections help ground-based telescopes approach the clarity of images taken from space. Space-based telescopes avoid the atmosphere altogether by orbiting above it. Instruments like the Hubble Space Telescope and the James Webb Space Telescope have provided views of the cosmos with unprecedented clarity, free from the shimmering distortion of Earth's air. Space telescopes can also access wavelengths of light that are absorbed by the atmosphere and never reach the ground, such as ultraviolet and X-rays. These observations open up entirely new windows on the universe, revealing phenomena that would otherwise remain hidden from view. Calibration is a crucial part of using telescopes and detectors. Even the best instruments can introduce subtle distortions or biases in the data they collect. Astrophysicists use carefully measured light sources and known standards to calibrate their instruments, ensuring that the data reflect the true properties of the light from celestial objects. This meticulous work allows for meaningful comparisons between observations and theoretical predictions, helping to refine our models of the universe. The data gathered by telescopes and detectors are often stored in massive archives, forming a collective memory of the universe as seen from Earth. These archives contain decades of observations, from the first images of distant galaxies to the faint signals of cosmic microwave background radiation. Astrophysicists sift through these vast repositories to uncover patterns, track changes, and test new theories. The accumulated data provide a foundation for understanding how the universe evolves over time. Modern telescopes and detectors are also designed to work together in networks and arrays. Radio telescopes are often linked in interferometric arrays that combine signals from widely separated antennas, creating images with the resolution of a telescope as large as the distance between them. Optical and infrared telescopes participate in time-domain surveys, scanning large areas of the sky repeatedly to detect transient events like supernova and variable stars. These collaborative efforts allow astrophysicists to observe the dynamic nature of the cosmos and to catch brief, energetic phenomena that might otherwise be missed. The interplay of telescopes and detectors is not limited to passive observation. Some instruments are designed to actively probe the universe, sending out signals and measuring their reflections or responses. Radar astronomy, for instance, uses radio waves to map the surfaces of planets and asteroids. Laser ranging can measure the distance to the moon with astonishing precision. These active techniques complement the passive collection of light, providing a fuller picture of celestial objects and their behaviors. As technology advances, so too do the capabilities of telescopes and detectors. New materials, improved electronics, and sophisticated data analysis techniques continually push the boundaries of what can be observed and measured. Future telescopes will be able to image exoplanets directly, detect the faint glow of the first galaxies, and perhaps even capture the echoes of gravitational waves from the birth of the universe. This ongoing journey of building better telescopes and more sensitive detectors is driven not only by a scientific desire to test theories and gather data, but also by an enduring curiosity about what lies beyond our familiar world. New instruments are designed with careful consideration of how light interacts with matter, how detectors can be cooled to reduce noise, and how complex data can be analyzed to reveal hidden structures in the sky. In modern astrophysics, the interplay between telescope design and detector technology is a marvel of precision and innovation. Scientists meticulously choose coatings for mirrors and lenses that maximize light collection while minimizing distortion. They develop detectors that can distinguish between the faint glow of a distant galaxy and the background noise of the cosmos. Every advancement brings us closer to seeing deeper into the universe and to answering questions that once seemed beyond our reach. Perhaps one of the most profound aspects of this work is the sheer scale of it all. Telescopes and detectors, in their quiet watchfulness, are constantly gathering light that has traveled across billions of years. That light, bent and scattered by dust and gas, carries the faintest whispers of the universe's past. By capturing it, we are not just looking outward, we are looking back in time, tracing the evolution of galaxies, stars, and cosmic structures from their birth to the present. In the end, telescopes and detectors are more than just tools. They are extensions of our senses, amplifying our ability to perceive and understand the vastness around us. They allow us to see beyond the limits of our own eyes, to measure forces and energies that we can barely comprehend. Through them, we transform ancient starlight into knowledge, and fleeting glimpses of the sky into a coherent narrative of the cosmos. The observatories themselves, whether nestled in remote mountain ranges or floating in the void of space, stand as monuments to human ambition and creativity. These facilities, equipped with their meticulously crafted mirrors and detectors, work tirelessly to capture fleeting photons that have traveled unimaginable distances. Each photon, no matter how faint, carries information that adds another brushstroke to our ever-expanding portrait of the cosmos. The data collected by telescopes and detectors do not remain isolated. They are shared across networks of scientists, integrated into broader studies, and compared with theoretical models that stretch the boundaries of human understanding. This collaboration, spanning continents and cultures, represents a shared journey to unravel the universe's secrets. In this shared quest, instruments become more than machines. They are silent witnesses to the interplay of light and matter, echoes of the fundamental forces that bind the universe together. As each new telescope begins its vigil, and as each new detector records its first photons, there's a sense of anticipation that pulses through the scientific community. What hidden galaxies will emerge from the darkness? What transient phenomena will be caught in the moment of their fleeting brilliance? These questions propel astrophysicists to push the limits of technology, to refine the delicate balance of optics and electronics that bring distant worlds into focus. In these quiet, patient pursuits, there is a subtle poetry. The cold precision of the detectors, the smooth sweep of the telescope across the sky, the hush of a control room as the first images appear. These are the moments when science and wonder converge. It is in this union that the work of astrophysics becomes more than data and equations. It becomes a meditation on our place in the universe, a reminder that even as we measure and record, we are also participants in the unfolding story of existence. For in the glow of distant galaxies, in the quiet hum of an instrument waiting for starlight, there lies a gentle reminder that the universe is not just a collection of objects to be cataloged and analyzed, but a vast and intricate dance of forces and energies playing out across time and space. And in the soft glow of each observation, there is a call to look deeper, to wonder at the infinite, and to find within it the faint but unwavering echo of our own curiosity. Chapter 3. The Nature of Light, Spectra, and What They Reveal. Light is the messenger of the cosmos, carrying with it the stories of distant worlds and ancient events. In astrophysics, light is more than just a source of illumination. It is the primary tool for understanding the universe. Each photon that reaches our detectors has traveled vast distances, and along its journey it has been shaped by the environments it passed through. The study of this light, its colors, its intensity, and the way it shifts, is at the heart of astrophysics. This process is known as spectroscopy. When we examine the light from a star or galaxy, we are not merely seeing a glow in the sky. We are witnessing a complex interplay of physics. Light is an electromagnetic wave, oscillating electric and magnetic fields that travel through the vacuum of space. As it moves, it interacts with matter, revealing the properties of whatever it encounters. By studying these interactions, we can uncover the composition, temperature, motion, and structure of objects that are otherwise inaccessible. Spectroscopy begins with the realization that light can be spread out into a spectrum, much like sunlight passing through a prism to form a rainbow. Each color in this spectrum corresponds to a different wavelength, and each wavelength carries information about the source of the light. A spectrum is more than just a beautiful array of colors. It is a scientific fingerprint that encodes the secrets of the universe. In astrophysics, spectra reveal three fundamental types: continuous, emission, and absorption. A continuous spectrum shows a smooth, unbroken range of colors produced by hot, dense objects like stars or incandescent solids. Emission spectra, on the other hand, consist of bright lines at specific wavelengths, emitted by atoms and molecules as they release energy. Absorption spectra show dark lines superimposed on a continuous background, created when cooler gas absorbs specific wavelengths of light from a hotter source behind it. The dark lines in an absorption spectrum, for example, are signatures of the elements present in a star's atmosphere. Hydrogen, helium, sodium, and many other elements each absorb light at characteristic wavelengths, leaving behind distinct fingerprints that can be used to identify them. By measuring these lines, astrophysicists can determine the chemical composition of stars and galaxies, even when they are light years away. This knowledge is essential for understanding the life cycles of stars, the formation of planets, and the enrichment of the cosmos with the elements necessary for life. Beyond composition, spectra also reveal the temperatures of celestial objects. The color of a star's light depends on its surface temperature, with hotter stars appearing bluer and cooler stars redder. By analyzing the shape and intensity of a spectrum, astrophysicists can calculate the temperature of a star's outer layers with remarkable precision. This information helps us map the stages of stellar evolution and understand the balance of energy within these distant suns. Spectroscopy also allows us to measure motion in the universe through the Doppler effect. When an object moves toward us, the light it emits is compressed to shorter wavelengths, shifting toward the blue end of the spectrum. Conversely, when an object moves away, the light is stretched to longer wavelengths, shifting toward the red. By measuring these shifts, astrophysicists can determine the speeds at which stars and galaxies are moving, unveiling the dynamic nature of the cosmos. The use of spectroscopy extends beyond individual stars and galaxies. It allows us to probe the vast spaces in between, where clouds of gas and dust drift through the void. The light passing through these clouds carries the imprints of their presence, revealing their density, temperature, and even their chemical makeup. In this way, spectroscopy acts as a cosmic probe, mapping the unseen structures that shape the evolution of galaxies and the flow of matter in the universe. Each spectrum is a story, written in light and waiting to be read. The patterns we see are not static. They change over time as stars evolve, as galaxies collide, and as the universe itself expands. By collecting and comparing spectra from different times and places, astrophysicists can reconstruct the history of the cosmos, piece by piece. This ongoing work requires meticulous observation, careful calibration, and the continual refinement of theories to match what we see. In modern astrophysics, spectroscopy is a field of both subtlety and power. The instruments that capture these spectra must be finely tuned, capable of detecting the faintest traces of light from across the universe. They must be cooled to near absolute zero to reduce noise and sharpen the signal, and they must be calibrated against known standards to ensure accuracy. This meticulous work is a testament to the precision of modern science and the dedication of those who seek to understand the cosmos. Yet, for all its precision, there is something almost poetic in the way spectra reveal the universe. Each line, each curve in the spectrum, is a direct connection to a distant object, a bridge across the gulf of space and time. It is a reminder that the universe is not silent, It speaks to us in the language of light, a language that we are only just beginning to fully understand. Spectroscopy has also allowed scientists to identify molecules in distant environments, opening a window to the chemistry of the cosmos. In the atmospheres of cool stars and giant planets, molecules leave distinct spectral features that reveal the presence of water vapor, carbon dioxide, methane, and other compounds. By analyzing these subtle molecular signatures, astrophysicists can infer the physical and chemical conditions in alien worlds, drawing connections between the familiar processes on Earth and those at work in the distant reaches of the galaxy. As we look beyond our solar system, spectroscopy becomes an essential tool for the study of exoplanets. When a planet passes in front of its star, some of the starlight filters through its atmosphere, imprinting a faint signature in the spectrum that tells us about the planet's gases. In this way, we can detect traces of elements and molecules that hint at possible climates and perhaps even the conditions for life. These observations demand extreme precision, for the signals are often faint and buried in the glow of the parent star. Yet with careful measurement and patient analysis, these tiny imprints reveal entire worlds otherwise lost to the darkness of space. Spectroscopy also plays a crucial role in measuring the expansion of the universe itself. As galaxies recede from us, their light is stretched by the expansion of space, shifting spectral lines to longer, redder wavelengths. This cosmological redshift encodes information about the rate of expansion and the age of the universe, allowing us to trace the evolution of cosmic structures over billions of years. By studying these shifts in the spectra of distant galaxies and quasars, astrophysicists map the large-scale structure of the cosmos and test our deepest theories about its origin and fate. The craft of spectroscopy is as much an art as it is a science. Each spectrum is carefully extracted from observations that may take hours or even days to collect, requiring instruments to be precisely aligned and detectors cooled to minimize noise. Once captured, the spectrum must be calibrated and corrected for the distortions introduced by instruments and the atmosphere. This painstaking work requires not only technical skill, but a deep understanding of the subtle ways in which light can be altered and obscured on its journey to our instruments. In laboratories and observatories around the world, scientists work in quiet rooms, bathed in the glow of computer screens, displaying the delicate traces of spectra. They adjust the data, compare it to models, and search for faint features that might reveal a new star, a distant quasar, or the thin atmosphere of an exoplanet. Each spectrum is a dialogue with the universe, a conversation carried out in the language of light. As technology advances, the detail and precision of spectra continue to improve. Instruments aboard spacecraft and observatories in orbit gather light that has never touched Earth's atmosphere, preserving its purity and extending our reach into the cosmos. Ground-based telescopes, equipped with adaptive optics and ever more sophisticated spectrographs, reveal features in the spectra that were once hidden by the blurring of our air. In this union of precision and passion, scientists and engineers push the limits of what can be seen and measured. In these faint lines and subtle curves, there is a story of creation and destruction, of calm and violence, of birth and death on a cosmic scale. The spectra of supernovae show the final moments of massive stars, their light echoing across the galaxy as they seed the cosmos with heavy elements. The spectra of active galactic nuclei reveal the voracious appetites of supermassive black holes, devouring matter and releasing torrents of energy. Even the soft glow of the interstellar medium, captured in the faint emission lines of ionized gas, tells of the slow dance of matter as it cycles through generations of stars. To the patient eye, spectra offer more than just data. They offer a glimpse into the timeless processes that shape the universe, processes that unfold over millions or even billions of years. In the quiet light of these distant sources, there is an echo of the vast scales of time and space that define our cosmos. Each photon, each spectral line is a message from a time and place far removed from our own, yet bound by the same laws that govern the world around us. In the end, the study of light and spectra in astrophysics is a testament to human curiosity and ingenuity. We have taken the simplest of tools, a prism splitting sunlight, and turned it into a means to read the deepest secrets of the universe. Through patient observation and careful analysis, we have learned to see beyond what is visible, to hear the whispers of ancient stars, and to trace the paths of galaxies across the ages. And in those final moments of contemplation, when the lines of a spectrum fade into the silence of the night, there is a soft, persistent echo, a reminder that in seeking to understand the light of distant worlds, we also illuminate the wonder within ourselves. It is a gentle hum that bridges the cold precision of science with the warmth of human curiosity, whispering that even in the darkness of space, there is always light to guide us. Chapter 4. The Life Cycles of Stars, from Birth to Remnants. The life cycle of a star is one of the most fundamental narratives in astrophysics, weaving together the interplay of gravity, pressure, nuclear fusion, and the cosmic alchemy that creates the elements of the universe. Stars are born from vast clouds of gas and dust known as molecular clouds that exist throughout galaxies. These clouds, cold and dense, provide the raw materials for stellar formation. Within them, tiny fluctuations in density can trigger a collapse, drawing more and more material inward. As a region within a molecular cloud collapses, it forms a dense core that grows hotter and denser at its center. The gravitational contraction converts potential energy into heat, and as the temperature rises, the cloud begins to glow faintly in the infrared, marking the birth of a protostar. The protostar stage is a time of gathering and growth, as material from the surrounding cloud continues to fall inward, feeding the growing mass of the young star. The formation of a star reaches a turning point when the core temperature becomes high enough for nuclear fusion to ignite. Hydrogen atoms begin to fuse into helium, releasing energy that counteracts the pull of gravity. The star achieves a delicate balance between the inward force of gravity and the outward pressure from fusion, settling into the main sequence phase of its life. This equilibrium can endure for billions of years, depending on the star's mass, as it steadily converts hydrogen into helium and shines with a steady light. During its time on the main sequence, a star's properties are determined largely by its mass. More massive stars burn hotter and brighter, consuming their hydrogen fuel at a much faster rate. They live short, intense lives compared to smaller stars, which can shine in steady light for billions of years. The Sun, a medium-sized star, will remain in this phase for roughly 10 billion years, maintaining the balance that makes life on Earth possible. But even the main sequence is not a permanent state. As hydrogen in the core is depleted, the balance begins to shift. The core contracts under gravity, heating up as it does, while the outer layers of the star expand and cool. This expansion marks the transition to the red giant phase for stars like the Sun, or the more luminous supergiant phase for more massive stars. The star's outer envelope swells outward, its light turning redder and its shape more diffuse. Within the core, the increasing temperature and pressure allow helium to fuse into heavier elements like carbon and oxygen. This stage of helium burning is shorter than the long reign of hydrogen fusion, and once the helium is exhausted, the star faces another crossroads. Lower mass stars like the Sun do not have the gravitational heft to ignite further fusion stages. Instead, they shed their outer layers into space, creating a planetary nebula, a delicate, glowing shell of gas that surrounds the dense, cooling core. This exposed core becomes a white dwarf, a stellar ember glowing with residual heat. White dwarfs no longer produce energy through fusion, but they can persist for billions of years as they slowly cool and fade. They represent the final chapter in the life of a medium-sized star, a quiet coda to the vibrant symphony of nuclear fusion that once powered them. For the most massive stars, the story is more dramatic. Their cores can reach temperatures and pressures high enough to fuse elements beyond carbon and oxygen, building up layers of heavier elements like silicon, sulfur, and eventually iron. But fusion of iron does not release energy, it requires energy. When an iron core grows too massive, it can no longer support itself against gravity. In a matter of seconds, the core collapses in a catastrophic implosion, triggering one of the most powerful events in the universe, a supernova explosion. The outer layers of the star are hurled into space in an immense explosion, enriching the surrounding interstellar medium with heavy elements forged in the dying moments of the star. This process seeds the galaxy with the raw materials for new stars, planets, and life itself. What remains of the core depends on the mass of the original star. If it is below a certain threshold, it becomes a neutron star, a dense object composed almost entirely of neutrons, held together by gravity and the strong nuclear forces at the heart of matter. If the collapsing core is massive enough, no known force can stop its inward plunge. The core becomes a black hole, a region of space-time where gravity is so strong that not even light can escape. Black holes are among the most enigmatic objects in the cosmos, their presence inferred from the way they warp the fabric of space and influence the motion of nearby stars and gas. The life cycles of stars thus connect the smallest scales of nuclear interactions with the largest scales of galactic evolution. They are engines of creation and destruction, forging the elements in their cores and dispersing them in cosmic winds and violent explosions. The light of stars illuminates the history of the universe, carrying the signatures of these cycles across billions of years and countless light-years of space. The study of stellar life cycles is not merely an academic pursuit. It is a way of understanding the profound connections between the life of a star and the matter that makes up planets, oceans, and living beings. Every atom of carbon in our bodies, every molecule of oxygen we breathe was forged in the heart of a star that lived and died long before our solar system was born. This cosmic recycling links us to the distant past and to the ongoing processes that continue to shape the universe. Stars, in their majestic arcs of birth and death, tell a story that stretches beyond the confines of any single lifetime. They are not static points of light, but dynamic laboratories where matter is transformed, energies are released, and the building blocks of worlds are forged. Every stage of a star's life, every subtle shift in temperature and pressure, reveals a new chapter in this cosmic narrative, a new layer of complexity that reflects the ceaseless interplay of fundamental forces. The processes that govern a star's life cycle are driven by the delicate balance between gravity and the pressure of radiation and heat. In the early stages, gravity is the sculptor, shaping the chaotic gas clouds into dense cores and igniting the nuclear fires that bring light to the darkness. Over time, however, the balance begins to tilt. The fuel that powers the star's brilliance is consumed, the weight of gravity pressing ever more insistently inward. The star responds by reshaping itself, each new phase a testament to the unyielding laws of physics and the inexhaustible creativity of the cosmos. These changes are not abrupt, but occur over timescales that dwarf human history. A red giant's slow inflation, the collapse of a supergiant's core, the quiet fading of a white dwarf, each unfolds over millennia or longer, processes so gradual that they seem almost eternal. Yet in these slow dances of matter and energy, there is constant motion, a continual reshaping of the universe that echoes the slow cycles of life and death on Earth. As stars evolve, they become crucibles for the creation of the elements that seed the cosmos with diversity and complexity. In the cores of massive stars, fusion reactions produce not just the light that illuminates the night sky, but the very atoms that make up planets, oceans, and living cells. The oxygen we breathe and the calcium in our bones were once forged in the hearts of stars, carried into space by supernovae and woven into new worlds by the quiet accretion of dust and gas. In studying these life cycles, astrophysicists are not merely cataloging distant phenomena. They are tracing the origins of everything familiar to us, finding in the death throes of ancient stars the seeds of future worlds. The data gathered by telescopes and instruments, spectra that record the light of stars, images that reveal their shapes and motions, are pieces of a puzzle that, when assembled, reveal the history of matter itself. The journey from a cool, dark cloud of gas to a shining star, and finally to a quiet remnant, is a journey that every star must take. Yet each path is unique, shaped by the star's mass, its environment, and the subtle currents of interstellar space. Even in the final stages, as a white dwarf cools or a neutron star spins down to silence, there are variations and subtleties that keep the story endlessly rich. These differences are not mere curiosities. They are clues to the processes that govern the cosmos, hints at the hidden laws that tie together the smallest scales of the atomic world and the grandest reaches of the galaxies. In these final remnants, there is a quiet dignity that belies the violence of their pasts. A white dwarf glows softly with the embers of a star's final light. A neutron star, dense beyond comprehension, spins with the momentum of a collapsed core, sending out pulses of radiation like the heartbeat of a dying giant. A black hole, shrouded in the darkness of its own gravity, warps the space around it in silent testimony to the power of collapse. These are the endpoints of stellar life, but they are also beginnings. The elements scattered by supernovae enrich the clouds of gas that will become new stars. The gravity of a black hole can gather matter into luminous disks that blaze with energy, shaping the cores of galaxies. In the quiet intervals between these cataclysms, the universe grows new structures from the debris of the old, each cycle building upon the last in a ceaseless dance of creation. Astrophysicists peer into these processes with instruments that can see far beyond the limits of human sight. They study the subtle shifts of spectral lines that reveal the fusion within stars, the ripples of gravitational waves that hint at the collapse of massive cores. In the data they gather, they find the signatures of ancient processes still at work today, shaping the future of the cosmos in ways both familiar and strange. And in this patient, methodical work, there is an echo of something deeper. Each measurement is an act of curiosity. Each calculation, a step in a journey that has no end. The story of the stars is the story of a universe in motion, of forces and energies that build and rebuild the cosmos in cycles that stretch across time and space. It is a story that began long before humanity learned to gaze at the night sky in wonder, and it will continue long after our brief moment has passed. Yet even in this grand scale, there is a thread of connection that runs through it all. The atoms that burn in the hearts of stars are the same atoms that flow through our bodies. The light that travels from a distant supernova is the same light that warms our skin on a summer day. In every spectrum, every image, there is a reminder that we are not separate from this cosmic dance, but participants in it, shaped by the same forces and bound by the same laws. In the quiet glow of a white dwarf, in the fierce brilliance of a supernova, in the cold gravity of a black hole, there is a lesson that transcends the numbers and equations. It is a lesson in patience and in perspective, a gentle reminder that even the mightiest stars must yield to the passage of time. And in that yielding, they give rise to new beginnings, to new possibilities written in the language of light and gravity. For in the end, the life cycles of stars are more than just an astrophysical phenomenon. They are a mirror of the cycles of life that unfold around us and within us, a testament to the quiet power of change and the enduring strength of connection. In their story, we find both our origins and our destiny, woven together in the silent, ceaseless symphony of the cosmos. Chapter 5. The Life Cycles of Galaxies, Growth and Transformation. Galaxies, those vast islands of stars and gas scattered throughout the universe, are not static structures. They are dynamic, evolving entities shaped by the forces of gravity, the birth and death of stars, and the subtle interactions that unfold across billions of years. The life cycles of galaxies are a story of growth and transformation, a narrative of change written in the light of countless stars. At the heart of every galaxy lies a collection of matter that binds together through gravity. Stars, gas, dust, and dark matter all contribute to the gravitational well that defines the galaxy's shape and structure. Yet, even within this gravitational binding, galaxies are in constant motion. Stars orbit the center, gas clouds drift and collide, and entire spiral arms can sweep slowly around the core, creating the graceful patterns we see in the night sky. Galaxies begin their lives as small, irregular clumps of gas and stars. Over time, they grow and change through the process of accretion, gathering material from their surroundings. This growth can occur slowly as gas from the intergalactic medium falls inward, feeding the birth of new stars. In other cases, galaxies merge with one another, colliding and combining their masses in spectacular cosmic events. These mergers can transform the structure of galaxies, creating new shapes and triggering waves of star formation that light up the universe. As galaxies evolve, the forces that shape them operate on scales that stretch the imagination. The interactions of dark matter, though invisible to our instruments, sculpt the gravitational scaffolding that defines a galaxy's extent. It is this unseen framework that guides the motions of stars and gas, creating the potential wells where matter can gather and new stars can ignite. The birth of stars within a galaxy is a continuous process. In the dense molecular clouds that drift through spiral arms or nestle in irregular regions, gravity slowly coaxes gas into new generations of stars. These young stars often form in clusters, their light brightening the galactic disk and driving the cycles of energy that keep the interstellar medium alive with motion. Yet even as new stars emerge, older ones drift along their orbital paths, gradually aging and changing the composition of the galaxy itself. The death of stars also leaves its mark. Supernova explosions enrich the surrounding gas with heavy elements, while the gentle winds of aging red giants return material to the galactic medium. This ongoing exchange of matter, driven by stellar processes, seeds the galaxy with the ingredients for future generations of stars and planets. In this quiet recycling of gas and dust, galaxies continually reshape themselves, weaving new tapestries of light and matter with each cycle. Over time, galaxies can transform dramatically. The mergers of galaxies, while violent on a cosmic scale, are essential to their growth and evolution. When two galaxies collide, their stars pass through one another like ghosts, rarely colliding directly. Yet their gravitational fields tug and warp the shapes of their disks, creating streams of stars and vast tidal tails that arc outward like cosmic sculptures. In the heart of such a merger, gas can be driven inward, feeding bursts of star formation that light up the galaxy in waves of brilliant activity. These interactions do more than rearrange the visible matter. They can awaken the central black holes that lie hidden in the cores of many galaxies. As gas and dust funnel inward during a merger, these supermassive black holes can flare to life, consuming matter and releasing enormous amounts of energy. These active galactic nuclei, or quasars, can outshine the entire galaxy around them for a brief moment in cosmic time, their radiation blazing across the universe and reshaping the gas that surrounds them. Not all galaxies follow the same path. Some grow steadily, building up their disks over billions of years without major mergers to disrupt them. Others form elliptical shapes, their ordered rotations lost in the random motions of countless stars, a legacy of past collisions and the gravitational mixing of their orbits. Each galaxy carries within it the history of these interactions, an imprint of the forces that have shaped its evolution. Astronomers study these processes using observations across the electromagnetic spectrum. Radio waves reveal the cool gas that forms the raw material for future stars. Infrared light shows the hidden glow of dusty star-forming regions. X-rays trace the violent interactions of hot gas, while optical telescopes capture the graceful arcs of spiral arms and the shimmering glow of old stellar populations. Together, these observations allow scientists to piece together the life stories of galaxies, from their first stirrings of star formation to the quiet grandeur of ancient structures that drift slowly through the cosmic web. The environments in which galaxies live also play a role in their evolution. Galaxies in dense clusters feel the gravitational pull of their neighbors, their gas stripped away by the harsh winds of the intracluster medium. Others drift in relative isolation, their growth shaped more by slow accretion than by violent mergers. These differences create the diversity of galactic forms we see in the universe today. From the elegant spirals that whirl in quiet solitude to the massive ellipticals that dominate the crowded hearts of clusters. Galaxies are not static in their transformations. They breathe in the flow of gas that surrounds them, converting it into new generations of stars, and exhale it back in the form of supernova-driven winds and jets from active nuclei. These outflows can carry gas out of the galactic disk, shaping the surrounding intergalactic medium and feeding back into the broader cosmic ecosystem. In this interplay of inflows and outflows, galaxies are both sculptors and subjects, constantly remaking themselves and their surroundings in a quiet, patient dance. At the largest scales, galaxies themselves are not isolated islands, but are woven into the cosmic web, a vast network of filaments and voids that stretches across the observable universe. Galaxies gather along these filaments, where gravity pulls matter together in streams that feed their growth. In the quiet darkness between the filaments, voids expand, shaping the cosmic landscape like the empty spaces between brushstrokes on a canvas. As galaxies continue to evolve, their fates are intertwined with the surrounding environment. Some galaxies experience a gradual loss of gas, a gentle fading as their reservoirs of star-forming material become depleted. In this quiet senescence, galaxies grow old gracefully, their bright regions of star formation slowly giving way to the cooler glow of older stars. Others, however, find themselves in more tumultuous surroundings, where interactions and mergers can spark intense periods of activity. These periods of heightened star formation, known as starbursts, can briefly transform a galaxy's appearance. The inflow of gas fuels a frenzy of star birth, brightening the galaxy and creating powerful winds that blow material out into the intergalactic medium. These winds can quench the very process they ignite, carrying away the fuel for future stars and reshaping the galaxy's future evolution. In this balance of growth and regulation, galaxies find a kind of equilibrium, a cycle of creation and dispersal that echoes the processes seen in individual stars. The study of these transformations is a window into the nature of cosmic time. Unlike the brief human lifespan, the changes that sculpt galaxies unfold over billions of years. To glimpse this slow dance requires patience and the ability to see beyond the present moment. Astronomers turn their instruments to the most distant reaches of space, capturing the light of galaxies as they appeared in earlier epochs. In these ancient signals, they find the threads that connect the universe's past to its present. Each observation is a step along this journey of understanding. The careful measurement of light, the precise mapping of structure. These are the tools by which scientists unravel the history of galaxies. And in that history, they find clues to the broader questions that animate all of astrophysics: how matter organizes itself, how structure emerges from chaos, and how the seeds of complexity are sown in the vast fields of interstellar and intergalactic space. The light of galaxies carries within it the memory of these processes. In the shifting colors of a spectrum, in the subtle shapes of a spiral arm or the smooth glow of an elliptical, there are stories of birth and death, of collisions and calm intervals. Each galaxy is both an individual and a part of a larger whole, its life shaped by the collective behavior of matter and energy on scales that defy ordinary experience. This interplay of forces is not just a scientific curiosity. It speaks to a deeper harmony that underlies the universe, a quiet order that emerges from the complexity of countless interactions. In the shapes of galaxies and the patterns of their light, there is an echo of the same principles that guide the evolution of stars and the formation of planets. It is a reminder that in the grand tapestry of existence, every structure, no matter how vast, is connected to the smallest processes that shape the cosmos. For those who seek to understand these cycles, there is a reward that transcends the data and the models. It is the gentle wonder that comes from seeing the universe as a living, changing whole, a system in which growth and transformation are woven into the very fabric of space and time. It is a sense of belonging to something larger, a quiet affirmation that the same forces that sculpt galaxies also touch our own lives in subtle, profound ways. As the study of galaxies advances, new tools and observatories promise to extend our reach even further. Telescopes that peer deeper into space and instruments that capture the faintest whispers of light will reveal details of galactic evolution that were once beyond our grasp. Each new image, each new spectrum, will add another brushstroke to the portrait of the cosmos, filling in the details of a story that continues to unfold. In the quiet light of a distant galaxy, in the faint arcs of stars that trace its edges, there is a reminder that the universe is always in motion. It grows, it changes, and it carries forward the echoes of every cycle that has come before. And in those echoes, in the silent glow of starlight across the darkness of space, there is a promise that even as we measure and map, we are also a part of this ongoing dance. For in the end, the life cycles of galaxies are more than an academic puzzle. They are a testament to the power of connection, to the ways in which gravity and light weave the universe into a single, coherent whole. In the swirling arms of a spiral galaxy, in the gentle fade of an aging elliptical, we find not just distant objects of study, but reflections of the enduring processes that shape us all. And in those reflections, we are reminded that even in the vastness of space, the story of the cosmos is also the story of us. Chapter 6. The Power of Gravity, From Orbits to Collisions. Gravity is the force that sculpts the universe, shaping the paths of planets, the structures of galaxies, and the vast tapestry of cosmic evolution. It is the quiet, invisible hand that binds everything together, from the orbits of the smallest moons to the majestic arcs of galaxy clusters stretching across the cosmos. In astrophysics, understanding gravity is essential to explaining the motion of celestial bodies and the grand architecture of the universe itself. Gravity emerges from mass, drawing objects together across empty space. It pulls at the stars within galaxies, holding them in sweeping orbits that span thousands of light years. It binds planets to their stars, creating the cycles of seasons and the rhythms of day and night that mark the passage of time. It is the engine that drives the collapse of gas clouds to form new stars, the sculptor of planetary systems, heat and the keeper of cosmic order. From the smallest scales to the largest, gravity dictates how matter organizes itself. In the solar system, gravity is the choreographer of planetary motions. It guides the Earth in its yearly journey around the sun, holds the moon in its monthly dance across the sky, and governs the paths of comets and asteroids that wander through the darkness. These motions are not static. They shift and change, each orbit a delicate balance between inertia and the pull of gravity's invisible embrace. Beyond the familiar neighborhood of the solar system, gravity exerts its power on grander scales. In the hearts of galaxies, it gathers matter into swirling disks of stars and gas, giving rise to the elegant spirals that arc across the night sky. In massive galaxy clusters, gravity pulls hundreds or thousands of galaxies into vast congregations, shaping the cosmic landscape with the slow, steady hand of attraction. These colossal structures are born of gravity's patient work, built up over billions of years of gentle pulls and quiet growth. Gravity also has the power to warp the very fabric of space and time. Einstein's general theory of relativity revealed that gravity is not merely a force acting at a distance, but a manifestation of spacetime curvature. Massive objects bend the geometry around them, altering the paths of light and the motions of bodies in their vicinity. This bending of light by gravity, known as gravitational lensing, allows astronomers to peer deeper into the universe by magnifying distant galaxies and revealing the shapes of structures otherwise hidden from view. The subtle warping of spacetime can be seen in the orbits of stars near massive objects. In the centers of galaxies, stars dance around supermassive black holes, their paths curving under the influence of gravity's deepest wells. Observing these orbits reveals the presence of black holes too dark to see directly, their gravity betraying their existence as it shapes the dance of the stars around them. Gravity's influence extends beyond shaping orbits and clusters. It is also the driver of collisions, the silent force that pulls galaxies together and sends stars plunging toward one another. When galaxies merge, gravity choreographs a complex dance of interactions, drawing streams of stars into graceful arcs and hurling others into new orbits. These cosmic collisions are slow, stately affairs, unfolding over hundreds of millions of years. Yet their effects are profound, reshaping galaxies and triggering bursts of star formation that light up the universe. In smaller scales, gravity sculpts the structures of planetary systems. The early solar system was a swirling disk of gas and dust, where gravity gathered material into clumps that grew into planets and moons. The same process unfolds around distant stars, as protoplanetary disks become the nurseries of new worlds. In these quiet cradles of gravity, matter coalesces and organizes, guided by the same invisible force that holds entire galaxies together. The beauty of gravity's power lies in its universality. It acts on all matter, regardless of its form or location, weaving together the cosmic fabric into patterns of motion and structure. In the delicate balance of forces that shape an orbit, in the grand collisions that birth new galaxies, there is a quiet order that emerges from gravity's patient pull. Astronomers measure gravity's effects with instruments of precision and sensitivity. They chart the motions of planets and moons, trace the paths of stars in distant galaxies, and watch for the subtle bending of light that reveals the presence of massive structures. These observations are windows into the workings of gravity, revealing its role as the silent architect of the cosmos. In the slow arcs of planets around the sun, in the majestic spirals of galaxies, in the deep wells of gravity that swallow even light, there is a continuity of form and motion that echoes across the universe. It is a language of curves and orbits, of gentle pulls and violent collisions, written in the quiet movements of matter and the patient shaping of time itself. Gravity is also the silent witness to the most energetic events in the universe. When massive stars exhaust their nuclear fuel and collapse, it is gravity that drives the formation of neutron stars and black holes. In these final acts of stellar evolution, gravity reveals its dual nature. It is both the creator of stability and the agent of transformation. The collapse of matter under gravity's relentless pull is a moment of violence and birth, creating some of the most extreme objects known. These objects, born of gravity's ultimate embrace, become laboratories for the testing of our deepest theories. Black holes, in particular, challenge our understanding of space and time. Their gravity is so strong that it creates a region from which nothing can escape, not even light. Yet it is also in these places that we see the unity of physics, where the elegant equations of relativity meet the strange probabilities of quantum mechanics. In these cosmic mysteries, gravity remains a guiding force, leading scientists to new frontiers of discovery. Gravity's reach is not limited to dramatic events. It also shapes the more familiar motions of everyday life. On Earth, it gives weight to our steps and defines the shapes of rivers and mountains. It binds the oceans to the planet, sculpting the tides that move in gentle rhythms. In the constant pull we feel as we stand on the ground, we are connected to the same gravity that shapes galaxies and bends the paths of light. In the modern era, our understanding of gravity has deepened with precision measurements and careful observations. Space missions have mapped the subtle variations in Earth's gravitational field, revealing the hidden patterns of mass that shape our planet. These measurements, combined with observations of distant stars and galaxies, create a tapestry of gravitational forces that stretch from our world to the furthest reaches of the cosmos. The study of gravity is a study of motion and stability, of cycles and transformations. It is a quiet exploration of the forces that shape existence, revealing that the universe is not a static backdrop, but a dynamic dance of matter and energy. In every orbit traced by a planet, in every slow drift of a galaxy across the sky, there is a story of gravity's patient work. This patient work is not uniform. In regions where mass gathers, gravity creates order out of chaos, drawing matter together and forging new structures. In the emptier spaces between, gravity's gentle pull shapes the slow expansion of voids, creating the balance that defines the large-scale structure of the universe. These patterns of motion and rest, of attraction and distance, echo across the cosmos in forms both subtle and grand. Gravity is also the quiet link between past and future. The motions it dictates today are the echoes of ancient forces, the inherited paths of matter that has danced to its rhythm since the dawn of time. In the slow spirals of galaxies and the patient curves of planetary orbits, there is a memory of the forces that shaped them long ago. And in that memory, there is the promise of change yet to come. As we observe the universe and map the patterns of motion, we are also mapping the reach of gravity. Each star's orbit, each planet's path, each flicker of light bent by a distant cluster is a testament to gravity's presence and power. These observations are not just data. They are glimpses into the deep workings of the cosmos, a window onto the invisible currents that shape everything we see. In the end, gravity is more than just a force. It is a quiet companion to existence itself, an ever-present reminder of the connections that bind all things. In its silent embrace, we find both the familiar comfort of Earth and the strange majesty of distant galaxies. And in that duality, there is a gentle whisper that speaks to the deepest parts of our curiosity, a reminder that in every fall of an apple and every drift of a star, we are touching the same force that shapes the destiny of the universe. For in gravity's patient pull, there is a story that reaches across the scales of existence. It is a story written in the arcs of orbits and the gentle curves of space, in the slow collapse of a star and the vast collisions of galaxies. It is a story that, even as we measure and model it, invites us to wonder at the quiet elegance that shapes the cosmos. And in that wonder, we find a connection that ties our own small world to the infinite expanse of the universe. Chapter 7. Dark Matter and Dark Energy, the Unseen Components. The universe we see is only a small fraction of what truly exists. When we look up at the night sky, we see stars and galaxies, nebulae glowing softly against the dark canvas of space. But these luminous objects, no matter how countless they appear, are merely the visible face of a cosmos that holds far more than what meets the eye. Hidden within the fabric of space are vast, unseen components, dark matter and dark energy, that shape the destiny of the universe and challenge our understanding of reality itself. Dark matter reveals itself not through light, but through its gravitational pull. It neither emits nor absorbs light in any form, making it invisible to even the most sensitive telescopes. Yet its presence can be inferred from the way galaxies rotate, from the motions of stars at their edges, and from the bending of light that passes through regions of intense gravity. These observations show that the luminous matter we can see, stars, gas, and dust, accounts for only a small portion of the gravitational mass required to hold galaxies together. The evidence for dark matter first emerged in the early studies of galaxy rotation curves. Astronomers expected that the speed of stars orbiting in a galaxy would decrease with distance from the center, just as the outer planets in the solar system move more slowly around the sun. Instead, they found that stars far from the center moved as quickly as those closer in. This unexpected observation implied that an unseen mass was providing the necessary gravitational pull, an invisible halo of dark matter that envelops each galaxy. Further clues to dark matter's presence come from gravitational lensing. Light from distant galaxies is bent as it travels through regions of strong gravity, creating distortions and arcs in the images we observe. The magnitude of this bending reveals the total mass present along light's path, and again, visible matter alone cannot account for the effect. The missing mass, inferred from the bending of light itself, is attributed to dark matter. Dark matter also plays a crucial role in the formation and evolution of cosmic structures. In the early universe, slight variations in density provided the seeds for the growth of galaxies and clusters. These variations, magnified over time by the gravitational pull of dark matter, guided the formation of the cosmic web, the vast network of filaments and voids that stretches across the observable universe. Without dark matter's stabilizing gravity, these structures could never have formed as we see them today. Despite its profound influence, the nature of dark matter remains a mystery. It does not interact with light, and it appears to pass through ordinary matter with hardly a trace. Physicists have proposed a variety of candidates for dark matter's identity, from exotic particles beyond the standard model of physics to primordial black holes that formed in the earliest moments after the Big Bang. Experiments on Earth and observations in space continue to search for clues, hoping to reveal the true nature of this hidden substance. As scientists delve deeper, they deploy sensitive detectors in deep underground laboratories, shielded from the noise of cosmic rays. These instruments wait for the faintest interactions between dark matter particles and atomic nuclei, tiny collisions that would reveal their presence. At the same time, particle accelerators strive to create conditions that might produce these elusive particles, offering another path to uncovering their identity. Dark matter's partner in the cosmic balance is dark energy, a force that works in an entirely different way. While dark matter binds galaxies together, dark energy drives the expansion of the universe itself. Its discovery came not from the study of galaxies, but from the observations of distant supernovae, stellar explosions that act as cosmic mileposts. These observations showed that the universe's expansion is accelerating, pushed apart by a repulsive energy that pervades space itself. Dark energy is even more enigmatic than dark matter. It does not clump or gather like matter does, and it cannot be traced through gravitational lensing. Instead, it is a smooth, uniform presence woven into the very fabric of space. The simplest explanation is that it represents a fundamental property of space itself, a cosmological constant that Einstein once proposed, then set aside, and which modern observations have now resurrected as a central component of our cosmic story. The impact of dark energy is profound. It shapes the ultimate fate of the universe, dictating whether expansion will slow and reverse or continue to accelerate forever. Current evidence suggests that dark energy will continue to drive the universe outward, stretching space itself and carrying galaxies further apart in a slow, inexorable drift. In this future of endless expansion, galaxies will fade beyond sight, and the universe will grow ever colder and darker. The presence of dark energy also offers clues to the very structure of space and time. It suggests that space itself is not empty, but infused with a quiet, persistent energy that shapes the motion of galaxies and the unfolding of cosmic history. The equations that describe dark energy are simple, yet they hint at a deeper truth, one that connects the smallest quantum fluctuations with the grand arcs of the universe's expansion. Together, dark matter and dark energy compose the vast majority of the universe's contents. Ordinary matter, the atoms that make up stars, planets, and life itself, accounts for only a small fraction. This realization is a humbling shift in perspective. Most of what exists is hidden from direct observation, accessible only through the subtle clues of motion and structure that reveal the presence of the unseen. Astronomers and physicists continue to search for direct evidence of dark matter. Deep underground detectors, shielded from cosmic rays and noise, wait for the faintest interactions between dark matter particles and ordinary matter. Space telescopes scan the cosmos for telltale signals that might hint at dark matter's identity. These experiments are exercises in patience and precision, requiring years of observation to test theories that reach to the edges of known physics. Meanwhile, the study of dark energy pushes the boundaries of cosmology and our understanding of fundamental forces. Its very nature challenges the foundations of physics, suggesting that our grasp of gravity and the structure of space may be incomplete. The equations that describe dark energy's behavior are elegant in their simplicity, yet they remain placeholders for a deeper truth still waiting to be revealed. The interplay of dark matter and dark energy is not a mere curiosity. It is a window into the ultimate questions of existence. Their invisible forces shape the past and the future, determining the growth of galaxies, the fate of stars, and the long arc of cosmic evolution. They are reminders that the universe is more mysterious than we can easily grasp, and that our understanding is always a work in progress. In the quiet night sky, as we peer into the darkness between the stars, we sense the vastness of these mysteries. We see the gentle glow of starlight, the faint arcs of distant galaxies, and we know that beyond this light, there is an invisible dance that shapes everything. In these moments of reflection, there is both humility and awe, a recognition that the universe is filled with forces we cannot yet see, but that nonetheless guide the rhythm of creation. For in the end, the study of dark matter and dark energy is more than a scientific quest. It is a meditation on the nature of existence itself. In these unseen components, we find a reminder that the universe is not only vaster than we imagine, but deeper and more interconnected than we can fully comprehend. It is a gentle echo of the truth that even in the darkness, there is structure and purpose, an unseen dance that guides the stars and whispers of the mysteries yet to be revealed. Chapter 8. The Expanding Universe, Hubble's Law and Cosmic History. The discovery that the universe is expanding was one of the most profound shifts in our understanding of the cosmos. It transformed our view of the universe from a static stage to a dynamic, evolving entity. At the heart of this discovery lies Hubble's law, a relationship that connects the distances of galaxies to the speeds at which they are receding from us. This simple observation has opened a window onto the history of the cosmos and provided a framework for understanding its past, present, and future. Hubble's law is based on the observation that galaxies are moving away from us, and that the farther away they are, the faster they recede. This relationship was first identified by Edwin Hubble in the 1920s, using observations of distant galaxies and the redshifts in their light. These redshifts, which indicate that the light's wavelength has been stretched, reveal that space itself is expanding, carrying galaxies with it like dots on the surface of an inflating balloon. This expansion is not a motion through space, but an expansion of space itself. Galaxies are not traveling through a static backdrop. Rather, the very fabric of space is stretching, creating more distance between galaxies over time. This concept is subtle and profound, requiring a shift in perspective to truly grasp its implications. It means that the universe has no center or edge in the traditional sense, and that every observer sees the same general pattern of expansion, regardless of their location. The measurement of this expansion has been refined over the decades. Observations of distant supernova, the cosmic microwave background radiation, and large-scale structures have all contributed to a more precise determination of the rate of expansion, known as the Hubble constant. This constant is a crucial parameter in cosmology, shaping our understanding of the universe's age, its contents, and its ultimate fate. The expansion of the universe carries with it the echoes of its beginning. The light we see from distant galaxies has traveled for billions of years, bringing with it a snapshot of the universe as it was long ago. In this ancient light, we see the story of cosmic evolution unfold. The birth of galaxies, the formation of stars, and the slow gathering of matter into the structures we observe today. The cosmic microwave background, a faint glow that fills the universe, is a remnant of the earliest moments after the Big Bang. It is the afterglow of a time when the universe was hot and dense, a time when light and matter were intertwined in a bright, uniform sea. As the universe expanded and cooled, this light was released, stretching into the microwave wavelengths we observe today. It carries with it a record of the conditions that existed when the universe was only a few 100,000 years old. In the decades since Hubble's discovery, astronomers have used the expanding universe as a tool to probe its history and structure. The distribution of galaxies, the clustering of matter, and the faint ripples in the cosmic microwave background all provide clues to the processes that have shaped the universe over billions of years. Each observation adds a piece to the puzzle, revealing the interplay of gravity, radiation, and dark energy that governs the cosmic tapestry. The expansion of the universe also has profound implications for its ultimate fate. If the expansion continues unchecked, galaxies will drift ever farther apart, their light redshifted into oblivion as the universe grows colder and darker. If gravity can halt or reverse the expansion, the universe might eventually collapse back upon itself, ending in a final moment of heat and density. Current observations suggest that the universe's expansion is accelerating, driven by the mysterious force of dark energy that permeates space. Astronomers have refined their observations of cosmic expansion through multiple lines of evidence. Supernova, used as cosmic distance markers, reveal the acceleration of this expansion. The large-scale distribution of galaxies, mapped in intricate detail by surveys that span vast swaths of sky, shows the subtle flows of matter shaped by gravity's patient pull and the relentless push of expansion. Each measurement adds clarity, filling in the outlines of a universe that has been growing since its fiery birth. One of the most profound insights of this expanding cosmos is that looking deeper into space is also looking further back in time. The finite speed of light means that distant galaxies show us their younger selves, snapshots of their early days frozen in the light that finally reaches us. In this way, the night sky becomes a window into cosmic history, a record of change written across billions of years. This realization brings with it a sense of continuity. The galaxies we see as faint smudges of light in the darkness are ancient, their stories unfolding long before Earth formed from the dust of earlier generations of stars. Their light carries the memory of beginnings, of turbulent collisions and slow, graceful growth. In the deep silence of space, the expansion of the universe becomes a quiet testament to the persistence of motion and the enduring nature of change. Yet the expanding universe also brings into focus the great mysteries that remain. The precise rate of expansion, captured in the Hubble constant, is still a topic of careful study and spirited debate. Different methods of measuring it, from the flickers of supernova to the echoes of the cosmic microwave background, give subtly different answers. These discrepancies hint at possible new physics, at layers of understanding yet to be uncovered. The expansion of the universe is not just a matter of galaxies drifting apart. It is a fundamental feature of spacetime itself. In the mathematical language of general relativity, the metric of the universe is dynamic, evolving with time as it responds to the interplay of matter, radiation, and dark energy. This expansion carries galaxies along with it like dust motes in a rising tide, their motions a reflection of the geometry of space. Cosmic expansion also shapes the large-scale structure of the universe, the grand tapestry of voids and filaments that stretches across the night sky. Gravity, working slowly over eons, gathers matter into clusters and threads, while expansion ensures that the spaces between grow ever wider. This balance of attraction and growth creates the cosmic web we observe, a structure that is both ancient and still evolving. For astronomers, measuring the expansion of the universe is a way to test the fundamental theories that describe reality. It connects observations of distant galaxies with the early moments of the cosmos, when quantum fluctuations became the seeds of all future structure. In the stretching of space, we find a record of those earliest times, a faint but persistent memory of the birth of the universe. As technology advances, new instruments promise even greater insights into the expanding universe. Space-based telescopes peer deeper into the darkness, capturing the faint glimmers of galaxies that formed when the universe was young. Observatories on Earth use the subtle wiggles in the distribution of galaxies, traces of sound waves frozen into cosmic structure, to measure the expansion with ever greater precision. Each new observation refines our picture, revealing not just the motions of galaxies, but the quiet workings of the forces that shape everything we see. It is a journey of curiosity, of patient exploration, driven by the human spirit's desire to understand the patterns that stretch across the cosmos. In the quiet depths of space, the expansion of the universe whispers of our place in a cosmos that is at once vast and connected. We are part of this growth, born from the same processes that shape the first stars and galaxies. In the faint glow of distant light, there is a reminder that the universe itself is a story in motion, one that began in a blaze of creation and continues to unfold in every corner of the sky. For in the end, the expanding universe is not just a scientific observation. It is a reflection of the quiet power of motion and change, of the deep forces that weave together time and space. It is a story of growth and transformation, written in the language of redshift and distance, of light that journeys across the darkness, to whisper of beginnings and of possibilities yet to come. Chapter 9. Black Holes and Neutron Stars. Extreme Physics in Action. Black holes and neutron stars are the most extreme manifestations of gravity's relentless pull, regions of the cosmos where the usual rules of matter and energy reach their limits. They are the final products of stellar evolution for the most massive stars, born from the deaths of these giants in supernova explosions. In these dense remnants, matter is compressed to extraordinary densities, and the familiar world of atoms and molecules gives way to the deep and mysterious domain of fundamental physics. A neutron star is the collapsed core of a massive star that has exhausted its nuclear fuel. When fusion can no longer resist gravity, the core implodes, crushing protons and electrons together to form neutrons. The result is a sphere of matter so dense that a single teaspoon would outweigh a mountain. Despite this density, neutron stars are only a few kilometers across, making them incredibly compact. They spin rapidly, sometimes hundreds of times per second, and possess magnetic fields trillions of times stronger than any magnetic field found on Earth. Black holes, by contrast, represent an even more dramatic endpoint. When the core of a collapsing star exceeds a certain mass, no known force can withstand the inward pull of gravity. The collapse becomes unstoppable, compressing matter into a singularity, a point of infinite density and zero volume. Surrounding this singularity is the event horizon, a boundary beyond which nothing, not even light, can escape. Black holes are invisible to direct observation, yet their presence is revealed by the way they warp the motions of nearby matter and the light that passes close to them. These exotic objects are not merely curiosities. They are natural laboratories for testing the boundaries of physics. In the intense gravity near a neutron star, matter behaves in ways that challenge our understanding of nuclear forces and quantum mechanics. The crust of a neutron star is a lattice of atomic nuclei crushed together, while its core may harbor states of matter that exist nowhere else in the universe. Observing neutron stars provides insights into the behavior of matter at the highest densities known. Black holes, too, are windows into fundamental physics. The warping of space-time near their event horizons causes time to slow and space to stretch. Light emitted near a black hole is redshifted, losing energy as it climbs away from the intense gravity. Matter that falls toward a black hole forms a swirling disk, heating up as it spirals inward and radiating energy across the spectrum. These accretion disks can outshine entire galaxies, revealing the black hole's hidden presence. Despite their reputation as cosmic devourers, black holes can also shape their environments in more constructive ways. Jets of particles can erupt from the regions near the event horizon, streaming across interstellar space at nearly the speed of light. These jets are driven by the intense magnetic fields and the rotation of the black hole itself, and they can carry energy far from the black hole's immediate surroundings. In galaxies with active black holes at their cores, these jets help regulate star formation and shape the structure of the surrounding gas. Observing these extreme environments requires innovative techniques and cutting-edge technology. Telescopes sensitive to X-rays and gamma rays can capture the high-energy emissions from matter near a black hole or the powerful magnetic storms on a neutron star's surface. Radio telescopes can detect the pulses of neutron stars known as pulsars, rhythmic beacons that reveal the precise rotations of these dense remnants. The detection of gravitational waves has added a new dimension to the study of black holes and neutron stars. When two of these dense objects spiral together and merge, they create ripples in the fabric of spacetime itself. These waves, first detected in 2015, offer a new way to observe the universe, a way that does not rely on light, but on the very structure of spacetime. Each detection is a glimpse into the cataclysmic collisions that shape the cosmos, revealing the masses and spins of the objects involved. The intense gravity near a neutron star bends the paths of light, creating a distorted view of the star's surface, known as gravitational lensing. In this strange geometry, we can see more than half of the neutron star at once, as light from the far side is bent back toward us. This effect allows astronomers to probe the shapes and temperatures of neutron stars, adding another layer of data to our understanding of their structure. Neutron stars also possess magnetic fields of staggering strength, billions of times stronger than any magnet on Earth. These fields channel streams of particles into intense beams of radiation, creating the pulsars that sweep the sky with their steady pulses. The regularity of these pulses is so precise that they rival the accuracy of atomic clocks, providing natural beacons for navigation and timing across the galaxy. Black holes, while invisible to direct observation, reveal themselves through their effects on nearby matter. The accretion disks that form around them can blaze with X-rays and gamma rays as matter is torn apart and heated to extraordinary temperatures. These emissions, flickering and shifting in intensity, provide indirect glimpses of the processes unfolding near the event horizon. In some galaxies, supermassive black holes millions of times the sun's mass anchor the cores, their gravity guiding the motions of stars and gas on scales that span thousands of light years. The study of these objects is not limited to astronomy alone. Physicists see in black holes and neutron stars the convergence of gravity and quantum mechanics, two pillars of modern physics that have yet to be fully reconciled. The event horizon of a black hole, for example, poses deep questions about the nature of information and its fate in the universe. Theorists propose that black holes may encode information about everything they consume, a puzzle that touches the foundations of how the universe stores and transforms information. The ongoing search for answers has driven astronomers and physicists to build ever more powerful observatories, peering deeper into the cosmos and capturing the faintest signals. Space-based telescopes that orbit above the Earth's atmosphere collect X-rays and gamma rays undimmed by the air, while radio observatories on the ground stretch their antennas across vast distances to catch the whispers of pulsars and the echoes of colliding neutron stars. In these observations, every photon and every wave carries the signature of processes so intense that they strain the very fabric of space and time. Each new piece of data refines our understanding, allowing us to test theories of gravity in the most extreme conditions known to nature. And in these tests, there is a profound sense of humility. For even in these violent, energetic regions, the same laws of physics that govern a falling apple or a planet's orbit apply. The universe does not reveal its secrets easily. The light from matter swirling into a black hole is fleeting, its patterns shifting in response to chaotic flows of gas and magnetic fields. The pulses of a neutron star may wink out in an instant, hidden by the star's own changes or swallowed by a companion's embrace. Yet with patience and precision, astronomers gather these faint signals, building a picture of a cosmos that is always moving, always changing. Black holes and neutron stars also show us how the universe recycles and transforms. The energy unleashed in a supernova not only creates these dense remnants, but seeds the surrounding space with the heavy elements that will become planets, oceans, and life itself. In the jets from black holes, in the winds that blow from neutron stars, there is a cosmic breath that stirs the galaxy, shaping clouds of gas and kindling the birth of new stars. In the quiet intervals between these cataclysms, there is a kind of cosmic patience. A neutron star spins down over millions of years, its magnetic field slowly unwinding. A black hole waits, invisible and silent, until a stray cloud of gas drifts too close and becomes a bright flare in the darkness. These rhythms of activity and quiet are written into the history of galaxies, a record of the ways matter and energy find balance across time. At the heart of this study is a profound question. What does it mean for matter to be so dense that it becomes a singularity, or so ordered that its pulses become cosmic metronomes? Black holes and neutron stars challenge our ideas of what is possible, showing us that even the most familiar substances can transform into states so alien that they defy direct comprehension. In their gravity, we glimpse the unity of physics, a dance of forces that binds the smallest scales of quantum mechanics to the largest curvatures of spacetime. This is not only a scientific journey, but also a quiet meditation on extremes. We marvel at the neutron star's steady glow and the black hole's silent pull, and we recognize that in these distant objects are echoes of the same forces that shape our world. The same gravity that binds us to the Earth binds stars to the galaxy and draws matter into the final darkness of a black hole. In the end, the study of black holes and neutron stars is a testament to curiosity and the willingness to look beyond the visible. It is a journey into the heart of the universe's most extreme environments, a search for the quiet laws that govern even the loudest explosions. And in that search, we find a gentle truth: that even in the fiercest forces of nature, there is an order and a balance that speaks to something deeper than chaos. For in the silent hearts of black holes and in the flickering pulses of neutron stars, there is a story that stretches across the scales of existence. It is a story of collapse and rebirth, of the quiet dignity of matter reshaped by gravity and time. And in that story, we are reminded that even in the darkest reaches of space, there is structure, there is motion, and there is the quiet promise of understanding yet to come. Chapter 10. The Cosmic Microwave Background. The cosmic microwave background, CMB, is a faint, ancient light that permeates the entire universe, offering an unparalleled glimpse into the cosmos' earliest moments. It is the remnant glow of the primordial fireball that once filled all of space, released when the universe was just a few 100,000 years old. As the oldest light we can observe, the CMB holds the keys to understanding the birth, composition, and ultimate fate of the universe. By studying its patterns and temperature fluctuations, astronomers can reconstruct the cosmic story from its infancy to the complex structure we see today. The cosmic microwave background, often called the afterglow of the Big Bang, is one of the most profound discoveries in modern astrophysics. It is a faint, pervasive radiation that fills the entire sky, a whisper from the earliest moments of the universe's history. This ancient light offers a direct glimpse into a time long before stars or galaxies had formed, a time when the universe was still a hot, dense sea of particles and radiation. Discovered by accident in 1965 by Arno Penzias and Robert Wilson, the cosmic microwave background provided the first concrete evidence that the universe had a beginning, a moment when everything was compressed into a single, dense point and began to expand outward. This radiation is remarkably uniform, yet subtle variations in its temperature reveal the seeds of structure that would eventually grow into galaxies, stars, and planets. The cosmic microwave background is not light in the sense that we see with our eyes. Instead, it is microwave radiation, stretched by billions of years of cosmic expansion from the brilliant glow of a plasma-filled universe to the gentle hum that now pervades space. This transformation of the light's wavelength is a record of the universe's growth, a signature of the slow cooling that has unfolded over billions of years. As the universe expanded and cooled, it reached a point when matter and radiation could decouple, when protons and electrons combined to form neutral atoms, allowing light to travel freely for the first time. This moment, known as recombination, occurred when the universe was only a few 100,000 years old. The light released in that era has been traveling through space ever since, stretched and redshifted by the expansion of the cosmos. Today, the cosmic microwave background is remarkably uniform, with a temperature just a few degrees above absolute zero. Yet, it is not perfectly smooth. Tiny fluctuations in its temperature detected by sensitive instruments represent the first faint ripples of structure. These subtle variations reveal how matter was distributed in the early universe and how gravity would later amplify those seeds into the vast cosmic structures we see today. Observing the cosmic microwave background requires instruments capable of measuring minute differences in temperature across the sky. Satellites like COBE, WMAP, and Planck have mapped these fluctuations with exquisite precision, creating detailed images of the universe as it appeared long before the first stars were born. These maps are not just beautiful pictures. They are scientific treasure troves that encode the fundamental properties of the cosmos. From the tiny fluctuations in the cosmic microwave background, scientists can deduce the composition of the universe, the relative amounts of dark matter, dark energy, and ordinary matter. They can measure the universe's geometry, revealing whether space is curved or flat on the largest scales. They can also trace the history of cosmic expansion, using the patterns imprinted in this ancient light as a guide to the universe's growth over billions of years. The cosmic microwave background is a window into the universe's infancy, but it also connects us to its later evolution. The light we see today has been traveling across the cosmos for nearly 14 billion years, carrying with it a memory of the universe's first moments. In every direction we look, this faint glow surrounds us, a soft echo of a time when the cosmos was young and unformed. Yet this quiet light is not static. It bears the imprints of everything that has happened since it was released. As it traveled through space, the cosmic microwave background passed through clusters of galaxies and clouds of gas, picking up subtle distortions along the way. These distortions, known as the Sunyaev-Zeldovich effect and gravitational lensing, allow astronomers to use the cosmic microwave background as a probe of the large-scale structures that have grown over cosmic time. In the delicate patterns of the cosmic microwave background, scientists see the faint signature of primordial sound waves, pressure ripples that echoed through the hot plasma of the early universe. These acoustic oscillations, frozen into the temperature variations we measure today, reveal the density and composition of matter in the young cosmos. They are a testament to the dynamism of the early universe, a record of the push and pull that shaped everything that followed. As our instruments have become more sensitive, the cosmic microwave background has revealed even more subtle features. Tiny variations in its polarization, how the light waves are oriented, offer new clues to the physics of the early universe. These measurements can test theories of cosmic inflation, a period of rapid expansion thought to have occurred in the first moments after the Big Bang. If inflation occurred, it would have left a faint but distinct imprint in the polarization of this ancient light. The study of the cosmic microwave background is not merely a technical achievement. It is a journey into the deepest reaches of cosmic history. The data it provides have become a cornerstone of modern cosmology, forming the foundation for our understanding of how the universe has grown and changed. Each measurement, each map of subtle variations is a window onto the forces that have shaped existence on the largest scales. The search for answers in the cosmic microwave background has also pushed the boundaries of technology. Instruments must be cooled to near absolute zero to detect the faintest signals, shielded from the noise of Earth's atmosphere and our own electronics. The precision required to measure tiny differences in temperature across the sky challenges engineers and scientists alike, driving innovation and collaboration across fields. Through these efforts, we have learned that the universe is not a static backdrop, but a living, evolving system. The cosmic microwave background is a snapshot of its earliest form, yet it is also a reflection of the dynamic processes that have shaped everything since. It tells a story of growth and structure, of the quiet forces that turn simplicity into complexity. In the quiet glow of this ancient light, there is a reminder that the universe is both vast and intimately connected. The photons that fill the sky today have journeyed across time, carrying with them a memory of the birth of everything we know. They speak of a time when matter and energy were woven together, when the seeds of galaxies were planted in the soft murmur of plasma. For those who study this faint glow, there is both challenge and wonder. The data reveal the echoes of a cosmic dawn, yet they also whisper of mysteries still beyond reach. Each new observation refines the picture, but also reminds us of how much remains to be discovered. The cosmic microwave background is both a map and an invitation, a map of what has been and an invitation to keep looking deeper. In the end, the cosmic microwave background is more than a remnant of the past. It is a quiet testament to the endurance of light and the patient unfolding of the cosmos. It is a gentle echo of creation itself, a glow that ties us to the very birth of time and space. And in that soft, pervasive glow, there is a promise that even in the vast cold of the universe, there is still warmth. A warmth that began in the first fire of the cosmos and that will forever link us to the mystery of what lies beyond. Section 2. General Relativity, Spacetime, Time Dilation, Black Holes and Gravitational Waves. Chapter 1. What is general relativity? When you look up at the night sky and see the moon slowly drifting across the heavens, or witness a shooting star tracing a quiet arc, you're observing the graceful ballet of celestial motion. For centuries, humanity tried to explain why things fall, why planets move, and why the universe feels ordered yet endlessly mysterious. For a long time, gravity was thought of as a force, an invisible pull between objects, growing stronger with mass and weaker with distance. Isaac Newton gave us this elegant idea, and it served remarkably well for over 200 years. It explained the fall of the apple, the tides, and the orbits of planets with unmatched precision. But there were things it couldn't fully explain. And at the dawn of the 20th century, a new way of thinking would quietly emerge, an idea that would change not just physics, but our very understanding of space, time, and reality. General relativity, developed by Albert Einstein and published in its complete form in 1915, is not merely a better version of Newtonian gravity. It is a complete transformation of how we understand the structure of the universe. It tells us that gravity is not a force at all. Instead, it is a manifestation of geometry, a warping of the very fabric of space and time caused by the presence of mass and energy. This shift in perspective is both subtle and profound. In Newtonian physics, space and time were fixed and absolute. They provided a rigid stage upon which objects moved and forces acted. Time ticked evenly for all observers, and space was flat, unchanging, and indifferent. The force of gravity, in this model, acted instantaneously across space, pulling masses toward one another without any physical medium through which that influence traveled. This worked well for celestial mechanics, but it left a deep conceptual gap. What exactly was transmitting this force, and why did it work so perfectly for some cases, but not all? For example, Newtonian gravity could not account for small anomalies in the orbit of Mercury. For decades, astronomers noticed that Mercury's orbit precessed slightly more than Newton's laws predicted. The discrepancy was small, but persistent. It became one of the many small puzzles that hinted something deeper was at play. Einstein's answer was to rethink gravity entirely. Instead of viewing it as a force, he proposed that mass and energy warp the geometry of spacetime itself, and that what we perceive as gravitational force is simply the result of moving through this curved geometry. To build this new theory, Einstein relied on a mathematical tool called Riemannian geometry, a branch of differential geometry capable of describing curved surfaces and higher dimensional spaces. With the help of mathematicians like Marcel Grossmann and David Hilbert, Einstein formulated a set of equations that related the curvature of spacetime to the distribution of mass and energy within it. These became known as the Einstein field equations. Although abstract in appearance, these equations serve as the core blueprint for describing everything from orbiting planets to the dynamics of expanding galaxies. The key insight that led Einstein to this realization came from a deceptively simple thought. He imagined a person in free fall, dropping inside a sealed elevator. Inside, that person would feel weightless, unable to tell whether they were falling on Earth or floating in deep space. This thought experiment became the foundation for what Einstein called the equivalence principle. The idea that locally, the effects of gravity are indistinguishable from those of acceleration. From this sprang the realization that gravity might not be a traditional force at all, but something more fundamental, a clue that geometry itself might govern the motion of objects. In general relativity, mass and energy tell spacetime how to curve, and curved spacetime tells objects how to move. It's not that planets are being pulled by the sun. Rather, the sun warps the geometry of spacetime around it, and the planets follow the natural paths, called geodesics, within that curved geometry. These paths may appear as ellipses or orbits, but they are simply the straightest possible lines in a curved environment. Much like how airplanes follow great circles across the globe, celestial bodies are following their own optimal paths, shaped not by a force, but by the terrain of spacetime itself. This concept may seem abstract, but its consequences are very real. Light itself, which always travels in straight lines in flat space, follows curved paths when it moves through curved spacetime. This leads to phenomena like gravitational lensing, where the light from distant stars and galaxies is bent around massive objects like galaxy clusters, forming arcs or even rings in the sky. In this way, spacetime acts like a cosmic magnifying glass. One of the earliest and most celebrated confirmations of general relativity came in 1919. British astronomer Arthur Eddington led an expedition to observe a total solar eclipse. During the brief darkness, stars near the sun's edge became visible. According to Einstein's theory, their light should appear displaced from their usual positions due to the curvature of spacetime around the sun. Eddington's measurements confirmed the prediction, and Einstein's name became synonymous with genius almost overnight. The Newtonian view of gravity had been challenged and surpassed, not by contradiction, but by deeper understanding. General relativity also provides insight into the passage of time. In regions of stronger gravity, near planets, stars, or black holes, time passes more slowly compared to regions of weaker gravity. This effect, called gravitational time dilation, has been confirmed experimentally in a number of ways. One involves placing highly precise atomic clocks at different altitudes. Clocks at higher elevations, where Earth's gravitational pull is weaker, tick slightly faster than those at sea level. This might sound like a minor curiosity, but it's crucial for technologies like GPS. Satellites orbiting Earth experience both weaker gravity and higher velocities, requiring time adjustments from both general and special relativity to provide accurate positioning data. Another prediction of general relativity is the existence of black holes, regions where spacetime becomes so curved that not even light can escape. These are no longer speculative objects. Observations of stars orbiting invisible companions, as well as gravitational wave signals from colliding black holes, have confirmed their reality. In 2019, humanity saw the first image of a black hole's shadow, captured by the Event Horizon Telescope, further validating Einstein's ideas at the extremes of physics. General relativity also gives us our best understanding of the universe at large. The equations, when applied to the universe as a whole, predict that spacetime itself can expand or contract. This led to the development of cosmological models that describe the Big Bang, the moment our universe began from a hot, dense state, and has since been expanding for over 13 billion years. The discovery of cosmic expansion by Edwin Hubble in the 1920s gave observational support to these models. Decades later, the observation of the cosmic microwave background radiation provided further evidence that the early universe was indeed hot and dense, just as the equations suggested. Interestingly, Einstein initially resisted the idea of an expanding universe. To maintain a static cosmos, he introduced an additional term into his equations called the cosmological constant, a kind of repulsive force to counteract gravity on large scales. When Hubble's data showed that the universe was expanding, Einstein reportedly called the cosmological constant his biggest blunder. Ironically, modern cosmology has resurrected the idea in a new form to explain dark energy, the mysterious phenomenon accelerating the expansion of the universe. Despite its remarkable successes, general relativity remains incomplete. When physicists attempt to apply its principles to extremely small scales, such as the interiors of black holes or the earliest moments of the universe, they encounter contradictions. The smooth, continuous nature of spacetime breaks down when quantum effects dominate. Reconciling general relativity with quantum mechanics is one of the most profound, unsolved problems in modern physics. It suggests that there may be a deeper theory still waiting to be discovered, one that includes both gravity and quantum principles in a unified framework. Still, general relativity stands as one of the most beautiful and successful theories ever conceived. It continues to pass every experimental test, and its predictions have transformed both our philosophical and practical understanding of reality. From the gentle tug of gravity on Earth to the majestic arcs of galaxies bending light across the cosmos, general relativity reveals a universe in motion, a universe not fixed in stone, but written in curves. To grasp general relativity is to understand that the universe is not just a collection of objects, but a living geometry. Every particle of matter, every flash of energy bends the structure of reality itself. We do not float in a static void. We ride the contours of spacetime, shaped by the presence of stars and shadows of mass. Even the empty spaces between galaxies are not truly empty. They are woven with invisible curvature, stretched by the expansion of the cosmos, and marked by the gentle pull of gravitation that never quite lets go. And in this quiet realization, something stirs, that you, a single mind afloat in space and time, are also part of this vast geometry. You are not outside it, you are a ripple in it. Your heartbeat bends it, your presence shapes it, just as it shapes you. General relativity does not only describe what the universe is, it reminds us softly that we belong to it completely. Chapter 2. The Geometry of Spacetime. To speak of the universe without geometry is to describe a melody without pitch. Geometry is not simply a language of shapes and forms. It is the architecture of physical law itself. In general relativity, the geometry of spacetime is more than a backdrop. It is an active participant in the unfolding story of the cosmos. Where classical physics once treated space and time as rigid, unchanging, and absolute, general relativity replaces that notion with a richer, more fluid understanding. Space and time are merged into a single entity, spacetime, whose shape and curvature are dynamic, determined by the contents of the universe itself. The concept of space-time curvature is central to general relativity, but it cannot be grasped through everyday intuition. In our daily experience, space seems flat. Objects move in straight lines unless pushed or pulled, and distances appear consistent, no matter where we are. But these are local approximations. On cosmic scales, or in the presence of strong gravitational fields, space and time bend subtly, then severely. To understand how this happens, one must think not just in terms of motion or forces, but in terms of geometry itself changing from point to point. Curved spacetime is not simply a metaphor. It is a literal description of how the distances between points and the intervals between events vary due to mass and energy. Just as a sheet of paper can lie flat or be crumpled into complex shapes, the fabric of spacetime can be flat or curved. But unlike a sheet, spacetime does not curve into a higher dimensional space that we can observe directly. Its curvature is intrinsic, meaning it can be measured from within, without referring to any external frame. This is where Riemannian geometry becomes essential. Developed in the 19th century by Bernhard Riemann, it provides the mathematical framework for understanding curved surfaces of any dimension. In general relativity, The geometry of spacetime is described using a specific kind of curved four-dimensional manifold, 3 dimensions of space and 1 of time. The curvature of this manifold is encoded in a mathematical object known as the metric tensor, which specifies how distances and times are measured locally at each point in spacetime. Unlike in Euclidean geometry, where the metric is fixed and simple, the spacetime metric in general relativity is dynamic and influenced by the distribution of mass and energy. If this sounds abstract, it's because it is, but it is also grounded in observable reality. The shape of spacetime affects everything that moves through it: planets, light beams, even time itself. The geodesics, the paths of least resistance, or the straightest possible paths through curved spacetime, are determined by the geometry described by the metric. In flat space, a geodesic is a straight line. On the surface of a sphere, it becomes a great circle. In spacetime, it is the trajectory a free-falling object follows, even if that path appears curved to an outside observer. What is profound about this framework is that objects in free fall are not being pushed or pulled. They are simply following the geometry laid out for them. When the Earth orbits the Sun, it is not being attracted in the Newtonian sense. Instead, it is following a geodesic in the curved spacetime created by the Sun's mass. If we could somehow eliminate the Sun while keeping Earth's velocity unchanged, Earth would no longer follow a curved path. It would shoot off in a straight line, according to the now flat geometry of empty spacetime. Different configurations of mass and energy generate different curvatures. A small planet creates a gentle well in spacetime. A massive star produces a much deeper one. A black hole represents a region where the curvature becomes so extreme that geodesics loop inward and no paths lead out. These curvatures are not imaginary or invisible. They have measurable consequences. Light from distant stars bends around massive objects. Travel times for signals vary near dense bodies, and the structure of spacetime itself determines the large-scale shape and fate of the universe. It's also important to understand that spacetime curvature is not localized. It propagates. A sudden change in the arrangement of mass, such as 2 black holes merging, sends ripples through the fabric of spacetime. These ripples, known as gravitational waves, are tiny distortions that travel outward at the speed of light, carrying energy and information across the cosmos. Their detection, first achieved by LIGO in 2015, provided direct evidence not only of black holes, but of the dynamism of space-time geometry itself. One of the elegant features of general relativity is that it eliminates the need for action at a distance. In Newtonian gravity, 2 objects can influence one another instantaneously across empty space. In general relativity, the influence of mass on spacetime geometry propagates at finite speed, no faster than light. This not only aligns gravity with special relativity's speed limit, but also creates a natural framework in which gravitational influence is embedded in spacetime's shape itself. The behavior of time within curved spacetime is another consequence of this geometry. In general relativity, time does not flow uniformly. The rate at which time passes depends on the gravitational potential, a measure of how deep within a curvature well an object lies. A clock closer to a massive body ticks more slowly than one farther away. This effect, called gravitational time dilation, is not merely theoretical. It has been confirmed with atomic clocks placed at different altitudes on Earth, in satellites, and even on airplanes. Time, as described by general relativity, is a coordinate that bends, stretches, and flows in ways utterly dependent on the geometry around it. Spacetime geometry also dictates the very structure of the universe on the largest scales. By applying Einstein's equations to the universe as a whole, cosmologists derive models that describe how the cosmos expands, curves, and evolves over time. These models predict that spacetime itself can have global curvature, flat, open, or closed, depending on the total energy density of the universe. Observational evidence from the cosmic microwave background suggests that our universe is very nearly flat, though not perfectly so. But even this apparent flatness is a local property of the observable universe. The full geometry of spacetime may extend far beyond what we can see. On even larger scales, spacetime geometry underpins the development of cosmological inflation, a rapid expansion of the universe in its earliest moments, which smoothed out irregularities and seeded the structures we observe today. The subtle geometry of spacetime during inflation left its imprint on the cosmic microwave background, visible today as tiny fluctuations in temperature and density. These fingerprints of geometry continue to inform our understanding of the universe's origin and fate. One fascinating implication of spacetime geometry is that it is affected not only by matter, but also by energy. This includes dark energy, a mysterious form of energy that permeates empty space and accelerates the universe's expansion. Dark energy contributes to the curvature of spacetime not by attracting mass, but by creating a kind of repulsive effect on cosmic scales. The discovery of this accelerated expansion in the late 1990s revealed that geometry and energy are inextricably linked, not just locally, but across the entire cosmos. Despite its successes, the geometric description of gravity raises deep questions. For example, at the center of a black hole lies a singularity, a point where space-time curvature becomes infinite and the laws of general relativity break down. Near such extremes, the smooth geometry of space-time may no longer apply. Physicists suspect that a quantum theory of gravity not yet discovered will eventually replace the classical picture and reveal a more granular structure of space-time itself. Nevertheless, the geometric vision of general relativity remains unmatched in elegance and accuracy. It reduces gravity to nothing more than a change in the fabric of existence. There are no invisible forces, no instantaneous influences, only the bending and flexing of a living, breathing space-time. The orbits of planets, the bending of light, the passage of time, and the expansion of the universe all emerge naturally from this geometry. It is not simply the arena in which physics takes place. It is the thing that is physics, in one of its purest forms. And so as we drift through this invisible geometry, we are not merely passengers on a cosmic journey. We are part of the geometry itself. Each breath, each heartbeat, gently shifts the curvature of the world around us, even if we can't feel it. Every object in the universe contributes its presence to the shape of space-time, just as every fold in a sheet is influenced by every crease nearby. In that quiet thought, there is a kind of existential grace, that even in the absence of motion or noise, you are never truly still. You are always embedded, always woven into the fabric of something greater, part of the cosmic shape that holds stars, galaxies, and the soft ticking of time. Chapter 3. Time Dilation and Gravitational Time Travel. Time as we experience it seems universal. It ticks forward steadily, indifferent to our movements or our position in space. From our everyday perspective, time appears absolute, constant, and evenly paced for everyone. But this is an illusion born of limited perception. In truth, time is deeply relative. It flows differently depending on your speed, your location, and the gravity around you. Under the lens of general relativity, time reveals itself to be as dynamic and malleable as space itself. The result is a universe where time can stretch, compress, and even lead to forms of travel that defy our everyday intuition. The concept of time dilation emerges naturally from the structure of space-time in general relativity. It describes the way in which time passes at different rates for observers in different gravitational potentials or moving at different velocities. This is not simply a theoretical quirk. It is a rigorously tested and measurable effect. In regions where gravity is stronger, time ticks more slowly compared to regions where gravity is weaker. This means that a clock near a massive planet A star or a black hole will accumulate less time than one in deep space. This slowing of time is not due to mechanical interference. It is not a malfunction. It is a fundamental consequence of how space-time itself is shaped. To understand why this happens, one must look again at the relationship between mass and geometry. In general relativity, massive objects bend the space-time around them, and this curvature affects both space and time. When a clock is placed in a gravitational well, it measures proper time, the time experienced along a path through space-time that is curved more steeply near massive objects. To an external observer at a higher altitude, that same clock appears to tick more slowly. The deeper in a gravitational well an object lies, the more dramatically time stretches for an observer outside that well. This is not a phenomenon confined to extreme environments. Even on Earth, time dilation is measurable and must be accounted for in modern technology. Atomic clocks flown on aircraft or placed at the tops of mountains run slightly faster than those at sea level. The global positioning system is one of the most striking demonstrations of this principle. GPS satellites orbit Earth at an altitude where gravity is weaker than on the surface. As a result, their internal clocks tick faster, by about 45 microseconds per day, compared to clocks on Earth. If uncorrected, this would cause GPS calculations to drift by several kilometers each day, rendering the system useless. Engineers compensate for this relativistic effect, confirming not only the theory's accuracy, but also its practical necessity. Beyond the everyday implications, time dilation becomes more dramatic in extreme gravitational environments. Near a neutron star or a black hole, time can slow to a crawl compared to a distant observer. In theory, if someone hovered just above the event horizon of a black hole, avoiding being pulled in but remaining deep within the gravitational well, their time would pass incredibly slowly relative to someone far away. Hours for the distant observer might correspond to mere minutes or even seconds for the person near the event horizon. If that person were then rescued and brought back to normal space, they would emerge having aged far less than everyone else. In this sense, gravitational time dilation creates a form of one-way time travel. A traveler can move into the future more quickly than those left behind. This idea has entered the public imagination, especially through science fiction and films, but the underlying physics is very real. It does not require hypothetical machines or violations of physical law. It only requires access to extreme gravity and the ability to resist falling in. In practice, surviving such conditions is extraordinarily difficult, but the theory offers a tantalizing glimpse into what is possible. Time travel into the future is not only allowed by general relativity, it is unavoidable in certain scenarios. Another form of time dilation arises from motion itself. According to special relativity, which general relativity subsumes and extends, time also slows down for objects moving at high velocities. The faster an object moves, the slower its internal clock ticks compared to a stationary observer. This effect is called kinematic time dilation, and like its gravitational counterpart, it has been tested extensively. Experiments with high-speed particles and accelerators show that unstable particles moving near the speed of light decay more slowly than those at rest. Time for them stretches, and they live longer than expected, not because of any external interference, but because motion alters the passage of time. This too has real-world applications. The muons produced by cosmic rays in Earth's upper atmosphere decay rapidly and should not survive long enough to reach the ground. Yet they do, because their high speed causes their internal clocks to tick slowly, allowing them to travel farther before decaying. This observation matches perfectly with predictions made by the theory of relativity. These two types of time dilation, gravitational and kinematic, are often seen as distinct effects, but general relativity unifies them. Both result from differences in the geometry of spacetime as experienced by different observers. Whether it's motion or gravity that creates the discrepancy, the underlying cause is the same: the space-time path each observer follows and the curvature along that path. When taken to extremes, time dilation raises deeply intriguing possibilities. If a civilization could orbit close to a black hole without crossing the event horizon, it could in principle witness immense stretches of cosmic time in what, to them, would feel like a brief moment. The future of the universe could unfold before their eyes, while they barely aged at all. This is not just fantasy, it is a direct consequence of the math. General relativity permits such trajectories through space-time, and nothing in physics forbids such one-way journeys into the future. Of course, returning from such a journey is more difficult. Gravitational time travel, unlike the fictional time machines of science fiction, cannot reverse itself. The equations of general relativity are time-symmetric, but the conditions necessary to travel backward in time remain elusive and possibly forbidden by deeper physical laws. Solutions to Einstein's equations do exist, like the Gödel metric or closed time-like curves, that allow for backward time travel in principle, but these require exotic conditions, such as rotating universes or negative energy densities, which may not be physically realizable. Most physicists believe that some version of the chronology protection conjecture, proposed by Stephen Hawking, prevents these scenarios from manifesting in reality. Still, the forward direction of time travel remains fully compatible with known physics. It blurs the line between science and philosophy, challenging our assumptions about identity, memory, and continuity. If two observers age at different rates due to space-time curvature or velocity, what does it mean to share a moment? What does it mean to be synchronized in a universe where time is not absolute? Time dilation also forces a reconsideration of causality. In a universe where time flows differently for different observers, the concept of simultaneity becomes relative. Events that are simultaneous for one observer may not be for another. This is not just a mathematical oddity, it reflects the fundamental structure of reality. Light cones, causal relationships, and the flow of time all depend on one's position and motion in spacetime. This relativity of simultaneity has profound implications for how we think about past, present, and future. There is no universal now, only sequences of events connected by light and causality. From this perspective, the universe is not a river of time carrying all things forward at the same rate. It is a complex topography of space and time, curved and tilted by mass and motion. Every object traces its own path through this terrain, and each path is governed by geometry. The passage of time is not dictated by a single clock, but by the world line of each traveler. Your heartbeat, your thoughts, your memories, all unfold along a curved thread of space-time that is unique to you. And so, while time appears linear in the rhythm of our days, the universe reveals it as a flexible dimension, shaped by context. Under general relativity, we are all travelers, not only through space, but through time, each of us moving forward along our own private axis of duration, influenced by where we are and how fast we move. It is a humbling thought. That time itself, something we so often take for granted, is not an absolute. It bends, it stretches, it folds. The ticking of a clock on your wrist is not a universal truth. It is a local rhythm, a beat set by the gravitational curvature of your world and the motion of your journey. To live is to surf the contours of time itself, never quite in sync with anything else. And in that quiet divergence lies something beautiful. That no two beings, no two moments, no two paths through space-time are ever truly the same. Each of us experiences a slightly different universe, a slightly different flow, a slightly different now, and yet somehow we share it, curved, shifting, and deeply connected. Chapter 4. Free Fall and the Equivalence Principle. To understand gravity as Einstein saw it, one must begin not with stars or equations, but with falling. Not the kind of falling we fear or avoid, but a precise, universal kind, the kind that made Galileo drop spheres from a tower and Einstein imagine an elevator plummeting through space. Free fall, so ordinary on Earth, became for Einstein the key that unlocked a hidden truth about nature. In Newtonian physics, an object in free fall is one that has been released from rest and allowed to move under the influence of gravity alone. It accelerates downward because a force, gravity, acts on it, pulling it toward the center of the Earth. The force is proportional to the object's mass and inversely proportional to the square of the distance from Earth's center. That model works well for most of our everyday experiences. But something peculiar has always lurked in its simplicity. Different objects, regardless of their mass, fall at the same rate. A feather and a bowling ball, dropped in a vacuum, fall together. In Newton's equations, this occurs because the object's mass appears on both sides of the force equation and cancels out. But Newton never explained why that cancellation happens. It was simply accepted as fact. Einstein took that observation and gave it new meaning. He recognized that the equality of inertial mass, resistance to acceleration, and gravitational mass, response to gravity, is not just a mathematical coincidence. It's a profound clue. In his view, this equality suggested that gravity might not be a force in the traditional sense. Instead, what we interpret as a force might be something more subtle, something geometric. To explore this idea, Einstein considered the experience of an observer in a falling elevator. Imagine you're sealed inside a windowless elevator in deep space, far from any stars or planets. Suddenly, the elevator begins accelerating upward. You feel pressed to the floor. To you inside, it feels exactly like gravity. Now imagine a second elevator, one that is stationary above Earth, then cut loose so it begins to fall freely. Inside that falling elevator, you float. You no longer feel your weight. If you let go of an object, it hovers beside you. In that brief moment of descent, the elevator and everything inside it are all falling together under gravity's influence, making the force disappear from your perspective. Einstein saw these two experiences, accelerating in empty space and falling freely in a gravitational field, as fundamentally equivalent. This is the essence of the equivalence principle, the idea that local experiments in a small enclosed environment cannot distinguish between uniform acceleration and gravitational free fall. From this principle, he began to construct a new theory of gravity, not as a force, but as a property of spacetime itself. In this view, when you drop an object, it doesn't accelerate because a force pulls it down. Instead, it moves along a natural path, a geodesic, through curved spacetime. If the object is released and no other forces act on it, it will follow the straightest path allowed by the geometry of spacetime. The only reason you perceive it as falling is because you're not in free fall. You, standing on the Earth's surface, are actually being pushed upward by the ground, away from the geodesic your body would naturally follow. Gravity, in this formulation, is not pulling things down. Surfaces are pushing objects away from their natural trajectories. This perspective seems strange at first because it reverses how we think about motion. But it matches reality. Astronauts in orbit feel weightless, not because there's no gravity, but because they are in continuous free fall. Their spacecraft, their bodies, even the water droplets floating beside them, all follow the same curved paths through space-time. The sensation of weight disappears when you're no longer being prevented from falling. The equivalence principle has been tested with extraordinary precision. Physicists have dropped objects of different compositions in vacuum chambers, compared atomic clocks in free fall and at rest, and flown satellites with test masses isolated from other forces. Every time the results align. All objects fall identically, regardless of their properties, so long as only gravity acts. Even quantum tests using atomic interferometry confirm the principle at microscopic scales. These experiments reinforce Einstein's core insight. Gravity is not about forces acting on things. It's about the shape of the paths things take. This understanding allowed Einstein to generalize special relativity, which described the behavior of objects moving at constant speeds, into a broader theory that could also describe acceleration and gravity. In doing so, he extended the flat, inert geometry of special relativity into the dynamic, curved geometry of general relativity. Free fall became not just a state of motion, but the key to unlocking how spacetime responds to energy and mass. When Einstein presented his full theory in 1915, it provided a new way of understanding gravitational phenomena that had puzzled scientists for decades. The strange precession of Mercury's orbit, which defied Newtonian predictions, emerged naturally from the geometry of curved spacetime. Light bending around the sun, the slowing of time near massive bodies, the dynamics of black holes, all followed from this elegant principle that falling is indistinguishable from floating, and that acceleration and gravity are two sides of the same coin. What makes the equivalence principle so powerful is its local nature. It doesn't attempt to describe gravity everywhere at once, but focuses on what can be said in small regions of spacetime, regions where curvature can be ignored or treated as uniform. In these local regions, the laws of physics take the same form as in special relativity. Light moves in straight lines, clocks tick at constant rates, and free-falling objects move uniformly. Only when comparing events at different locations, where curvature varies, do the effects of gravity emerge. In this sense, general relativity is a patchwork of locally flat regions sewn together by curvature. Even time, in this framework, becomes relative to the path an object takes through spacetime. A clock in free fall does not tick more slowly because it is falling. It ticks at its proper time, measured along its geodesic. It is only when we compare that clock to one not in free fall that we see the difference. Gravity, therefore, is not acting directly on time. It shapes the path through which time flows. This insight also reshapes our understanding of what it means to be stationary. On Earth, we feel the force of gravity because we are being held up, resisted from falling by the ground beneath us. From the perspective of general relativity, we are accelerating upward relative to a freely falling frame. A satellite in orbit is actually the one experiencing no force. It is coasting along its natural geodesic. We, here on the surface, are the ones deviating from that natural motion. The counterintuitive nature of this truth can be unsettling. We are used to thinking of ourselves as stationary, held securely to Earth by gravity. But from spacetime's point of view, it is the orbiting satellite that is free, and we who are under constant deviation from freedom. Gravity no longer pulls. Instead, geometry guides, and resisting that guidance produces the sensation of weight. The implications of the equivalence principle extend into other areas of physics as well. It has inspired attempts to unify general relativity with quantum mechanics by suggesting that gravity might emerge from more fundamental principles. Some approaches in theoretical physics, such as those involving entropic gravity or holographic duality, seek to explain spacetime and gravity as emergent phenomena arising from information, thermodynamics, or entanglement. While none have yet succeeded in replacing general relativity, they all draw in part from Einstein's insight that the nature of gravity is deeply tied to how we experience motion and acceleration. At the heart of all of this is the simple realization that falling freely is indistinguishable from floating, that to let go is to return to the natural path determined by the universe's geometry, and that what we once thought of as force is instead a whisper in the structure of space and time. And so every time you drop an object, every time it slips from your fingers and falls, you are witnessing not a pull, but a path. A quiet, ancient trajectory carved into the shape of the cosmos. The object is not being acted upon. It is being released. It is returning to the line it was always meant to follow. Perhaps that's all we're doing, that in the end, falling freely through a universe that bends around us, unaware of the deeper structure beneath our feet. And in that falling, we are not alone. We are part of a pattern, an unfolding, a geometry written long before we knew how to look. Chapter 5. Curved Paths in a Curved Universe. Motion through space has always carried with it an intuitive simplicity. From ancient observations of wandering stars to Newton's precise laws, humanity has long imagined that if left undisturbed, objects move in straight lines, and any deviation from that motion must result from an applied force. This idea formed the backbone of classical mechanics, where straight-line trajectories were the norm, and orbits were the result of constant acceleration caused by gravity. But Einstein's theory of general relativity replaces this mechanical picture with a geometric one. Objects do not move because they are pushed or pulled. They move because they are following the natural structure of spacetime. A planet orbiting a star, a comet tracing an elliptical path, or even a spacecraft drifting silently in the void, they all follow curved trajectories, not because something bends them, but because spacetime itself is curved, and they are simply tracing the straightest possible paths within it. In general relativity, the concept of a straight line is generalized to that of a geodesic. A geodesic is the path through spacetime that a free-falling object follows when no other forces are acting upon it. In flat spacetime, as described by special relativity, a geodesic is identical to a straight line. But in the presence of mass and energy, spacetime becomes curved, and the straightest path becomes a more complex trajectory, often appearing curved or even looping from an external point of view. This curvature is not a property of the object, but of the space through which it moves. Imagine placing a marble on a stretched rubber sheet. If the sheet is flat, the marble will roll in a straight line. But if you place a heavy ball on the sheet, it will deform, creating a dip. Now, if you roll the marble again, it will spiral toward the depression, curving as it follows the altered geometry of the surface. No external force acts laterally on the marble. It simply follows the shortest path available in the new geometry. This analogy, though imperfect, captures the essence of what general relativity proposes. Gravity is not a force, but a feature of the landscape. The presence of mass alters the shape of spacetime, and objects respond by following the contours of that shape. In the actual universe, this curvature occurs in 4 dimensions, 3 of space and 1 of time, and is described mathematically by the metric tensor, which specifies the geometry at each point. When mass or energy is introduced into this framework, the curvature changes, and the geodesics adapt accordingly. A star does not tug on a planet. It reshapes the space-time around it, and the planet moves along the new geometry. The orbit of Mercury provides a concrete example of this phenomenon. For centuries, astronomers noted that Mercury's orbit shifted slightly with each revolution. While Newtonian mechanics could explain most of the motion, a small discrepancy remained. This anomaly was unaccounted for until Einstein applied his field equations to the problem. When he modeled the curvature of spacetime near the Sun and calculated Mercury's path as a geodesic in that curved geometry, the unexplained precession appeared naturally. It was one of the first major triumphs of general relativity and showed that the apparent deviation in Mercury's orbit was not due to unknown forces or unseen objects, but to the warping of spacetime itself. Curved spacetime also affects light. Although photons are massless, they still travel along geodesics, called null geodesics in this context. When a light beam passes near a massive object, its path bends, not because gravity is pulling on it, but because space-time is curved in such a way that the straightest path itself is no longer straight in the Euclidean sense. This bending of light was famously confirmed during the 1919 solar eclipse, when starlight passing near the Sun was observed to shift position, validating Einstein's predictions and confirming that light, too, follows the geometry of the universe. But the implications go far beyond individual orbits or deflected beams. The geometry of spacetime determines the entire structure of cosmic motion. The rotation of galaxies, the behavior of galaxy clusters, and the evolution of the universe itself all arise from the curved pathways shaped by mass and energy. In this view, motion is no longer about objects pushing against one another, but about the universe guiding everything along invisible rails formed by geometry. On cosmological scales, general relativity reveals that spacetime itself is not only curved locally, near stars or black holes, but may be curved on the scale of the universe. Depending on the total amount of mass energy in the cosmos, the universe may be globally flat, positively curved like a sphere, or negatively curved like a saddle. These possibilities correspond to different global geometries, each with distinct implications for the shape, fate, and size of the cosmos. Observations of the cosmic microwave background suggest that the universe is very close to flat, meaning that on the largest scales, spacetime behaves like a Euclidean plane. But small curvatures remain possible, and in any case, local curvature dominates the experiences of objects like stars, planets, and us. Even in flat universes, local curvature due to galaxies and clusters remains deeply relevant. Gravitational lensing, one of the key observational tools in modern astrophysics, relies entirely on this principle. As light from distant galaxies passes through curved spacetime shaped by intervening mass, it bends and distorts, creating multiple images, arcs, or rings. These features are not artifacts of flawed optics, but natural outcomes of geodesics passing through dynamically curved geometries. One of the most counterintuitive ideas of general relativity is that stationary objects, such as a rock resting on the ground, are not following geodesics. In fact, they are being held in place by a force preventing them from following their natural path through curved spacetime. The ground pushes upward, deviating the object from free fall, and thus from its geodesic. Conversely, an object in orbit is actually moving along a geodesic. Though it may appear to be accelerating, it is in a state of pure inertial motion within a curved geometry. The curved path is not the result of a changing force, but the geometry defining what it means to move without force at all. Einstein's insight replaces the classical image of orbits as balances between centripetal and centrifugal forces with a cleaner, subtler concept. The orbit is simply what a straight path looks like when space and time are curved. The same is true of free fall. Objects fall not because they are drawn toward the Earth, but because their natural path through space-time dips inward toward the center of mass. The Earth's surface prevents us from continuing on that geodesic, which is why we feel weight. The apparent force we attribute to gravity is, in this sense, the result of resisting the natural geometry of our motion. The tools used to describe this geometry, tensors, connections, curvature scalars, may be mathematically abstract, but they encode physical reality. The Riemann curvature tensor, for instance, quantifies how space-time bends in the presence of energy. Through Einstein's field equations, this curvature is related directly to the distribution of matter and energy via the stress-energy tensor. In doing so, general relativity makes a profound statement. Motion arises from curvature, and curvature arises from content. The paths traced by planets, photons, and even empty space are all consequences of what resides within the universe. This geometric vision does not stop at astronomy. Even the passage of time itself, measured by clocks, is influenced by curvature. As established in earlier discussions, time passes differently depending on the geodesic an object follows and the curvature it experiences. The deepest implication of this is that every experience, every movement, every signal exchanged between particles is governed by geometry. The full power of general relativity becomes apparent when we consider how consistently it predicts physical behavior. Gravitational waves, observed a century after their prediction, are not mysterious emanations from deep space. They are ripples in the geometry of spacetime itself, propagating outward from cataclysmic events like merging black holes. These waves affect matter by stretching and compressing the distances between objects, not through traditional forces, but by altering the geometry through which they move. And yet, despite this complexity, the essential idea remains beautifully simple. Mass curves spacetime. Curved spacetime tells matter how to move. And that motion, from planetary orbits to cosmic expansion, arises not from mystical forces, but from geodesics through a flexible, responsive universe. In this framework, nothing is truly static. Even a lone object in the darkness of space is part of a broader structure, a curvature it both experiences and contributes to. The object's path, though it may seem empty or isolated, is guided by the geometry woven into the fabric of the cosmos. It is not alone. It is not disconnected. It is embedded always in a larger whole. And perhaps that is the most profound idea of all, that every motion, every orbit, every fall is not an act of separation, but a quiet unfolding of connection. The curve of your path is written by the stars. The shape of your time is guided by distant galaxies. In every movement, you are in dialogue with the universe itself. Chapter 6. Light bends and echoes through gravity. For much of human history, light was thought to be the fastest and straightest moving thing in the universe, an entity immune to influence, untouched by gravity or matter. In Newtonian physics, gravity affected only objects with mass, and light, having none, should have remained forever unbent, an untouchable probe of the cosmos. But general relativity, with its sweeping reimagining of gravity not as a force but as geometry, changed that understanding forever. In Einstein's framework, light does not travel through space as though the medium is flat and passive. Instead, light travels through spacetime itself, and when that spacetime is curved by mass or energy, the path of light must curve as well. The effect is not because gravity pulls on light in the traditional sense, but because the spacetime that light moves through is itself bent. Light always moves along what are called null geodesics, the natural paths dictated by the curvature of spacetime for entities that have no mass. These paths, when projected into space alone, often appear bent or distorted. This idea had a bold and testable prediction. If light from a distant star passed near a massive object, such as the sun, its path should curve, and the star would appear to shift position in the sky. In 1919, during a total solar eclipse, astronomers led by Sir Arthur Eddington confirmed this effect. Starlight that passed close to the sun was indeed deflected by an amount precisely predicted by Einstein's equations. It was the first observational triumph of general relativity, and the moment when the theory began to reshape not only physics, but the popular imagination. But the bending of light is not limited to stars seen during eclipses. It happens constantly throughout the universe, on scales large and small. Galaxies and galaxy clusters act as gravitational lenses, distorting and magnifying the light from more distant objects behind them. Sometimes this leads to visible effects like Einstein rings, perfect circles of light created when a background source, a foreground lens, and the observer are perfectly aligned. Other times, the result is more subtle. Multiple images of the same galaxy or quasar, arcs stretching across the sky, or faint duplications of light that has taken different curved paths to reach us. Gravitational lensing, as this phenomenon is known, has become one of the most powerful tools in astrophysics and cosmology. It allows us to study galaxies too faint or too distant to observe directly. It can reveal the presence of dark matter, an otherwise invisible form of matter, through its gravitational effects on light passing nearby. Because dark matter does not emit or absorb light, we cannot see it directly, but we can detect how it distorts the paths of light around it, mapping its distribution throughout the cosmos. Even more subtly, gravitational lensing can affect the cosmic microwave background, the afterglow of the Big Bang. As this ancient light travels across billions of years, it passes through the gravitational fields of intervening structures. These fields gently nudge the paths of the photons, altering the distribution of temperature and polarization we observe today. By studying these tiny distortions, cosmologists gain insight into the structure and evolution of the universe, as well as the nature of dark energy and the shape of spacetime itself. Another profound consequence of curved spacetime is the gravitational redshift of light. As light climbs out of a gravitational well, it loses energy, not in the sense of slowing down, since the speed of light remains constant, but by stretching its wavelength. This shift to longer, redder wavelengths is a prediction of general relativity and has been observed in laboratory settings and in astronomical environments. Light emitted from the surface of a white dwarf star, for instance, is redshifted due to the star's intense gravity. Similarly, light escaping from the edge of a black hole becomes so redshifted that, to an outside observer, it fades into invisibility, a phenomenon that defines the event horizon itself. Gravitational redshift is not just a curiosity, it has practical implications. The clocks aboard GPS satellites experience both special relativistic time dilation from their motion and general relativistic shifts due to the weaker gravity at orbital altitude. As a result, signals from the satellites are slightly redshifted compared to ground-based clocks. Engineers must correct for this shift to maintain the accuracy of positioning systems. Without accounting for the redshift, the entire GPS network would fail within hours. Another elegant prediction of general relativity is gravitational time delay, sometimes called the Shapiro delay. When light passes near a massive object, not only is its path bent, but the time it takes to traverse that path is increased. This delay arises because the geometry of spacetime near mass is stretched compared to flat space. Even if the spatial distance between 2 points remains the same, the temporal interval increases. This effect has been measured with radar signals sent to planets and reflected back. When the signals pass near the Sun, they take slightly longer to return than expected, an effect that matches the predictions of general relativity with remarkable accuracy. Gravitational time delay has also been observed in more distant settings. When light from a quasar or supernova is gravitationally lensed by a galaxy, it can take multiple paths to reach us. Because each path traverses a different region of spacetime, the light arrives at slightly different times. In some cases, we see the same cosmic event, such as a supernova, occur multiple times, each image appearing days, weeks, or even years apart. These echoes through gravity offer unique opportunities to measure the expansion of the universe, probe the structure of spacetime, and test the predictions of general relativity under extreme conditions. Even gravitational waves, ripples in spacetime caused by accelerating masses, interact with light in measurable ways. When a gravitational wave passes through a region, it stretches and compresses spacetime itself. Light moving through that region is affected by these distortions. In detectors like LIGO, laser beams are split and sent down perpendicular arms. As a gravitational wave passes, the length of each arm changes slightly, causing the beams to shift in phase when they recombine. The result is a pattern that reveals the passage of the wave, not because the light itself is distorted, but because the space it travels through has changed. This interplay between light and spacetime makes it possible to use photons as messengers, not just of the matter that emitted them, but of the geometry they've traversed. Every beam of light carries with it a memory of the spacetime it moved through. Every deflection, every shift, every delay encodes information about the gravitational landscape it encountered. Light is not merely illumination. It is a probe, an explorer, and a silent archivist of the universe's shape. Perhaps one of the most dramatic applications of these ideas is in the study of black holes. Near a black hole, spacetime is so curved that light can become trapped in orbit. There exists a region, known as the photon sphere, where light can circle the black hole endlessly. If a photon enters this region at just the right angle, it can orbit indefinitely, though any slight deviation will either send it spiraling into the event horizon or escaping into space. These photon spheres contribute to the visual appearance of black holes, and were crucial in generating the shadow observed in the Event Horizon Telescope's image of the supermassive black hole in M87. The light that grazes the photon sphere and escapes carries with it a distorted and amplified image of the surrounding space. Multiple images can be formed as light orbits the black hole several times before emerging, each image increasingly demagnified and delayed. These layers of light encode an intricate map of the black hole's geometry, a fingerprint of spacetime under the most extreme conditions. Even in more modest settings, the interaction between light and gravity shapes how we perceive the cosmos. The expansion of the universe causes distant galaxies to appear redshifted, their light stretched as space itself expands. While this cosmological redshift is distinct from gravitational redshift, it is another way in which light reflects the nature of space-time. By measuring these redshifts, astronomers can determine how fast galaxies are moving away from us, and thus reconstruct the history and future of cosmic expansion. Together, these phenomena, bending, redshift, delay, and lensing, reveal a picture of light not as a passive traveler, but as a participant in the story of the universe. Light moves through space-time, but it also responds to it. The photons we detect in our telescopes are not just bearers of information from distant places. They are witnesses to curvature, to expansion, to distortion, and to delay. Every star we see, every galaxy we map, every flare we observe from the distant universe comes to us through a winding, curved, and gravitationally textured path. And yet, despite these twists and bends, light still arrives. Across billions of years and unfathomable distances, it travels with fidelity, bringing us echoes of ancient events, glimpses of unreachable places, and evidence of the very structure of space-time. It is light that allows us to see, but more profoundly, it is light that allows us to know. Perhaps, then, the bending of light is not just a demonstration of gravity's reach, but a quiet reminder that in the deepest fabric of reality, even the straightest thing we know, the photon's path, yields to the shape of existence. And that in bending, light shows us how connected everything truly is. Chapter 7. Black holes, the ultimate curves in spacetime. Among all the predictions of general relativity, few are as startling, extreme, or counterintuitive as the black hole. In the mathematical structure of Einstein's theory, black holes arise not as artificial constructs or theoretical indulgences, but as natural, unavoidable solutions to the field equations. They represent the ultimate expression of gravitational curvature, regions where space-time is no longer gently bent, but folded so severely that all paths lead inward, and nothing, not even light, can escape. The existence of black holes was first hinted at long before Einstein in the late 18th century, when scientists like Jean Michel and Pierre-Simon Laplace speculated that a sufficiently massive object could have an escape velocity greater than the speed of light. But without a theory of light as particles or a relativistic framework, these ideas remained little more than curiosities. It wasn't until Karl Schwarzschild in 1916 provided the first exact solution to Einstein's equations for a non-rotating, spherically symmetric mass that the black hole concept took a more rigorous shape. This solution revealed a critical radius, now called the Schwarzschild radius, within which the curvature of space-time becomes so intense that all geodesics, whether followed by particles or photons, converge inward. This boundary is known as the event horizon. It is not a surface in the traditional sense. It has no substance, no material structure. It is a one-way threshold. Once crossed, no signal, no information, and no influence can return to the outside universe. From the perspective of general relativity, the event horizon marks the boundary beyond which the known laws of physics cease to provide predictive power for external observers. What lies within the event horizon remains speculative, but according to classical general relativity, the collapse of matter continues inward, compressing into a single point of infinite density, a singularity. At this singularity, the curvature of spacetime becomes infinite, and tidal forces stretch and compress matter into oblivion. While such infinities are likely signs that general relativity breaks down at quantum scales, no complete theory of quantum gravity yet exists to replace this prediction. What is certain is that no known mechanism prevents collapse once the event horizon has formed, making black holes some of the most stable and persistent objects in the universe. Despite their terrifying mathematical properties, black holes are real astrophysical objects. They form naturally when massive stars reach the end of their nuclear life cycles. When a star runs out of fuel, it can no longer support itself against the inward pull of gravity. If the remnant core is sufficiently massive, no known force, not even the degeneracy pressure that holds white dwarfs and neutron stars apart, can halt the collapse. The result is a stellar mass black hole, typically several times the mass of our Sun, but occupying a region only a few kilometers wide. Such objects were once considered invisible, detectable only through indirect effects on nearby matter. But observational techniques have advanced dramatically. One key method is the study of accretion disks of gas and dust spiraling into a black hole. As material falls inward, it heats up due to friction and compression, emitting intense radiation, particularly in the X-ray spectrum. Space telescopes like Chandra and XMM Newton observe these emissions, allowing astronomers to detect black holes even when the event horizon itself cannot be seen. Another major breakthrough came with the observation of gravitational waves. When two black holes spiral toward one another and merge, they generate ripples in space-time, gravitational waves that travel outward at the speed of light. In 2015, the LIGO detectors made the first direct observation of such a signal, marking the dawn of gravitational wave astronomy. These waves carry information about the mass, spin, and distance of the colliding black holes, offering a new window into the dark and dynamic processes of the cosmos. Then, in 2019, came the first image of a black hole's shadow, captured by the Event Horizon Telescope, a global network of radio observatories working in synchrony. This composite image of the supermassive black hole at the center of Galaxy M87 showed a dark central region surrounded by a glowing ring of light. The ring was not light emitted from within the black hole, but rather from hot gas swirling just outside the event horizon, bent and focused by the intense gravitational lensing. The image confirmed predictions made decades earlier, including the size and shape of the shadow cast by the event horizon on the glowing backdrop of inflowing matter. Black holes vary in size from the stellar mass kind formed in supernovae to the supermassive ones found at the centers of galaxies, which can contain millions or even billions of solar masses. The origin of these supermassive black holes remains an open question in astrophysics. They may have formed from the collapse of massive primordial clouds or through the mergers of many smaller black holes and stars over cosmic time. Whatever their origin, they play a crucial role in galactic evolution, regulating star formation through feedback mechanisms powered by accretion and relativistic jets. Some galaxies contain active galactic nuclei, where matter falling into a supermassive black hole releases enormous amounts of energy, outshining the combined light of billions of stars. These objects, known as quasars when viewed from afar, are powered by the conversion of gravitational potential energy into radiation. In falling matter heats to extreme temperatures, emitting light across the electromagnetic spectrum. These phenomena provide not only a laboratory for testing extreme physics, but also a means of probing the early universe, since many quasars are seen at great distances, revealing conditions billions of years ago. The physics near black holes also challenges our understanding of information and entropy. In the 1970s, Stephen Hawking showed that black holes are not entirely black. Quantum effects near the event horizon cause them to emit radiation, now known as Hawking radiation. This radiation is incredibly faint for astrophysical black holes, but has profound implications. It suggests that black holes can slowly lose mass and eventually evaporate over timescales far longer than the current age of the universe. This leads to the so-called black hole information paradox. If Hawking radiation is purely thermal and carries no information about the matter that fell in, then information appears to be lost when a black hole evaporates. This contradicts a core principle of quantum mechanics, that information must be conserved. Resolving this paradox is a major challenge in theoretical physics, and several proposed solutions, ranging from holographic principles to quantum entanglement across the horizon, are currently under investigation. Black holes also raise profound questions about the nature of spacetime itself. Near the event horizon, coordinate systems behave strangely. Time for an outside observer appears to slow to a halt as an object approaches the horizon, while the falling object experiences no such slowdown. This discrepancy is not an illusion, but a real consequence of the geometry of spacetime. The division between what is visible and what is not, between causally connected and disconnected regions of the universe, becomes sharp and absolute. In theoretical extensions of general relativity, even more exotic objects are predicted. Solutions such as the Kerr metric describe rotating black holes which possess not just mass but angular momentum. These rotating black holes exhibit complex structures, including ergospheres, regions outside the event horizon where no object can remain stationary, and the possibility of extracting energy through processes like the Penrose mechanism. Some solutions even allow for hypothetical wormholes, tunnels through spacetime that might connect distant regions, but these require forms of matter or energy that violate known physical laws. Despite these speculative extensions, the core concept remains solid. Black holes are not science fiction. They are testable, observable, and deeply integrated into our understanding of the universe. They serve as the ultimate laboratories for physics, where theories are pushed to their limits and where new physics may one day be discovered. Their formation, evolution, and interactions shape galaxies, seed quasars, and emit gravitational waves that ripple across the universe. They also serve as boundaries, both literal and conceptual. Boundaries beyond which we cannot see, cannot send signals, cannot retrieve data. And yet, these boundaries are not just limits. They are portals to deeper understanding, to more refined theories, to questions still unanswered. They remind us that even the most elegant theories may reach an edge, and that at those edges, new insights await. Perhaps what makes black holes so compelling is not just their power or their mystery, but their precision. They are not chaotic or arbitrary. They obey the laws of physics with an exactness that challenges us to refine those laws further. They are the ultimate expression of curvature, the final answer to what happens when gravity is taken to its logical extreme. And yet, in their silence, in their darkness, they speak volumes. They tell us that nature does not flinch from extremes, that the fabric of reality can stretch, fold, and collapse in on itself, and that even in those places where no light escapes, something fundamental is preserved. The unity between geometry and motion, between energy and space, between time and its end. Chapter 8. Gravitational Waves. ripples in the fabric of reality. In the framework of general relativity, mass and energy shape the geometry of spacetime, and in turn, that geometry dictates how matter and light move. For many years after Einstein's theory was published, physicists understood that this interaction could be static, like the persistent curvature around a star or a planet. But the equations also implied something more dynamic. If spacetime could bend, then it could also ripple. And if those ripples could propagate outward, then gravity, like light, might carry energy across the cosmos in the form of waves. These hypothetical distortions are known as gravitational waves. They are not vibrations in a medium like air or water. They are not waves traveling through space. They are waves of space, oscillations in the very metric that defines distance and time. As they pass through a region, they stretch and compress space-time itself, altering the relative positions of objects without applying any force in the traditional sense. These waves are fantastically weak, difficult to detect, and yet they are among the purest messengers the universe can offer. Unlike light or particles, they are unaffected by dust, gas, or magnetic fields. They pass through matter with near impunity, preserving the imprint of the cataclysmic events that produced them. Einstein first predicted the existence of gravitational waves in 1916, just 1 year after completing his general theory of relativity. The mathematical foundation was clear, but whether these waves could be physically real and whether they could ever be observed remained topics of debate for decades. Some believed they might be mere artifacts of coordinate choice, mathematical ripples with no measurable consequences. Others argued they must exist, but would be so weak that no instrument could ever detect them. The generation of gravitational waves requires the acceleration of mass, but not just any motion will do. Because gravity is a quadrupole interaction, meaning it cannot radiate energy from spherically symmetric motion, objects must accelerate asymmetrically. A pair of orbiting stars, for example, constantly changes the shape of the gravitational field around them, sending out ripples in the geometry of spacetime. The more massive the objects and the faster they move, the stronger the signal. The most powerful gravitational waves come from the most violent processes in the universe: black hole mergers, neutron-star collisions, and core collapse supernovae. For many years, the evidence for gravitational waves was indirect. In 1974, astronomers Russell Hulse and Joseph Taylor discovered a binary pulsar system, 2 neutron stars orbiting each other with extraordinary precision. Over time, they observed that the orbit was shrinking, with the 2 stars spiraling slowly toward one another. The rate of this orbital decay matched perfectly the predictions of general relativity, assuming that gravitational waves were being emitted and carrying energy away. This discovery earned them the Nobel Prize in Physics and provided the first compelling observational support for gravitational wave theory. But the waves themselves still had not been directly detected. That changed in 2015, nearly a century after Einstein's prediction, when the Laser Interferometer Gravitational Wave Observatory, LIGO, made history. On September 14th of that year, detectors in Livingston, Louisiana and Hanford, Washington recorded the passing of a gravitational wave. The signal matched the theoretical waveform of 2 black holes, each about 30 times the mass of the Sun, merging over 1 billion light-years away. In just a fraction of a second, the black holes coalesced, releasing a burst of gravitational radiation that briefly exceeded the total power output of the observable universe. But by the time the wave reached Earth, its effect was tiny, changing the length of LIGO's 4-kilometer arms by less than 1,000th the diameter of a proton. LIGO works by using laser interferometry. A beam of laser light is split and sent down 2 perpendicular arms. The light reflects off mirrors and returns to the starting point, where the beams are recombined. If a gravitational wave passes through, it slightly stretches one arm while compressing the other, creating a telltale interference pattern in the recombined light. The engineering precision required to isolate such minuscule distortions is staggering. Vibrations from seismic activity, traffic, or even thermal fluctuations in the atoms of the mirrors must be meticulously filtered out. But when the signal emerges, clean, distinct, and matched to theoretical models, it carries with it the fingerprint of a distant cosmic dance. Since that first detection, dozens more gravitational wave events have been observed, including mergers between black holes, collisions between neutron stars, and mixed systems of black holes and neutron stars. These discoveries have expanded our understanding of stellar evolution, compact objects, and the population of massive remnants in the universe. In 2017, the detection of a neutron star merger, GW170817, was observed not only in gravitational waves, but across the electromagnetic spectrum. Telescopes around the world captured the fading light from the aftermath of the collision, revealing the creation of heavy elements like gold and platinum. This event marked the beginning of multi-messenger astronomy, where gravitational waves and light combine to provide a richer view of the universe. Gravitational waves have also opened new avenues for testing general relativity. By analyzing the detailed structure of the waveforms, how quickly they rise and fall, how they shift in frequency, scientists can test the predictions of Einstein's equations in the strongest gravitational fields ever observed. So far, the results have been remarkably consistent with general relativity. No deviations have been found, no signs of alternative theories emerging. But the search continues, and as detectors become more sensitive, they may uncover subtle differences or new phenomena that hint at deeper physics. Current observatories like LIGO and Virgo are already being upgraded, and new detectors such as CAGRA in Japan and the planned Einstein telescope in Europe will increase both sensitivity and coverage. Perhaps even more transformative will be LISA, the Laser Interferometer Space Antenna, a European Space Agency mission scheduled for the 2030s. LISA will consist of 3 spacecraft orbiting the Sun in a triangle millions of kilometers apart, detecting gravitational waves with periods far longer than ground-based instruments can measure. This will allow it to detect signals from supermassive black hole mergers, extreme mass ratio inspirals, and possibly even waves from the early universe. At the largest scales, some scientists hope to detect a gravitational wave background, a persistent hum of waves from countless unresolved sources, or even from primordial events shortly after the Big Bang. This background, if discovered, would serve as a cosmic fossil, preserving information about epochs otherwise inaccessible to direct observation. Pulsar timing arrays, networks of precisely monitored pulsars, are already seeking this signal by looking for correlated fluctuations in the arrival times of pulses due to passing gravitational waves. Preliminary hints have emerged, suggesting that the background may be within reach. What makes gravitational waves so remarkable is that they extend our senses. For centuries, astronomy was limited to what we could see, and later to what we could detect across different forms of light. Gravitational wave astronomy is not a replacement for electromagnetic observation. It is a new sense entirely. It reveals objects invisible to telescopes, events hidden behind gas and dust, and motions too subtle to emit light. It is like hearing the universe for the first time, not in metaphor, but in physical truth. The signals we now detect were always there, always passing through us. We just didn't know how to listen. Each detection is a record of movement, a fossil of motion in spacetime. Where light tells us what something looks like, gravitational waves tell us how something changed. They do not scatter. They do not reflect. They carry the story directly, unedited, across billions of light years. A black hole merger that took place before life arose on Earth can shake our detectors today, connecting our present to a past far beyond memory. In the coming decades, gravitational waves may also help answer some of the deepest questions in physics. They may provide clues about the behavior of matter at nuclear densities, the limits of neutron star stability, or the equation of state for ultradense matter. They may hint at the nature of dark matter if compact objects made of exotic material contribute to the observed signals. And they may one day point toward a unification of general relativity with quantum mechanics, revealing cracks in the smooth fabric of classical gravity. The ripples that travel through space-time are not loud. They do not announce themselves with brilliance or color. They pass quietly, gently stretching the dimensions of space and time as they go. And yet, in those subtle distortions lies an entire narrative. The slow collapse of orbiting stars, the final breath of a massive core, the echo of symmetry broken in the early cosmos. Gravitational waves are silent messengers, but they carry deep truth. And perhaps that is what makes them feel so profound. That the universe does not speak only in light. That sometimes the cosmos whispers, and if we listen carefully enough, we can feel it moving. Chapter 9. Testing Einstein, How We Know It's True. A theory is only as powerful as its predictions and only as trustworthy as the experiments that verify them. When Albert Einstein published his theory of general relativity in 1915, he offered not just a reinterpretation of gravity, but a radical reshaping of our understanding of space, time, and the geometry of the universe. Yet elegant mathematics and philosophical appeal alone are not enough to validate a scientific theory. General relativity made specific, testable predictions about the behavior of light, the motion of planets, the ticking of clocks, and the transmission of gravitational influences. Over the following century, those predictions have been tested in one of the most rigorous and expansive programs of empirical scrutiny in the history of science. Perhaps the earliest and most iconic test came in 1919. Einstein had predicted that light would bend as it passed near a massive object like the sun, not because the sun exerted a force on photons, but because its mass curved the space-time through which the light traveled. During a total solar eclipse that year, teams of astronomers led by Arthur Eddington photographed stars whose light passed close to the sun's edge. When the sun's brilliance was momentarily blocked, they could see that the stars appeared displaced, shifted slightly outward from their expected positions. The amount of bending matched Einstein's prediction, and the result catapulted general relativity from mathematical speculation into the realm of observable reality. But that was only the beginning. One of the strongest early confirmations came from the motion of Mercury, the innermost planet in the solar system. For centuries, astronomers had puzzled over the slow rotation of Mercury's orbit. Its perihelion, the point of closest approach to the Sun, shifted slightly with each revolution. Newtonian mechanics could account for most of the precession due to perturbations from other planets, but not all of it. About 43 arcseconds per century remained unexplained. When Einstein applied his equations to the curvature of spacetime near the Sun, the discrepancy vanished. General relativity provided precisely the amount of additional precession needed. This success offered not just a checkmark, but a quantitative triumph, turning the long-standing anomaly into a signature prediction. Another crucial area of confirmation involves time itself. One of general relativity's boldest implications is that time does not pass uniformly across space. In regions of stronger gravity, time moves more slowly compared to regions of weaker gravity. This gravitational time dilation was tested directly in 1960 using an experiment known as the Pound-Rebka test. Gamma rays were emitted from the top of a tower and detected at the bottom, where Earth's gravity was slightly stronger. The frequency of the gamma rays shifted in exactly the manner predicted by Einstein's equations, confirming that time had indeed flowed differently over the short vertical distance. Later experiments extended this to ever greater precision. Atomic clocks flown in airplanes or carried to mountain peaks ticked at slightly different rates than identical clocks at sea level. Satellite-based systems, such as the Global Positioning System, must account for both special and general relativistic effects to maintain accuracy. The onboard clocks in GPS satellites tick faster due to the reduced gravitational potential in orbit. If engineers ignored these relativistic effects, even though they amount to mere nanoseconds per second, location errors would accumulate rapidly, leading to positional drift of kilometers each day. The practical necessity of relativistic corrections provides one of the most everyday demonstrations of the theory's predictive power. Beyond Earth, the behavior of binary pulsars, rotating neutron stars locked in close orbits, has offered profound confirmation of general relativity in strong gravitational fields. The Hulse-Taylor pulsar system, discovered in 1974, allowed astronomers to measure the orbital decay caused by the emission of gravitational radiation. The rate of orbital tightening matched exactly the predictions from general relativity, providing indirect but compelling evidence for gravitational waves long before their direct detection. Over time, additional binary pulsars have been found and studied, and each system has reinforced the theory's accuracy. In the realm of light propagation, gravitational lensing, the bending and distortion of light by massive objects, has become both a tool and a test. Astronomers routinely observe galaxies whose light has been curved around other galaxies or clusters, forming arcs, rings, or multiple images. These observations match detailed simulations based on Einstein's equations. Moreover, when background sources vary in brightness over time, such as quasars, the lensed images vary with slight time delays. These delays encode the curvature of spacetime along different paths and have been used to test the theory on cosmological scales. One of the most striking demonstrations came with the Event Horizon Telescope in 2019. By linking radio observatories across the globe, astronomers created a virtual Earth-sized telescope capable of resolving the region near a black hole's event horizon. The image of the supermassive black hole in Galaxy M87 revealed a bright, asymmetric ring of light encircling a dark shadow, consistent with predictions made decades earlier. The size and shape of the shadow, as well as the lensing of light around it, matched models derived from general relativity, confirming the theory's applicability in extreme conditions near a black hole. The arrival of gravitational wave astronomy has brought even more precise and dynamic tests. When LIGO first detected a gravitational wave in 2015, the waveform was not merely an unexpected signal. It was a fingerprint of two black holes spiraling into each other and merging. The shape of the wave, its frequency, and its amplitude evolution all matched numerical simulations derived from Einstein's field equations. Since then, dozens of events have been recorded, each one allowing scientists to probe the theory in new ways. Observations of neutron star mergers, in particular, have allowed researchers to test general relativity not only through gravitational waves, but also through light, as the collisions emit gamma rays, visible light, and other electromagnetic signals. No deviations have been found. Across scales, from subatomic timing to cosmological motion, general relativity has passed every test. But physicists do not take this success as final proof. They seek areas where the theory might break down, both to refine their understanding and to find hints of deeper physics. For instance, the theory does not yet account for the quantum nature of particles and fields. In regions of extreme curvature, such as the center of black holes or the origin of the universe, quantum gravitational effects are expected to become important. Yet general relativity is a classical theory with no inherent quantum structure. Bridging that gap is one of the grand challenges of modern theoretical physics. In some scenarios, proposed alternatives to general relativity introduce new fields, or modify the equations slightly to explain phenomena like cosmic acceleration or the nature of dark energy. These alternatives often reduce to Einstein's theory in familiar situations, but diverge under extreme conditions. Testing these differences requires ultra-precise observations. Ongoing and future missions, such as the LISA Gravitational Wave Observatory, the Euclid Space Telescope, and pulsar timing arrays, aim to explore regimes where new physics might reveal itself. Even the constancy of the speed of gravity has been tested. When gravitational waves and light from the neutron star merger GW-7817 arrived nearly simultaneously, despite traveling over 100 million light-years, scientists confirm that gravitational waves move at the speed of light to within a fraction of a percent. This ruled out entire families of modified gravity theories and reaffirmed Einstein's original formulation. The breadth of experimental confirmation for general relativity is vast. From solar system tests to binary stars, from GPS corrections to black hole images, from gamma-ray shifts to spacetime ripples, the evidence forms a coherent, interlocking web. It is one thing to make a single correct prediction. It is another to predict, with unwavering accuracy, the outcome of hundreds of tests across nearly every branch of physics and astronomy. Still, the very strength of general relativity invites scrutiny. The more successful a theory, the more important it becomes to probe its limits. Physicists continue to test for violations of the equivalence principle, the constancy of physical constants, and possible quantum deviations in gravitational behavior. The search is not driven by doubt, but by curiosity. If the theory does break down somewhere, that crack may be the doorway to the next stage in our understanding of reality. What makes Einstein's work endure is not just that it has passed so many tests, but that it invited so many in the first place. It provided a framework not merely to explain existing data, but to anticipate phenomena we had never before imagined. It guided the design of satellites, observatories, and missions decades before the necessary technology existed. And when the instruments finally caught up, the universe behaved exactly as the equations had predicted. There's something quietly profound in that consistency, that the patterns traced in chalk on a blackboard a century ago now describe the behavior of galaxies, the ticking of satellite clocks, the bending of light, and the shudder of space-time itself. That a mind on Earth once peered into the nature of geometry and found the universe written there. And perhaps that is the real test of Einstein's theory, not only that it is true, but that it makes reality itself more intelligible. In the curves of space-time and the rhythm of falling objects, we glimpse not just accuracy, but clarity, a harmony between thought and world. Chapter 10. The Edges of Understanding, where relativity meets quantum physics. General relativity and quantum mechanics are the two great pillars of modern physics. Each is a triumph of human understanding, elegant, predictive, and experimentally verified to astonishing precision. General relativity describes the world of the very large, the motion of planets, the bending of starlight, the warping of space-time around black holes, and the expansion of the universe itself. Quantum mechanics, in contrast, rules the realm of the very small, electrons and atoms, photons of light, the behavior of subatomic particles, and the fundamental uncertainties built into nature. Each theory works extraordinarily well in its own domain, but they are not compatible with one another. At ordinary scales, this incompatibility is unnoticeable. For most practical purposes, the effects of both theories can be applied independently. A GPS satellite uses quantum mechanics to operate its atomic clock and general relativity to correct for gravitational time dilation. Each part of the system works because it applies to different aspects of the satellite's operation. But in extreme environments, where very strong gravitational fields interact with very small distances, this separation breaks down. In these domains, such as the center of a black hole or the first moments of the Big Bang, both theories must apply simultaneously, and when they are brought together, contradictions emerge. General relativity treats spacetime as continuous and smooth. It is a geometric object whose curvature changes in response to mass and energy. The Einstein field equations describe how this curvature evolves, and the solutions are deterministic. Given initial conditions, the theory predicts what spacetime will look like at all future times. It is a classical theory in the deepest sense. Quantum mechanics, by contrast, is probabilistic. It introduces a fundamental uncertainty into nature, embodied in Heisenberg's uncertainty principle. Particles do not follow precise paths. Instead, they exist as wave functions, clouds of probability describing where they might be. Quantum theory also introduces discrete quantities, energy levels, spin states, and the quantization of fields. It is a world built from indivisible units and governed by inherent fuzziness. Bringing these views together, quantizing a geometric fabric, proves immensely difficult. Efforts to merge them have produced various lines of inquiry, none of which is yet complete. One of the earliest approaches was quantum field theory in curved spacetime, which treats matter and radiation as quantum fields but keeps gravity classical. This semi-classical approximation has had success in limited domains, such as explaining Hawking radiation, the theoretical prediction that black holes emit thermal radiation due to quantum effects near the event horizon. But it is not a full quantum theory of gravity because it treats spacetime as a passive stage rather than a dynamic quantum entity. A complete quantum theory of gravity would treat spacetime itself as quantized. That is, just as matter is made of atoms and energy is made of photons, space and time would be composed of discrete units, perhaps tiny loops, strings, or spin networks. Several theoretical frameworks attempt to describe this possibility. String theory is one such candidate. It proposes that the fundamental constituents of the universe are not point particles, but one-dimensional strings vibrating at different frequencies. These strings naturally include a graviton, a hypothetical quantum particle that mediates gravity, suggesting that gravity might emerge from string dynamics. String theory also predicts extra dimensions beyond the familiar four, compactified on scales too small to observe directly. In this higher dimensional framework, the apparent conflict between relativity and quantum mechanics might be resolved by embedding both in a more fundamental theory. Another approach is loop quantum gravity, which attempts to quantize spacetime directly without requiring extra dimensions. In this model, spacetime is represented as a network of finite loops of quantum geometry. These loops form a spin network, and the evolution of this network over time describes a spin foam. Loop quantum gravity predicts that space and time are discrete at the Planck scale, around 10 nomiusborn spin meters. In this picture, smooth spacetime emerges as an approximation, much like fluid behavior emerges from molecules. Despite their differences, both string theory and loop quantum gravity attempt to do the same thing. Describe a quantum version of gravity that reduces to general relativity on large scales and agrees with quantum mechanics on small ones. Yet neither has been experimentally confirmed. One reason is that the effects of quantum gravity are expected to be extremely subtle, only significant near singularities or in the early universe. Testing these ideas directly requires energy scales far beyond those currently accessible by particle accelerators. Still, indirect tests may eventually come. Some theorists propose that quantum gravitational effects could leave traces in the cosmic microwave background, the afterglow of the Big Bang, or in high-energy astrophysical phenomena like gamma-ray bursts. Others hope that tiny violations of known symmetries, such as Lorentz invariants, might offer clues. Even gravitational waves already detected from black hole mergers could someday carry imprints of quantum corrections if our detectors become sensitive enough. Another area of tension lies in the information paradox. According to quantum mechanics, information about a physical system is never lost. It may be scrambled, but it remains preserved. Yet if black holes evaporate through Hawking radiation, and that radiation is purely thermal, then information about the matter that fell into the black hole appears to be destroyed. This conflicts with the principle of unitarity in quantum mechanics. Resolving this paradox remains one of the key unsolved problems in physics. Some propose that information escapes in the radiation after all, in ways not yet understood. Others suggest that black holes may store information on their event horizons, a possibility captured in the holographic principle. The holographic principle suggests that all the information contained within a volume of space can be encoded on its boundary, much like a hologram stores three-dimensional information on a two-dimensional surface. This idea emerged from studies of black hole entropy, particularly the work of Jacob Bekenstein and Stephen Hawking, and has been developed further in the context of string theory and the ADS-CFT correspondence. These concepts hint at a radical possibility that spacetime itself might be emergent, arising from more fundamental quantum processes. If that is true, then general relativity would not be a fundamental theory, but an effective one, an approximation that emerges from a deeper quantum reality, just as thermodynamics arises from the collective motion of molecules. In this view, gravity, space, and time are not primary ingredients of the universe, but emergent phenomena arising from quantum entanglement, information theory, or other foundational structures. This line of thought also suggests that time itself might not be fundamental. In quantum mechanics, time is usually treated as an external parameter, not an operator like position or momentum. But if space-time is quantized or emergent, then time may arise from correlations between quantum systems, a statistical property rather than an absolute dimension. Such ideas challenge our deepest assumptions and open the door to a radically new understanding of causality, chronology, and the structure of the universe. Despite the elegance and ambition of these theories, the path forward remains uncertain. There is no consensus on which approach, if any, will ultimately succeed, nor is it clear what kinds of experiments might decisively verify a quantum theory of gravity. Some physicists are exploring analog systems, laboratory experiments that simulate aspects of black holes or expanding universes. Others are focused on finding mathematical consistency, believing that a coherent and beautiful theory must eventually connect to reality. The tension between general relativity and quantum mechanics is not a sign of failure, but a signal of incompleteness. Both theories have passed every test in their respective domains. Yet nature, in its fullness, encompasses both gravity and quantum behavior. Somewhere in the deep structure of space-time and matter, the two must come together. The search for this union is not merely a technical pursuit, it is a philosophical one, touching on the nature of existence, the meaning of measurement, and the ultimate architecture of reality. For now, we live in a world where both theories are true, but not yet unified, where black holes bend space-time while entangled particles defy classical intuition, where the expansion of the universe and the jitter of electrons coexist in uneasy silence, and in that silence, the next great theory waits. Something beyond geometry and probability, beyond curvature and collapse. Perhaps one day we will look back at both general relativity and quantum mechanics as stepping stones, brilliant but partial, on the way to a deeper insight. A theory that will not only describe the edge of black holes and the birth of the cosmos, but will also explain why space, time, and existence themselves came to be. And until then, we listen to the curve of gravity, to the whisper of particles, to the faint echo at the boundary between the known and the unknowable. Section 3, Special Relativity, the speed of light, time dilation, and E equals mc square. Chapter 1. What is special relativity? A quiet introduction. In the quiet world of physics before the 20th century, the universe seemed stable and predictable. The framework laid down by Isaac Newton in the 17th century described the motions of planets, falling apples, and cannonballs alike with extraordinary precision. For more than 2 centuries, this classical worldview offered comfort and clarity. Space was thought to be an unchanging stage upon which the drama of matter unfolded, and time was the universal rhythm to which everything danced. Every observer, it seemed, could agree on the ticking of the cosmic clock, and the distances in the vast theater of the universe appeared absolute. But as the 19th century unfolded, small cracks began to appear in the seemingly perfect structure. These cracks did not come from any failure of Newton's equations in describing everyday life, but from deeper questions raised by the strange behavior of light and electricity. James Clerk Maxwell had unified electricity and magnetism into a single, elegant theory, one that predicted electromagnetic waves moving through space at a fixed speed. This speed matched the measured speed of light, leading to the remarkable conclusion that light itself was a form of electromagnetic radiation. But this brought with it a puzzle. If light was a wave, what medium did it move through? Ocean waves need water, sound waves need air, and so physicists of the time imagined a kind of invisible medium called the luminiferous ether, filling all of space. The ether was supposed to be the substance against which absolute motion could be measured, the universal backdrop for the vibrations of light. Yet, as experiments tried to reveal this medium, it remained elusive. The most famous of these was the Michelson-Morley experiment of 1887, which attempted to measure the Earth's motion through the ether by detecting tiny differences in the speed of light moving in different directions. The result was baffling. No matter how carefully they looked, no difference was found. Light appeared to move at the same speed in every direction, regardless of the motion of the Earth. This result was not just puzzling, it was revolutionary. If the ether did not exist, then what did it mean for light to have a constant speed? If light traveled at the same speed no matter how fast an observer moved, then the basic assumptions about space and time had to be reconsidered. Yet for nearly 2 decades, no one fully resolved the dilemma. Some proposed that the apparatus of Michelson and Morley had contracted as it moved through the ether, a desperate explanation that patched the problem but offered no real clarity. Physics stood at a threshold, sensing a transformation, but unable to step through. Into this uncertainty stepped a young man working as a patent clerk in Bern, Switzerland. Albert Einstein was not a professor, nor part of the great European universities, but he carried with him an instinct for clarity, an ability to see through the clutter of assumptions and imagine a world built on simple, universal principles. In 1905, in a paper modestly titled On the Electrodynamics of Moving Bodies, he proposed a daring idea. Perhaps there was no ether, no hidden medium. Perhaps space and time themselves were not absolute at all. Einstein began from 2 postulates. The first was the principle of relativity. The laws of physics are the same in all inertial frames of reference, meaning that whether you are standing still or gliding at constant speed, the fundamental rules of the universe do not change. This was already familiar from Galileo's work centuries earlier, who had noted that the motions inside a smoothly sailing ship could not reveal whether the ship was moving steadily or at rest. The second postulate, however, was far more radical. The speed of light in a vacuum is constant, independent of the motion of the source or the observer. No matter how fast you chase after a beam of light, it will still recede from you at the same speed. At first glance, these two statements seem almost trivial, yet taken together they demand a complete reshaping of our understanding. For if the speed of light is always the same, then something else must give way. That something is our intuitive sense of time and space. Time cannot tick at the same rate for everyone if light is to maintain its constancy. Space cannot remain rigid if measurements of distance are to stay consistent across different observers. The absolutes of Newton's universe give way to a flexible fabric where intervals of time and space depend on motion and perspective. To appreciate the magnitude of this shift, imagine two observers watching the same event. One stands on a train platform, the other rides a train rushing past. In the Newtonian world, both would agree on when the event happened and where. But Einstein's insight revealed that they may disagree on both, not because one is mistaken, but because reality itself is relative to their state of motion. Their measurements of time and distance would differ, yet each would be entirely correct within their own frame of reference. There is no single universal clock, no shared grid of absolute space. Instead, the universe offers a deeper consistency. The laws of physics and the speed of light remain unbroken, even as time and space bend around them. This new picture did not emerge without resistance. To discard centuries of assumption required a boldness that unsettled many. Yet the elegance of Einstein's reasoning could not be denied. He showed that time slows down for moving clocks, distances contract for moving rulers, and events that seem simultaneous to one observer may not be simultaneous to another. These were not philosophical speculations, but logical necessities flowing from the postulates. The mathematics that supported them, though simple compared to the machinery of later physics, left no room for doubt. What makes special relativity so extraordinary is that it does not rely on exotic conditions or distant galaxies. It applies to every object moving at any speed. In daily life, the effects are too small to notice because we move so slowly compared to light. But at speeds approaching the cosmic limit, the consequences become dramatic. A spacecraft traveling near the speed of light would find its onboard clock ticking more slowly compared to clocks on Earth. Its length in the direction of motion would contract when measured by outside observers. The passengers would experience their journey as perfectly normal, yet the outside world would record a very different passage of time and distance. The term special in special relativity refers not to its importance, but to its scope. It is special because it applies only to inertial frames, those moving at constant speeds without acceleration. Gravity and acceleration require the broader framework of general relativity, which Einstein developed a decade later. But even within its limited domain, special relativity reshaped physics so profoundly that it became the foundation for all that followed. It revealed a universe woven together by space and time into a single continuum, a fabric whose structure could stretch and shift depending on motion. The implications extended beyond physics into philosophy and culture. The idea that time is relative, that simultaneity is not universal, challenged deep intuitions about reality. It forced people to reconsider what it means for events to happen and whether there is an objective now. Philosophers debated whether relativity undermined free will or supported determinism, while artists and writers found inspiration in the fluidity of time and space. The 20th century was already an era of upheaval and Einstein's work mirrored the shifting sands of human thought. And yet, for all its revolutionary character, special relativity retains a serene simplicity. At its core are just two postulates, each easy to state and grasp, yet together, leading to consequences that still astonish us. It shows that the universe is not built on rigid absolutes, but on relationships, that reality is shaped by perspective without ever descending into chaos. Light, the fastest thing in existence, becomes the anchor around which space and time arrange themselves. It is worth pausing here to reflect on the humility of its origins. Einstein wrote his paper while working at the patent office, reviewing the inventions of others while nurturing his own ideas in spare hours. He had no laboratory, no team of assistants, no powerful observatory. What he had was the ability to think deeply, to imagine riding alongside a beam of light and asking what the universe would look like from that impossible vantage point. From such thought experiments came insights that reshaped physics forever. Special relativity is, in a sense, a reminder of how fragile our intuitions can be. We assume that time is universal because our lives unfold at human speeds where differences are imperceptible. We assume that distances are fixed because we have never ridden a spacecraft near light speed. But the universe is not beholden to human scale. The cosmos is vast, the speed of light immense, and reality accommodates conditions far beyond everyday experience. In that broader view, our familiar absolutes dissolve, replaced by a deeper harmony. When you look up at the night sky, the light reaching your eyes may have traveled for hundreds or thousands of years. In that journey, it has passed through a universe where time stretches and distances contract depending on perspective. Each photon carries not just information about its source, but a testament to the relativity of space and time. The stars above us are not fixed points on a rigid canvas, but actors in a universe where the stage itself bends and shifts. And as you drift towards sleep, it may be comforting or perhaps unsettling to realize that even something as fundamental as time is not absolute. The seconds ticking on your bedside clock belong to your frame of reference, but to a distant traveler, they may stretch or shrink. In this way, special relativity invites us to see reality not as a single fixed truth, but as a network of perspectives, each valid, each woven together by the unchanging speed of light. Perhaps in that realization lies a quiet lesson beyond physics, that the universe is not designed to match our intuition, but to reveal its own deeper order if we dare to look closely. Chapter 2. The Principle of Relativity, Physics for Everyone, Everywhere. When Einstein published his paper in 1905, one of his most disarmingly simple statements was that the laws of physics are the same for all observers moving at constant velocity relative to one another. To the untrained ear, this might not sound revolutionary at all. After all, Galileo had said something similar centuries before, that the motions of objects inside a smoothly sailing ship cannot reveal whether the ship is at rest or moving steadily forward. If you drop a ball, it falls to your feet whether the ship is anchored or gliding across a calm sea. You cannot tell by such an experiment if the ship is moving. This was the original idea of relativity, and Einstein openly acknowledged that his own principle of relativity grew directly out of that tradition. But in the 19th century, physicists were beginning to wonder if there might be hidden subtleties, particularly when it came to the behavior of light and electromagnetism. Galileo's statement applied to mechanics, the physics of motion and forces, but Maxwell's new laws of electromagnetism added complexity to the picture. His equations seem to describe waves rippling through space, and waves, as far as physicists understood them, required a medium. That medium was imagined as the ether, and if the ether existed, then it could define a kind of absolute rest. You could, at least in principle, measure your velocity relative to it. The Michelson-Morley experiment challenged that notion, showing that no matter how carefully you measured the speed of light in different directions, you would always get the same value. Einstein's bold move was to declare that Galileo's principle of relativity is not limited to mechanics, but extends to all of physics, including electromagnetism. That means there is no absolute rest, no hidden ether, no preferred frame of reference. If you are drifting in a spaceship with the engines off, you can perform any experiment you like, mechanical or electromagnetic, and you will never be able to prove whether you are at rest or in uniform motion. The universe does not privilege one state over the other. This is what physicists mean when they talk about inertial frames. An inertial frame is simply a state of motion that does not involve acceleration. Imagine sitting in a train moving smoothly on straight tracks. If the ride is steady enough, you might not even know you are moving. Inside the cabin, you can toss a ball to a friend, let water drip from a bottle, or swing a pendulum, and everything behaves exactly as it would if the train were parked. You would only notice the difference if the train accelerated, braked, or turned. The moment acceleration enters the picture, the principle of relativity no longer applies in its simple form. But as long as you move steadily, you and an observer on the platform can both apply the laws of physics, and each will find them to hold without contradiction. Einstein elevated this idea from a mechanical curiosity to a universal truth. This is why the theory is called special relativity. The special refers not to its importance, but to its restriction to inertial frames. It says that in every inertial frame, the laws of physics take the same form. This is not merely a philosophical claim. It has deep mathematical implications. If you write down Maxwell's equations for electricity and magnetism, or Newton's second law of motion, they must look the same to all inertial observers. No one is given a special version of the laws just because they happen to be moving. This principle, however, leads us to rethink how we understand motion itself. Imagine again the train example. If you are inside the train and you drop a ball, you will say the ball falls straight down. But an observer on the platform will say the ball follows a diagonal path, moving forward with the train while falling downward. Both descriptions are correct, each relative to its own frame of reference. The difference is reconciled because the observers disagree about the decomposition of the ball's motion into vertical and horizontal components, not because the ball behaves differently. The principle of relativity ensures that both observers will use the same underlying laws to explain what they see. Now, when we extend this principle to include light, the picture becomes more subtle. Suppose the train has a lamp mounted on the ceiling, and it shines a beam of light straight downward. For the passenger inside, the light moves vertically, hitting the floor directly below the lamp. But for the observer on the platform, the light follows a diagonal path, since the train is moving forward while the beam travels downward. If both observers measure the speed of that light, however, they will both find the same value. This invariance of light's speed is consistent with the principle of relativity, but it forces us to let go of the idea that time and distance are absolute. What makes the principle of relativity so profound is that it acts as a safeguard for the coherence of physics. Without it, we might expect nature to play favorites, with different sets of rules applying depending on how fast or in what direction you move. That would make physics a patchwork, fractured and inconsistent. Instead, Einstein's principle provides a kind of universal equity. It declares that the cosmos does not distinguish between travelers gliding smoothly at different speeds. Every inertial observer is equally entitled to describe the world with the same physical laws. One might ask, why should this be true? Why shouldn't the universe have a special reference frame, a cosmic anchor against which all motion is measured? After all, in everyday life, we constantly compare our speeds to the ground beneath our feet. If I tell you I'm driving at 100 kilometers per hour, it is understood that I mean relative to the road. But physics insists that no such absolute stage exists. The Earth itself is spinning on its axis and orbiting the Sun. The Sun is circling the center of the Milky Way, which in turn drifts relative to other galaxies. At no point can we say we are truly at rest. Motion only has meaning as a relation between objects. Einstein's insight removed the need for an invisible medium like the ether because it was redundant. The laws of physics do not care about your velocity relative to an imagined backdrop. They only care about relative velocities between actual objects. If one spaceship flies past another at a constant speed, each crew sees the other in motion, and each is entitled to call themselves at rest. There is no experiment either ship can perform to prove otherwise. This radical symmetry lies at the heart of the principle of relativity. Over the years, experiments have confirmed this principle again and again. Particle accelerators routinely propel electrons and protons to speeds close to that of light. The laws governing their behavior, how they bend in magnetic fields, how they scatter off one another, are identical to the laws describing particles moving more slowly. There is no hidden correction that appears only at high speeds. Astronomical observations confirm the same principle. Whether light comes from a nearby laser or a distant quasar, its speed is constant, indifferent to the motion of its source. What is striking about the principle of relativity is its universality. It does not apply only to esoteric laboratories or rare cosmic events. It applies everywhere, to every inertial observer. This makes it one of the most democratic principles in science. No matter where you are in the universe, no matter how fast you are moving, as long as your speed is steady, you are entitled to claim your perspective as valid. There is no privileged vantage point. This universality also reshapes how we think about the very structure of space and time. If the laws of physics must look the same for all observers, then the transformations between different frames of reference must have a certain symmetry. These transformations are not mere translations or rotations, as in classical mechanics, but Lorentz transformations, which weave time and space together in order to preserve the constancy of light's speed. This is where special relativity acquires its distinctive flavor. The principle of relativity alone does not dictate the details, but once combined with the invariance of light's speed, it forces us into a new geometry of space-time. One might say that the principle of relativity is the philosophical heart of Einstein's work, while the invariance of light is the physical anchor. Together, they form a foundation upon which the strange but consistent edifice of relativity is built. Neither alone would be sufficient to overturn Newton's absolutes, but together they demand a reality where clocks tick differently depending on motion, rulers shorten when measured in flight, and simultaneity dissolves as an illusion of perspective. For students encountering relativity for the first time, this principle can feel abstract. It can seem like a statement about fairness rather than physics. Yet its power lies in its ability to guide our understanding across domains. Consider, for instance, the design of GPS satellites. They orbit the Earth at high speeds and experience time differently than clocks on the ground. The system must account for both special and general relativistic effects to provide accurate navigation. If the principle of relativity did not hold, if different inertial frames required different physical laws, such corrections would be incoherent. But because the principle ensures consistency, we can calculate and adjust with confidence, and the system works. The principle of relativity is, in essence, an assertion of unity. It ties together the experiences of all observers, insisting that beneath the shifting appearances lies a set of rules that never changes. This unity is not obvious to our senses, which are attuned to human scales and speeds. But the deeper we peer into nature, the more clearly we see its imprint. The universe does not indulge our intuition of absolutes. Instead, it offers a harmony of relative perspectives, bound together by unchanging laws. And as with many truths in science, this principle carries a quiet existential resonance. It tells us that there's no central stage in the universe, no throne from which to declare a privileged view. Every perspective is valid, provided it moves steadily, and every observer carries with them the same laws of nature. In this way, relativity reflects not just physics, but a certain humility. We are not at the center. We are not special in our vantage point. We are part of a grand network of observers, all moving, all measuring, all connected by the same silent rules of existence. Perhaps there is comfort in this. As you drift toward sleep, imagine the universe filled with countless observers on ships, planets, or drifting stations, each one watching, each one describing reality in their own frame. None of them is wrong. None of them is more privileged than another. The cosmos does not play favorites. It embraces all perspectives equally, and in doing so, it reveals a truth both scientific and human, that reality is not anchored to a single view, but to the shared consistency that binds them all together. Chapter 3: The Speed of Light, a Universal Limit. The discovery that the speed of light is not just a number, but a universal constant is one of the great turning points in human understanding of nature. In ordinary experience, speed feels like something relative, something that depends on the observer. If you are walking through a park and a cyclist overtakes you, you describe the bicycle as moving quickly relative to you. Someone else standing on the sidewalk may measure a different speed, depending on their perspective. In Newton's world, this was a natural and unquestioned feature of motion. Velocity simply added and subtracted depending on the frame of reference. If you throw a ball forward on a moving train, its speed relative to the ground is the sum of the train's speed and the throw. The arithmetic of motion felt intuitive, and for centuries it matched the observations of human-scale life. But light refused to obey these simple rules. As physicists investigated the nature of electromagnetic waves in the 19th century, a curious fact emerged. Light seemed to move at the same speed, no matter how you approached the problem. Maxwell's equations predicted this speed with beautiful precision, giving a value that today we know to be about 299,792 kilometers per second in a vacuum. Unlike the motion of sound or water waves, this speed appeared to be fixed, unyielding, and immune to the ordinary arithmetic of relative motion. The Michelson-Morley experiment made this fact plain by showing that no motion of the Earth through space could alter the measured speed of light. The strangeness of this result cannot be overstated. Imagine again the moving train. If you run toward the front of the train and shine a flashlight ahead of you, common sense suggests that the light beam should move faster relative to the ground than if you had shown it while standing still. In Newtonian mechanics, the speeds would simply add. But in reality, the beam travels at exactly the same speed in both cases. The universe refuses to allow the speed of light to be altered by the motion of the source. This is not just a technical detail. It is a fundamental truth about the structure of reality. Einstein recognized that if the speed of light is constant, then our understanding of time and space must bend to accommodate it. Instead of light's velocity shifting with the motion of its source, time itself must stretch and distances contract to ensure that all observers measure the same speed. This adjustment is so counterintuitive that it requires a complete reframing of what we mean by space, time, and simultaneity. To appreciate why this is so radical, it is helpful to compare light to sound. If you are standing still on the ground and an ambulance approaches with its siren on, you hear the pitch rise because the sound waves are compressed. If you move toward the ambulance, the pitch rises further because your motion adds to the relative speed of the waves. Sound depends on the air as a medium, and velocities of source and observer both matter. Light, however, has no such dependence. Whether you move toward or away from its source, its speed remains fixed. You may still observe a change in frequency, known as the Doppler effect, but the velocity itself is untouchable. This constancy has profound consequences. It means that no matter how hard we try, no object with mass can ever be accelerated to the speed of light. As an object's speed increases, its kinetic energy grows not linearly, but in a way that makes further acceleration increasingly difficult. Approaching light speed, the required energy becomes effectively infinite. The speed of light therefore stands as a cosmic speed limit, not only for particles and spacecraft, but also for the transmission of information and cause and effect relationships. Nothing can outrun light without violating the fabric of relativity. The universality of this limit is not a matter of conjecture, but of experimental certainty. High-energy particle accelerators, like those at CERN, propel protons to velocities within a fraction of a percent of light speed. Yet no matter how much energy is poured into them, the protons never quite reach the limit. Their masses increase, their lifetimes extend, their behavior matches exactly what relativity predicts, but the speed itself remains inviolate. The universe enforces this law with unwavering consistency. Even more striking is the role of the speed of light beyond the domain of optics. In modern physics, it is not just the speed of light, but the maximum speed at which any interaction can propagate. Gravitational waves, ripples in spacetime itself, move at this same speed. Information about the position or state of a particle cannot travel faster. This makes the speed of light the ultimate governor of causality. If a star explodes in a distant galaxy, its light cannot reach us before the time set by this limit. Until then, for all practical purposes, the event does not yet exist for us. The cosmic speed limit is the universe's way of ensuring order in the sequence of cause and effect. This principle reshapes even how we think about distance. Astronomers routinely measure the universe in light years, the distance light travels in a year. This unit is not chosen out of convenience, but necessity. Because information cannot travel faster than light, distance and time are bound together. To look out into the cosmos is to look back into time. When we see a galaxy a billion light years away, we are seeing it as it was a billion years ago. The light's finite speed transforms the night sky into a time machine, one that reveals not just where, but when the light began its journey. The constancy of light speed also underlies technologies that permeate daily life. Global positioning system satellites must account for both special and general relativistic effects in order to maintain accuracy. The clocks on board experience time differently due to their velocity and their position in Earth's gravitational field. Without correcting for relativity, GPS would quickly accumulate errors that render it useless. The fact that your phone can tell you where you stand within a few meters is a practical triumph of the cosmic speed limit. Still, the most profound implication of the speed of light as a universal limit is philosophical. It forces us to abandon the dream of instantaneous communication across space. No signal, no matter how advanced our technology becomes, can leap across the galaxy faster than light. This creates a fundamental isolation between stars, between civilizations, even between the farthest reaches of our own observable universe. If intelligent beings exist in a galaxy millions of light years away, they may have already sent signals toward us, but we will not know until that light arrives, long after both civilizations may have changed or vanished. The speed of light sets not only a physical, but a communicative boundary on existence. There have been attempts to imagine what it would mean to surpass this limit. Science fiction often plays with ideas of warp drives, wormholes, or tachyons. Hypothetical particles always move faster than light. Yet within the framework of relativity, such ideas come with paradoxes that unravel the very order of causality. If signals could move faster than light, it would be possible to send information backward in time, creating contradictions where an effect could precede its cause. The prohibition on faster-than-light travel is not merely a rule of mechanics, but a safeguard against logical collapse. At the same time, quantum physics has introduced subtleties that complicate this picture without breaking it. Phenomena like quantum entanglement seem to allow instantaneous correlations between particles separated by vast distances. Yet these correlations cannot be used to transmit information faster than light. The cosmic speed limit holds firm, even as the quantum world offers strange hints that reality is more interconnected than our macroscopic intuition allows. One might ask why light, of all things, should play this defining role. The answer lies in the structure of Maxwell's equations, which describe electromagnetic waves. They predict that these waves travel at a speed determined by the electric and magnetic properties of the vacuum itself. There is no need for a medium like air or water. The vacuum is sufficient. The number that emerges from these equations matches the observed speed of light, tying the behavior of a fundamental constant to the very fabric of empty space. Einstein's genius was to take this number not as an accident, but as a cornerstone of physics. This reimagining of light as the universe's limiting speed reveals a profound unity in nature. It shows that what we perceive as illumination from a lamp or the glow of a star is not just a convenient physical phenomenon, but a manifestation of the deepest laws of spacetime. Light's speed is not an incidental property of photons. It is a reflection of the structure of reality itself. In considering this, one cannot help but feel a sense of awe. The limit imposed by light is not something that can be overcome by engineering or ingenuity. It is woven into the nature of existence. It binds together time, space, and causality, ensuring that the universe remains coherent. And yet, far from limiting us, it has opened pathways to deeper understanding. By respecting this limit, physics has unlocked technologies that guide spacecraft across the solar system, allow us to peer into the earliest moments of the cosmos, and connect billions of people through global networks. As you think about this universal constant, it may be worth reflecting on what it says about our place in the cosmos. The speed of light tells us that we are bound by a horizon, that our knowledge of the universe can only extend as far as light has had time to travel. Beyond that, there are mysteries forever beyond our reach. The light that surrounds us is a messenger, but it is also a gatekeeper, deciding how much of reality we can ever know. In that recognition lies both humility and wonder. Perhaps, as you drift towards sleep, you can imagine yourself floating in the silence of space, watching beams of light race outward in every direction. They move at the ultimate speed, faster than anything you could ever hope to follow, carrying with them the story of stars, galaxies, and time itself. And maybe in that thought, you find a quiet sense of belonging. Not as one who can outrun the universe, but as one who bears witness to its endless unfolding, carried always at the pace of light. Chapter 4. Time Dilation. Why Moving Clocks Tick Slower. Few consequences of Einstein's special relativity are as startling and counterintuitive as time dilation. At first glance, the idea that time itself flows differently for observers in relative motion seems impossible, almost paradoxical. Time is something we take for granted as universal. A second on one person's watch should be the same as a second on anyone else's. This was the comfortable assumption of centuries of physics and everyday life. Yet relativity tells us that this is not the case. Time is not absolute but depends on motion, and the faster you move relative to another observer, the slower your own time passes compared to theirs. This is not science fiction or philosophical speculation. It is a rigorously tested and experimentally confirmed fact. From the operation of satellites orbiting Earth to the behavior of subatomic particles racing through accelerators, time dilation has become one of the most well-established truths of modern physics. To understand it, we must follow the path Einstein took in realizing that the constancy of the speed of light demands a new picture of time itself. Consider a thought experiment often used to introduce the concept. Imagine a spaceship moving smoothly through space at a constant velocity. Inside the ship is a clock unlike any familiar timepiece. Instead of gears or digital displays, this clock is built from light. A beam of light bounces between two mirrors, one on the floor and one on the ceiling, and each round trip of the beam marks a tick of the clock. To an observer inside the ship, the light simply travels up and down between the mirrors, and the clock ticks steadily. Now imagine another observer outside the ship, watching it pass by at great speed. To this observer, the light beam does not travel straight up and down. Because the ship is moving, the light traces out a diagonal path, like the bouncing of a ball inside a moving train. The beam has to cover more distance between the mirrors from this outside perspective. Yet the speed of light is the same for both observers, and since the outside observer sees the light traveling a longer path at the same speed, the intervals between ticks must be longer. In other words, the clock inside the moving ship runs slower when observed from the outside. This simple thought experiment reveals the essence of time dilation. Motion alters the measurement of time. For the passenger inside the ship, nothing feels unusual. The clock ticks normally and life proceeds as expected. But to the outside observer, everything inside the ship appears to move more slowly. The heartbeats of the passengers, their conversations, even their aging, all unfold at a reduced pace relative to the outside world. The striking feature of time dilation is that it is not just an illusion or a trick of perspective. Both observers are correct in their own frames of reference. Each has their own proper time, measured by clocks at rest in their frame. Relativity tells us that there is no single universal time flowing everywhere at once. Instead, time is bound to motion and must be described relative to the observer. At everyday speeds, this effect is imperceptible. If you walk down the street or ride in a car, the difference in time flow compared to a stationary observer is vanishingly small, far beyond the resolution of any clock you carry. But at speeds approaching the speed of light, the effect becomes dramatic. A spacecraft moving at 99% the speed of light would experience time at less than half the rate of a stationary observer. Push closer to the limit, and the dilation grows even more extreme. In the ultimate case of moving exactly at the speed of light, something only massless particles like photons can do, time does not flow at all from the particle's perspective. For a photon, there is no before or after. Its journey from emission to absorption is timeless. The experimental confirmation of time dilation came swiftly after Einstein's predictions. In the mid-20th century, physicists studied particles known as muons, created when cosmic rays strike Earth's atmosphere. Muons are unstable and decay with a well-known lifetime. If they traveled at ordinary speeds, few would survive the trip to Earth's surface. Yet detectors found far more muons than expected. The explanation was time dilation. From the muons' perspective, only a short time had passed as they sped toward the ground at near light speeds. Their internal clocks ran slower relative to Earth's frame, allowing them to live long enough to reach detectors. This was one of the earliest and most dramatic confirmations of relativity's predictions. Further experiments have pushed the verification of time dilation to extraordinary precision. Atomic clocks flown on airplanes or mounted on satellites show measurable differences compared to clocks on Earth. The famous Halfili-Keating experiment of 1971 flew atomic clocks around the world on commercial airliners and compared them to clocks left at the U.S. Naval Observatory. The traveling clocks returned with times shifted by amounts exactly predicted by relativity, accounting for both their speeds and their altitudes in Earth's gravitational field. Modern GPS systems must include these relativistic corrections, or they would drift by kilometers each day. Without accounting for time dilation, the entire infrastructure of global navigation would fail. The reality of time dilation also introduces fascinating thought experiments. The most famous is the so-called twin paradox. Imagine identical twins, one of whom remains on Earth while the other travels on a spacecraft near the speed of light. Upon returning, the traveling twin will have aged less than the one who stayed home. The paradox arises because from the traveler's perspective, it seems the Earth was moving, and so one might expect the Earth-bound twin to be younger. The resolution lies in the fact that the traveling twin must accelerate and decelerate to make the round trip, breaking the symmetry of the situation. Relativity predicts unambiguously that the traveler will indeed be younger, and this has been supported by experiments with fast-moving particles. Time dilation challenges our most basic intuitions. We are used to thinking of time as a river, flowing at the same rate for all. Relativity reveals it as more like a network of streams, each flowing at its own rate depending on the motion of the observer. Yet this does not lead to chaos. The laws of physics ensure consistency between frames, and the discrepancies can always be calculated precisely. Time dilation is not a breakdown of order but a reshaping of it, woven into the geometry of spacetime. There are subtle consequences for our understanding of causality. Because time flows differently in different frames, the ordering of events can depend on motion. Two flashes of lightning that appear simultaneous to one observer may occur at different times for another. But relativity preserves the sequence of cause and effect. If one event can influence another, all observers agree on their order. The slowing of clocks does not undermine causality, but ensures that it remains consistent across all perspectives. This understanding also leads us into the realm of astrophysics and cosmology. Time dilation plays a crucial role in the life cycles of stars and the dynamics of black holes. As matter spirals into a black hole, distant observers see its processes slow down, appearing to freeze near the event horizon. From the falling matter's own perspective, however, time flows normally. The difference is an extreme form of time dilation caused not just by motion but by gravity, a domain belonging to general relativity, but built upon the same principle that time is not absolute. Even at the scale of the expanding universe, the redshift of light from distant galaxies is partly understood in terms of the stretching of time and space. The human implications are equally striking. If interstellar travel were ever achieved at relativistic speeds, crews could journey for what seemed like only a few years to them, while decades or centuries passed on Earth. For the travelers, the voyage would be brief, but for those they left behind, entire generations could come and go. Time dilation means that explorers of the cosmos would always be out of step with the worlds they departed, returning as strangers to futures they never lived. And yet, despite the unsettling implications, there's also a quiet beauty in the idea. Time dilation reminds us that the universe does not conform to human expectations. It operates according to deeper rules, rules that remain consistent across all scales and situations. The fact that our technology must correct for relativity every time you open a map application on your phone is a reminder that this strange truth is not abstract. It is woven into the everyday world, even if we do not notice it directly. Perhaps the most humbling realization is that time itself, the very medium of our existence, is not fixed. It bends and flexes with motion, and its flow is not universal but relative. For all our efforts to measure it, divide it into hours, and regulate it with atomic precision, time is not a simple backdrop. It is dynamic, intertwined with space and motion, part of a larger continuum that cares nothing for our intuitions. And maybe there is something existential to be learned here. If time flows differently depending on where you are and how you move, then perhaps our own sense of permanence is also more relative than we imagine. We measure our lives by clocks and calendars, but those are only one perspective among many. The universe holds countless timelines, all valid, all unfolding in their own rhythm. As you rest, you might consider that somewhere out there, aboard a spacecraft racing near the speed of light, time itself is passing differently, yet just as truly. The cosmos, vast and indifferent, carries every clock at its own pace, reminding us that even the seconds we hold most dear are part of a greater relative fabric of reality. Chapter 5. Length contraction. Space shrinks when you move. Among the many strange predictions of special relativity, length contraction often feels the most visual, the one easiest to picture, and at the same time the hardest to truly believe. Time dilation suggests that moving clocks tick more slowly, which challenges our intuitions about time, but remains abstract until we imagine real experiments with particles or spacecraft. Length contraction, however, tells us that objects themselves, physical rulers, spaceships, planets, literally change their lengths depending on their state of motion. The universe insists that when an object moves relative to you, it becomes shorter in the direction of its motion. This shrinking of space is not an illusion or a trick of perception. It is a real, measurable effect arising directly from the same principles that demand time dilation. If the speed of light is constant for all observers, then space, as well as time, must bend in response. The contraction of lengths is the counterpart of the dilation of time, each balancing the other to preserve the invariance of light's speed and the consistency of physical laws. To see why, consider once more the idea of measuring distance with light. Imagine that you want to determine the length of a spaceship as it speeds past at a significant fraction of the speed of light. You set up detectors to record the times when the front and back of the ship pass by. From your perspective, the ship is moving, and the time interval between the passing of the two ends allows you to calculate its length. Yet when you compare this length to what the crew inside the ship would measure with their own rulers at rest, you find a discrepancy. To you, the ship is shorter than it is for them. The faster it moves, the more its length contracts along the direction of travel. The key to understanding this lies in the relativity of simultaneity. To measure the length of a moving object, you must note the positions of its front and back at the same time in your frame of reference. But simultaneity is not absolute. What counts as the same time for you may not be simultaneous for the crew inside. When each frame insists on applying its own notion of simultaneity, the result is a difference in measured length. Neither measurement is more real than the other. Each belongs to the perspective of the observer making it. Importantly, length contraction does not mean that people or objects are squeezed in their own experience. The crew inside the spaceship notices nothing unusual. Their rulers remain the same, their bodies unchanged, their environment perfectly normal. It is only from the outside, relative to observers who see the ship moving, that the contraction appears. This reciprocity is central to relativity. Each observer sees the other as subject to these effects, while feeling none of them in their own frame. Reality allows for both views, and no absolute perspective adjudicates between them. The effect becomes more dramatic as speeds approach that of light. At half the speed of light, the contraction is modest, barely noticeable with ordinary tools. But at 90%, the length shrinks to less than half of its rest value. At 99%, it becomes a fraction of its original size. Push even closer to light speed, and the contraction becomes extreme. In the theoretical limit of moving at light speed, something that massive objects cannot achieve, the length along the direction of travel would contract to zero. Though unreachable in practice, this illustrates the principle that motion reshapes not only time, but also space itself. Experiments confirm length contraction indirectly through the same processes that confirm time dilation. Particles accelerated to near light speeds in laboratories live longer than expected and travel farther than they otherwise could, a result that only makes sense if distances in their frame are shorter than in ours. Muons created in the upper atmosphere, for example, reach Earth's surface in far greater numbers than Newtonian physics would allow. From our frame, this is explained by their slowed decay. From the muon's own perspective, however, the atmosphere itself is contracted, compressed along the line of their motion, allowing them to traverse it in their short lifetimes. Both descriptions are correct, each belonging to its own frame. The implications of length contraction ripple outward into our understanding of the universe. It forces us to abandon the comforting notion of fixed dimensions. Objects do not possess one true length independent of context. Instead, length is relative, tied to the observer's state of motion. This relativity does not create inconsistency but enforces a deeper consistency, ensuring that all observers, regardless of their speed, agree on the fundamental laws of physics. Length contraction also plays a role in the resolution of paradoxes. One classic example is the so-called ladder paradox, in which a ladder moving at relativistic speed is said to fit entirely inside a barn shorter than the ladder's rest length. From the barn's frame, the ladder contracts and fits. From the ladder's frame, the barn contracts and cannot contain it. The paradox dissolves when one accounts for relativity of simultaneity. For the barn observer, the entire ladder is inside at one instant. For the ladder observer, the front is leaving before the back has entered. Both perspectives are correct within their own frames, and no contradiction exists. In practical terms, length contraction is less directly observed than time dilation, but its consequences are no less real. The design of particle accelerators, the interpretation of cosmic ray showers, and the analysis of high-energy astrophysical phenomena all rely on its predictions. Without accounting for contraction, the observed paths and interactions of particles would be inexplicable. The principle also extends beyond physical rulers to the very structure of spacetime. Just as time intervals stretch depending on motion, spatial intervals compress. Together, these effects maintain the invariant speed of light, binding time and space into a single fabric. This unity is why physicists speak not of separate entities, but of spacetime, where events have coordinates in both space and time, and transformations between frames weave the two together. For those encountering the idea for the first time, it can feel like a violation of common sense. How can the same object have different lengths depending on who measures it? Yet the lesson of relativity is that length is not an intrinsic property, like mass or charge, but a relational one. To ask for the length of something without specifying the frame of reference is meaningless. Length, like time, only exists in context. Astrophysics provides striking illustrations of this principle. Jets of particles streaming from active galactic nuclei, for example, travel at speeds close to that of light. Observations of their apparent brightness and structure must account for relativistic contraction and time dilation to make sense. Without these corrections, the distances and timescales would not align with the physics of emission and propagation. The very appearance of the cosmos in high-energy phenomena is shaped by relativity. Even within the realm of speculative exploration, length contraction carries weight. If humans were ever to travel at relativistic speeds, entire interstellar distances would contract in their frame. A journey to a star 20 light-years away, which would take decades in Earth's reckoning, could feel dramatically shorter to the crew aboard. The universe, in effect, becomes smaller for those who move quickly through it. While no technology we possess today can approach such speeds, the principle illustrates how relativity reshapes our very imagination of exploration. Philosophically, length contraction underscores a humbling truth. The dimensions of the world are not fixed absolutes, but mutable quantities. We often imagine the universe as an objective backdrop, a grand stage of fixed proportions. Relativity reveals instead a dynamic fabric, one that bends with motion, one that refuses to offer any observer the privilege of declaring their perspective the only true one. From a human perspective, this may feel disorienting. The idea that a spaceship, a ruler, or even the very atmosphere of Earth can be longer or shorter, depending on who observes it, challenges our trust in physical solidity. Yet it also offers a profound vision of harmony. Relativity does not reduce reality to confusion, but raises it to a deeper order. where differences in perspective are not errors but essential features of the universe's design. And perhaps here lies the quiet existential note. If the dimensions of space itself depend on where you stand and how you move, then reality is less rigid than we imagine. There is no single map that all must follow, no universal measurement that rules them all. Instead, the universe allows for multiplicity, for perspectives that differ, yet remain true. In that sense, relativity is not only a scientific revolution, but a gentle reminder of humility, that our view of the world, no matter how carefully measured, is only one among many, and the cosmos has room for them all. Chapter 6. Relativity of Simultaneity, when now depends on you. In everyday life, simultaneity feels absolute. If two bells ring at opposite ends of a room, we assume they rang at the same moment in time, and everyone present would agree on that fact. We may disagree about which one sounded louder or came from the left or right, but the idea of when feels fixed, universal, and beyond dispute. Yet special relativity tells us that even simultaneity, one of the most basic elements of our perception of time, is not absolute. Events that appear simultaneous to one observer may not be simultaneous to another who is moving at a different velocity. The very concept of now, which we instinctively take for granted, dissolves into something relative. The seeds of this insight were planted in Einstein's recognition that the speed of light is constant for all observers. To see why this matters, imagine a thought experiment that Einstein himself described: a long train moving smoothly along the track. Lightning strikes both ends of the train at the same time, according to an observer standing at the midpoint of the track. From this perspective, the flashes of light from the two strikes travel equal distances and reach the observer simultaneously. It seems beyond dispute that the strikes occurred at the same moment. But now imagine another observer riding on the train, also sitting at its midpoint. This person is moving relative to the track observer. As the lightning strikes, the train is advancing toward the position where the front strike occurred and away from the position where the rear strike occurred. Because the speed of light is constant, the flash from the front has less distance to cover to reach the train observer, while the flash from the rear must travel farther. As a result, the passenger sees the flash from the front before the flash from the back. From their perspective, the lightning strikes were not simultaneous. The front strike happened first. Neither observer is wrong. Both are applying the same laws of physics. Both measure the same speed of light, and both interpret their observations consistently. Yet they disagree about simultaneity. The only conclusion is that simultaneity itself is not absolute but relative to the observer's frame of reference. What one observer calls at the same time, another may call separated in time. This idea is subtle because it cuts directly against human intuition. We are accustomed to treating simultaneity as universal because, at the speeds we experience, relativistic effects are too small to notice. Even when we watch distant fireworks, the differences in arrival times of light are negligible compared to our perception. But at higher velocities or across cosmic distances, the relativity of simultaneity becomes not only noticeable but essential. The implications of this relativity run deep. It means that the universe does not offer a universal now shared by all observers. If two events occur in distant places, whether they are simultaneous depends on the frame of reference. This undermines the notion of a global present, a cosmic slice of time shared by all beings across the universe. Instead, each observer carries their own present, their own definition of simultaneity, shaped by their motion. This realization reshaped not only physics, but philosophy. In Newtonian physics, time is a single thread weaving through the cosmos, tying all events together. In relativity, time is more like a web of threads, each belonging to an observer, intersecting and diverging, without a single universal strand. The absence of an absolute now challenges us to rethink what we mean when we say something is happening at the same time elsewhere in the universe. To make this more concrete, imagine two astronomers on distant planets observing a supernova in a remote galaxy. Each records the event and measures the time it occurred according to their own local clocks. If these astronomers are in relative motion to one another, they may not agree on whether the explosion was simultaneous with some other event, like the birth of a star in a neighboring system. The disagreement is not due to error or miscalculation, but is a natural feature of relativity. The notion of simultaneity does not transcend reference frames. This concept also plays a role in the structure of spacetime as described by Minkowski geometry. In this framework, time and space are woven together, and the distinction between past, present, and future becomes more subtle. Events that are simultaneous in one frame may lie in different time orderings in another. The invariant structure of spacetime ensures consistency, but it does not preserve a universal division into now slices. The relativity of simultaneity is not a quirk or anomaly, but a fundamental property of the geometry of the universe. Einstein himself struggled with how counterintuitive this idea was, but he embraced its consequences. In his writings, he emphasized that simultaneity is not a self-evident concept, but one that requires definition through physical procedures, such as the synchronization of clocks using light signals. If two observers synchronize their clocks differently because of their relative motion, they will disagree on the simultaneity of events. This is not a defect in the method, but a revelation of the nature of time. Experimental evidence supports this aspect of relativity just as firmly as time dilation and length contraction. Particle physics provides a domain where simultaneity is tested constantly. In collisions at high speeds, the ordering of particle decays and interactions must be interpreted within specific frames. The mathematics of relativity ensures that no contradictions arise, but the results depend on the frame chosen. The relativity of simultaneity also plays a key role in resolving apparent paradoxes. In the ladder and barn thought experiment discussed earlier, whether the ladder fits entirely within the barn depends on how simultaneity is defined. For the barn observer, the entire ladder is inside at once. For the ladder observer, the front is leaving before the back has entered. Without relativity of simultaneity, these two descriptions would contradict each other. With it, they are simply two valid perspectives. The dissolution of absolute simultaneity also forces us to reconsider the flow of time itself. If now is not universal, then the division between past, present, and future is not as rigid as we imagine. Some philosophers have taken this to imply a block universe, in which all events exist equally, and the passage of time is an illusion of human perception. Others see it as evidence of a deeper relativity of reality itself, where the universe refuses to grant primacy to any single viewpoint. Physics does not settle these debates, but it provides the framework in which they must be considered. In cosmology, the relativity of simultaneity takes on grand importance. The observable universe is limited by the speed of light, and the events we see in distant galaxies occurred in the deep past. When we ask what is happening now in a galaxy billions of light years away, relativity warns us that there is no absolute answer. Depending on our frame of reference, that galaxy's present could correspond to vastly different eras of cosmic history. The very notion of a universal present moment across the cosmos becomes meaningless. This realization can be unsettling. We are deeply attached to the idea of sharing a common now with others, of existing together in the present. Relativity shows that while this may hold within our immediate environment, it does not extend across the universe. Each observer's now is unique, bound to their motion, and cannot be imposed universally. The fabric of reality is stitched together not by a single time, but by the interplay of many times, overlapping and diverging. And yet, the relativity of simultaneity does not lead to chaos or disorder. It is part of the coherent structure that preserves causality. All observers, no matter their motion, agree on which events can influence others. If one event lies in the causal past of another, all frames preserve that order. The disagreements occur only for events that are separated in such a way that no signal can pass between them. Relativity does not permit contradictions in cause and effect, only differences in perspective about simultaneity. Perhaps the most profound aspect of this idea is how it humbles our sense of time. We like to think of the present as something we share with the universe, a moment stretching from here to the most distant star. Relativity reveals instead that the present is local, personal, and relative. What we call now is not a cosmic truth, but an observer-dependent slice of spacetime. And here lies the quiet existential reflection. If now is not universal, then perhaps our attachment to the present moment is also less absolute than we imagine. Each of us carries a personal now, stitched into the vast fabric of spacetime, overlapping with some, diverging from others, never extending infinitely. The universe does not give us a single present to share, but countless presents, each valid in its own frame. In this, we glimpse a universe that is at once less comforting and more wondrous, a cosmos where time itself resists simplification, inviting us to accept its multiplicity. Chapter 7. E equals mc squared, the energy-mass connection. Few ideas in the history of science are as widely recognized and yet as profoundly misunderstood as Einstein's relation that energy equals mass multiplied by the speed of light squared. It appears simple, consisting of only a few symbols, yet it encapsulates a transformation in how we understand the universe. It tells us that mass is not an immutable property of matter, but a condensed form of energy, and that energy itself is bound to the very fabric of matter. When Einstein first derived this relation in 1905, it was not presented as a headline or a grand revelation. It appeared almost quietly near the end of one of his papers on relativity. Yet its consequences would ripple outward through physics, reshaping our understanding of atoms, stars, and the cosmos itself. To understand why this relation arises, we must recall the central feature of relativity: the constancy of the speed of light and the invariance of the laws of physics for all observers moving at steady velocity. These principles force a rethinking of how quantities like momentum and energy behave at high speeds. In Newton's world, momentum was simply mass times velocity, and energy was 1/2 of mass times velocity squared. But as velocities approach the speed of light, those formulas no longer suffice. To preserve consistency across frames, new relationships are required, and from them emerges the realization that mass itself contributes to energy, independent of motion. Even an object at rest carries energy by virtue of its mass alone. This so-called rest energy is given by Einstein's relation. It tells us that even a small amount of matter contains an extraordinary reservoir of energy. To put this in perspective, if the mass of something as small as a paperclip could be completely converted into energy, the release would equal that of a large nuclear explosion. The everyday solidity of matter hides an unimaginable store of energy bound within it. The recognition of mass-energy equivalence transformed physics into a more unified science. It showed that energy and matter are not separate categories, but two forms of the same underlying quantity. Mass can be transformed into energy, and energy into mass. This realization is not only theoretical, but observable. When particles collide at high energies, new particles with mass can be created. In nuclear reactions, small differences in mass appear as large releases of energy. The sun itself shines because of this principle, converting mass into light and heat through nuclear fusion in its core. In nuclear physics, this explains why the energy released in nuclear reactions is so vast compared to ordinary chemical processes. In combustion, say, burning coal or wood, energy comes from rearrangements of electrons around atoms. The masses of the nuclei remain unchanged, but in nuclear fission and fusion, changes occur in the very structure of the nuclei, and the difference in binding energy translates directly into released energy. Even a tiny fraction of mass loss corresponds to enormous energy, because the speed of light squared is such a large factor. This principle underpins both the destructive power of nuclear weapons and the sustaining light of the stars. In the sun, hydrogen nuclei fuse to form helium, and the resulting helium atom has slightly less mass than the original hydrogen nuclei. That missing mass is not lost, but converted into energy, which radiates outward as sunlight. Over billions of years, this process gradually reduces the sun's total mass, though by amounts negligible on human timescales. Without this conversion of mass into energy, life on Earth would not exist. Particle physics has revealed even more striking confirmations of mass-energy equivalence. In accelerators, when particles are smashed together at extreme velocities, new particles can appear that are more massive than the originals. The extra mass comes from the energy of motion. Conversely, unstable massive particles decay into lighter ones, plus bursts of radiation, conserving the total energy mass of the system. The universe continually demonstrates this interchangeability. The relation also reshaped our understanding of conservation laws. In classical physics, mass and energy were considered separate conserved quantities. Relativity merged them into a single conservation law. The total mass energy of a closed system remains constant. This principle underlies everything from the stability of stars to the balance of reactions in laboratories. It is important, however, to clarify what energy equals mass times the speed of light squared does and does not mean. It does not suggest that mass can casually disappear into energy in everyday processes. The conversion requires conditions where nuclear or particle interactions occur. A rock sitting on the ground does not spontaneously radiate away its mass's energy. Instead, the relation tells us that the rock's very existence as matter carries with it an enormous quantity of stored energy, whether or not it is released. The power of this insight lies not only in its applications, but in the way it unifies our picture of reality. Before Einstein, matter and energy seemed like fundamentally different entities. Matter was substance, solid and enduring. Energy was activity, motion, or heat. This relation revealed them to be manifestations of the same underlying reality, different guises of a single essence. In astrophysics, this equivalence explains phenomena on the grandest scales. The luminosity of stars, the dynamics of supernovae, and the synthesis of heavy elements all depend on the conversion of mass into energy. When a massive star ends its life in a supernova explosion, the sudden release of energy comes from the rearrangement and fusion of nuclei, with mass-energy equivalents dictating the scale of the event. The elements that make up planets and living beings are forged in such processes, scattering the products of mass-to-energy conversion across the galaxy. The relation also enters cosmology, where the balance of mass and energy in the universe shapes its evolution. Even massless particles like photons carry energy and contribute to the overall energy density of the cosmos. The universe's expansion, its thermal history, and the cosmic microwave background are all described in terms of mass-energy content. Relativity ensures that matter and radiation are different aspects of the same story. Technologically, the mastery of mass-energy conversion has changed human history. Nuclear reactors harness controlled fission to release energy that powers cities. Medical technologies such as positron emission tomography rely on the annihilation of particles and antiparticles, converting their mass into detectable radiation. At the frontier of research, particle colliders continue to probe the transformations of energy into mass, recreating conditions that resemble the earliest moments after the Big Bang. Despite its fame, the equation remains easily misrepresented. Popular accounts sometimes suggest it explains why nuclear bombs explode or why stars shine, as though the relation itself is the mechanism. In reality, it is the principle that enables us to calculate the energy yield of processes that convert mass differences into radiation or kinetic energy. It is a statement of equivalence, not a recipe. Its power lies in its universality. One might also ask, why does the speed of light squared appear in this relation? The answer lies in the geometry of spacetime itself. The factor arises naturally from the relativistic relationships between energy, momentum, and mass. The speed of light serves as the conversion constant between units of mass and energy, linking them in a way that reflects the underlying structure of physical law. It is not arbitrary, but a reflection of how the universe itself is woven together. There is also a subtlety in how physicists interpret the terms. Mass in this context refers to rest mass, the intrinsic property of an object independent of motion. Energy includes both rest energy and kinetic energy. The relation does not mean that moving objects gain mass in the everyday sense, but that their total energy increases. This distinction matters in modern physics, where precision is essential, but the essential insight remains. Mass and energy are interchangeable, bound by a constant of nature. From a broader perspective, the mass-energy connection underscores a theme in physics, that simplicity can conceal profound depth. Three elements, energy, mass, and the speed of light, capture an idea that reshapes how we see stars, atoms, and ourselves. The clarity of the expression belies the richness of its meaning. And perhaps here we can pause for a quiet reflection. If matter is condensed energy, then everything around us, the chair you sit on, the air you breathe, your own body, is a form of frozen light, bound into substance by the rules of physics. The energy that blazes in the cores of stars is the same energy bound in every atom of your being. The universe reveals itself not as a collection of separate categories, but as a continuous transformation of one essence into another. And maybe there is something humbling in realizing that the solidity of matter is not so solid after all, but a temporary arrangement of energy destined to transform, to radiate, to return to the wider cosmos. In this sense, energy equals mass times the speed of light. Squared is not only a scientific relation, but a quiet reminder that even the most enduring things are part of a ceaseless exchange, energy and mass flowing into one another, shaping the story of the universe across time. Chapter 8. Paradoxes that aren't. Twin paradox and beyond. One of the surest signs that a scientific theory has touched something deep about reality is that it generates apparent paradoxes. These are scenarios that, when described in ordinary language or thought experiments, seem contradictory, even absurd. Special relativity, with its insistence that time and space depend on the observer, has produced many such puzzles. They are often called paradoxes because they challenge intuition, but none of them, once carefully examined, truly undermines the theory. They are not paradoxes in the sense of irreconcilable contradictions. Rather, they are invitations to rethink our assumptions and to glimpse the strange but consistent structure of space-time. Perhaps the most famous of these is the so-called twin paradox. It is a story simple enough to capture the imagination, yet profound enough to trouble even those who study relativity seriously. Imagine two identical twins. One stays on Earth while the other boards a spacecraft and travels close to the speed of light before returning home. According to relativity, time for the traveling twin flows more slowly compared to the twin who remains on Earth. When they reunite, the traveler has aged less. In some versions, the difference is only a few years. In others, depending on the speed and duration of the journey, it could be centuries. At first, this seems straightforward, until one recalls the principle of relativity itself. If all motion is relative, could we not equally well say that the twin on Earth was the one moving while the spacecraft remained at rest? In that case, wouldn't the Earth-bound twin be the younger one when they meet again? Each twin could point to the other as the traveler, and so the situation seems symmetrical. How then can relativity produce an unambiguous result? The resolution lies in the details of the journey. The twin who departs Earth must accelerate to reach high speed, decelerate to turn around, and then accelerate and decelerate again to return. These periods of acceleration break the symmetry. The twin on Earth remains in a single inertial frame while the traveler switches between frames. Special relativity applies cleanly only to inertial motion, but when acceleration is taken into account, the mathematics yields a consistent answer. The traveling twin is younger. This is not a flaw in relativity, but a consequence of applying it carefully. Experiments, though not with human twins, have confirmed the effect. Fast-moving particles decay more slowly than identical particles at rest, just as the traveling twin's body would age more slowly than the one left behind. Atomic clocks flown on aircraft or satellites record measurable differences in elapsed time compared to clocks on the ground, matching the predictions. The twin paradox is not just a thought experiment, but a reflection of the universe's behavior. Philosophers and physicists alike have reflected on the deeper implications of this scenario. It is not just about comparing two clocks, but about comparing two lives. The paradox dramatizes the idea that time itself is personal, linked to one's path through space-time. Two people born together can diverge not only in experience, but in the very number of years they live before reuniting. The story of the twins captures the essence of relativity, that time is not universal, but relative to motion. Beyond the twin paradox, other scenarios often spark confusion. One is the ladder paradox, sometimes called the barn paradox. In it, a long ladder is carried at relativistic speed into a barn shorter than the ladder's rest length. From the barn's perspective, the ladder contracts and fits neatly inside, even allowing the doors to close momentarily. From the ladder's perspective, however, it is the barn that contracts, making it impossible for the ladder ever to be fully enclosed. At first glance, this seems contradictory, but the resolution comes from the relativity of simultaneity. For the barn observer, there is a moment when the entire ladder is inside. For the latter observer, the front has already emerged before the back has entered. Each description is valid in its own frame, and no contradiction arises once simultaneity is recognized as relative. Variations of this paradox add richness. What if the doors are closed simultaneously in the barn's frame? Then indeed the ladder fits. But in the ladder's frame, the rear door closes after the front door opens. The doors never trap the ladder, and again, no contradiction arises. The paradox highlights how our intuition about simultaneity fails when objects move near the speed of light. Another well-known puzzle is the Ehrenfest paradox, which concerns a rotating disk. In relativity, objects moving at high speed contract in the direction of motion. If a disk spins rapidly, the circumference moves at high speed relative to the center, and thus should contract. But the radius perpendicular to the motion does not contract. If the radius remains the same while the circumference shrinks, the familiar relation between circumference and radius from Euclidean geometry no longer holds. This appears paradoxical, but in fact reveals an important truth. In relativity, space is not strictly Euclidean. The geometry of a rotating disk is curved. What the paradox uncovers is not a contradiction, but a glimpse of non-Euclidean geometry, which later became central to Einstein's general relativity. There is also Bell's spaceship paradox, another scenario designed to test the edges of relativity. Imagine two spaceships connected by a thin thread, both accelerating in unison as seen from an external observer. Will the thread break? Intuition might suggest not, since both ships move together. But relativity shows that because of length contraction and the relativity of simultaneity, the distance between the ships as measured in their own accelerating frame actually increases. The thread is stretched and eventually breaks. The paradox dissolves once the proper relativistic description of acceleration is applied. Other paradoxes play with similar themes. In the so-called pole in the barn version of the ladder paradox, a runner carries a pole that is longer than a barn but fits inside because of length contraction. In some retellings, the runner insists the barn is contracted so the pole cannot possibly fit. Once again, the key lies in simultaneity. In the barn's frame, the entire pole is inside at one instant, while in the runner's frame, it never is. There is no contradiction, only differing perspectives. Another classic is the watch and spaceship paradox, in which observers argue about whether two clocks remain synchronized after one undergoes acceleration. Confusion arises because people attempt to apply inertial logic to non-inertial frames. Once acceleration and relativity of simultaneity are properly accounted for, the predictions agree perfectly. What unites all these examples is that they arise from trying to apply Newtonian intuition to relativistic situations. Our everyday experience teaches us that lengths are fixed, time is universal, and simultaneity is absolute. When those assumptions fail at high speeds, paradoxes seem to emerge. But when the full machinery of relativity is applied, they are resolved and consistency is restored. Relativity does not invite contradiction, it demands a more subtle logic. The persistence of these paradoxes in popular imagination speaks to how deeply counterintuitive relativity remains. Even more than a century after Einstein's work, the idea that time and space can change depending on motion still feels foreign. It is easy to imagine a spaceship moving near light speed. It is harder to accept that such motion alters the fundamental measures of length and simultaneity. The paradoxes give us a way to confront that discomfort to wrestle with the consequences until they become, if not intuitive, at least coherent. It is also important to emphasize that relativity preserves causality. None of these paradoxes allow an effect to precede its cause or create genuine contradictions in physical law. The apparent contradictions come from mixing frames of reference without accounting for how relativity transforms between them. Once those transformations are included, the puzzles vanish. The universe remains orderly, even if its order is stranger than we once imagined. On a deeper level, the so-called paradoxes highlight the relativity of human perspective. We tend to assume that our view of the world, our sense of simultaneity, our definitions of length and time, is the natural one. Relativity reveals that such assumptions are bound to our limited range of speeds and scales. In the broader universe, perspectives differ, and all are valid within their own frames. The twin paradox, in particular, invites existential reflection. It reminds us that time itself is not a universal rhythm, but a personal one, linked to one's path through spacetime. Two lives beginning together can diverge not only in experience but in the very number of years they live before reuniting. The notion that a traveler could return to find decades passed while only years slip by for them is not only possible but inevitable under relativity. And perhaps this is the quiet lesson behind all the paradoxes, that reality resists being reduced to a single narrative. The universe does not grant one privileged frame of reference or one absolute now. It offers a web of perspectives, consistent but relative, each revealing its own truth. What seems paradoxical at first is simply the mismatch between our intuition and the cosmos's deeper order. As you drift towards sleep, consider that these paradoxes are not failures of logic, but invitations to expand it. They show us that the universe is more subtle than our instincts suggest, but also more coherent. The cosmos allows no contradictions, only new ways of seeing. And in that recognition lies both humility and wonder, that even in its strangest puzzles, reality remains whole, consistent, and beautifully resistant to simplicity. Chapter 9. Experiments that prove special relativity. The true strength of a scientific theory lies not in its elegance or its ability to capture imagination, but in its ability to withstand the scrutiny of experiment. Einstein's special relativity, proposed in 1905, emerged from a combination of logical reasoning, mathematical consistency, and insights into the constancy of light. Yet for all its boldness, it would have remained speculation if not for a century of empirical confirmations. The beauty of relativity is not only that it transforms our understanding of time, but that it has been tested, refined, and confirmed in countless experiments. Each test, whether performed with light beams, atomic clocks, or high-energy particles, has reaffirmed the same truth. The universe behaves exactly as relativity predicts. The earliest experimental hints came even before Einstein's work. The most famous of these is the Michelson-Morley experiment of 1887, an attempt to detect the motion of Earth through the hypothetical luminiferous ether. If light were a wave, physicists reasoned, it must have a medium in which to propagate, just as sound requires air or water requires the sea. By splitting a beam of light and sending the parts along different paths, Michelson and Morley expected to measure a difference in their travel times depending on the Earth's velocity through this ether. But no such difference was observed. The speed of light appeared constant in all directions, regardless of Earth's motion. The result was baffling at the time, but it later became one of the cornerstones supporting Einstein's postulate that the speed of light is invariant for all observers. A few years later, further optical experiments reinforced this conclusion. Variations of Michelson-Morley with greater sensitivity, as well as experiments involving moving sources of light, consistently failed to detect any motion through an ether. These null results did not immediately overturn classical physics, but they created mounting tension. The absence of an ether wind demanded explanation, and relativity eventually provided it. No ether was needed because the speed of light is constant in all inertial frames. After Einstein proposed special relativity, experimentalists sought more direct confirmations of its predictions. Among the first was the observation of time dilation in radioactive particles. Unstable particles such as muons, created when cosmic rays strike the upper atmosphere, decay rapidly, with lifetimes far too short to allow them to reach Earth's surface at ordinary speeds. Yet detectors on the ground consistently record their arrival in large numbers. The explanation is relativity. From our perspective on Earth, the muons' internal clocks tick more slowly because they are traveling close to the speed of light. They live longer, long enough to penetrate deep into the atmosphere and reach detectors. From the muons' own perspective, their lifetimes are unchanged, but the atmosphere they must traverse is contracted, allowing them to cover the distance. In either frame, the predictions of relativity resolve the puzzle, and the experimental data match perfectly. Controlled laboratory experiments have replicated this phenomenon with precision. Particle accelerators routinely create unstable particles moving at relativistic speeds, and their decay times are measured with exquisite accuracy. Each time, the observed lifetimes are extended exactly as relativity predicts. The muon, once a curiosity from cosmic rays, has become one of the best confirmations of time dilation in the laboratory. Another striking test came from experiments with fast-moving atomic clocks. In 1971, Joseph Hafele and Richard Keating placed 4 cesium beam atomic clocks aboard commercial airliners that circled the globe, some eastward, some westward. When the clocks were compared to those kept stationary at the U.S. Naval Observatory, they showed measurable differences. The airborne clocks had experienced time differently depending on their direction of travel, their speed, and their altitude. The results were in precise agreement with relativity, which had predicted not only time dilation from velocity, but also gravitational effects described by general relativity. This experiment, performed with technology available half a century ago, confirmed in real-world conditions what Einstein had described in abstract theory. Modern technology relies on these relativistic effects to function. The Global Positioning System, a network of satellites orbiting Earth, depends on clocks accurate to billionths of a second. Yet these clocks tick differently from those on the ground because of both their speed and their position in Earth's gravitational field. Engineers must correct for these relativistic effects, or GPS positions would drift by kilometers each day. The fact that your phone can tell you your location with astonishing accuracy is possible only because relativity is true. Experiments with high-energy physics have further confirmed length contraction and energy mass equivalence. In accelerators like the Large Hadron Collider, particles are accelerated to speeds within a fraction of a percent of the speed of light. Their behavior under collisions, their production of new particles, and their decay patterns all match the predictions of relativity. For example, the equivalence of mass and energy is demonstrated every time a high-energy collision creates particles heavier than those that entered. The additional mass comes from the kinetic energy of the collision, transformed exactly as relativity demands. Other precision experiments have tested the relativity of simultaneity and the invariance of light's speed. One approach involves comparing atomic clocks separated by large distances and linked through networks of lasers. These comparisons show that no matter the orientation of the system or the Earth's motion through space, the speed of light remains invariant. Similarly, particle physics experiments with electron-positron collisions have demonstrated that the rules of relativity hold even under extreme conditions of energy and velocity. In the 20th and 21st centuries, technology has reached levels where relativity can be tested with breathtaking accuracy. Optical lattice clocks, among the most precise devices ever built, can measure differences in time dilation when one clock is raised by just a few centimeters in Earth's gravitational field or moved at tiny velocities. Even such minuscule effects align with relativity's predictions. The theory has survived every attempt to find deviations. There are also astrophysical confirmations. When jets of plasma shoot from the centers of active galaxies, they move at speeds so close to light that their behavior must be interpreted using relativistic models. The observed radiation and apparent motions confirm time dilation, relativistic beaming, and other effects predicted by Einstein. Likewise, the observation of high-energy cosmic rays, which travel across millions of light-years, matches expectations only if time dilation extends their lifetimes in transit. Even the discovery of gravitational waves in 2015 indirectly confirmed the consistency of relativity at high precision. Although gravitational waves belong to general relativity, their propagation at the speed of light and their detection through interferometry reaffirmed the invariance of light speed that underpins special relativity. It is worth pausing to recognize that these experiments span scales from the subatomic to the cosmic. They involve delicate laboratory clocks, massive particle colliders, satellites orbiting Earth, and signals from galaxies billions of light-years away. Yet all of them tell the same story. Relativity's predictions hold. No matter how strange its claims about time, space, and simultaneity may seem, the empirical world continues to validate them. This unbroken record of confirmation has a philosophical weight. It shows that relativity is not merely a clever reinterpretation of mathematics, but a faithful description of reality itself. The constancy of light speed, time dilation, length contraction, the equivalence of mass and energy, all are not only ideas in textbooks, but physical truths etched into the behavior of particles, the ticking of clocks, and the light of distant stars. And perhaps there is something existential in this. The experiments remind us that our intuitions, shaped by slow movements and short lifetimes, are not reliable guides to the universe. Reality is deeper, stranger, and more coherent than common sense would allow. That a plane flying around the world or a particle racing through a collider can alter its experience of time shows us that even the most familiar quantities are relative. In these experiments, we glimpse a universe that does not conform to our expectations, but to its own profound order. As you rest, you might think of those tiny muons streaking through the atmosphere, their lives stretched by their speed, or of atomic clocks circling the globe, each ticking at its own rhythm. These experiments are not just tests of a theory. They are reminders that time and space are malleable, woven into a fabric far subtler than our senses reveal. The cosmos, tested and measured again and again, whispers the same truth. Relativity is real, and in its strange order lies a beauty beyond intuition. Chapter 10. How Special Relativity Changed Our Universe. When Albert Einstein submitted his 1905 paper on the electrodynamics of moving bodies, he likely did not imagine that he was altering the course of human thought as profoundly as Copernicus or Newton had centuries before. At the time, it was one of several works he produced in what has since been called his miracle year. Yet among those papers, Special Relativity was the one that permanently shifted the foundations of physics. What began as a re-examination of how light behaves soon reshaped our understanding of time, space, energy, and motion. Its consequences ripple outward into modern technology, cosmology, and even philosophy. The immediate impact of special relativity was to break the centuries-old idea of absolute space and time. Newton had envisioned a universe in which time flowed uniformly everywhere, a cosmic clock ticking in unison across the stars, and space provided a rigid, immutable stage on which events played out. This view was not merely scientific, but almost metaphysical. It gave people confidence in a universe ordered by absolutes. Einstein dismantled that certainty. In its place, he offered a universe woven together by relative measures of time and distance, bound by the constancy of the speed of light. It was not that the cosmos had lost its order, but that its order was subtler, more relational, and more deeply intertwined than previously imagined. The philosophical shock was immense. Suddenly, questions that had seemed straightforward, such as whether two events happened at the same time, had no universal answer. Simultaneity became relative, time became personal, and distances depended on perspective. These were not abstract musings, but direct consequences of experimental fact. The Michelson-Morley experiment had already hinted at the collapse of the ether concept. Einstein completed the revolution by declaring that no ether was needed. The universe itself had no preferred frame, no ultimate perspective. Reality was egalitarian, granting validity to every inertial observer. This restructuring of time and space was not accepted overnight. Many physicists initially resisted, some preferring alternative explanations, such as Lorentz's ether theory. The idea that time itself could flow differently for different observers seemed too radical. Yet within a few years, the mathematical consistency of relativity and its agreement with experiment won converts. Max Planck, already famous for founding quantum theory, was among the first to recognize the theory's significance. Hermann Minkowski soon reformulated it into the geometry of four-dimensional spacetime, giving the theory an elegant mathematical framework that deepened its reach. By the 1920s, relativity had become foundational to physics, taught in universities and applied to new problems. What had seemed outrageous in 1905 was, within 2 decades, indispensable. The philosophical impact extended far beyond physics. Writers and thinkers seized on relativity as a metaphor for a world in which absolutes were dissolving. In art and literature, movements such as Cubism and Modernism played with fractured perspectives and multiple viewpoints, echoing the relativity of simultaneity. Philosophers debated whether relativity implied a deterministic block universe, in which past, present, and future coexist equally. Others wondered whether it undermined human freedom or reinforced it by showing the diversity of perspectives. Relativity became more than a scientific theory. It became a symbol of modernity itself, embodying the collapse of old certainties and the embrace of new, unsettling truths. Special relativity also redefined the concept of energy. The realization that mass is a form of energy changed not only physics, but technology. Nuclear energy, whether in reactors that light cities or in weapons that destroy them, is a direct consequence of Einstein's insight. The equivalence of mass and energy explained why the sun shines, why stars live and die, and why the cosmos itself evolves. It bound together the smallest scales of particle physics with the largest scales of astrophysics. The theory revolutionized experimental practice as well. Particle accelerators, designed in the 20th century and still central to physics today, operate entirely within a relativistic framework. They accelerate protons and electrons to speeds close to that of light, requiring relativistic equations to describe their behavior. Without relativity, such machines could not be designed or interpreted. Every discovery made in high-energy physics, from quarks to the Higgs boson, rests on the scaffolding of Einstein's 1905 insight. Technology in daily life, too, is shaped by relativity. Global navigation systems, which depend on atomic clocks aboard satellites, must correct for time dilation due to both their speed and their position in Earth's gravitational field. The engineers who designed them did not include relativity out of philosophical preference, but because without it the system would fail. Each time a smartphone locates its user with meter-scale precision, it demonstrates that relativity is not merely an abstract theory, but an active component of modern infrastructure. Medical technology, though less obvious, also benefits from relativity. Positron emission tomography, PET scanning, relies on the annihilation of particles and antiparticles, in which their mass is converted into photons of pure energy. This principle derives directly from mass-energy equivalence. The ability to peer into the human body with such precision, to diagnose disease at early stages, is a consequence of Einstein's insight into the deep connection between mass and energy. Relativity also changed the way humanity conceives of travel and exploration. Though we have yet to build spacecraft capable of approaching light speed, the thought experiments of relativity shape our imagination of interstellar journeys. The twin paradox reminds us that high-speed travel comes with the price of time dilation. Travelers may return home to find centuries past. This reality reshapes how we dream about colonizing the stars, grounding those dreams in the unyielding limits of physics. For science fiction writers, relativity became a narrative boundary, sometimes respected, sometimes circumvented with imagined technologies like warp drives or wormholes. But even those fictions acknowledge Einstein by defining themselves in relation to his limits. Cosmology, too, owes much to special relativity. The framework of spacetime, the interplay between energy and mass, and the constancy of light speed all form the foundation upon which general relativity was built. General relativity then gave rise to modern cosmology. The expanding universe, the Big Bang, black holes, and gravitational waves. Without special relativity, there could be no general relativity. Without general relativity, our view of the universe's origin, structure, and fate would remain incomplete. What makes the impact of special relativity remarkable is not only its reach, but its resilience. For more than a century, physicists have tested its predictions with ever greater precision. Atomic clocks, subatomic particles, and astrophysical phenomena all behave exactly as relativity demands. No experiment has yet contradicted it. This robustness is a hallmark of great science. Ideas that begin as radical challenges to intuition become pillars of knowledge, shaping every generation that follows. And yet, for all its success, special relativity also left open questions. It reconciled mechanics with electromagnetism, but did not incorporate gravity. It reshaped our view of space and time, but did not address the quantum behavior of matter. Einstein himself, after publishing his general theory in 1915, spent much of his later career searching for a deeper unification, one that might bring relativity and quantum mechanics together. That search continues today, with string theory, loop quantum gravity, and other approaches, all seeking to extend the legacy of relativity into a broader framework. The cultural legacy of relativity endures as well. It symbolizes the modern scientific spirit, bold enough to question the most basic assumptions, rigorous enough to follow reason wherever it leads, and humble enough to accept that reality may be stranger than intuition. It has entered language itself. To say something is relative is to acknowledge the lesson Einstein made famous, that truth may depend on perspective. There is, too, an existential echo in its lessons, to learn that time is not absolute, that simultaneity is not universal, and that mass is simply another form of energy, is to confront a universe stranger than intuition allows. We are reminded that our everyday sense of reality, shaped by slow speeds and small scales, is not the measure of truth. The cosmos moves according to deeper laws, indifferent to our assumptions. And perhaps that is the quiet gift of special relativity. It tells us that reality is consistent, but not simple, coherent, but not comforting in the ways we once imagined. It reveals a universe without a single center, without an absolute present, without a privileged perspective. Yet in stripping away those absolutes, it gives us something richer. A vision of the cosmos as a web of relationships, where every observer carries their own time, their own space, and yet all are bound together by the same laws. As you rest, you might think of how extraordinary it is that such a profound shift came not from vast observatories or grand experiments, but from the imagination of a young man working in a patent office. With clarity and courage, Einstein asked what would happen if one took the speed of light seriously, if one followed its consequences without compromise. Out of that question came a theory that reshaped not only physics, but our conception of reality itself. The universe we inhabit is no longer Newton's fixed stage, but Einstein's dynamic, relative spacetime. And in that realization lies a humbling beauty, that the cosmos is far stranger and far more wondrous than the world of absolutes we once believed in. Section 4. The Physics of Time, Relativity, Gravity, and Time Travel Limits. Chapter 1. What is time, really? Time is one of those concepts that feels so familiar we rarely stop to question it. We sense it passing in the rhythm of our days, in the slow brightening of morning, in the ticking of a clock on the wall. We feel it when we wait for something to happen, and we measure it when we try to be precise. Yet for all its apparent simplicity, time is one of the most elusive and puzzling aspects of reality. The more closely science has looked at it, the less it has behaved like the simple, universal background we once thought it to be. For much of human history, time was assumed to be absolute, a steady river flowing at the same pace for all people, in all places. The ancient Egyptians used sundials, tracking the shadow of a gnomon to mark the hours. The Babylonians divided the day into segments of 60, a system that still lingers in our minutes and seconds. Mechanical clocks emerged in the Middle Ages, ticking away in city squares, giving the impression that time could be perfectly uniform. In Newton's physics, this was more than just an impression. It was a foundation. Isaac Newton imagined time as an unchanging, universal backdrop, flowing evenly and independently of anything else in the universe. According to this view, the time between two events was the same for everyone, everywhere. But our understanding of time changed radically in the early 20th century. Experiments and theory began to suggest that time is not the universal constant we once assumed. Instead, it is woven into the very fabric of the universe, and it can stretch compress, and even behave differently depending on where you are and how you move. This shift in thinking began with the work of Albert Einstein, who showed that space and time are inseparable parts of a single four-dimensional continuum known as spacetime. Einstein's breakthrough was not just in describing how space and time fit together, but in revealing that they are not fixed. They are dynamic, flexible, and influenced by the presence of matter and energy. The speed at which time passes depends on factors like motion and gravity, meaning two observers can disagree on the amount of time that has elapsed between the same pair of events. This is not an illusion or a trick of perception. It is a real, measurable effect that has been confirmed by countless experiments. To grasp why this is so surprising, it helps to think about what we actually mean by time. In science, time is not simply the ticking of a clock, but a measure of change. It is the ordering of events, what happened first, what came after, and by how much. In classical physics, time was treated as a stage upon which events play out. But in modern physics, the stage itself can bend, twist, and change shape depending on what is happening within it. This is why time is so deeply connected to motion. One of Einstein's key insights in special relativity is that the speed of light is the same for all observers, regardless of how they are moving. This may sound like a small technical detail, but it has extraordinary consequences. If the speed of light is fixed, then space and time must adjust themselves to preserve that constancy. And they do so by allowing time to flow at different rates for different observers. Imagine two people, one sitting still on Earth and another moving at a significant fraction of the speed of light. For the person in motion, time will pass more slowly relative to the person at rest. This is not a matter of perception, it is a physical difference. If they carry identical clocks, each will find that the other's clock ticks more slowly. This phenomenon, known as time dilation, is not a matter of faulty instruments. It is built into the structure of spacetime itself. This strange behavior is not confined to theoretical thought experiments. It has been observed and measured in real life. Particles called muons, created when cosmic rays strike Earth's atmosphere, live for only a fraction of a second before decaying. If they were at rest, they would never survive the trip to the surface. But because they travel at nearly the speed of light, their internal clocks run slower relative to Earth's frame of reference, and they last long enough to reach detectors at ground level. In laboratories, scientists have placed extremely precise atomic clocks on fast-moving aircraft and satellites and compared them with identical clocks on the ground. The results match Einstein's predictions perfectly. The moving clocks register slightly less time having passed. Gravity, too, plays a role in shaping time. General relativity, Einstein's extension of special relativity, describes how massive objects warp space-time around them. This curvature affects the passage of time itself. In a stronger gravitational field, closer to a massive object, time runs more slowly compared to regions with weaker gravity. Experiments have confirmed this as well. Two identical atomic clocks, one placed at the base of a mountain and another at the summit, will tick at slightly different rates, with the clock in the stronger gravity at the base running more slowly. This effect is tiny in everyday life, but becomes extreme near black holes, where time can appear to nearly freeze for an outside observer watching something fall toward the event horizon. All of this means that time is not a universal metronome ticking away at the same rate for everyone. Instead, it is local. Each observer carries their own clock, and while those clocks may agree under some conditions, they can also diverge in measurable ways, depending on motion and gravity. The common idea of a now shared by the entire universe is an illusion. In relativity, simultaneity is not absolute. Two events that happen at the same time for one observer may happen at different times for another. Still, for most of us moving slowly through relatively weak gravitational fields, these differences are so small they escape notice. A person walking down the street experiences time almost identically to someone standing still on the corner. But zoom out to cosmic scales or speed up to relativistic velocities, and these subtle differences grow into something profound. Astronauts aboard the International Space Station orbiting Earth at about 7.7 kilometers per second experience time slightly differently from people on the ground. Over 6 months, the difference might be only a fraction of a second, but it is real and measurable. Understanding that time is relative challenges deeply ingrained intuitions. Our brains evolved in a world where such effects are too small to notice. We are accustomed to thinking of time as a single thread that everyone follows together. Modern physics shows us instead that time is a tapestry of many threads, each belonging to its own observer, all woven together by the geometry of spacetime. And yet, even as science reshapes our understanding of time, it does not take away its mystery. We can describe in exquisite detail how time behaves under different conditions, how it stretches and compresses, how it connects to motion and gravity. But the question of what time truly is, why it exists at all, why there is a past and a future, remains unanswered. We can measure time, manipulate it, and account for its distortions, but we cannot yet say why it flows in the first place, or whether it flows at all in the way we imagine. It is here that physics brushes against philosophy. Perhaps time is not something that flows, but rather a landscape through which we move. Perhaps past, present, and future all coexist, and our consciousness merely experiences them in sequence. Or perhaps the flow of time is an emergent property of deeper laws we have not yet discovered. In this way, time remains both the most familiar and the most mysterious aspect of reality, a constant companion in our lives, yet a puzzle that resists complete understanding. As you sit here now, you are moving inexorably forward in time, even if you feel still. Every beat of your heart marks another step into the future. And somewhere, far away in the universe, there are places where that step is slower, and others where it is faster. But it is always yours, a personal journey through a dimension we all share, yet never experience in quite the same way. Chapter 2. Einstein's breakthrough, Time is Relative. At the dawn of the 20th century, physics stood on what seemed to be a solid foundation. Newton's laws had reigned for more than 2 centuries, predicting the motion of planets, the fall of apples, and the swing of pendulums with unfailing accuracy. Space was seen as an immutable stage, time as the ever-flowing river upon which events unfolded. Together, they formed the backdrop to all physical phenomena, absolute and unaffected by anything happening within them. But there were cracks in the foundation, small at first, yet persistent enough to trouble the most attentive minds. These cracks appeared in the study of light and electromagnetism, and they eventually forced physicists to question ideas that had seemed self-evident for generations. For centuries, people assumed that motion through space could always be measured relative to some ultimate rest frame, a cosmic zero point, against which all motion could be judged. When it came to sound, that reference frame was the air. When it came to light, physicists assumed something similar existed, an invisible medium called the luminiferous ether. Light, it was thought, traveled through this ether in the same way that waves travel through water or vibrations through air. This made perfect sense at the time. If light was a wave, then surely it needed something to wave through. And if such an ether existed, then moving relative to it should subtly change the speed of light you measure. In 1887, Albert Michelson and Edward Morley set out to detect this effect with an exquisitely sensitive experiment. They expected to find that light moved slightly faster in one direction than another, depending on how Earth was moving through the ether. But they found nothing. The speed of light was exactly the same in all directions, no matter how they measured it. The ether, it seemed, was undetectable. This was deeply puzzling. It contradicted the intuition that speeds should add and subtract in a straightforward way. If you are running toward a sound source, the waves should reach you faster. If you are running away, they should reach you slower. Why should light be any different? Some physicists tried to save the ether by inventing ad hoc explanations, such as the idea that objects moving through it might physically contract in the direction of motion. Others suspected something more radical might be at play, but they lacked a coherent framework to explain it. It was into this climate of uncertainty that a young Albert Einstein stepped in 1905, in what is now called his miracle year. In one of his papers, he presented what he modestly called "On the Electrodynamics of Moving Bodies," the work that would later be known as the special theory of relativity. Instead of trying to patch Newtonian physics with extra assumptions, Einstein began with two deceptively simple postulates. First, the laws of physics are the same for all observers moving at constant speeds relative to one another. There is no preferred frame of reference. Second, the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the source. At first glance, these statements seem harmless, but together they demand a profound rethinking of space and time. If the speed of light is fixed and the laws of physics are the same in all inertial frames, then the only way to reconcile these facts is to abandon the idea that space and time are separate, absolute entities. Instead, they must adjust themselves to preserve the constancy of light's speed. This adjustment is what we now recognize as the relativity of time and space. Einstein's logic was both simple and shocking. Imagine two observers, one standing still on a train platform, the other riding on a train moving at high speed. If a flash of light occurs midway between the front and back of the train, the observer on the train sees the light reach both ends simultaneously. But for the observer on the platform, the rear of the train is moving toward the point of the flash, while the front is moving away from it. To them, the light should reach the rear sooner than the front. Since both observers must measure the same speed for light, the only possible resolution is that they disagree on whether the two events, the light reaching the front and back, happened at the same time. Simultaneity itself becomes relative. From this simple realization follows a cascade of consequences. Time intervals and distances are not fixed quantities that all observers agree on. They depend on the relative motion between the observers. A moving clock runs slower relative to one at rest. A moving ruler measures shorter than one at rest. These are not illusions caused by measurement errors. They are intrinsic features of reality as described by relativity. Einstein's equations showed exactly how these effects depend on relative velocity. For speeds much less than the speed of light, the differences are tiny, too small to matter in everyday life. But as an object's speed approaches that of light, the differences grow dramatic. In the limit of moving at light speed, time would appear to stop entirely for that object from an outside perspective, though in reality, nothing with mass can reach that ultimate speed. What made Einstein's breakthrough so powerful was that it explained the Michelson-Morley result without invoking any mysterious ether. There was no hidden medium for light to travel through. Instead, space and time themselves formed the arena in which light moved, and that arena had properties far stranger than anyone had previously imagined. Light's constant speed was not an accident, but a fundamental feature of the geometry of spacetime. It is worth emphasizing that Einstein did not merely propose a new philosophy of time. His theory made concrete predictions that could be tested. One such prediction was the time dilation effect on moving clocks. This was later confirmed in particle physics experiments, where unstable particles moving at high speeds live longer than identical particles at rest. It was also confirmed when highly precise atomic clocks were flown on airplanes and compared to those on the ground. The airborne clocks fell behind exactly as relativity predicted. The special theory of relativity deals only with observers moving at constant speeds relative to one another, without acceleration. But Einstein's work did not stop there. Within a decade, he extended his ideas to include acceleration and gravity in the general theory of relativity. In that broader framework, gravity itself is understood as the curvature of spacetime, and time is affected not just by motion, but by the presence of mass and energy. That is the domain in which gravitational time dilation, the slowing of time in stronger gravitational fields, naturally emerges. But even in the special theory, stripped of gravity's complexities, the relativity of time is an astonishing shift in perspective. For centuries, we assumed that there was one master clock governing the universe, ticking away in perfect synchrony everywhere. Einstein showed us that this was an illusion. Every observer carries their own clock, and there is no absolute sense in which one is correct, and the others are wrong. The laws of physics care only about the relationships between these clocks, not about any universal timekeeper. This realization has profound consequences. It means that the sequence and timing of events can depend on your path through spacetime. It means that the notion of a shared now across the cosmos is meaningless without specifying an observer's frame of reference. It also means that time is not something separate from the physical world. It is part of the fabric that matter and energy shape and are shaped by. In the years since Einstein's 1905 paper, relativity has become one of the most thoroughly tested theories in all of science. Its predictions have been confirmed in particle accelerators, in the timing of pulsars, in the operation of the global positioning system, and in countless other ways. Yet the core insight remains as startling today as it was more than a century ago. Time is not absolute. It is relative to motion and to the geometry of the universe itself. If there is an existential lesson to be drawn from this, it might be that our everyday sense of reality is only a narrow window into a far richer structure. We imagine ourselves all moving together through time, synchronized in the same moment. In truth, each of us carries our own personal thread through spacetime, woven in ways that others cannot perfectly match. Somewhere out there in the vastness, another clock is already ahead of yours, another is behind, and neither is more real than the other. Time belongs to no one and to everyone, and in that quiet truth, we find both our individuality and our connection to the cosmos. Chapter 3. Moving through time at different speeds. In everyday life, time seems to flow at the same pace for everyone. Whether you are walking to the store, sitting in an office, or riding a train, you feel as though the seconds are slipping past in a steady rhythm. Clocks appear to agree with each other, and if there is any difference at all, it is small enough to be ignored. This common experience has shaped our intuitive sense of time for centuries. But physics shows us that this sense is incomplete. The flow of time is not uniform across all observers. How quickly time passes for you depends on how you move through space, and by extension, through space-time itself. In Einstein's framework, space and time are inseparable. They form a single four-dimensional continuum in which all events take place. Every object, from a grain of dust to a galaxy, follows a path through this continuum called a world line. The speed at which an object moves through space determines how it moves through time. In a deep and precise sense, all objects travel through space-time at the same overall rate, but the division between motion in space and motion in time shifts depending on the object's velocity. The faster you move through space, the less you move through time. This idea can be difficult to picture because our senses are not equipped to detect changes in the rate of time directly. If you were on a spaceship traveling close to the speed of light, your own clock would tick normally. Your heartbeat, your thoughts, the rhythm of your speech, all would feel exactly as they do now. But if someone back on Earth could somehow watch your clock as you flew past, they would see it ticking more slowly than theirs. If they could monitor your heart rate, they would see it slow. From their point of view, you would be living in slow motion, and the effect is mutual. From your perspective aboard the ship, it would be the people on Earth whose clocks run slow. Both points of view are valid. This symmetry is one of the most striking aspects of time dilation and special relativity. There is no universal right answer to the question of whose time is moving correctly. The only thing that matters is the relative motion between observers. This concept is famously illustrated by the so-called twin paradox. Imagine two identical twins. One remains on Earth, while the other sets off on a high-speed journey to a distant star and back. Upon returning, the traveling twin finds that less time has passed for them than for their sibling. Perhaps the earthbound twin has aged by 10 years, while the traveler has aged by only 6. Despite the name, there is no real paradox here. The resolution lies in the fact that the traveling twin must accelerate to turn around and come back, breaking the symmetry of motion between the two. But even without acceleration, the basic principle remains. Moving through space at high speed changes how you move through time. This is not mere speculation. Time dilation has been measured and confirmed in numerous experiments. One of the most elegant involves subatomic particles called muons. These particles are unstable, with a mean lifetime of about 2.2 millionths of a second when at rest. Produced high in Earth's atmosphere by cosmic rays, muons should decay long before they reach the surface. Yet many do reach the ground. The reason is that they are moving close to the speed of light, and in their own frame of reference, the time before they decay is unchanged. But from Earth's point of view, their internal clocks run slow, stretching their lifetimes enough for them to survive the journey. Laboratory experiments have reproduced this effect under controlled conditions. Physicists can create beams of fast-moving muons in particle accelerators and measure their lifetimes. Sure enough, the faster the muons move, the longer they live compared to their at-rest counterparts. The agreement between experiment and Einstein's predictions is exact, with no measurable deviation. A more down-to-earth example comes from experiments with atomic clocks. These devices are among the most accurate timekeepers ever built, able to measure time to within billionths of a second. In the 1970s, scientists placed synchronized atomic clocks on commercial airliners flying around the world, while identical clocks remained stationary in a laboratory. When the flying clocks were brought back, they were found to have lost tiny amounts of time compared to the stationary ones, exactly as special relativity predicts. The differences were small, mere billionths of a second, but they were real and measurable. In fact, modern technology must account for this effect. The global positioning system relies on satellites orbiting Earth, each carrying its own atomic clock. These satellites move at thousands of kilometers per hour relative to the ground, and their clocks tick more slowly because of time dilation. At the same time, they are farther from Earth's surface and experience weaker gravity, which causes their clocks to tick faster due to gravitational time dilation. The combination of these two effects must be precisely calculated and corrected for. Without these adjustments, GPS would accumulate navigation errors of several kilometers each day. That our devices can guide us within a few meters is a testament to the accuracy of Einstein's theory. These real-world demonstrations make it clear that time dilation is not a theoretical oddity, but a fundamental feature of the universe. When you move quickly relative to someone else, you are quite literally moving through time at a different pace. The effect is negligible at the walking speeds and car speeds of daily life, but it grows rapidly as you approach the speed of light. At 99% of that ultimate speed limit, time for you would run at less than half the rate experienced by someone at rest. Push the speed higher still, and the effect becomes even more dramatic. It is sometimes said that a spaceship capable of near-light travel could serve as a one-way ticket to the future. By accelerating to such speeds, a traveler could journey across the galaxy in what feels like a few years of personal time, only to find that centuries have passed on Earth. Science fiction has explored this idea for decades, and while the engineering challenges are immense, the physics behind it is sound. In this way, relativity offers a form of time travel, one that moves only forward, but as far forward as you like, depending on how fast you can go. This also means that time dilation is an inseparable aspect of space exploration at relativistic speeds. Any human mission that approached a significant fraction of the speed of light would return to an Earth much older than the crew. For the astronauts, their subjective experience of the voyage might be short, but they would come back to a planet that had changed beyond recognition. This is not a philosophical idea, but a mathematical certainty grounded in experimental fact. It is worth noting that time dilation does not involve any distortion of the traveler's own experience. To them, their clock runs normally, their heartbeat is steady, and their conversations unfold at the usual pace. The slowing down happens only relative to another observer in a different frame of motion. This is why the effect can be so counterintuitive. We are used to thinking of time as something we all share in common. But in reality, each of us carries our own personal version of it, shaped by our unique trajectory through spacetime. In this sense, motion through space is a kind of trade-off with motion through time. When you are at rest, all your motion is through time. As you move faster through space, less of your total motion is in the time direction. This trade-off is invisible to us at ordinary speeds, but it becomes unavoidable near the cosmic speed limit. Photons, the particles of light, are an extreme example. They move at the speed of light through space and not at all through time. From their point of view, if such a point of view could be meaningfully defined, no time passes at all between being emitted and being absorbed. This interplay between space and time underscores the unity of spacetime. We cannot change how fast time flows for us in an absolute sense, but by moving differently relative to others, we change how our time compares to theirs. Each observer's experience is internally consistent, yet different from every other's. This is why relativity is as much a revolution in perspective as it is in mathematics. Understanding this makes the universe feel both more strange and more connected. The notion that you could travel for what feels like a year and return to find that decades or centuries have passed elsewhere is not science fiction fantasy. It is a built-in feature of the way reality works. And this feature holds whether you are a muon in the upper atmosphere, an astronaut in orbit, or a hypothetical traveler skimming the edge of light speed. We live our daily lives far from these extremes, yet we are all moving through space-time at our own pace. No two clocks in the universe tick exactly alike, because no two share exactly the same motion or location in gravity's field. In a quiet way, we are all travelers through time, each following a unique path. And though our differences are small, they are real. A reminder that even something as familiar as the passing of seconds holds within it the deep and subtle structure of the cosmos. Chapter 4. Gravity's Grip on Time. It is natural to think of gravity as a force that pulls things down. Drop an apple and it falls to the ground. Release a stone above a pond and it plummets into the water. This is the gravity of everyday life. A steady, invisible hand that anchors us to Earth. For centuries, this picture was the foundation of our understanding. Newton described gravity as a universal attraction between masses, acting instantly across empty space. It was powerful and accurate enough to predict the motion of planets and the return of comets. But in Newton's world, time was untouched by gravity. No matter where you were, the seconds ticked away at the same universal rate. Einstein changed this view completely. In his general theory of relativity, published in 1915, gravity is not a force in the Newtonian sense. Instead, it is the manifestation of space-time curvature. Massive objects like planets, stars, and black holes deform the geometry of space-time around them. Other objects, and even light itself, move along paths dictated by this curvature. The result is that what we perceive as gravitational attraction is actually motion through a warped space-time landscape. One of the most surprising consequences of this new understanding is that gravity affects time itself. The stronger the gravitational field you are in, the slower time runs for you relative to someone farther from that source of gravity. This is not a matter of perception, nor is it caused by the physical stress of being in a gravitational field. It is a direct result of the way space-time geometry works. Just as gravity bends the paths of moving objects, it bends the path that time itself follows. To visualize this, imagine space-time as a vast, flexible surface. A massive object like Earth creates a dent in that surface, curving it inward. Clocks placed at different depths in that curvature tick at different rates. A clock closer to the mass, deeper in the gravitational well, runs more slowly than one farther away. This is gravitational time dilation. The effect is subtle in our daily lives. On Earth, the difference between a clock at sea level and one at the top of Mount Everest is tiny but measurable. Experiments with precise atomic clocks have confirmed this repeatedly. In one famous experiment in 2010, researchers placed one atomic clock on the floor and another just 33 centimeters higher. Even over such a small height difference, The clock closer to the ground, experiencing slightly stronger gravity, ticked more slowly than the higher one. The difference was only a few parts in 100 trillion, but it was real, exactly as predicted by general relativity. The same principle applies on larger scales. A satellite in orbit is farther from Earth's center and feels weaker gravity, so its clock ticks slightly faster than clocks on the ground. This effect is combined with the special relativistic time dilation caused by the satellite's speed, and both must be accounted for in systems like GPS. Without correcting for gravitational time dilation, GPS errors would grow by about 10 kilometers each day. The fact that our navigation devices work at all is a daily, silent confirmation that Einstein was right. Gravitational time dilation becomes far more dramatic near extremely massive and compact objects. Consider a neutron star, the collapsed core of a massive star, with a mass greater than the Sun's, packed into a sphere only about 20 kilometers wide. The gravitational field at its surface is billions of times stronger than on Earth. A clock placed there would tick far more slowly compared to one far away in interstellar space. From the perspective of a distant observer, any process on the neutron star, the ticking of a clock, the beating of a heart, even the decay of radioactive atoms, would appear to proceed at a glacial pace. And then there are black holes, the ultimate demonstration of gravity's effect on time. A black hole's mass is concentrated in a singularity, a point of infinite density, surrounded by an event horizon, the boundary beyond which nothing can escape. As you approach the event horizon from a safe distance, gravitational time dilation grows more and more extreme. To an outside observer watching from far away, your approach seems to slow. Your clock ticks ever more sluggishly. In the final moments before crossing the event horizon, your movement appears to freeze. Light from you becomes increasingly redshifted, stretched to longer and longer wavelengths until it fades from view entirely. From your own perspective, however, nothing unusual happens to your clock. Time flows normally for you as you cross the horizon. But the rest of the universe races ahead, possibly by millions or billions of years, depending on the black hole's size and the details of your trajectory. This extreme warping of time is not just a theoretical curiosity. Astronomers can see its effects in the light coming from matter near black holes. As gas spirals inward in an accretion disk, its emitted light is gravitationally redshifted, a direct fingerprint of time running differently in the intense gravity near the event horizon. These observations match the predictions of general relativity with extraordinary precision. Einstein's equations show that gravitational time dilation is a universal feature of spacetime. It is not confined to black holes or neutron stars. It happens everywhere there is mass, which means everywhere in the universe. Even Earth's modest gravity stretches time ever so slightly, enough for sensitive instruments to measure it. This universality is part of what makes general relativity so powerful. The same mathematics describes the tiny difference between two clocks a meter apart and the staggering slowdown near a black hole. From a practical standpoint, accounting for gravitational time dilation is essential in many areas of science and technology. In satellite navigation, in precision geodesy, in the operation of deep space probes, the effects of gravity on time are as real as the pull of gravity on a falling object. The equations that predict planetary orbits also predict the way time itself is bent by gravity. They are two sides of the same underlying geometry. It is striking to realize that gravity, which we experience so casually every day, is quietly altering the pace of time for us and everything around us. The difference is too small to feel, but it is there. You age ever so slightly more slowly at sea level than you would on a mountaintop. A pilot flying at high altitude ages a fraction more than someone sitting in an airport cafe. And if you could spend years near the surface of a neutron star without being crushed by its gravity, you could return to find that entire epochs had passed elsewhere. In this way, gravitational time dilation offers another route to what might be called time travel into the future. By living in a region of stronger gravity, you move more slowly through time compared to those in weaker gravity. Science fiction often imagines enormous time jumps achieved through high-speed spaceflight, but they could equally well be achieved by parking yourself near a compact massive object. Of course, in practice, the dangers of such environments make this a far less appealing option. There is something humbling in the realization that time is not the same everywhere. In the vast cosmic web of galaxies and stars, every region has its own pace, set by its motion and by the gravitational landscape it inhabits. The universe is not synchronized by a single master clock. Instead, it is a patchwork of times, each tied to its own place in spacetime's curvature. We are part of that patchwork, bound to Earth's gravity, moving through our own slightly slowed version of time. From a distance, the differences are tiny for most of us, but they are real and measurable. They remind us that time is not the fixed, unchanging backdrop we once thought it to be. It is pliable, influenced by mass and energy, bent by gravity into different shapes for different observers. Our everyday sense of time's universality is a useful approximation, but it hides the deeper truth that time itself is part of the gravitational fabric of the cosmos. And here, perhaps, lies the most unsettling and beautiful thought of all. Each of us lives in our own private river of time, flowing at a pace shaped by where we are and how we move. Two people standing side by side are almost perfectly synchronized, yet not entirely. Somewhere out there, deep in the heart of a galaxy, near the crushing pull of a black hole, someone else's river runs far more slowly, and all these rivers flow together into the vast, uncharted ocean of spacetime, a place where the seconds of one world may be the centuries of another. Chapter 5. Time Dilation in Everyday Technology. For most people, time dilation sounds like something distant, a phenomenon that belongs to the realm of high-energy physics experiments, deep space travel, or the extreme gravity near a black hole. But the truth is more surprising. Time dilation is part of the everyday infrastructure that quietly underpins modern life. It is not a theoretical curiosity you might only encounter in a physics classroom. It is a measurable effect that engineers, scientists, and technicians must account for if they want our technology to work correctly. Without the corrections dictated by relativity, some of the tools we rely on every day would quickly drift into uselessness. One of the most striking examples is the Global Positioning System. GPS is a network of satellites orbiting Earth at an altitude of roughly 20,000 kilometers. Each satellite carries multiple atomic clocks, which are among the most accurate timekeeping devices ever made. These clocks broadcast signals containing the precise time and the satellite's position. A GPS receiver, whether in a car, a smartphone, or a ship's navigation system, calculates its own position by comparing the arrival times of signals from at least 4 satellites. The calculation is essentially a timing problem. By knowing how long the signal took to arrive and the constant speed of light, the receiver can determine its distance from each satellite and thus pinpoint its location. This process depends critically on the synchronization of the satellite clocks with clocks on the ground. If the timing is off by even a few billionths of a second, the resulting position error can be tens or hundreds of meters. That might not matter much when looking at a map on a casual walk, but for navigation in aviation, shipping, or military operations, such errors could be disastrous. And here is where relativity steps in. The satellites are moving at about 14,000 kilometers per hour relative to the Earth's surface. According to special relativity, a moving clock ticks more slowly than one at rest relative to the observer. This causes the satellite clocks to lose about 7 microseconds per day relative to those on Earth. At the same time, because the satellites are farther from Earth's center, they experience weaker gravity. General relativity tells us that clocks in weaker gravity run faster, and in this case, the effect is stronger than the velocity-based slowdown. The reduced gravity speeds up the satellite clocks by about 45 microseconds per day. When both effects are combined, the net result is that satellite clocks tick about 38 microseconds faster per day than clocks on the ground. A difference of 38 microseconds might not sound like much, but light travels about 11 kilometers in that time. Without correcting for this difference, GPS positions would drift by roughly 10 kilometers each day. That level of inaccuracy would make GPS useless for navigation. Engineers solve the problem by pre-adjusting the satellite clocks before launch so that when time dilation effects are taken into account, they remain synchronized with ground-based time. In addition, the system constantly monitors and corrects for tiny variations that arise from other factors, such as changes in satellite orbits and temperature fluctuations affecting clock performance. GPS is perhaps the most widely known technological application where time dilation must be considered, but it is far from the only one. Modern communications networks, the global web of fiber optic cables, satellites, and switching stations, rely on precise timing to coordinate data transfer. Financial markets use high-frequency trading systems that depend on timestamps accurate to billionths of a second to determine the order of trades. In such systems, even small timing errors can have significant financial consequences. The synchronization of these systems across different locations on Earth must account for relativistic effects, especially when satellites are involved in the transfer of timing signals. Scientific research also depends heavily on an understanding of time dilation. Large-scale particle accelerators, such as the Large Hadron Collider, push particles to speeds approaching the speed of light. In these environments, time dilation is no longer a subtle effect. It becomes essential to interpreting experimental results. As particles move faster, their internal clocks, such as the processes governing their decay, slow down relative to the laboratory frame. By measuring these lifetimes and comparing them with those predicted by relativity, scientists confirm the theory's accuracy to extraordinary precision. In this way, high-energy physics is both a user and a tester of time dilation. Relativity also plays a role in astronomy. Observations from spacecraft traveling through the solar system must account for the time dilation effects of both their motion and their position in the sun's gravitational field. Signals from distant probes, such as those from the Voyager spacecraft, must be interpreted with these corrections in mind to ensure accurate tracking and navigation. When scientists time the arrival of pulses from distant pulsars, rotating neutron stars that emit regular radio bursts, they must include relativistic corrections if they want to measure positions, distances, and velocities accurately. Even in metrology, the science of measurement, time dilation is part of everyday work. Laboratories that maintain national time standards keep their atomic clocks in constant comparison with international counterparts. These comparisons require detailed corrections for the effects of both gravitational and velocity-based time dilation. A clock on a mountaintop will tick at a measurably different rate from one at sea level, and both will differ slightly from clocks in orbit. By carefully accounting for these effects, scientists can keep coordinated universal time, the global time standard, synchronized across the planet. These examples reveal a simple truth: time dilation is woven into the infrastructure of the modern world. We do not notice it because we live in a society that has quietly built Einstein's corrections into its systems. When your phone maps a route to a restaurant, it is relying on equations born from special and general relativity. When you stream a video via satellite internet, those signals are being timed and synchronized with relativistic corrections. When a spacecraft lands on Mars, its navigation is guided by systems that would fail without accounting for the bending and stretching of time. This should be a humbling realization. In Newton's day, time was thought to be uniform and absolute, a background on which the events of the universe played out. Today, our everyday technology depends on the understanding that this is not true. Time is not the same everywhere, and its variations matter. Enough to shift your navigation by kilometers, enough to confuse a global financial network, enough to alter the lifetime of a particle whirling inside a collider. If anything, the quiet presence of time dilation in technology is a reminder of how deeply the universe's subtle structure permeates our lives. We often imagine fundamental physics as something remote from daily concerns, hidden away in observatories or research laboratories. But in truth, the principles uncovered by Einstein more than a century ago operate in the background of almost everything we do. They are there when an aircraft's navigation system finds its way through the clouds, when a container ship charts a course across the Pacific, when a rescue team uses GPS to locate a missing hiker. It also reframes how we think about progress. We tend to see technology as the driver of scientific understanding, as if new machines push science forward. But here, the flow runs both ways. The abstract insights of relativity, once thought of as purely theoretical, became indispensable tools for building the interconnected world. Physics is not just the domain of distant stars and subatomic particles. It is in your pocket, guiding your steps through a city. And there is another, quieter thought. We live inside a framework where time itself is elastic, where every clock in the sky, on the ground, on a mountaintop, in a satellite, keeps its own subtly unique beat. Our technology forces these differences to align, to create the illusion of a single, shared time. But beneath that illusion, the diversity of time's flow remains, an unspoken feature of reality that even the simplest phone navigation depends on. Every time your location is updated, you are unknowingly making use of a fact about the universe that says, your time is not the same as mine, and neither of us measures the same time as a clock circling overhead. In this way, relativity lives with us constantly, whether we are aware of it or not. It is the invisible hand on the systems we trust, the quiet adjustment in the background that keeps our digital lives in step with the cosmos. And perhaps, knowing this, we can feel a little more connected to the larger universe, not as passive observers, but as active participants, moving within its warped and beautiful fabric. Chapter 6. Falling into the slowest time in the universe. In the vastness of the cosmos, most places share roughly the same rhythm of time. Whether you stand on the surface of a quiet moon, float between the stars, or orbit a familiar planet, the seconds flow in a steady, almost indistinguishable beat. The differences are there, subtle and measurable, but they do not define your everyday reality. Yet there are regions of the universe where this rhythm breaks down, where time slows to an unimaginable crawl. These are the domains of the strongest gravitational fields, the places where space itself curves so steeply that even light struggles to escape. Here, time dilation is not a small correction to a clock's tick, but a defining feature of existence. And the slowest time in the universe belongs to the neighborhood of a black hole. Black holes are the most extreme consequence of Einstein's general theory of relativity. They are regions where matter has collapsed beyond the point where it can resist its own gravity. The mass is concentrated into an infinitely dense point called a singularity, surrounded by an invisible boundary known as the event horizon. The event horizon is not a physical surface you could touch. Instead, it is the limit at which escape velocity equals the speed of light. Beyond it, no signal, no matter, no light can return. What lies inside remains forever hidden from the rest of the universe. From far away, a black hole may seem deceptively ordinary. If you orbited one at a safe distance, your experience would not be so different from orbiting any other massive object of comparable mass. But as you approach, the pull of gravity grows rapidly, and the curvature of space-time becomes more severe. And with that curvature comes an equally dramatic warping of time. To understand what happens, imagine lowering a clock toward a black hole. From your safe vantage point far away, you watch as the clock descends. As it nears the event horizon, you see its ticks grow farther and farther apart. At first, the change is small, almost imperceptible. But as the clock approaches the horizon, the effect intensifies. Each second on that falling clock seems to take longer to arrive. The light carrying the image of the clock becomes stretched, its color shifting toward the red end of the spectrum, a gravitational redshift caused by the intense warping of space-time. The closer the clock gets to the event horizon, the slower it appears to run, until in the final moments, it seems to freeze altogether. From your perspective, time for that clock has stopped. This effect is not an illusion in the sense of being a trick of the eye. It is a direct consequence of the geometry of space-time near a black hole. Your observations are entirely consistent with the mathematics of general relativity. For you, the outside observer, it will always take an infinite amount of time for the clock, or any object, to actually cross the event horizon. This is why, in a sense, the black hole's surface is never truly seen to be crossed by anything in real time. But for the clock itself, and for anything falling with it, the experience is completely different. In its own frame of reference, time flows normally. The clock ticks in steady rhythm, seconds passing just as they do on Earth. A falling astronaut would feel no sudden slowing of time as they cross the event horizon. They might notice the outside universe speeding up in a surreal way, but their own experience would be continuous. The paradox is only apparent. It is the relativity of time made visible in its most extreme form. The closer you get to the singularity, the steeper the gravitational well becomes. In this region, tidal force, the differences in gravitational pull between your head and your feet, can grow immense. For stellar mass black holes, these tidal forces would stretch and compress you violently, a process sometimes called spaghettification. For supermassive black holes, such as those at the centers of galaxies, the tidal forces near the event horizon are much weaker, and you might cross without immediate physical harm. but the slowing of time relative to the outside universe would still be extreme. If you could somehow hover just above the event horizon, supported by a hypothetical engine or tether, your clock would run incomprehensibly slower than clocks in interstellar space. A few hours for you might correspond to centuries, millennia, or more for someone far from the black hole. The outside universe would change in a blur. Stars would evolve, galaxies would drift, entire civilizations could rise and fall while you experience the passage of only a short personal time. This is not merely a thought experiment. Astronomers see evidence of gravitational time dilation in the real universe. In the accretion disks around black holes, matter spirals inward, heating up and emitting intense radiation before it crosses the event horizon. The light from this matter is redshifted by gravity, a signal that the time near the black hole is running more slowly relative to our own. In some cases, we can even use this effect to estimate the black hole's mass and spin. One of the most famous fictional depictions of this effect appeared in the film Interstellar, in a scene where astronauts land on a planet orbiting close to a supermassive black hole. Due to the intense gravity, time on the planet is slowed so much that an hour there corresponds to 7 years for the crew's colleagues waiting farther away. While the film's exact numbers are stylized for drama, the underlying physics is correct in principle. A sufficiently close orbit around a massive black hole would indeed produce such enormous time differences. The mathematics behind gravitational time dilation near a black hole is precise, but its implications are vast. For example, consider the possibility of using such an environment for one-way travel into the far future. If you could orbit just outside the event horizon for a few months of your own time and then return to a safe distance, you might find that decades, centuries, or longer had passed in the wider universe. While this is far beyond our current technology and fraught with deadly challenges, it remains a genuine prediction of relativity. The slowest clocks in the universe, then, are not in human laboratories or orbiting satellites. They are deep in gravitational wells at the very edge of black holes. And the idea that time can all but stop relative to the rest of the cosmos forces us to rethink our intuitive sense of now. There is no universal present that applies everywhere. In the shadow of a black hole, now is stretched almost beyond recognition. In this context, time dilation is not a minor detail. It is central to how black holes interact with the universe. It shapes the way they accrete matter, how they appear to observers, how they affect surrounding stars. Even the famous concept of Hawking radiation, the slow leakage of particles from black holes predicted by quantum theory, must be understood against the backdrop of the strange way time behaves at the horizon. If you stand far from any black hole, it is easy to imagine that the seconds you count are the same seconds ticking in all corners of the cosmos. But this is a comforting illusion. Out there in the deepest wells of gravity, time is crawling almost to a standstill. A photon of light climbing out of such a place stretches and fades, carrying with it a silent record of the slower pace from which it came. It is tempting to imagine what it would feel like to live in such a place, not just to visit briefly, but to experience life with the rest of the universe racing ahead. Perhaps your world would seem unchanged, while the stars in the night sky shifted from week to week, and the constellations you knew twisted into new patterns. You might watch galaxies drift perceptibly in the sky, a cosmic ballet sped up beyond anything we can see from Earth. And yet for you, the days would pass as they always have. In these extreme realms, we are reminded that time is not an absolute river flowing at the same pace everywhere. It is a local phenomenon, a rhythm that depends on where you are in the geometry of space-time. The slowest time in the universe belongs to the deepest pockets of gravity, where the curvature of space-time bends clocks almost to stillness. And in those places, the future of the universe unfolds at dizzying speed, but only for those who watch from afar. It is an extraordinary thing to realize that such regions exist, perhaps in the centers of most galaxies, quietly shaping the flow of time in their surroundings. They are not simply exotic astrophysical objects. They are reminders that the cosmos is a place where even the most basic aspects of reality, the order and pace of moments themselves, are not fixed, but molded by the invisible architecture of space-time. And perhaps in the quiet moments when we think of such places, there is a deeper reflection to be found. We tend to think of our time as the only measure of our lives, but the universe holds countless other clocks, each beating to its own gravitational rhythm. Somewhere near the edge of a black hole, a second lasts almost forever. And in that stretched-out moment, the rest of the cosmos rushes on without pause. Chapter 7. Cosmic Time Machines. Is time travel possible? The idea of traveling through time has fascinated humanity for centuries. Long before the equations of relativity, stories were told of people who awoke to find that years had passed in what felt like a single night, or who wandered into hidden realms where time flowed differently. In the modern imagination, time travel has become a staple of science fiction, a narrative device that lets us visit ancient civilizations, witness the birth of the stars, or correct mistakes from our own past. But behind the storytelling lies a genuine scientific question. Is time travel physically possible? In one sense, the answer is already yes. Every one of us is traveling through time right now, advancing into the future at a steady pace of 1 second per second. Relativity extends this by showing that the rate at which we move into the future is not fixed. We have already seen that velocity and gravity can change how fast time passes for us relative to others. This is not theoretical. It has been measured countless times in laboratories, in satellites, in high-speed particles, and in the precise signals from GPS systems. If you can move fast enough or spend time in a region of strong gravity, you can slow your own clock compared to those who remain behind. When you return, more time will have passed for them than for you. In this way, relativity allows a kind of one-way time travel into the future. We have also seen, in the context of black holes and high-speed journeys, that such effects could, in principle, be extreme. A sufficiently fast spaceship could take you on a journey lasting a few years by your clock, while centuries passed on Earth. A carefully chosen orbit near a supermassive black hole could allow you to experience hours while decades unfolded elsewhere. These are not speculative fantasies, but direct consequences of relativity. They would require enormous energy and extraordinary engineering, but the underlying physics is sound. What about travel to the past? This is where the science becomes far more uncertain. The equations of relativity do not outright forbid the idea, but they make it extremely difficult to achieve in any physically reasonable way. General relativity admits solutions to its equations in which closed time-like curves exist, paths through space-time that loop back on themselves. Following such a path, an object could, in principle, return an event in its own past. But these solutions tend to involve conditions or structures that may not exist in our universe, or that require forms of matter and energy that violate known physical laws. One such theoretical structure is the wormhole, a hypothetical tunnel connecting two distant points in spacetime. If wormholes exist and could be stabilized, they might allow rapid travel between their endpoints. In certain configurations, they could also function as time machines. If one mouth of the wormhole were moved at high speed or placed in a strong gravitational field, time would pass differently for it than for the other mouth. Upon reuniting the mouths, a traveler entering one side could emerge from the other at an earlier time. This is a straightforward application of time dilation to a hypothetical shortcut through spacetime. But wormholes come with daunting challenges. Even if they exist, keeping them open would require exotic matter with negative energy density, something not yet observed in usable quantities. Quantum field theory suggests that such negative energy can appear in small amounts for brief times, but whether it can be harnessed to stabilize a wormhole remains speculative. And even if these obstacles were overcome, questions about stability, causality, and quantum effects near the wormhole mouths remain unsolved. Another class of solutions involves rotating universes or massive rotating cylinders, such as the Gödel universe model. In these spacetimes, the geometry can permit closed time-like curves without exotic matter. But these models generally do not match the observed properties of our universe, and they often require unrealistic conditions, such as an infinitely long cylinder of extremely dense material. Even if a stable past-traveling time machine could be built in principle, physics raises further difficulties. Quantum field effects in curved spacetime suggest that attempts to create such a device might trigger enormous energy feedbacks, destroying the time machine as soon as it formed. This is sometimes called the chronology protection conjecture, proposed by Stephen Hawking, which suggests that the laws of physics may conspire to prevent time travel to the past. While this remains unproven, it aligns with the absence of evidence for visitors from the future. Philosophically, travel to the past also raises deep questions about causality, the principle that causes precede effects. If you can visit your own past, could you change it? If you prevent an event from happening, what becomes of your reason for going back? These logical puzzles, often framed as paradoxes, hint at the complexity of allowing backward time travel in a consistent universe. One way physicists sometimes sidestep these paradoxes is through the idea of self-consistency. The universe might permit past travel, but only if events unfold in ways that do not change history. In this view, any actions you take in the past were always part of history to begin with. Another resolution comes from the many worlds interpretation of quantum mechanics, in which different outcomes of events exist in separate, branching universes. In this framework, traveling to the past might place you in a different branch of history rather than altering your own. But this moves the question into the territory of quantum cosmology, where experimental evidence is scarce and theory is still evolving. It is important to note that even without past travel, relativity already makes our universe a kind of cosmic time machine. The combination of high-speed motion and strong gravity can, in principle, move you arbitrarily far into the future of others. If you wanted to see the far future of Earth without living through the intervening centuries, the laws of physics offer ways to do it, though they are far beyond our current technology. Such journeys would not change the past, but they would alter your relationship to it, severing your direct connection to the time you left behind. In a way, this future-only time travel is the safer, more consistent form. It avoids paradoxes and fits neatly within our current understanding of physics. It also connects naturally with the idea that all of us are already moving into the future at our own rates. By controlling the conditions, speed, gravity, and trajectory, we could, in theory, choose how far ahead we wish to leap. The dream of moving freely through time in either direction continues to inspire research, not because physicists expect to build a time machine next year, but because studying the limits of what is possible deepens our understanding of space-time. Investigating whether wormholes can exist, whether quantum effects enforce chronology protection, and how causality emerges from the laws of physics helps refine our theories and may even reveal new connections between gravity and quantum mechanics. And yet, beyond the mathematics and engineering challenges, there is something more elemental at work. Time travel, whether forward or backward, forces us to confront our place in the unfolding of events. If the past is fixed and the future open, what does it mean to alter one's path through time? If the universe is a block where all events coexist, is travel just another way of saying we experience different parts of it? These questions touch the boundary between physics and philosophy, where the language of equations meets the language of meaning. Ultimately, whether or not we ever build a literal time machine, relativity has already shown us that time is not the uniform backdrop we once imagined. It bends, stretches, and curves with the geometry of the universe, allowing travelers to experience it differently. In this sense, the universe itself is our time machine, one we are riding every moment of our lives. Perhaps this is the quiet truth hidden behind the grander fantasies of science fiction. We are all time travelers already, each on a unique trajectory shaped by our motion, our gravity, and our choices. Some paths run almost parallel, keeping us close to those we know. Others diverge sharply, carrying us far from the rhythms of others' lives. And somewhere out there, among the stars and black holes, the slowest and fastest clocks in the cosmos are keeping their own silent time, marking out the infinite variety of journeys through the ever-changing landscape of space-time. Chapter 8. The Universe's Many Clocks. If you could stand outside the universe and listen to it as if it were a great cosmic machine, you might expect to hear a single steady tick, a universal heartbeat shared by all matter and all events. But the deeper we look into the nature of time, the more we see that such a rhythm does not exist. Instead, the universe is filled with countless clocks, each ticking at its own pace, each marking the passage of time along its own unique path through space-time. There is no master clock that keeps them all in step, no central metronome that sets the tempo for existence. The rhythm of time is local, personal, and deeply dependent on where you are and how you move. In physics, a clock can be almost anything that measures change in a predictable way. It could be the oscillation of atoms in an atomic clock, the swing of a pendulum, the vibration of a crystal, the rotation of a pulsar, or even the decay of a radioactive isotope. Each of these is a physical process that can be counted, and from that count, we can infer the passage of time. In a Newtonian world, all such clocks could be synchronized perfectly, provided they were built well enough and compared often enough. In our actual universe, as described by relativity, such perfect agreement is impossible. Relativity teaches us that the rate at which a clock ticks depends on its path through space-time, its world line. A clock deep in a gravitational well will tick more slowly than one far from any massive object. A clock moving at high speed relative to another will also tick more slowly from the other's perspective. These effects are not illusions or malfunctions. They are consequences of the geometry of spacetime itself, and because every object in the universe follows its own path through that geometry, every clock has its own story. Consider the clocks on Earth alone. A clock at sea level is deeper in Earth's gravitational field than one on a mountain peak, and so, according to general relativity, it ticks more slowly. The difference is tiny but measurable with modern instruments. If you placed an atomic clock at the top of a tall skyscraper and another identical clock in the basement and let them run for a year, the clock upstairs would end up slightly ahead. The difference would be on the order of billionths of a second, negligible for human experience but vital for precise physics. Now widen your view to include the entire planet. The Earth is rotating, so points near the equator move faster than points near the poles. From the perspective of special relativity, this motion causes an additional time dilation. Combining the gravitational and rotational effects, we find that no two clocks on Earth tick exactly the same, unless they are in the same place and moving in the same way. Coordinated universal time, the standard we use to keep civil time, is maintained by averaging the readings of hundreds of atomic clocks around the world, with careful corrections for these relativistic effects. The differences become more dramatic beyond Earth. A clock on the Moon, in weaker gravity and moving at a different speed around the Sun, would drift relative to one on Earth. A clock on Mars would follow yet another tempo, shaped by Mars's mass, radius, and orbital motion. In interplanetary navigation, these differences must be calculated and compensated for, or spacecraft tracking would quickly lose accuracy. In deep space, the variety grows richer still. A pulsar, a rapidly rotating neutron star, is a kind of natural clock, its beams sweeping past our telescopes with astonishing regularity. The timing of these pulses can be measured to millionths of a second, but even they are subject to relativistic influences. A pulsar in a binary system orbiting another massive star will have its ticking rhythm altered by the gravitational field of its companion. As it moves toward us and away from us in its orbit, the special relativistic Doppler effect further changes the apparent timing of its pulses. By studying these variations, astronomers can not only confirm the predictions of relativity, but also weigh the stars, map their orbits, and test theories of gravity. Even the Sun itself is a clock of sorts. The fusion reactions in its core proceed at a steady rate, setting the pace for the light and heat that reach Earth. But the Sun's own clock is affected by its position in the Milky Way's gravitational field, by its motion through the galaxy, and by the immense gravitational pull of the galaxy's mass. From the standpoint of relativity, the Sun's clock is no more universal than any other. If we turn our attention to the galaxy as a whole, we find that stars in different regions live in different temporal environments. Near the galactic center, the gravitational field is stronger, and time runs slightly more slowly relative to the galaxy's outskirts. A star orbiting close to a supermassive black hole experiences a different pace of time than one drifting in the thin halo far above the galactic plane. The differences are small on a human scale, but significant over cosmic ages. All of these variations are bound by one rule. Each clock is correct in its own frame of reference. There is no sense in which one is truly ahead or behind, in any absolute way. If two observers meet and compare clocks after following different paths through spacetime, their readings may differ, but both are right. The disagreement is not a matter of error. It is a matter of geometry. This multiplicity of times can be disorienting because it runs against our everyday intuition. We are used to the idea that events happen at the same time in different places. Relativity tells us that simultaneity is relative, that two events judged simultaneous in one frame may occur at different times in another. This is not just a philosophical twist, but a measurable reality, confirmed in experiments and required for technologies like GPS to function. If we imagine the universe as a vast web of world lines, the paths of all particles and objects through space-time, then each point along each line carries its own local time. These times are linked by the structure of space-time, but they are not synchronized by any overarching clock. Instead, they form a patchwork, a mosaic of rhythms, each as real as the next. We can think of this mosaic as a kind of cosmic music. Each clock is an instrument playing its own part, shaped by its environment and motion. Some tick slowly in deep gravitational wells, others more quickly in the openness of intergalactic space. From a distance, their tempos might seem to blend into a background hum, but up close, each has its own distinct beat. There is beauty in this diversity, a reminder that the universe's unity is not the sameness of a rigid grid, but the harmony of many variations. On a practical level, the recognition of many clocks is essential for modern science. In space exploration, in astronomy, and fundamental physics, accurate timekeeping requires careful accounting of relativistic effects. Ignoring them would mean losing precision, misunderstanding signals, and misinterpreting data. But beyond its utility, the concept reshapes our philosophical picture of time itself. Time is not a single universal stream. It is a network of local flows, connected yet distinct, shaped by the curvature and motion of the cosmos. And there is an existential dimension to this realization. We live our lives inside one tiny thread of the cosmic tapestry, measuring time with the clocks of our world and imagining that all others match ours. But in truth, every star, every planet, every particle moves to its own time. The universe is not a chorus of identical voices, but a symphony of endless variations. Somewhere, far away, a clock may be ticking slower or faster than ours, but both are equally part of the universe's story. And as we go about our days, unaware of the infinite diversity of time's flow, we are still part of that grand, intricate rhythm, one beat among countless others in the vast and beautiful score of space-time. Chapter 9. Does time itself flow, or do we just experience it that way? For most of us, the flow of time feels as real as the ground beneath our feet. We sense the moments sliding past, one after another, carrying us from the cradle to the present and on toward whatever lies ahead. Our entire mental life is embedded in this sense of passage, a constant forward movement from past to future. And yet, when we look at the world through the lens of modern physics, this familiar intuition becomes less certain. Does time truly flow in the way we imagine, or is that flow a feature of our perception rather than of the universe itself? In everyday life, we take time to be directional. We remember the past, but not the future. We can act now in ways that influence what will happen, but we cannot act to change what has already occurred. This asymmetry is woven into our language, our thinking, and our sense of causality. Physics, however, paints a more ambiguous picture. The fundamental equations that govern the motion of particles, whether in classical mechanics, relativity, or quantum theory, are almost entirely time-symmetric. That is, they work equally well whether time runs forward or backward. If you were shown a film of two billiard balls colliding and had no other information, you could run it forward or backward and the laws of physics would be satisfied in either case. At the most fundamental level, Nature's rules do not appear to distinguish between past and future. Where, then, does our sense of time's arrow come from? One answer lies in the concept of entropy, a measure of disorder or the number of possible microscopic configurations of a system. The second law of thermodynamics tells us that, in an isolated system, entropy tends to increase over time. A neatly stacked pile of papers can fall into disarray, but the reverse will not happen spontaneously. Eggs break, but do not unbreak. This increase of entropy defines a preferred direction for processes, from lower entropy to higher entropy. This is often called the thermodynamic arrow of time, and it is the closest thing we have to a physical explanation for why time seems to move in one direction. But even this explanation comes with subtleties. The laws that govern individual particles do not force entropy to increase. It is the statistical behavior of large numbers of particles that makes it overwhelmingly likely. The thermodynamic arrow is therefore not a fundamental law in the same sense as relativity's equations. It is an emergent property arising from the overwhelmingly probable behavior of complex systems given their initial conditions. If the universe had begun in a high-entropy state, there would be no thermodynamic arrow at all, and time's direction might be imperceptible. Relativity complicates the picture even further. In Einstein's view, space and time form a four-dimensional continuum called spacetime. Every event, every location in space at a particular moment can be represented as a point in this continuum. Once an event has happened, it is fixed in space-time, just as a mountain peak is fixed in a landscape. From this perspective, all moments, past, present, and future, exist equally as parts of the structure of space-time. This is sometimes called the block universe or eternalism. In such a view, the passage of time is not a property of the external world, but a feature of our consciousness moving along our own world line. If the block universe is correct, then now is not a universal feature of reality. It is a local concept, tied to each observer's position in space-time. Relativity already tells us that simultaneity is relative. Two events that appear simultaneous to one observer may occur at different times for another. This means there is no single slice of space-time that can be called the present for all observers. The present moment is not an objective cosmic fact. It is a subjective experience emerging from your perspective. This view can be unsettling because it undermines our most immediate experience of time. In daily life, we imagine that the present is constantly advancing, that the future is coming toward us, and that the past is slipping away. But if all events exist equally in space-time, then the passage of time is not an external phenomenon, but an internal one, a product of the way our brains process sequences of events. In this sense, our minds may be projecting a sense of motion onto a timeless landscape. Some physicists and philosophers, however, resist the block universe interpretation. They argue for a growing block model in which the past and present exist, but the future does not yet. In this view, the universe is genuinely evolving, and new moments are being created as time advances. Others support presentism, the idea that only the present is real and that both past and future are abstractions. These perspectives preserve a sense of becoming and change as fundamental aspects of reality, rather than illusions of perception. Experimental physics has yet to provide a definitive answer to which of these models is correct. Relativity itself is consistent with the block universe, but it does not strictly demand it. Quantum mechanics adds further layers of complexity. In standard interpretations, quantum events are described by probabilities that collapse into definite outcomes when measured. This apparent collapse seems to introduce a moment of change, a point at which the future becomes the present. Some interpretations, like the many worlds view, avoid collapse entirely by positing that all possible outcomes occur in parallel branches of the universe. In such interpretations, the sense of time flowing into a single determined future may again be just a feature of our limited perception. What is clear is that the flow of time is deeply tied to the way we, as conscious beings, experience the world. Our brains integrate sensory inputs over short intervals, binding them into a continuous narrative. This process creates a sense of motion from one moment to the next. It also aligns with our ability to remember the past, but not the future, reinforcing the asymmetry of time in our lived experience. But just because we experience time this way does not mean the universe itself shares that experience. Relativity forces us to separate the psychological arrow of time from the physical description of spacetime. In the equations, time is simply another coordinate, much like the 3 coordinates of space. You can move along your world line in time just as you move through space. But there is nothing in the mathematics that insists on a universal flow. The perception of flow may emerge from the interaction between our physical world and our cognitive architecture. This distinction between time as experienced and time as described is not merely philosophical, it has practical implications in physics. In cosmology, for instance, the question of whether time began at the Big Bang or whether it extends infinitely into the past depends on how we define time in the first place. In quantum gravity research, where physicists attempt to merge general relativity with quantum mechanics, the very concept of time may need to be reformulated. In some approaches, time is not a fundamental variable at all, but an emergent property of more basic, timeless laws. It is possible that our difficulty in reconciling relativity, quantum mechanics, and the arrow of time stems from treating time as a single, unified concept, when it may in fact be layered, part geometry, part thermodynamics, part perception. The flow we feel may belong entirely to the perceptual layer, with no direct analog in the underlying geometry of the universe. This idea challenges the way we think about existence itself. If all moments are equally real, then in some deep sense, nothing is ever truly lost. The past is still there, in its own region of space-time. The future already exists in some form, waiting for us to encounter it along our world line. From this vantage, our lives are not lines drawn across a blank page, but intricate patterns woven into a vast and timeless tapestry. And yet, in the midst of this grand structure, we experience life as a fleeting present. We remember, anticipate, hope, and regret. We measure our days not in the static geometry of space-time, but in the unfolding of moments. Whether or not time truly flows in the external world, it flows for us, and in that flow lies the human story. Perhaps this is the paradox we must live with. Physics tells us that time may be static, a dimension laid out in full. Our minds tell us it is a river carrying us forward. Both may be true, each in its own domain. And as we move through our days, we are both inhabitants of a timeless universe and travelers on a one-way journey, measuring the distance between birth and death in the only way we know, moment by passing moment. Chapter 10. You are a traveler through time. You may never have set foot on a spaceship. You may never have hovered near a black hole or raced close to the speed of light. And yet, you are traveling through time right now, in this very moment. You have been on this journey since the instant you were born, and you will remain on it for as long as you exist. This is not a metaphor. It is a physical fact. Every living being, every inanimate object, every particle in the universe is on a path through space-time, moving from one moment to the next. In the framework of relativity, time is not an external backdrop that flows past us while we stand still. We ourselves are in motion, not just through space, but through time. Even sitting perfectly still in a chair, you are moving forward in the time dimension at a measurable rate. In a simplified sense, if you are at rest in space, nearly all of your motion through space-time is in the time direction. This steady progression is why you can't stop aging, why clocks tick, and why events line up in a sequence you can recall. The idea that we are all travelers through time can be seen most clearly in the concept of a world line, the path an object traces through the four-dimensional continuum of space-time. Your world line begins at your birth and extends into your future, marking every event, every location, every second you occupy. It is unique to you, shaped by your specific movements through space and your experiences of gravity. No two world lines are identical, even for people who seem to share the same life circumstances. Relativity tells us that these world lines are not all traveled at the same rate. Your personal clock, the measure of how much time you experience along your journey, is called your proper time. If you move faster through space, you move more slowly through your own proper time relative to those at rest. If you spend time in a stronger gravitational field, your proper time also slows compared to those in weaker gravity. This is the essence of time dilation, the realization that different travelers can experience different amounts of time between the same two events. In everyday life, these differences are imperceptible. Walking across a room or driving to work will not produce a measurable difference in your proper time compared to someone staying home. The effect is there, but it is far too small to notice without the most sensitive instruments. Still, the fact remains, your journey through time is unique. The second you are living right now is not ticking at exactly the same rate as the second experienced by someone standing on a mountain, flying in an airplane, or orbiting Earth. On Earth, we rarely notice these variations because they are so small. But nature provides us with more dramatic examples. Astronauts aboard the International Space Station orbit at about 7.7 kilometers per second. They experience a tiny amount of velocity-based time dilation, which slows their clocks relative to people on the ground. At the same time, they are farther from Earth's center and feel weaker gravity, which speeds their clocks up relative to the surface. The combination of these two effects results in a net difference of milliseconds over the course of months. Small, but measurable. When astronauts return to Earth, they have aged ever so slightly less than their colleagues who remained here. They have literally taken a different route through time. The differences grow more dramatic at higher speeds and in stronger gravitational fields. If you could travel near the speed of light for a few years of your own proper time, centuries might pass for those you left behind. If you could linger near the event horizon of a supermassive black hole and then return, you would find that the rest of the universe had leapt far ahead of you. These are extreme scenarios, but they are not impossible in principle. They are built into the way space-time works. What's striking is that you don't need to think of these situations as special cases of time travel. They are just different ways of tracing a path through space-time. Whether your world line is almost vertical, as it is when you are at rest relative to Earth, or tilted at a steep angle because you are moving rapidly through space, you are still moving forward through time. The difference is in how much proper time elapses for you compared to others. This perspective reframes the idea of time travel. You do not need a machine to begin the journey. You are already on it. The question is not whether you are moving through time, but how you are moving through time and how your path compares to the paths of others. Even without exotic technology, every one of us is on a slightly different schedule. Two people standing side by side are not perfectly synchronized in the deepest physical sense, because they have taken different routes to arrive at this shared moment. Once you see time this way, the familiar concepts of now and later take on new meaning. Now is simply where you are on your world line, and later is further along it. Other people have their own nows, which may not perfectly align with yours. The relativity of simultaneity means that your present is not necessarily someone else's present if they are far away and moving differently. This doesn't change our day-to-day experience. We still make plans, meet at agreed-upon times, and share events, but it tells us that beneath the surface, the structure of time is far richer than it appears. In a sense, our entire understanding of life is bound up in the fact that time moves forward for us. We remember the past because our brains store information about previous events, building a chain of cause and effect. We do not remember the future because we have not yet traveled that part of our world line. This forward-moving experience is what allows us to speak meaningfully about change, growth, and history. Without it, the concept of being a traveler through time would be meaningless because there would be no difference between where you are now and where you will be. Physics leaves open the possibility that the universe as a whole does not experience time's passage in the way we do. The block universe interpretation, which we explored earlier, treats your world line as already existing in its entirety, from birth to death. Your motion through time is then a motion of awareness, not of the universe itself. Whether or not this interpretation is correct, it does not change the fact that your experience of moving along your world line is real to you. The physics gives you the map. Your mind provides the journey. The beauty of this picture is that it places you directly inside the grand architecture of space-time. You are not an observer looking in from the outside. You are a part of the structure, a curve in the fabric, shaped by your motion, your environment, and the gravitational landscape you inhabit. The same laws that govern the orbit of a planet or the fall of a star govern your own progress through time. Every second that passes for you is a manifestation of the geometry of the universe itself. This makes the simple fact of being alive even more extraordinary. From the moment you were born, you have been moving forward in a one-way journey, and every other person, every object, every photon of light has been moving forward along their own. Sometimes your paths run nearly parallel, and you share events closely. Sometimes they diverge, and the same stretch of external time feels different for each traveler. But in every case, you are part of the great procession of all things through the temporal dimension. The relativity of time ensures that there will never be perfect synchrony among all travelers. The universe does not keep a single beat. It is a symphony of many tempos, and you are one of the instruments in that symphony, playing your part according to the conditions of your journey. Whether your seconds are running fast or slow relative to someone else's, they are uniquely yours. They mark your own path from the beginning of your story to wherever it will lead. And this is perhaps the most human way to understand relativity. It tells us that while we are all bound by the same physical laws, we each have our own personal time, our own unfolding of moments. In a purely scientific sense, you are moving through space-time at the speed of light in some combination of space and time. In a personal sense, you are moving through the story of your life, step by step, heartbeat by heartbeat. Physics can measure the differences between your clock and another's to unimaginable precision, but it cannot measure the value of your journey. That part is yours alone. Somewhere in the vast web of space-time, your world line threads its way forward, carrying with it everything you have been, everything you are, and everything you will be. And that, whether you travel far or stay close to home, makes you a traveler through time in the truest possible sense. Section 5. Stephen Hawking's Key Ideas, Singularities, Black Hole Thermodynamics, and Information. Chapter 1. The Young Rebel, From General Relativity to Black Holes. When we speak about Stephen Hawking, it is tempting to begin with the myth, the brilliant young man struck by illness, who nevertheless rose to become one of the most celebrated scientists of the 20th century. But if we want to understand the roots of his greatest theories, we have to start with the intellectual landscape into which he entered, and the way he used general relativity, a theory that was already half a century old when he began his work, as the foundation for his radical insights about the universe and black holes. Einstein's General Relativity, published in 1915, describes gravity not as a force but as the curvature of spacetime. Mass and energy tell spacetime how to curve, and spacetime tells mass how to move. This framework explained the orbit of Mercury, predicted the bending of light by the sun, and laid the foundations for modern cosmology. But by the time Hawking was born in 1942, relativity had both triumphs and limitations. On one hand, it had predicted phenomena like gravitational redshift and was being used to model expanding universes. On the other hand, its equations were notoriously difficult to solve, and many physicists preferred the quantum field theories that were flourishing in mid-century particle physics. Relativity seemed remote, abstract, and mathematically forbidding, and cosmology was not considered a fashionable field of research. Hawking entered Cambridge in the early 1960s, already showing signs of the motor neuron disease that would later confine him to a wheelchair. Despite his illness, he carried a rebellious spirit into his studies. He was impatient with conventional thinking and sought to use general relativity in ways that others had overlooked. His PhD supervisor was Dennis Sciama, a leading figure who encouraged his students to tackle fundamental questions in cosmology rather than narrow technical problems. Under Sciama's guidance, Hawking gravitated toward the study of singularities and the ultimate fate of collapsing stars. At that time, the understanding of black holes was incomplete. Karl Schwarzschild had found an exact solution to Einstein's equations in 1916, describing a spherically symmetric mass. Yet for decades, this solution was regarded as a mathematical curiosity rather than a physical object. It seemed absurd that real stars could collapse into an infinitely dense point. Only in the 1960s did the work of John Wheeler and others begin to establish black holes as plausible astrophysical entities. Wheeler coined the term black hole in 1967, and the field began to grow rapidly. Hawking was entering this area just as it transformed from fringe speculation into a serious branch of physics. His early work focused on applying general relativity to questions of cosmic origin. The prevailing cosmological model was the Big Bang, but some alternatives, such as the steady-state theory, still had defenders. The central issue was whether singularities, points where density and curvature become infinite, were unavoidable consequences of Einstein's equations or merely artifacts of idealized assumptions. Roger Penrose, a mathematician at Oxford, had recently proved that singularities were inevitable in the collapse of massive stars, provided certain reasonable conditions held. This was a breakthrough because it suggested that singularities were not mathematical accidents, but physical predictions of general relativity. Hawking was inspired by Penrose's methods, which used global techniques in differential geometry rather than local coordinate systems. These techniques allowed physicists to make general statements about spacetime without solving the equations in detail. Hawking realized he could extend Penrose's approach to the entire universe. If singularities are unavoidable inside black holes, might they also be unavoidable in the past history of the universe? Working through the mathematics, Hawking demonstrated that under very general conditions, an expanding universe must have originated in a singularity. In other words, the Big Bang was not just a speculative story, but a rigorous implication of Einstein's equations. This was a daring conclusion, especially for a young researcher. At the time, many physicists preferred to imagine that the Big Bang could be smoothed out by some mechanism that avoided infinite density. Hawking, however, embraced the singularity as a clue that general relativity was pointing beyond itself. Singularities marked the limits of the classical theory, where quantum effects must take over. He had already set the tone for his career, pushing general relativity as far as it could go, showing its surprising consequences, and then using those consequences to highlight the need for new physics. Hawking's rebellious streak was not only intellectual, but also personal. Despite his diagnosis of amyotrophic lateral sclerosis, doctors initially gave him only a few years to live. Rather than discouraging him, this prognosis seemed to focus his energy. He married Jane Wilde in 1965, just as his health was deteriorating, and threw himself into his research with extraordinary intensity. Friends and colleagues remember his mischievous humor, his refusal to dwell on limitations, and his competitiveness. He wanted to challenge the giants of physics, not revere them. General relativity provided the perfect arena for such challenges. While quantum theory was crowded with Nobel-level researchers, relativity and cosmology were fields where a bold young thinker could make a mark. By the late 1960s, Hawking had already become a central figure, collaborating with Penrose and others, and driving forward the understanding of spacetime singularities. His work helped establish that black holes were not just mathematical constructs, but unavoidable features of gravitational collapse, and that the universe itself had sprung from a singular state. The path from general relativity to black holes was therefore both scientific and personal for Hawking. He took a theory created by Einstein, extended by Penrose, and pushed it further, showing that the cosmos itself carried the imprint of these ideas. In doing so, he helped transform black holes from exotic possibilities into central players in astrophysics. Later, he would go further, showing that black holes emit radiation, evaporate, and raise paradoxes about information. But even in his earliest work, we see the outlines of his style: clarity about the rules of general relativity, courage to follow them to extreme conclusions, and a willingness to embrace paradox rather than avoid it. Scientifically, this first phase of Hawking's career illustrates how a single theory, general relativity, can yield profound consequences when interpreted creatively. Relativity is deterministic, but its solutions can lead to breakdowns where predictability fails, such as singularities. Hawking recognized that these breakdowns are not failures of mathematics but signals of deeper layers of physics. His insistence on taking singularities seriously laid the groundwork for later explorations of quantum gravity. The implications extend far beyond technical results. If singularities are inevitable, then our universe had an origin in which the known laws of physics ceased to apply. This forces us to ask whether the universe had a cause, whether time itself began, and whether physical explanation can ever be complete. Hawking was not the first to ponder such questions, but his mathematical proofs gave them a new authority. He showed that the mysteries of origin are not philosophical ornaments but scientific necessities. Looking back, it is striking how the trajectory of Hawking's own life echoed the themes of his science. His body was collapsing, but his mind pursued the structure of collapsing stars. He was given a finite prognosis, but his work dealt with the finitude of time itself. He took a theory developed by Einstein half a century earlier and showed that it still contained secrets, much as his own life, though constrained by illness, contained an astonishing productivity. And so Hawking began his career as the young rebel of cosmology, turning general relativity from a beautiful theory into a tool for unveiling the darkest and most mysterious aspects of the universe. His early work set the stage for everything that followed: the radiation, the paradoxes, the no-boundary proposal. It showed that physics was not done with the great questions, that even in a world of particle colliders and quantum electrodynamics, there was still room to ask about beginnings and infinities. Perhaps this is why Hawking's work resonates so widely. It reminds us that the universe is not tidy, that the very equations we use to describe it can point us to their own limits, and that those limits are where discovery begins. In confronting singularities, Hawking did not shy away from the abyss but leaned into it, insisting that science must grapple with the deepest unknowns. At the existential level, there is something both humbling and inspiring in this story. If the universe began in a singularity, then everything we are, our stars, our planets, our lives, emerged from a point where the laws of physics themselves falter. Out of that opacity came the clarity of existence. Hawking's own life mirrored this lesson. Out of physical limits came intellectual expansion. Out of struggle came insight. It suggests that even when the structures around us collapse, new possibilities can emerge. As you let these thoughts settle, imagine the calm persistence of the cosmos itself. The stars wheel slowly in their courses, black holes bend light silently in the dark, and space-time continues its patient unfolding. Hawking's theories invite us to marvel, but also to rest, knowing that we are part of a universe whose mysteries stretch far beyond the concerns of a single day. Whatever challenges have filled your hours, you can let them fade now, as the quiet immensity of the universe surrounds you. Let the questions linger in the background, but allow your mind to drift, calm and unburdened, into rest. Chapter 2. The Hawking-Penrose Singularity Theorems. The early years of modern cosmology were filled with speculation, competing models, and vigorous debate. In the decades after Einstein formulated general relativity, solutions to his equations suggested strange possibilities: universes that expand or contract, stars that collapse beyond recognition, and regions where the known laws of physics break down. Yet for much of the mid-20th century, many physicists believed that these extreme consequences were artifacts of idealized assumptions rather than robust predictions. Surely nature would find a way to avoid infinities. It was in this intellectual climate that Roger Penrose and Stephen Hawking made their mark. proving with mathematical precision that singularities are not optional quirks, but unavoidable features of spacetime under quite general conditions. Their singularity theorems changed the way physicists thought about the universe's origin, the interior of black holes, and the ultimate reach of Einstein's theory. A singularity in the context of general relativity is a place where curvature becomes infinite, and where geodesics, the natural paths through spacetime, come to an end. To speak more plainly, it is where the framework of relativity itself ceases to provide predictions. This is not merely a point of high density or pressure. It is a breakdown of the theory's descriptive power. For decades, physicists hoped these singularities were only consequences of assuming perfect symmetry, like a star collapsing in a perfectly spherical manner. Real matter distributions are messy and uneven, so perhaps nature would smooth over the infinities. The Hawking-Penrose theorems demonstrated that this hope was misplaced. Penrose struck the first blow in 1965, when he published a paper showing that under very reasonable conditions, the gravitational collapse of a sufficiently massive star would inevitably lead to a singularity. He introduced the concept of trapped surfaces, regions where light rays are forced to converge. Once such a surface forms, general relativity dictates that the collapse cannot be halted. Penrose's proof did not rely on symmetry or on special properties of matter. It showed that collapse to a singularity is the generic outcome of Einstein's equations. This work earned Penrose wide recognition and set the stage for Hawking's entry into the field. Hawking, then a young researcher, saw that Penrose's methods could be extended beyond stellar collapse to the entire cosmos. If general relativity was taken seriously, then the same mathematics that proved singularities inside black holes could also prove a singularity at the origin of the universe. Working through the details, Hawking showed that under the assumption of general relativity and the presence of matter satisfying certain energy conditions, an expanding universe must have begun in a singularity. This was a striking result. It meant that the Big Bang was not just a convenient story, but a necessary consequence of the theory. Together, Hawking and Penrose developed the singularity theorems that now bear their names. These theorems use techniques of global differential geometry to make statements about entire spacetimes rather than local patches. Instead of solving Einstein's equations for particular cases, they considered the causal structure of spacetime and the behavior of light cones. By analyzing how geodesics can or cannot be extended, they proved that under quite broad assumptions, spacetimes with trapped surfaces or persistent expansion inevitably contain incomplete geodesics, signatures of singularities. One of the striking aspects of these theorems is their generality. They do not require exact symmetry, nor do they demand exotic matter. They work under conditions that are entirely reasonable by the standards of classical physics. This generality forced physicists to confront singularities as genuine predictions rather than as artifacts of oversimplified models. The universe we inhabit and the stars within it are messy and dynamic, yet the theorems show that singularities still arise. The implications were profound. In cosmology, the singularity theorems supported the Big Bang model by showing that any universe undergoing expansion, given the energy conditions, must have originated from a singular state. This was a powerful blow to the steady-state model, which posited an eternal universe with continuous creation of matter. Observational evidence, such as the discovery of the cosmic microwave background, had already tilted the balance toward the Big Bang, but Hawking's mathematical result gave it theoretical inevitability. In astrophysics, The theorems reinforced the reality of black holes. If massive stars collapse beyond a certain point, they must end in singularities. The question was no longer whether black holes existed, but how they behaved, how they interacted with their surroundings, and what role they played in galactic evolution. The singularity theorems thus turned black holes from speculative curiosities into central actors in the cosmic story. Equally important was the philosophical consequence. Singularities mark boundaries where classical general relativity ceases to function. They are not merely locations of high density, they are regions where predictability fails. If spacetime has an edge, then physical law cannot be extended beyond it. For the universe as a whole, this means that the Big Bang singularity is a point where the known laws cannot say what, if anything, preceded it. For black holes, it means that inside the event horizon, physics cannot describe the final state of collapse. In both cases, the theorems force us to acknowledge the limitations of our theories and the need for a deeper framework, most likely a theory of quantum gravity. The collaboration between Hawking and Penrose also illustrates the power of combining different perspectives. Penrose approached the problem with the tools of mathematics, bringing rigor and new techniques from geometry. Hawking, trained as a physicist, brought physical intuition and cosmological ambition. Together, they produced results that were both mathematically elegant and physically consequential. This partnership cemented Hawking's reputation as a bold thinker willing to confront the most fundamental questions. One of the subtler points of the theorems is their reliance on certain energy conditions, assumptions about the nature of matter and energy. For example, the so-called strong energy condition asserts that gravity is always attractive in classical contexts. These conditions are reasonable for normal matter, but quantum field theory has shown that they can be violated in exotic circumstances, such as with negative energy densities. This does not invalidate the theorems, but it points to the edge where quantum effects may alter the conclusions. Hawking himself later explored how quantum mechanics could modify the fate of black holes, leading to his discovery of Hawking radiation. It is worth noting that the singularity theorems do not describe what happens at a singularity. They only prove that geodesics cannot be extended, that the structure of spacetime is incomplete. They tell us that there is a boundary to classical physics, but not what lies beyond it. This is why singularities are often described as signs that our theories are incomplete. They are less predictions about specific physical states than they are indicators of where our current framework breaks down. In retrospect, the impact of the Hawking-Penrose theorems can hardly be overstated. They reshaped cosmology by giving the Big Bang theoretical necessity. They reshaped astrophysics by demonstrating the inevitability of singularities and gravitational collapse. They reshaped the philosophy of physics by confronting scientists with the limits of prediction. And they reshaped Hawking's own career, setting him on a path that would lead to his most famous discoveries. For Hawking, the theorems were more than a technical triumph. They were a statement of method, push existing theories to their logical limits, no matter how uncomfortable the results. Where others might have sought to avoid infinities, Hawking embraced them as clues. This willingness to follow equations into the unknown became his hallmark. Whether studying black holes, radiation, or the structure of the cosmos, he was always guided by the conviction that the mathematics, taken seriously, would point to new truths. At the existential level, the singularity theorems remind us that the universe has edges of knowability. There are boundaries beyond which our concepts fail, places where the familiar language of space and time ceases to apply. For some, this is unsettling. For others, it is a source of wonder, a reminder that reality is not exhausted by our theories. Hawking and Penrose showed us that mystery is not a failure of science, but a necessary part of its advance. And as you reflect on these ideas, you can also let them bring you a measure of calm. The cosmos has been unfolding for billions of years, governed by laws that reach to the very edge of comprehension. Singularities remind us that we are part of something vast, intricate, and still unfinished in our understanding. As the day winds down, let your own thoughts settle like dust in the great silence of space. The questions remain, but for now, you can rest in the knowledge that wonder itself is part of the human inheritance, and tomorrow will bring new light to explore it. Chapter 3. Black Hole Thermodynamics, When Gravity Meets Entropy. The singularity theorems establish that black holes in the Big Bang were not avoidable oddities, but necessary outcomes of general relativity. Yet those theorems raised as many questions as they answered. If black holes are real, and if they contain singularities where the known laws break down, how do we describe them as physical objects? What rules govern their behavior? In the early 1970s, Stephen Hawking and his contemporaries began to realize that black holes could be understood not only as gravitational phenomena, but also as thermodynamic systems. Out of this realization was born the field of black hole thermodynamics, an unexpected union between Einstein's theory of gravity and the laws of heat and entropy. To appreciate the depth of this achievement, we need to recall what thermodynamics represents in physics. The 19th century science of heat and work, developed by figures like Carnot, Clausius, and Kelvin, gave us the concept of entropy, a measure of disorder or of the number of microscopic configurations consistent with a macroscopic state. Entropy always tends to increase in an isolated system, a principle known as the second law of thermodynamics. This law underpins our understanding of irreversibility, the arrow of time, and the tendency of energy to spread out. It is one of the most universal statements in all of science. On the other hand, general relativity seems far removed from these concerns. It describes the smooth geometry of spacetime and the motion of matter under gravity. A black hole, in its simplest form, is a region where gravity is so intense that nothing, not even light, can escape. From the outside, it appears perfectly featureless. According to the no-hair theorems developed in the 1960s, a black hole is completely characterized by only three parameters: its mass, its electric charge, and its angular momentum. All other information about the matter that collapsed to form it is hidden behind the event horizon. A black hole seems to erase details and reduce complexity. It was precisely this simplicity that led physicists to wonder if black holes might obey thermodynamic laws. In 1972, Jacob Bekenstein, then a graduate student, argued that black holes must have entropy. His reasoning was straightforward but profound. Imagine throwing a cup of hot tea full of entropy into a black hole. From the outside, the entropy seems to vanish because the black hole absorbs the matter and gives back no details. If this were truly the case, the second law of thermodynamics would be violated. To preserve the universality of the second law, Bekenstein proposed that black holes themselves must carry entropy proportional to the area of their event horizons. The more mass or energy they absorb, the larger their surface area becomes and the greater their entropy. At first, Hawking was skeptical. The idea of attributing entropy to an object that appeared to be perfectly featureless seemed strange, even wrong. but his own calculations soon led him to a startling realization. In collaboration with Bardeen and Carter, Hawking helped formulate the 4 laws of black hole mechanics, analogues of the 4 laws of thermodynamics. The surface gravity of a black hole, for instance, behaved like temperature. The area of the event horizon behaved like entropy. These were suggestive parallels, but Hawking still doubted that black holes could truly radiate or have temperature in a physical sense. They seemed too perfect, too absolute. The breakthrough came when Hawking considered the interaction between quantum fields and curved spacetime. In 1974, he discovered that black holes are not entirely black, but emit radiation due to quantum effects near the horizon. Virtual particle pairs, normally confined to fleeting existence, can be separated by the horizon, with one particle escaping while the other falls in. To an external observer, the black hole appears to radiate. This phenomenon, now known as Hawking radiation, implied that black holes have a real temperature and a real entropy. What Bekenstein had proposed as a necessity became a concrete prediction. Black hole thermodynamics therefore revealed a deep and unexpected unity between 3 great pillars of physics: general relativity, quantum theory, and thermodynamics. The entropy of a black hole is proportional not to its volume, but to the area of its event horizon. This was an astonishing result because it suggested that information about the contents of a region of space is encoded on its boundary, a hint of the holographic principle that would later emerge in string theory. The proportionality constant is enormous. The entropy of a stellar mass black hole dwarfs the entropy of any ordinary object. In effect, black holes are the most entropic entities in the universe. The thermodynamic picture of black holes also changed the way physicists thought about the arrow of time. The area theorem, proved by Hawking before his radiation discovery, showed that the area of a black hole's event horizon never decreases in classical general relativity. This mirrored the second law of thermodynamics, in which entropy never decreases in an isolated system. Once quantum effects were included, black holes could shrink as they radiated, but their entropy remained consistent with the generalized second law, which combines ordinary entropy with black hole entropy. This marriage of laws provided reassurance that the great principles of physics were not in conflict, but it also highlighted puzzles that remain unsolved to this day. One of those puzzles is the information paradox. If black holes radiate like black bodies and eventually evaporate, what happens to the information about the matter that fell in? Does it disappear, violating the fundamental principles of quantum mechanics, or is it somehow preserved in the radiation or in subtle correlations? Hawking initially argued that information is lost, while others believed it must be conserved. The debate raged for decades and remains a central problem in theoretical physics. Black hole thermodynamics thus not only unified fields, but also exposed their tensions. It is difficult to overstate how radical these ideas were at the time. The notion that black holes could glow, that they had entropy proportional to area, and that their properties were deeply tied to thermodynamics was revolutionary. It transformed black holes from bizarre dead ends of general relativity into laboratories for fundamental physics. They became testing grounds for ideas about quantum gravity, string theory, and the very structure of spacetime. What is most remarkable is how these insights grew from a simple insistence on consistency. Bekenstein refused to believe that the second law could fail, and Hawking, though initially doubtful, followed the mathematics where it led. The result was a synthesis that continues to guide research 50 years later. Black hole thermodynamics is no longer a curiosity. It is a cornerstone of theoretical physics, pointing toward the still unknown theory that unites gravity with quantum mechanics. For Hawking personally, this was a defining moment. It propelled him to international fame, not just among physicists, but among the public. The idea that black holes glow faintly in the darkness captured the imagination of scientists and non-scientists alike. It symbolized his ability to take abstract concepts and show their tangible consequences. From then on, Hawking was not merely a contributor to cosmology. He was one of its central figures. At a deeper level, black hole thermodynamics forces us to reconsider what we mean by information, order, and reality. If the entropy of a black hole measures its hidden degrees of freedom, what are those degrees of freedom? If the surface area encodes information, what does this say about the dimensionality of the universe? And if radiation allows black holes to vanish over time, what does this mean for permanence and stability in the cosmos? These questions remain open, but the framework that Hawking helped build continues to shape the search for answers. Existentially, there is something haunting in the idea that the darkest objects in the universe are not silent voids, but participants in the great thermodynamic flow. They consume, they radiate, and they obey the same deep principles that govern the boiling of water and the cooling of stars. In their apparent finality, they mirror our own lives. Finite, governed by irreversible processes, yet rich with hidden structure. Black hole thermodynamics tells us that even in the abyss, the universe preserves its order, its balance, and its laws. And as you consider these vast processes, let them ease the weight of your own concerns. The entropy of a black hole grows slowly over cosmic timescales. The universe itself keeps its secrets with patience beyond imagination. Whatever burdens you carried through the day, they are small beside the silent balance of gravity and heat at the edge of physics. Let that perspective be calming. You are part of a universe where even the most mysterious objects follow profound laws, and where rest is as natural as radiation from the horizon of a black hole. So allow yourself to rest now, letting the quiet rhythms of the cosmos carry you into sleep. Chapter 4. Hawking Radiation. Black Holes That Glow. By the early 1970s, Stephen Hawking had already helped push general relativity to its limits, making clear that singularities are not mathematical mirages and that black holes obey laws eerily similar to thermodynamics. The next leap came when he combined quantum field theory with curved spacetime and reached a conclusion that overturned the classical picture. Black holes emit thermal radiation. This quiet glow is unimaginably faint for astrophysical black holes, yet it is a robust prediction that arises when quantum fields are allowed to live on a space-time containing an event horizon. In one stroke, black holes were promoted from cold, featureless endpoints of collapse to thermodynamic systems with temperature and entropy, and the old analogy became real physics. Classically, the event horizon is a one-way membrane. Light cones tilt inward so severely that even light cannot escape once it crosses the horizon. Combine this with the no-hair theorems and you get a stark portrait. After transient dynamics settle, a black hole is fully characterized by mass, electric charge, and angular momentum. Temperature and radiation seem irrelevant, but the quantum vacuum is not empty. Even in flat spacetime, fluctuations are always stirring every field. And in curved spacetime, the very definition of particles becomes observer-dependent. Hawking's calculation lives inside this framework of quantum fields on curved backgrounds. quantize matter fields on the geometry formed by gravitational collapse, and then ask what a late-time observer at infinity actually sees. The standard intuitive picture invokes pairs of particles briefly materializing near the horizon. Usually the pair annihilates almost immediately. Near a horizon, however, one mode can propagate outward to infinity while its partner is trapped behind the horizon. To a distant observer, this looks like spontaneous emission. Energy conservation is preserved because the black hole's mass decreases by the amount radiated. The partner that falls in can be viewed as carrying negative energy relative to infinity. This story is helpful for intuition, but it is not the derivation. Hawking's computation relates in modes to out modes via Bogoliubov transformations and shows that late-time observers see a thermal spectrum. The perceived temperature is set by the surface gravity of the horizon and falls as the black hole's mass rises. Real black holes add refinements. The outgoing radiation is not perfectly black body because curvature outside the horizon partially scatters modes. The resulting gray body factors distort the spectrum and reduce the luminosity measured far away. Rotation introduces superradiance, in which certain bosonic waves are amplified when they scatter from the rotating geometry and extract spin energy. Electric charge and near-extremal conditions cool the horizon dramatically, pushing the temperature toward zero. Across all of these cases, the core message endures. Horizons and quantum fields together produce emission with a temperature governed by the near-horizon geometry. Because the temperature falls with increasing mass, stellar mass black holes are fantastically cold, far below the cosmic microwave background. Placed in an environment warmer than themselves, they absorb more than they emit. Only when the universe has cooled much further, or for much smaller holes, does evaporation dominate. Hypothetical primordial black holes, formed in the early universe from large density fluctuations, could be small enough that their Hawking flux today might be detectable. In that regime, evaporation accelerates as mass drops because the temperature climbs. A shrinking hole gets hotter, radiates faster, and races toward a brief, energetic finale. Hawking's result is one of the few rigorous predictions we possess about quantum fields on curved backgrounds. The calculation tracks modes that look vacuum-like in the far past, before the horizon forms, and then asks what those modes become for late-time observers. What counts as particles depends on how space-time is sliced into time and space, so the notion of vacuum is not absolute. A state that looks empty to one class of observers appears populated to another. The presence of a horizon makes that relativity of particles unavoidable and yields a clean, calculable thermal flux at infinity. A closely related phenomenon in flat spacetime clarifies the logic. The Unruh effect shows that a uniformly accelerating observer perceives the ordinary Minkowski vacuum as a thermal bath with a temperature proportional to the acceleration. Hawking's horizon temperature is the gravitational cousin of this effect. Where the Unruh temperature arises from acceleration through flat space, the Hawking temperature arises from a causal horizon in a curved spacetime. Horizons and heat travel together across gravitational settings, and the same mathematics that links acceleration, horizons, and thermality appears on both sides. Even though no instrument has directly detected Hawking quanta from an astrophysical black hole, the theoretical footing of the effect has only grown firmer. Independent derivations emphasize different aspects. Tunneling approaches model emission as barrier penetration and incorporate small back reaction corrections that nudge the spectrum away from perfect thermality. Euclidean methods relate temperature to periodicity in imaginary time by requiring smoothness of the Euclideanized geometry. The required periodicity fixes the inverse temperature. Simplified two-dimensional reductions capture universal near-horizon physics and reproduce the same flux. The convergence of these approaches shows that Hawking radiation is not a fragile artifact of one formalism, but a deep feature tied to horizon structure. Back reaction, the way the radiation drains mass and alters the geometry, is negligible for large holes, but grows as a hole shrinks. Early on, one can treat the geometry as fixed, but eventually the mass decreases, the temperature rises, and the emission accelerates. For a black hole of stellar mass, the total evaporation time is fantastically long, on the order of 10 to the 67th years, far beyond the current age of the universe. For much lighter holes, the timescales can be cosmologically short. Models of primordial black holes predict that those born below a critical mass would complete their evaporation today, perhaps producing brief bursts of high-energy gamma rays. The so-called trans-Planckian problem sparked early doubts. Modes that appear low frequency to a distant observer correspond to extremely high frequencies when traced back toward the horizon, exceeding the Planck scale where known physics may fail. Would the result depend on untested microphysics? Analyses that modify the high-frequency dispersion relation, making it subluminal or superluminal, show the thermal character of the emission is strikingly insensitive to the details, provided the horizon is smooth. The kinematic origin of the effect, rooted in redshift near a horizon, appears robust against such ultraviolet deformations. Because genuine Hawking flux is so faint, experimentalists have turned to analog gravity systems that mimic horizon kinematics. Acoustic horizons in flowing fluids, horizons engineered in Bose-Einstein condensates, and optical analogs in nonlinear media create conditions where horizon-induced spontaneous emission can occur. Several groups have reported correlated phonon pairs in condensates and horizon-like optical scattering with spectra consistent with thermal emission. These platforms do not probe quantum gravity, but they reproduce the mechanism by which horizons create thermality, lending empirical plausibility to the underlying physics. Cosmology supplies a complementary arena. If primordial black holes formed shortly after the Big Bang, their mass spectrum would determine whether any survive. Those with initial masses below a certain scale would have evaporated already, potentially seeding the diffuse gamma-ray background or producing transient flashes. Space and ground-based observatories use such signatures to bound their abundance, ruling out large swaths of parameter space while leaving narrow windows still under investigation. Even null results are informative because they tie the viability of early universe scenarios to Hawking's prediction. One of the most striking conceptual payoffs of Hawking radiation is the way it reframed entropy in gravity. Black hole entropy scales with the area of the horizon, not the volume enclosed. That peculiar scaling suggested that the fundamental degrees of freedom of spacetime might be encoded on surfaces, not in bulk regions. This insight inspired the holographic principle and later precise dualities in which a gravitational system in a higher dimensional spacetime is equivalent to a non-gravitational quantum theory on its boundary. Within such frameworks, the thermal properties of black holes map onto ordinary finite temperature physics, giving statistical meaning to the thermodynamic quantities Hawking's work demanded. A further layer of clarity comes from the choice of quantum state. The Boulware state looks empty to static observers at infinity, but is pathological at the horizon and cannot describe a hole formed by collapse. The Hartle-Hawking state represents a black hole in equilibrium with a bath of its own radiation and is appropriate in settings where radiation is reflected back, such as idealized cavities or anti-de Sitter spacetimes. The Unruh state captures the realistic situation of a hole formed by collapse that radiates outward into nearly empty space with no incoming flux from infinity. Each state encodes a different physical scenario, and Hawking's calculation selects the Unruh-like behavior relevant to astrophysical black holes. One can also sharpen the thermal character using ideas from statistical physics. In Euclidean formulations, regularity at the horizon requires imaginary time to be periodic, and that periodicity fixes a temperature in the same way the Kubo-Martin-Schwinger condition characterizes thermal states. Operationally, an idealized particle detector carried by a hovering observer just outside the horizon would register clicks with a rate determined by that temperature. Much as an Unruh DeWitt detector, with constant acceleration through flat space, clicks at a rate set by the Unruh temperature. These perspectives translate abstract field theory statements into the concrete language of detectors and counting events. The spectrum depends on what fields exist in nature. Emission rates differ for scalars, spin-1 photons, spin-2 gravitons, and neutrinos, and gray body factors weight their contributions differently as a function of frequency and angular momentum. At the low temperatures relevant to stellar mass holes, heavy particles are exponentially suppressed, so the flux is dominated by very light or massless degrees of freedom. As the temperature climbs in the late stages of evaporation, additional channels open, the spectrum hardens, and the luminosity rises sharply until the final brief phase. Observation in the wild remains difficult because ordinary astrophysical processes drown the signal. Accretion disks, jets, magnetic turbulence, and ambient radiation fields around black holes produce luminosities many orders of magnitude above the Hawking flux. Practical searches therefore focus either on analog systems in the laboratory or on the signatures of small relic black holes in the cosmos. Constraints from gamma-ray telescopes and air shower arrays limit the rate of final evaporation events and translate non-detections into upper bounds on how many primordial black holes could be lurking in specific mass windows. From a methodological perspective, the derivation's elegance is that it requires no full quantum theory of gravity. It is a semi-classical result, quantized matter on a classical spacetime. That makes Hawking radiation a precious guidepost. Any candidate theory of quantum gravity must reproduce this effect in the appropriate limit and must explain the microscopic origin of black hole entropy, whose scaling with area rather than volume is so distinctive. In this way, Hawking's calculation acts as a boundary condition on deeper theories. Whatever the ultimate microphysics, it has to leave this thermality and this entropy law intact, where semi-classical reasoning should hold. The discovery also reshaped our picture of cosmic time. In the unimaginably distant future, after stars have burned out, galaxies have dispersed, and perhaps even protons have decayed, the last luminous beacons will be black holes. Over stupendous durations, they will radiate away their mass, leaving only low-energy quanta behind. In that view, Hawking radiation is not just a feature of horizons. It defines the closing chapter of cosmic history, a slow coda in which darkness quietly converts itself into light and then fades to the thinnest whisper. Existentially, the image is sobering and beautiful at once. Objects once thought eternal prove temporary, releasing their mass into the void in a patient exchange governed by deep symmetry between geometry and heat. Even the most absolute-seeming structures are woven into change, and the faint warmth leaking from a horizon tells us that endings are processes, not abrupt voids. As you let that thought settle, let it ease the weight of the day. If even black holes, the heaviest and darkest entities in the cosmos, can shed their burdens bit by bit, then so can you. Whatever you have carried, you can release it slowly and gently until you feel lighter. The universe unfolds with patience, and tonight you too can find rest within its quiet rhythm. Chapter 5. The Information Paradox. Can the universe lose memory? When Stephen Hawking announced in the mid-1970s that black holes radiate, he also set off a conceptual earthquake. His calculation of thermal emission was accepted quickly, but the implications shook the foundations of physics. If black holes evaporate through Hawking radiation, and if that radiation is purely thermal, then all details about the matter that fell into the black hole are erased. When the black hole disappears completely, nothing remains to encode the lost information. The universe, it seemed, could forget. This scenario clashes violently with quantum mechanics, which insists that information is preserved in the evolution of physical systems. The tension between Hawking's prediction and quantum theory became known as the black hole information paradox, and it remains one of the central unsolved problems of fundamental physics. To understand why this paradox matters, we have to look at the principle of unitarity. In quantum mechanics, the state of a system evolves smoothly according to the Schrödinger equation. Probabilities may change, but the total information contained in the wave function is conserved. If you know the complete quantum state at one time, you can, in principle, reconstruct it at any other time. This reversibility is a cornerstone of quantum theory. Thermodynamics, by contrast, allows entropy to increase, but this increase reflects our limited ability to track every microscopic detail, not a literal destruction of information. Even when entropy grows, the underlying quantum state still evolves unitarily. Hawking's calculations seem to undermine this principle. His radiation had a thermal spectrum, meaning it depended only on the black hole's mass, charge, and spin. It carried no imprint of the specific matter that formed the black hole or later fell in. Two very different stars collapsing into identical black holes would, in Hawking's picture, produce indistinguishable radiation. When the black hole eventually evaporated, the detailed information about those stars would be gone forever. If true, this meant that quantum mechanics was incomplete, and that the universe could erase history in ways no laboratory experiment had ever shown. Initially, Hawking embraced this radical conclusion. He argued publicly that information loss was a fact of nature, and that quantum mechanics must be modified to accommodate it. This stance set him against many leading physicists, including John Preskill, Gerard Hooft, and Leonard Susskind, who were convinced that information must be preserved. What followed became known as the Black Hole War, a long-running debate that spanned conferences, seminars, and even wagers. Hawking and Kip Thorne bet that information was lost, while Preskill bet it was preserved. Decades later, Hawking would concede, but the journey to that point reshaped theoretical physics. One way to grasp the paradox is to think of a book thrown into a black hole. In principle, the quantum state of every atom in the book contains information. If the black hole erases it, the universe has lost more than just the text of the book. It has lost the fine-grained details of the matter's state. When the black hole radiates away, Nothing in the outgoing thermal flux encodes the words. In ordinary thermodynamic processes, entropy grows because we ignore microscopic correlations, but the information still exists. In Hawking's case, the information seemed genuinely gone. The paradox grew sharper when physicists tried to apply the rules of quantum theory more carefully. The entanglement structure of Hawking radiation is especially troubling. In the standard picture, each emitted quantum is entangled with a partner that falls into the black hole. As evaporation continues, the radiation outside is entangled with the interior, but once the black hole vanishes, there is no interior left. The external radiation, then, is left in a mixed state with no partner to purify it. This violates unitarity and leaves us with a universe that produces fundamentally unpredictable outcomes. Over the decades, several possible resolutions have been proposed. One idea is that information truly is lost, meaning quantum mechanics must be revised. This is the path Hawking originally favored, but such modifications would likely lead to observable violations of probability conservation in ordinary experiments, something never seen. Another idea is that black holes leave behind stable remnants that store the information. But remnants would have to hold arbitrarily large amounts of information in tiny packages, raising concerns about instability and uncontrolled particle production. The most popular line of thought is that the radiation is not perfectly thermal after all. Instead, subtle correlations between emitted quanta could encode the information. These correlations would be invisible in leading order calculations, but might emerge in a complete quantum gravity theory. In this view, Hawking's spectrum is only an approximation, and fine-grained details ensure unitarity. The challenge is to explain how this works while preserving the equivalence principle, which says that an observer falling across the horizon should encounter nothing unusual. In the 1990s, Susskind and 't Hooft argued that the resolution lies in holography. The entropy-area relation, already suggested by Bekenstein and confirmed by Hawking's work, hinted that information about a volume of space might be stored on its boundary. This led to the holographic principle, the idea that the physics inside a region is fully encoded on its surface. In the context of string theory, this principle was given precise form through the ADS-CFT correspondence, which showed that a gravitational system in a higher dimensional space can be equivalent to a quantum field theory without gravity on its lower dimensional boundary. In this framework, black hole evaporation is unitary because the dual quantum theory is manifestly unitary. Still, holography does not eliminate all puzzles. It tells us that information is preserved globally, but not how it escapes from the horizon in a way consistent with local physics. This issue came to the forefront in the 2010s with the firewall paradox. If information does emerge in the radiation, then late-time quanta must be entangled with both early radiation and their partners behind the horizon. But quantum mechanics forbids a single system from being fully entangled in two independent ways. To resolve the conflict, one option is to break entanglement across the horizon, but that would replace the smooth experience of falling into a black hole with a wall of high-energy quanta, a firewall, violating the equivalence principle. Recent progress has come from new calculations and simplified models of gravity. These studies, often using techniques called replica wormholes, have been able to reproduce the so-called Page curve. This curve describes how the entanglement entropy of the radiation should behave if information is preserved. It grows at first as the black hole radiates, peaks around the halfway point of evaporation, and then declines as information comes out in later quanta. Hawking's original calculation gave only a monotonically rising curve, implying information loss. The new methods, by contrast, recover the unitary page curve, suggesting that subtle non-local effects in quantum gravity allow information to escape. Despite this progress, the mechanism by which information escapes remains elusive. Does it leak out gradually in correlations among quanta? Is it encoded holographically on the horizon? Do wormhole-like connections carry it outward in ways we only partly understand? Each proposal challenges some aspect of our intuitions about locality, causality, or smoothness of spacetime. What unites them is the conviction that Hawking's prediction, though correct at the semi-classical level, must be refined by quantum gravity. The information paradox has been fertile ground for new ideas because it sits at the intersection of relativity, quantum theory, and thermodynamics. It forces us to ask whether space-time itself is emergent from more fundamental degrees of freedom, whether locality is approximate rather than exact, and whether horizons are as impermeable as they seem. The paradox also shows how a thought experiment, throwing matter into a black hole and watching it evaporate, can probe physics far beyond our current experimental reach. For Hawking himself, the paradox was not just a technical problem, but a test of scientific courage. He was willing to stake his reputation on the claim that information is lost, even though it clashed with mainstream opinion. Later in life, he conceded the bet, admitting that information might be preserved after all. But his willingness to follow the mathematics to a radical conclusion is what gave the paradox its power. It inspired generations of physicists to explore the edges of theory, to seek unification, and to imagine physics beyond what we can currently measure. Existentially, the information paradox is more than a debate about quanta. It touches on the question of memory itself. If the universe can forget, what does that mean for meaning and continuity? If information is preserved, then every trace of existence is woven into the fabric of reality, indelible even when transformed. The paradox forces us to confront whether impermanence is absolute or whether beneath it lies a permanence of pattern. And as you let these questions linger, allow them to ease the day's concerns. The paradox is not solved, and perhaps it never will be fully resolved, but that is part of its beauty. In a universe where even black holes challenge our understanding, your own uncertainties can rest quietly. The cosmos carries them, just as it carries its deepest mysteries, into the patient unfolding of time. Let that perspective calm you. Tonight, you can set aside what cannot yet be answered and sink into rest as the universe itself holds its secrets gently in the dark. Chapter 6. Imaginary Time and the Shape of the Universe. Among Stephen Hawking's many contributions to theoretical physics, one of the most striking and philosophically provocative was his use of the concept of imaginary time. At first glance, the phrase seems nonsensical. Time is what we measure with clocks, the steady ticking that separates past from future. How could time be imaginary? Yet Hawking used this mathematical tool to propose a new way of thinking about the origin of the universe, one that avoids the infinite singularities predicted by classical general relativity. By turning time into a spatial dimension in certain calculations, he suggested that the universe may be finite but without boundaries, much like the surface of a sphere. The notion of imaginary time emerges from a technique widely used in physics called Wick rotation. In quantum field theory and statistical mechanics, calculations often become simpler if one substitutes real time with imaginary values, effectively rotating the time axis into the complex plane. This turns oscillating exponential functions into decaying ones, smoothing out divergences and making integrals converge. After performing the calculation, one can rotate back to real time. In most contexts, this is a purely mathematical trick with no claim to physical reality. But Hawking realized that in cosmology, imaginary time might describe something about the actual structure of spacetime itself. Classical general relativity predicts singularities in the past. If the universe has been expanding since the Big Bang, then tracing it backward implies a point of infinite density and curvature. At such a singularity, the laws of physics break down. This is unsatisfactory not only scientifically but philosophically, for it suggests a beginning outside the scope of explanation. Hawking's proposal was to consider the universe in imaginary time near what would otherwise be a singularity. By making this substitution, the equations that describe spacetime take on a Euclidean character. Instead of a sharp boundary where time starts, one finds a smooth, rounded geometry. To visualize this, consider the surface of the Earth. If you travel southward, you eventually reach the South Pole. But the pole is not a boundary where the Earth stops. It is simply a point where one direction ends and another begins. The surface is finite, yet without edges. In Hawking's picture, imaginary time plays a similar role. Near the origin of the universe, time behaves like a spatial coordinate, so the beginning of the universe resembles the smooth cap of a sphere, not a singular edge. The universe is finite in extent, but without a boundary where the laws of physics would fail. This idea was developed in Hawking's collaboration with James Hartle, leading to the no-boundary proposal. The proposal states that the universe is described by a quantum wave function defined over possible geometries, and that these geometries include compact Euclidean ones without boundaries. Imaginary time is the mathematical key that allows such geometries to exist smoothly. While Chapter 7 will focus on the broader no-boundary proposal, it is important here to recognize that the very use of imaginary time was the conceptual leap that made it possible. One of the scientific motivations for this approach was to reconcile quantum mechanics with cosmology. Quantum mechanics is naturally formulated in Euclidean time because probabilities and path integrals are easier to compute when oscillatory phases become decaying exponentials. Hawking and Hartle applied this logic to the universe as a whole, treating its history as a kind of quantum path integral over geometries. Imaginary time eliminated the singularity and provided well-behaved contributions to the integral. The outcome was a model in which the universe could arise spontaneously without requiring a sharp initial condition. Critically, imaginary time does not mean that we literally experience time as imaginary. Our everyday sense of past, present, and future corresponds to real time. Imaginary time is a coordinate transformation that reveals deeper structure in the mathematics. What makes Hawking's use distinctive is that he entertained the possibility that imaginary time reflects something physically real about the universe's geometry at its earliest stages. Near the Planck epoch, when quantum gravity dominates, our familiar conception of time might simply not apply. The smooth Euclidean character of space-time and imaginary time could replace the singular origin of real time. The implications of this are profound. If the universe has no boundary in imaginary time, then asking what came before the Big Bang is meaningless, just as asking what lies south of the South Pole is meaningless. Time as we know it simply does not extend further back. The universe is self-contained, finite yet unbounded, with no external cause or beginning. This picture does not eliminate the need for explanation. one must still account for why the laws of physics are as they are, but it removes the conceptual problem of a singular starting point. Imaginary time also changes how we think about the shape of the universe. In real time, we experience expansion, galaxies receding, space stretching, time flowing forward. In imaginary time, the geometry is static and compact, more like a sphere than a line. This duality suggests that the universe may be understood as a four-dimensional object with both Euclidean and Lorentzian aspects, depending on how one slices it. Our flow of time is one perspective, but beneath it lies a structure where time and space are more deeply unified. While elegant, Hawking's use of imaginary time is not without challenges. Many physicists treat it as a calculational device rather than a literal description. The transition between imaginary and real time is not fully understood in quantum gravity, and the no-boundary proposal has faced technical difficulties in defining probabilities unambiguously. Some cosmologists favor alternative models, such as eternal inflation or bouncing universes, which handle the singularity differently. Nevertheless, imaginary time remains one of the most creative attempts to merge mathematical consistency with physical interpretation. Over the years, the concept has inspired both scientific and popular imagination. In his book A Brief History of Time, Hawking wrote that if the universe is finite but without boundary, it has no beginning and no end. It simply is. This statement captivated readers because it framed cosmology in existential terms. Imaginary time offered a scientific way to envision a cosmos that requires no external cause, no creation event, no before. Instead of confronting a singular wall, we encounter smoothness. The universe folds back on itself, and our questions about ultimate origins are transformed. From a technical perspective, imaginary time has also been useful in black hole physics. Euclidean methods, which rely on imaginary time, are used to compute black hole entropy and temperature. The requirement that Euclidean spacetime be smooth at the horizon fixes the periodicity of imaginary time, which in turn yields the Hawking temperature. Thus, the same mathematical trick underlies both black hole thermodynamics and Hawking's cosmological ideas. This coherence suggests that imaginary time is more than a curiosity. It is a unifying concept across gravitational physics. Imaginary time has also found resonance in discussions about the arrow of time. In real time, entropy increases, and we perceive a direction from past to future. In imaginary time, there is no arrow. The geometry is symmetric, without a privileged direction. This symmetry may help explain why the universe began in a low entropy state. In imaginary time, there is no distinction between before and after, so the asymmetry of time emerges only when real time takes over. The arrow of time, then, could be a derived property rather than a fundamental one. For Hawking, the idea of imaginary time was a way to tame the infinities that threatened to break physics. Instead of accepting a singularity where the laws failed, he used the mathematics of Euclidean spacetime to propose a consistent, boundary-free universe. This was not a final answer. Quantum gravity remains elusive, but it was a bold attempt to extend our reach into the earliest moments of the cosmos. It showed how far imagination, grounded in mathematics, can take us. Existentially, imaginary time is both humbling and liberating. It suggests that our sense of beginnings and endings may be parochial, tied to the way we experience real time. The universe itself may have no sharp start, no edge, no outside. It may simply be timeless in its foundation. In this view, our questions about what came before the Big Bang dissolve not because they are answered, but because they were never meaningful to begin with. And as you contemplate this vision, allow it to soften the edges of your own day. If the cosmos itself flows without a beginning or end, then you too can release the need for closure tonight. There is no singular boundary between wakefulness and rest, only a smooth transition, a gentle rounding off. Let the thought of a universe without edges cradle you, and let yourself drift calmly into sleep, carried by the timeless quiet of imaginary time. Chapter 7. The No-Boundary Proposal, Hartle-Hawking State. If Hawking's idea of imaginary time opened a new way to think about the beginning of the cosmos, the no-boundary proposal developed with James Hartle was its boldest realization. Known as the Hartle-Hawking state, this model aimed to answer one of the deepest questions in cosmology: how did the universe begin? The standard Big Bang picture describes a singular origin, where density and curvature become infinite. But singularities are not places. They are breakdowns of the laws that should describe them. Hawking and Hartle sought a model that would avoid singularities and instead produce a self-contained universe, finite yet without edges. The essence of the no-boundary proposal is that the universe's wave function, which encodes the probabilities of different histories, can be defined by summing over all possible compact Euclidean geometries. In this view, the early universe is not described by a singular point in real time, but by a smooth, rounded geometry in imaginary time. Just as the Earth's surface is finite yet without a boundary, so too the universe would be finite in extent, but without an edge where time begins. The metaphor Hawking often used was the South Pole. Asking what happened before the Big Bang is like asking what lies south of the South Pole. It is not a meaningful question because the geometry simply closes off smoothly. The proposal arose at the intersection of quantum mechanics, general relativity, and cosmology. Quantum mechanics tells us that systems are described by wave functions, evolving in time according to deterministic equations, but yielding probabilistic outcomes. General relativity tells us that spacetime itself is dynamical, shaped by matter and energy. Bringing these together means treating the universe as a quantum system, with a wave function defined not over particles in spacetime, but over possible spacetimes themselves. The no-boundary wave function is precisely this: a functional that assigns amplitudes to different geometrical histories of the universe. To make this concrete, Hartle and Hawking formulated the wave function as a path integral, a sum over possible geometries weighted by the exponential of the Euclidean action. This was inspired by Feynman's path integral in quantum mechanics, where the probability amplitude for a particle to move from one point to another is obtaining over all possible paths, each weighted by a phase. For the universe, one sums not over paths but over geometries. Imaginary time is the crucial element because it makes the geometries compact and the integral mathematically manageable. Without imaginary time, the integrals diverge. With it, they yield smooth, finite contributions. The resulting picture is that the universe did not begin with a bang, but with a smooth, rounded cap in imaginary time. From this Euclidean regime, the universe transitioned into the Lorentzian regime we inhabit, where time behaves as we experience it. In this view, the cosmos has no boundary in the past. Instead of an edge where physical law fails, there is continuity. This does not mean that time existed forever. Rather, it means that the notion of before is not defined. The universe is self-contained, with no need for external conditions. One of the strengths of the no-boundary proposal is that it naturally predicts inflation, the brief period of rapid expansion that solves many puzzles of cosmology. When the path integral is evaluated for simple geometries, the most probable histories are those that begin with a short period of exponential growth. This aligns the proposal with observations of the cosmic microwave background, which are consistent with inflationary models. Thus, the no-boundary idea is not just philosophical, it has explanatory power for real data. The proposal also shifts how we think about causality and initial conditions. In classical physics, the state of a system at one moment determines its state at the next. To know the universe's history, we would need initial data specified at its beginning. But if the beginning is a singularity, such data cannot be given. The no-boundary proposal avoids this by eliminating the boundary altogether. Instead of initial conditions, the universe is described by the no-boundary wave function, which assigns probabilities to entire histories. The need for an external input disappears. This self-contained character of the universe resonated with Hawking's philosophical sensibilities. In public lectures, he often emphasized that if the universe has no boundary, then it has no beginning and no need for a creator. This statement was not meant as theology, but as physics. If the laws are self-sufficient, then the universe can be understood entirely from within. In that sense, the no-boundary proposal was as much about intellectual completeness as it was about technical cosmology. Despite its elegance, the proposal has faced challenges. The path integral over geometries is difficult to define rigorously. Not all geometries contribute positively, and the measure of the integral is subtle. Critics have argued that the no-boundary wave function may not be mathematically well-defined without additional restrictions. Others have suggested alternative boundary conditions, such as the tunneling proposal advanced by Alexander Vilenkin, which envisions the universe emerging from nothing through a quantum tunneling event. These alternatives produce slightly different predictions for inflationary models and the structure of the cosmic microwave background. Nevertheless, the no-boundary proposal has remained influential. It continues to inspire refinements in quantum cosmology and has been adapted to frameworks like string theory and loop quantum gravity. Recent work on semi-classical methods and holographic cosmology has revisited the idea, suggesting that the no-boundary wave function may connect to deeper principles about holography and entropy. In this way, Hawking's imaginative leap still guides modern research. It is also important to note what the no-boundary proposal does not claim. It does not deny that the universe had an early hot dense phase. Rather, it reframes how that phase is understood in quantum terms. Nor does it assert that imaginary time is literally experienced. It is a mathematical representation that captures the geometry of the earliest universe. The proposal is less about what we would see if we traveled back to the beginning, and more about what the equations tell us when applied consistently. From a scientific standpoint, the proposal's value lies in its coherence. It shows that it is possible to formulate a model of the universe that avoids singularities, incorporates quantum principles, and makes contact with cosmological observations. Even if refinements are needed, the framework demonstrates that questions about the universe's origin can be approached with physics rather than deferred to metaphysics. On a deeper level, the no-boundary proposal reshapes how we imagine the cosmos. We often think in terms of origins and causes, searching for a first event or a prime mover. The no-boundary view denies us that comfort. Instead, it offers a universe that is finite, but without edges, self-contained, and complete. This challenges our intuitions, but also frees us from the paradoxes of singular beginnings. The universe does not need a before, it simply is. Philosophically, this raises questions about time itself. If time as we know it emerges only after the transition from imaginary to real time, then our most basic categories, past, present, future, are emergent features, not fundamental truths. The deep structure of the universe may be timeless in its foundation. What we perceive as the flow of time could be a secondary phenomenon, arising only when the universe enters the Lorentzian regime. For Hawking, the no-boundary proposal represented both scientific ambition and personal vision. It showed his ability to use mathematics not just as a tool for calculation, but as a canvas for reimagining reality. His willingness to consider imaginary time as more than a trick and to build an entire cosmological model from it exemplifies the blend of rigor and imagination that defined his career. Existentially, the no-boundary proposal suggests that we are inhabitants of a universe that requires no external explanation. There is no edge beyond which lies nothingness. There is only continuity. To live in such a cosmos is to live in a world that contains within itself the reasons for its being. This vision is both unsettling and deeply calming. And as you let these ideas drift through your thoughts, let them bring you peace. If the universe itself can be smooth and without boundaries, then so too can your mind tonight. There's no sharp edge where you must stop. There's only the gentle rounding off into rest. Let yourself follow that curve into calm as the cosmos itself folds quietly into timelessness. Chapter 8. Chronology Protection. Why Time Travel May Be Impossible. Time travel has fascinated humans for centuries, long before Einstein revealed that space and time are flexible and dynamic. In myths and stories, people imagine revisiting the past or glimpsing the future, changing outcomes or fulfilling destiny. In physics, the concept is both alluring and troubling. Einstein's general relativity describes space-time as a malleable fabric curved by energy and mass, and within this theory lie solutions that seem to permit closed time-like curves, paths through space-time that loop back on themselves, allowing an object or observer to return to an earlier point in their own history. The possibility of such curves has led to serious scientific debate. Could time travel really happen? Stephen Hawking was skeptical. He believed that the logical consistency of the universe demanded safeguards against paradoxes. In 1992, he gave this conviction a name: the chronology protection conjecture. It was his witty but serious attempt to argue that the laws of physics prevent macroscopic time machines. In his words, the laws of physics conspire to prevent time travel on a macroscopic scale. To understand what was at stake, it helps to recall that general relativity admits a wide variety of exotic spacetimes. Kurt Gödel, a logician best known for his incompleteness theorems, discovered in 1949 a solution to Einstein's equations that describes a rotating universe filled with matter. In this model, closed time-like curves naturally exist. One could in principle travel along such a curve and arrive back at one's own past. Other proposed scenarios include the Tipler cylinder, a hypothetical, infinitely long rotating cylinder of dense matter that could generate closed time-like loops, and wormholes, tunnels connecting distant regions of space-time. In many of these constructions, if one manipulates the geometry correctly, paths through the structure allow effective backward time travel. At first glance, nothing in general relativity forbids such geometries. Einstein's equations are differential equations, and given exotic enough distributions of energy and momentum, they yield exotic spacetimes. But not all mathematically consistent solutions are physically realizable. For instance, Gödel's universe requires global rotation inconsistent with our observed cosmos. Tipler cylinders must be infinitely long, something no real object could be. Wormholes require exotic matter, a form of material with negative energy density, to remain open. While quantum field theory allows negative energy densities in limited circumstances, such as the Casimir effect, sustaining them at macroscopic scales seems implausible. The challenge is not only practicality, but logical consistency. Time machines generate paradoxes. The grandfather paradox is the most famous example. If you traveled back in time and prevented your ancestor from existing, you would remove your own reason for traveling in the first place. More subtle are consistency paradoxes involving information. If a message is sent into the past and used to create itself, information appears from nowhere, violating the principle that causes precede effects. These paradoxes suggest that something deeper must forbid closed time-like curves from becoming physical realities. Hawking proposed that the safeguard lies in quantum physics. When spacetimes threatening to develop closed time-like curves are examined with quantum field theory, calculations often show that quantum fluctuations become uncontrollably large near the would-be time machine. The expectation value of the stress-energy tensor diverges at the boundary of chronology violation. This energy buildup would curve spacetime so strongly that the closed loops are destroyed before they can form. In effect, the universe defends itself. Quantum mechanics, usually thought to allow uncertainty and strangeness, here acts as a guardian of consistency. This logic resembles another guiding principle in relativity, the cosmic censorship conjecture, which posits that singularities are always hidden behind horizons so that observers never directly encounter them. Just as cosmic censorship prevents naked singularities from undermining predictability, chronology protection prevents causal loops from undermining determinism. Both are not yet proven theorems, but conjectures supported by strong evidence and motivated by the demand for consistency in physics. The semi-classical analyses that support chronology protection are illuminating. In spacetimes where closed time-like curves threaten to appear, vacuum fluctuations are not gentle ripples but violent storms. Quantum fields become infinitely excited as one approaches the chronology horizon, the boundary beyond which closed loops would exist. The back reaction of this energy cannot be neglected. It forces space-time to rearrange itself in ways that close off the loophole. This is why Hawking argued that time machines are unstable. Even if general relativity permits them mathematically, quantum effects destabilize them physically. The chronology protection conjecture does not forbid all speculation. Tiny, transient violations of chronology might exist at microscopic scales, hidden within quantum foam at the Planck length. But large, stable, traversable time machines, the kind beloved by science fiction, would be ruled out. For Hawking, this was a relief. He quipped that one reason we should believe in chronology protection is the lack of tourists from the future. If time travel were possible, wouldn't we have met visitors from centuries ahead? His humor underscored a serious point. Nature seems to enforce causality. At the same time, other physicists have considered alternative possibilities. Igor Novikov proposed the self-consistency principle, which suggests that if closed time-like curves exist, events along them must be globally self-consistent. In this view, paradoxes are avoided not because time travel is impossible, but because the universe arranges events so that contradictions cannot occur. You might travel back in time, but your actions would always be part of history as it already happened. This is a logically consistent framework. but it implies a strange fatalism. Free will becomes illusory if your journey to the past is already woven into the tapestry of events. Hawking found such solutions unsatisfying. He preferred the cleaner safeguard of chronology protection, where quantum effects prevent paradoxes before they arise. His perspective reflected both physical reasoning and philosophical taste. Physics should not merely accommodate paradoxes with clever consistency conditions. It should prevent them. The broader significance of chronology protection is how it points toward quantum gravity. Both black hole evaporation and time machine scenarios show that general relativity alone cannot answer the hardest questions. Quantum effects matter, even when space-time curvature is gentle. Hawking radiation revealed that black holes are not eternal, while chronology protection suggested that time machines are unstable. In both cases, quantum field theory in curved spacetime supplies corrections that restore logical coherence. In the search for a full quantum theory of gravity, chronology protection offers a guiding principle. Any consistent theory must either enforce it or provide an alternative mechanism that ensures consistency. String theory and loop quantum gravity both contain structures that appear to safeguard causality. In holographic dualities, causality in the boundary quantum field theory forbids causal loops in the bulk gravitational theory, reinforcing the idea that chronology protection is a natural feature of a deeper framework. Still, the debate is not closed. Some exotic spacetimes evade obvious divergences, at least in simplified models. Could stable time machines exist in corners of the theory we do not yet understand? Could the quantum fluctuations be tamed by new physics? These questions remain open, though the consensus leans toward Hawking's intuition. Time travel to the past is forbidden, not by decree, but by the self-consistency of nature's laws. The cultural impact of Hawking's conjecture is notable. While popular culture continues to imagine time machines, science grounds us in more sober possibilities. This does not diminish wonder but reshapes it. The universe may not allow backward journeys, but it still offers cosmic expansion, gravitational waves, black hole mergers, and quantum entanglement. All phenomena more astonishing than fiction. Hawking's wit and clarity helped bridge these two worlds, reminding us that imagination and rigor can coexist. Existentially, chronology protection gives us something comforting, the assurance that time's arrow is stable. The past cannot be rewritten, and causality is preserved. This permanence means our memories are anchored, our choices matter, and the coherence of life is maintained. While we may long for do-overs, the structure of time gives weight to our actions and meaning to our histories. And as you let that thought rest in your mind, allow it to calm the day's turbulence. Whatever has unfolded cannot be undone, but it can be accepted. The future remains open, not to paradox, but to possibility. Like the universe itself, you are carried forward by the flow of time, steady and secure. Tonight, let go of regrets, release the loops of thought that circle back on themselves, and allow yourself to move smoothly into rest. The arrow of time guides you gently onward, and in that certainty, you can close your eyes and drift peacefully into sleep. Chapter 9. Primordial Black Holes and Dark Matter. Black holes are usually thought of as the end states of stellar evolution. When massive stars exhaust their fuel, gravity overwhelms all other forces, and collapse creates a singular region of spacetime from which nothing can escape. But in the early universe, long before the first stars formed, conditions were radically different. The cosmos was hot, dense, and filled with violent fluctuations. In that environment, It is possible that black holes formed directly from the primordial soup itself. These are called primordial black holes, and they are distinct from the stellar and supermassive black holes we observe today. Stephen Hawking was one of the first to recognize their importance, not only as possible relics of the early universe, but also as potential candidates for dark matter, the unseen mass that shapes galaxies and cosmic structure. The idea is rooted in the physics of the Big Bang. In the first fractions of a second, the universe expanded rapidly, but the density was so enormous that even small fluctuations in matter could collapse under their own gravity. If a region of space had just the right conditions, denser than average, above a critical threshold, it could overcome pressure forces and collapse into a black hole. The mass of the black hole would depend on the scale of the fluctuation. Smaller fluctuations could produce tiny black holes, while larger ones could create objects of planetary or stellar mass. Unlike ordinary black holes, primordial ones are not the product of dying stars. They are fossils from the infant universe. What makes primordial black holes fascinating is the wide range of masses they could have. Some could be as small as a mountain, with masses comparable to asteroids but compressed into microscopic radii. Others could weigh as much as planets, stars, or even more. Their formation would depend on conditions such as the spectrum of density fluctuations, phase transitions in the early universe, or the dynamics of cosmic inflation. Because they are not tied to stellar processes, they could exist in mass ranges where no ordinary astrophysical black holes form. Hawking's work on black hole radiation immediately connected with this idea. He realized that small primordial black holes would evaporate quickly through Hawking radiation. A black hole with mass around 10^² kilograms, roughly the mass of a mountain, would evaporate on timescales comparable to the current age of the universe. Such an object, if formed at the Big Bang, would be reaching the end of its life today, releasing a burst of high-energy radiation in its final moments. Larger primordial black holes would still be around, slowly radiating but far from complete evaporation. The possibility of detecting such bursts or of constraining their abundance through the absence of signals became one of the first ways to test Hawking's ideas. At the same time, astrophysicists were grappling with the puzzle of dark matter. Observations of galaxies and clusters showed that visible matter accounted for only a fraction of the gravitational pull. Something unseen was holding galaxies together, bending light through gravitational lensing and shaping the cosmic web. Particle physicists proposed new particles, such as weakly interacting massive particles, or WIMPs. But another possibility was that dark matter consisted of compact, non-luminous objects. Primordial black holes, being massive but invisible except through gravity, fit the bill. The attraction of primordial black holes as dark matter is that they require no new particles beyond those we already know. If conditions in the early universe favored their formation, they could have survived in large enough numbers to account for the missing mass. Their gravitational influence would mimic that of dark matter, clustering around galaxies and shaping cosmic evolution. Hawking's recognition of this possibility made primordial black holes a bridge between early universe cosmology, black hole physics, and the dark matter problem. Testing this idea, however, is complex. Primordial black holes interact gravitationally, but otherwise they are elusive. If they are too small, they would have evaporated already, potentially leaving behind gamma rays or other high-energy relics. If they are too large, their gravitational effects on astrophysical systems should be detectable. Astronomers have used many strategies to search for them. Gravitational lensing is one of the most powerful. When a compact object passes in front of a background star, it can briefly magnify the star's light. Surveys of stars in the Magellanic Clouds in the Milky Way have looked for such microlensing events. The absence of large numbers of these events has ruled out primordial black holes in certain mass ranges. Other constraints come from cosmic microwave background measurements. Black holes accrete matter and radiate energy, which could disturb the delicate balance of the early universe's radiation field. If primordial black holes were too abundant, the imprint they left would conflict with the observed smoothness of the microwave background. Observations from satellites like Planck have been used to place tight bounds on how many primordial black holes could exist. Yet, despite these constraints, certain mass windows remain viable. Black holes of asteroid mass, lighter than a planet but heavier than small comets, are still possible candidates. Likewise, very heavy black holes, hundreds or thousands of times the mass of the Sun, have not been completely excluded. Intriguingly, the detection of gravitational waves by LIGO has reopened interest in primordial black holes. The first signals came from black hole mergers of around 30 solar masses, heavier than most stellar remnants known at the time. Some physicists suggested that these could be primordial in origin, though stellar explanations remain likely. Theoretical models continue to explore how inflationary physics could generate density fluctuations that seed primordial black holes. Certain inflation models naturally predict enhanced fluctuations at specific scales, potentially leading to black hole formation. Phase transitions in the early universe, where symmetries broke and fields shifted, could also generate conditions ripe for collapse. These scenarios connect black holes to the deepest questions about high-energy physics, unification, and the structure of spacetime at its earliest moments. If primordial black holes make up some or all of dark matter, their discovery would revolutionize physics. Instead of requiring entirely new particle species, the mystery of dark matter could be explained by gravitational relics of the Big Bang. This would unify cosmology and black hole physics in an elegant way, fulfilling Hawking's instinct that the boundaries between disciplines often hide the most profound insights. Even if primordial black holes are only a small fraction of dark matter, they could still play a role in cosmic history. They may have acted as seeds for supermassive black holes at galactic centers, accelerating the growth of structure. They might have influenced reionization, the epoch when the first stars and galaxies lit up the universe. Their evaporation, if it occurred, could have left imprints in cosmic radiation backgrounds or in the abundance of light elements. Each possibility extends the reach of Hawking's original insight, that tiny black holes born at the dawn of time might still shape the universe today. The search continues with ever greater precision. Future gravitational wave detectors, surveys of microlensing in distant galaxies, and high-energy astrophysical observatories will refine the parameter space. Whether primordial black holes turn out to be the dark matter or not, the pursuit deepens our understanding of both early universe physics and gravitational phenomena. Hawking's role in this story is pivotal. He not only introduced the idea of primordial black holes, but also tied their fate to the evaporation process he discovered. His calculations showed that their existence could be probed indirectly, linking the tiniest scales of quantum gravity with the largest structures of cosmology. In doing so, he exemplified his gift for connecting distant realms of physics into a coherent picture. Existentially, primordial black holes remind us that the universe carries fossils of its earliest moments. Hidden in the darkness may be objects older than stars, silent witnesses to creation itself. If they make up the dark matter, then galaxies, stars, planets, and life all owe their structure to these primordial seeds. We live in a cosmos whose present is sculpted by remnants of its birth. And as you rest with that thought, let it calm your mind. The universe remembers its own infancy through these ancient black holes, just as you carry memories of your own beginnings. Whether or not we ever find them, the possibility itself tells us that the past is never entirely gone. Tonight, you can set aside the day, knowing that the cosmos holds its history quietly, and that in its quiet presence, you too can drift gently into sleep. Chapter 10. Hawking's Legacy, Top-Down Cosmology, and Beyond. As Stephen Hawking's career advanced into its later decades, he continued to push against the boundaries of cosmology, not only refining earlier insights about black holes and the origin of the universe, but also venturing into new proposals that would shape discussions long after him. Among his most distinctive contributions was the idea of top-down cosmology, a framework that shifted how physicists think about the relationship between quantum theory and the history of the cosmos. This approach, developed with Thomas Hertog, challenged the traditional picture of a universe with a single, well-defined past, and instead suggested that multiple histories could coexist, with the past itself dependent on how we observe the present. In many ways, it was the culmination of Hawking's life's work, blending relativity, quantum mechanics, and philosophical imagination into a vision that redefined our place in the cosmos. The starting point is the recognition that cosmology is not like ordinary physics. In laboratory experiments, we set up initial conditions and watch how a system evolves. The laws of physics then determine the outcomes. But when the system is the universe itself, there is no external experimenter who can fix the initial conditions. Classical cosmology assumes that the universe began in some specific state, such as a singular Big Bang, or the smooth geometry proposed in the no-boundary condition, and then evolved forward. In this bottom-up approach, one specifies the beginning and calculates the rest. Hawking and Hertog proposed a reversal. Instead of assuming that the universe had one unique beginning, they suggested that it is better described by summing over many possible histories, each weighted by their probability amplitude. This is a direct application of Feynman's path integral philosophy to cosmology. Just as a particle does not take a single path but explores all paths, the universe may not have a single past, but rather a quantum superposition of many possible pasts. The top-down approach means we start from the present with its observed properties, and then trace backward through all histories compatible with those properties. The universe's past, in this view, depends on what we measure in the present. This shift has both technical and philosophical implications. On the technical side, it reframes how we compute the probabilities of different cosmological scenarios. Instead of asking what the universe inevitably looked like at its origin, we ask what configurations of the past are consistent with the universe we see now. The mathematics employs path integrals over geometries, building on the same Euclidean techniques that underpinned Hawking's earlier work with the no-boundary proposal. But where the no-boundary idea posited a specific smooth geometry at the origin, top-down cosmology embraces a spectrum of possibilities, reflecting the probabilistic essence of quantum mechanics. Philosophically, the proposal presents the very notion of a fixed past. In classical history, the past is determinate. Events occurred in one particular way. In quantum cosmology, however, the past may be as uncertain as the future until it is observed. Hawking often emphasized that the wave function of the universe encodes all possible histories and that observation selects among them. In this sense, cosmology becomes participatory. Our measurements of the present help determine which histories are relevant, collapsing the multitude of potential pasts into the one that fits our observations. This idea aligns with a broader theme in quantum physics, the inseparability of observer and system. In the double-slit experiment, particles take many paths until an observation singles out an outcome. Hawking extended this logic to the cosmos itself. The universe may contain many possible paths in its early history, but the reality we observe today is shaped by the act of observation. In top-down cosmology, there is no single, observer-independent account of the universe's origin. Instead, the past is conditional, tied to the present in a feedback loop that blurs the arrow of explanation. Top-down cosmology also addresses puzzles about the apparent fine-tuning of the universe. Many features of our cosmos seem delicately balanced to allow for the existence of galaxies, stars, and life. Classical cosmology often frames this in terms of initial conditions. The universe began with just the right properties. But in a top-down framework, such fine-tuning arises naturally. Out of the many possible histories, we find ourselves in one consistent with our existence. Not because the universe was set up that way from the start, but because only those histories compatible with observers like us are realized in our measurements. This is not quite the anthropic principle as usually stated, but it resonates with it. Our perspective as observers is built into the structure of quantum cosmology itself. Hawking and Hertog elaborated these ideas in the context of inflationary cosmology. Inflation, the exponential expansion of the early universe, is an established component of modern cosmology, supported by the smoothness of the cosmic microwave background and the distribution of large-scale structure. But in some models, inflation can continue eternally, generating an infinite multiverse of pocket universes with varying properties. This picture raises conceptual and mathematical difficulties, including how to assign probabilities across an infinite ensemble. Hawking was critical of such unbounded multiverse scenarios. Top-down cosmology provided an alternative. By summing over histories that match our current observations, it avoids the infinities of eternal inflation while still accommodating quantum variety. The idea also connects to holography, the principle that physics in a volume of space can be described by data on its boundary. In some formulations, top-down cosmology can be reinterpreted through holographic dualities, where the probabilities of different universes correspond to correlation functions in a lower-dimensional quantum theory. This link reinforces the sense that the universe is not a machine unfolding from a single origin, but a web of probabilities shaped by fundamental quantum rules. Critics have raised objections, noting that top-down cosmology is difficult to test directly. Its reliance on path integrals over geometries makes calculations technically challenging, and the connection between observation and history remains conceptually murky. Still, the proposal is valuable precisely because it forces cosmologists to question assumptions. Rather than taking initial conditions as given, it treats them as emergent. Rather than separating physics from observation, it acknowledges their entanglement. Hawking's goal was never to provide final answers, but to push the field toward deeper questions, and top-down cosmology achieved exactly that. Beyond top-down cosmology, Hawking's later work engaged with broader themes. He continued to refine arguments about information loss in black holes, eventually conceding that information may be preserved, but pressing on how this occurs in detail. He explored the role of holography in cosmology, speculated about the nature of fundamental laws, and popularized science in ways that brought cosmology into the cultural mainstream. His collaborations with students and colleagues ensured that his influence extended well beyond his own publications. The legacy of his ideas is not limited to the technical literature. Hawking exemplified how a scientist can balance rigor with imagination. He was unafraid to propose bold conjectures: chronology protection, no-boundary cosmology, top-down histories, even when evidence was incomplete. He saw science as a process where daring speculation, guided by mathematics, could open new horizons. Many of his proposals remain unproven, and some may ultimately be replaced, but their influence endures in the way they reframe questions. Existentially, Hawking's vision was one of continuity and self-containment. From imaginary time to top-down cosmology, his work suggested that the universe requires no external cause or boundary. It is a closed system, governed by laws that encompass its origin and fate. This perspective invites us to see ourselves not as separate from the cosmos, but as participants in its unfolding wave function. Our presence, our measurements, even our wonder, are part of the story the universe tells about itself. And as you sit with this thought, let it settle gently. The universe is vast, with histories branching and intertwining, yet it coheres into the world you experience here and now. You do not need to resolve every paradox or master every equation tonight. Just as Hawking sought calm clarity within the complexities of the cosmos, so can you. Let the day's noise recede. Breathe steadily. You are part of a universe that contains its own answers, and in that assurance, you can find rest. Drift into sleep, carried by the quiet certainty that the cosmos holds you within its timeless whole. Section 6. The Milky Way Explained: Structure, Sagittarius A, and Galactic Evolution. Chapter 1. What is the Milky Way? A quiet introduction to our galactic home. When you look up into a clear night sky, far from city lights, a faint, milky ribbon stretches across the darkness. For most of human history, no one truly knew what it was. To ancient eyes, it looked like a path of mist, perhaps a celestial river or trail of light left by the gods. The Greeks called it Galaxius Kyklos, the Milky Circle. And centuries later, the Latin name Via Lactea became our modern Milky Way. For millennia, this glowing band was thought to belong to the heavens themselves, not to be made of stars at all. Aristotle imagined it as the reflection of sunlight in the upper atmosphere. Only in the 17th century did Galileo's telescope reveal the truth. The Milky Way is made of countless stars, so distant and numerous that their light merges into a continuous glow. That discovery marked the first step toward understanding the galaxy we live in. Yet even with telescopes, the Milky Way remained mysterious. For hundreds of years, astronomers could not determine its true shape or size. It was only in the early 20th century that Jacobus Kapteyn and Harlow Shapley used measurements of star positions and brightness to map its structure. They found that the sun was not near the center, but rather in the outskirts of a vast, disc-shaped system. Later, radio and infrared observations revealed even more detail. Our galaxy is a barred spiral composed of stars, gas, dust, and invisible dark matter, all rotating together through interstellar space. The Milky Way's form is elegant and complex. At its heart lies a bright central bulge wrapped around a bar of stars. From this bar, spiral arms wind outward like glowing waves. Within those arms are clusters of young, hot stars and vast clouds of gas and dust, the raw material for new generations of suns. The entire disk is only a few thousand light-years thick, but more than 100,000 light-years across. Surrounding it all is a spherical halo containing ancient stars and globular clusters, remnants from the galaxy's earliest days. Beyond that lies an enormous, unseen halo of dark matter that exerts most of the galaxy's gravity. We cannot see this structure directly because we live inside it. From our position about halfway between the center and the outer rim, the Milky Way's disk surrounds us on all sides, and interstellar dust blocks much of the light. But astronomers have found ways to pierce the veil. Radio telescopes trace the glow of hydrogen gas that marks the spiral arms. Infrared observatories like the Spitzer Space Telescope see through the dust to the crowded stars near the core. And the European Space Agency's Gaia mission has mapped the precise positions and motions of more than 1 billion stars, transforming our understanding of the galaxy's shape and motion. Our solar system sits in a minor spur of one spiral arm, known as the Orion arm, between the Sagittarius and Perseus arms. The Sun orbits the galactic center roughly once every 230 million years, a single galactic year. Since its birth about 4.5 billion years ago, it has made only around 20 of those long revolutions. During that time, the galaxy around us has continued to evolve, as stars are born, live out their lives, and die, enriching interstellar space with heavier elements. At the Milky Way's center lies a region of immense power, a supermassive black hole called Sagittarius A star. Hidden behind clouds of dust, it contains about 4 million times the mass of the Sun. Stars near it move at enormous speeds, orbiting an invisible point that gives away the black hole's presence. Although it is mostly quiet today, occasionally it flares as gas and dust fall inward. Sagittarius A star anchors the galaxy's structure, its gravity shaping the orbits of stars throughout the central bulge. The Milky Way is not static. Stars orbit in graceful patterns. Gas clouds drift and collide, and spiral density waves ripple through the disk like gentle tides. Where gas becomes compressed, new stars ignite. Where stars die, supernovae scatter heavy elements into space. Over billions of years, this cycle of creation and destruction has forged every atom in our bodies. The oxygen we breathe, the calcium in our bones, the iron in our blood. In a very real sense, we are fragments of the Milky Way made conscious. The galaxy's history stretches back almost to the dawn of time. It formed about 13 billion years ago from smaller proto-galaxies that merged under gravity. Evidence of those ancient collisions remains today in the halo's old stars and in long, thin streams of stellar debris, the ghostly remnants of galaxies the Milky Way absorbed. Even now, the process continues. The Large and Small Magellanic Clouds, 2 small satellite galaxies visible from the southern hemisphere, are being slowly pulled apart by our galaxy's gravity. Their stars and gas are stretching into long arcs that wind around us. In the far future, perhaps 4 billion years from now, the Milky Way itself will collide with its great neighbor, the Andromeda Galaxy, merging into a single, larger system. From Earth, we see only a narrow slice of all this complexity. The Milky Way appears as a luminous band across the sky because we are looking along the plane of its disk, seeing layer upon layer of stars. When you look toward the constellation Sagittarius, you face the galactic center, where the density of stars is greatest. Looking toward Cygnus or Cassiopeia takes you outward toward the edges. Every point of light you see is part of the vast structure we inhabit, a glimpse from within of our home in space. Studying the Milky Way is an act of both science and humility. Because we cannot step outside it, astronomers reconstruct its shape through careful observation, measuring distances with parallax, tracing orbits, and modeling how gravity shapes motion. Modern surveys like Gaia have turned this once static picture into a living map, showing how stars stream, oscillate, and even ripple through the disk, echoes of past encounters. Each discovery reminds us that the galaxy is a dynamic system, not a fixed structure, but a constantly evolving one. The Milky Way is also a part of something greater. It belongs to a small family of galaxies called the Local Group, which includes Andromeda and dozens of smaller companions. Together, these galaxies move within an even larger web of cosmic structure, filaments and clusters stretching across the universe. From the largest scales to the smallest atoms, everything in the cosmos is connected by the same laws of physics and by the same cosmic history that began with the Big Bang. Our understanding of the Milky Way deepens every year. Astronomers now study magnetic fields threading through its disk, high-energy bubbles extending above and below the plane, and mysterious flows of dark matter that influence its evolution. Yet for all our measurements, the galaxy retains a quiet mystery. It is both knowable and beyond full comprehension, a reminder that the universe can be studied and yet still inspire awe. When you step outside on a clear night and see the Milky Way arching above you, you are seeing light that has traveled for tens of thousands of years. It left its stars long before human civilization began and crossed interstellar space to reach your eyes tonight. Every photon carries a fragment of the galaxy's story, its birth, its rotation, its endless renewal. You are part of that story, living briefly within a structure that has endured for billions of years. And now, as night deepens and the galaxy drifts overhead, you can let the thought settle quietly. The same gravity that binds its stars together binds you to the earth beneath your feet. The same atoms that once burned in distant suns are within you. The Milky Way is not somewhere far away. It is everything around you, the home that carries you through the endless dark. So breathe deeply, let go of the day, and rest under its calm, eternal light. Chapter 2. The structure of the galaxy, spiral arms, and the galactic disk. From a distance, the Milky Way would appear as a glowing spiral, a great pinwheel of stars suspended in the darkness of space. Its luminous arms curve gracefully outward from a bright central region, forming a structure at once orderly and chaotic. Yet from within, this vast design is almost invisible to us. Dust and distance blur its pattern into a diffuse haze. To piece together the true shape of our galaxy, astronomers have relied on decades of careful observation and inference, mapping what cannot be directly seen. The Milky Way is classified as a barred spiral galaxy, a designation confirmed through infrared observations that reveal a dense, elongated bar of stars at its center. From this bar emerge several spiral arms, which extend outward across the galactic disk. The disk itself is an immense rotating plane of stars, gas, and dust, spanning more than 100,000 light-years from edge to edge, but only a few thousand light-years thick. It is in this thin, luminous layer that most of the galaxy's visible stars reside. along with the complex interstellar medium that gives the Milky Way its form and vitality. The spiral arms are not rigid structures. They are regions of enhanced density, like standing waves in a sea of stars and gas. The stars within them are continually moving, passing in and out of the arms as they orbit the galactic center. The arms persist not because the same stars remain fixed there, but because density waves, slow-moving gravitational patterns, compress the interstellar medium as they rotate through the disk. This compression triggers new bursts of star formation. Hot, young, massive stars illuminate these regions with brilliant blue light, outlining the arms we see in distant galaxies and indirectly within our own. Our Milky Way contains several major arms. Closest to the center lies the Norma arm, followed by the Scutum Centaurus arm and the Sagittarius arm. Farther out are the Perseus arm and the outer arm. The solar system sits between two of these in a smaller feature known as the Orion Spur or the Orion Cygnus arm. This spur is a minor branch of the larger Sagittarius arm and contains many of the bright constellations visible in our night sky. Each arm is a vast region of gas, dust, and star clusters bound by gravity, yet constantly reshaped by the galactic rotation. The structure of the spiral pattern was first proposed in the mid-20th century, when radio astronomers began mapping the emission from neutral hydrogen gas. Hydrogen emits at a precise radio wavelength, and because radio waves penetrate interstellar dust, these observations allowed astronomers to see deep into the galaxy. By measuring the Doppler shifts of this emission, they determined the distribution of gas and inferred the existence of spiral arms. Later observations in carbon monoxide, a tracer of molecular clouds, provided an even clearer view of the regions where new stars form, confirming that the Milky Way's disk is organized into a majestic spiral pattern. At the center of the Milky Way lies the galactic bulge, a dense, roughly spherical concentration of older stars surrounding the supermassive black hole Sagittarius A star. The bulge transitions outward into the bar, a thick, elongated structure of stars and gas that stretches across tens of thousands of light years. This bar acts as a gravitational engine, funneling gas inward toward the center and outward into the spiral arms. The bar's presence influences the overall dynamics of the disk, helping to sustain the spiral density waves that organize the galaxy's structure. Beyond the spiral arms, the disk gradually thins into the galactic halo, a sparse, roughly spherical region containing ancient stars and globular clusters. While the halo represents the oldest part of the Milky Way, the disk is where the ongoing processes of star birth and death continually reshape the galaxy's appearance. Within the disk, massive clouds of gas collapse under gravity to form new stars. When those stars die in supernova explosions, they enrich the surrounding gas with heavier elements, which are later incorporated into new generations of stars and planets. Over cosmic timescales, this recycling has built up the chemical complexity that makes life possible. The vertical structure of the disk is as fascinating as its spiral form. Astronomers distinguish between a thin disk and a thick disk, two overlapping populations of stars with different ages and compositions. The thin disk contains younger stars, open clusters, and much of the interstellar gas and dust. It is where star formation is most active. The thick disk, extending farther above and below the galactic plane, contains older stars with fewer heavy elements, relics from the early history of the galaxy, likely formed when it was still merging with smaller protogalaxies. The existence of these two disks tells a story of gradual evolution. The Milky Way began as a chaotic assembly of gas clouds and smaller galaxies, which over time flattened and stabilized into the ordered, rotating disk we inhabit today. Rotation itself is a key to understanding the galaxy's structure. Every star and gas cloud orbits the galactic center, but not in the same way planets orbit the Sun. The outer parts of the galaxy rotate almost as fast as the inner regions, a phenomenon known as flat rotation. This observation was one of the earliest clues to the existence of dark matter, an unseen form of mass that dominates the galaxy's total gravitational pull. Without dark matter, the stars in the outer disk would not have enough gravity to keep them bound to the Milky Way. Their high orbital speeds would tear the galaxy apart. The persistence of the flat rotation curve implies that an enormous invisible halo of dark matter extends far beyond the visible disk, shaping its dynamics and holding it together. The disk itself is not perfectly smooth. It bends and ripples, warped like a vast sheet of fabric stirred by unseen winds. Surveys of distant stars and gas clouds have revealed that the Milky Way's outer regions curve upward on one side and downward on the other. This warp may have been caused by gravitational interactions with nearby satellite galaxies, such as the Magellanic Clouds, or by the uneven distribution of dark matter in the halo. The warp gives our galaxy a subtle, asymmetric shape, a reminder that even large cosmic systems are never entirely at rest. Within the spiral arms, star formation occurs in bursts. Dense molecular clouds collapse under their own gravity to form clusters of newborn stars. The most massive of these stars live fast and die young, their ultraviolet radiation and stellar winds blowing bubbles and cavities into the surrounding gas. When they explode as supernova, they trigger further waves of collapse, spreading star formation through the arm like a slow-moving flame. This process gives the Milky Way its patchwork of bright nebulae, glowing regions of ionized gas, and dark lanes of dust that obscure the starlight behind them. The interstellar medium within the disk is a complex mixture of gas, dust, and plasma, existing in several distinct phases: cold molecular clouds, warm atomic gas, and hot ionized regions created by stellar radiation. This mixture is far from uniform. It is constantly stirred by shock waves, magnetic fields, and turbulence on every scale. The interplay between these forces creates the structures we observe: filaments, shells, and cavities that make the galactic disk a living, dynamic environment. Modern astronomical surveys have transformed our understanding of the Milky Way's structure. Data from the Gaia spacecraft have mapped the positions and velocities of more than 1 billion stars, allowing scientists to reconstruct the galaxy's three-dimensional shape with unprecedented precision. These observations have revealed ripples in the disk, subtle vertical waves in the distribution of stars, possibly caused by ancient collisions with smaller galaxies. Other studies using infrared telescopes have confirmed the bar's orientation and the pattern of the spiral arms. Step by step, a coherent picture has emerged. The Milky Way is a rotating, self-sustaining system, shaped by gravity, motion, and time. From a cosmological perspective, the Milky Way's structure reflects a universal pattern. Spiral galaxies like ours make up the majority of large galaxies in the observable universe. Their disks form naturally as gas cools and settles into rotation within dark matter halos. The balance between gravity and angular momentum shapes them into flattened rotating systems with spiral patterns that arise from density waves. Though each galaxy is unique, the same physical principles govern them all. The Milky Way, in that sense, is both ordinary and extraordinary, a familiar example of the universe's artistry. For those living within it, the Milky Way's structure offers both a map and a metaphor. We occupy a small neighborhood within one of its minor arms, circling quietly as part of a vast gravitational dance. Every star you see in the night sky belongs to this same disk, each moving along its path in harmony with billions of others. The spiral arms, though invisible from the ground, define the great architecture that has shaped our cosmic environment for billions of years. If one could look upon the Milky Way from afar, perhaps from the perspective of an intergalactic traveler, it would appear serene, a swirl of light against the dark. Yet, within that calm exterior lies unending motion. The orbits of stars, the turbulence of gas, the pulse of radiation, and the slow evolution of form. What we call structure is, in truth, a balance between chaos and order, maintained across incomprehensible spans of time. When we reflect on this, a quiet realization emerges. The galaxy's spiral pattern, so vast it takes hundreds of millions of years to complete a single turn, is the setting of our entire history. Every life, every memory, every thought. We exist as part of a disk of stars that has endured for more than 10 billion years, held together by the same gravity that holds us to the Earth. To contemplate the structure of the Milky Way is to recognize our place in something enduring and immense. And as the galaxy turns, carrying us through the silent dark, there's a strange comfort in its permanence. The spiral arms will continue to wind, the disk will continue to spin, and the starlight will continue to flow long after our brief stories have ended. Beneath that endless motion, you are part of the pattern, a fleeting awareness born of the same forces that shape the stars. Chapter 3. The Heart of the Galaxy, the Supermassive Black Hole, Sagittarius A. At the very center of the Milky Way, hidden behind dense clouds of interstellar dust, lies a place where ordinary physics breaks down. It is a region of such immense gravity that nothing, not even light, can escape its grasp. This is Sagittarius A star, the supermassive black hole that anchors our galaxy. Although invisible, it shapes the motion of millions of stars, governs the dynamics of the galactic core, and serves as the quiet heart around which the Milky Way revolves. For centuries, the idea of a cosmic abyss was little more than a mathematical curiosity. When Albert Einstein formulated his general theory of relativity in the early 20th century, the equations suggested the possibility of points where gravity could become infinite. Karl Schwarzschild, working only months after Einstein's publication, derived a solution describing a perfectly spherical object with an escape velocity greater than the speed of light. Such an object, though purely theoretical at the time, would later be called a black hole. It took decades, however, for astronomers to accept that these extreme structures might actually exist. The Milky Way's central region was long thought to contain something massive and unseen. Observations in visible light were useless. The dense clouds of gas and dust in the galactic plane absorb nearly all optical radiation from the center. It was only with the development of infrared and radio astronomy that scientists could peer through the obscuring material. In the 1970s, powerful radio telescopes detected a compact, bright source of radio waves near the constellation Sagittarius, precisely at the galactic core. They named it Sagittarius A star. Over the following decades, increasingly precise measurements revealed something extraordinary. Stars near the center of the galaxy were moving at incredible speeds, some thousands of kilometers per second, in tight elliptical orbits around an invisible point. By tracking these orbits over many years, astronomers were able to calculate the mass of the object exerting such powerful gravitational influence. The result was astonishing. Roughly 4 million times the mass of the Sun, confined within a region no larger than our solar system. There was no known object that could fit those conditions except a black hole. The most compelling evidence came from long-term observations by two teams of astronomers, one led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics, and the other by Andrea Ghez at the University of California, Los Angeles. Using adaptive optics and interferometry, they tracked the motion of individual stars orbiting the galactic center over decades. One of these stars, called S2, moves so close to the center that it completes an orbit in just 16 years. A mere blink compared with the Sun's galactic circuit of hundreds of millions of years. The precise shape of its orbit confirmed Einstein's predictions of general relativity. The immense mass and compact size of the central object left no doubt. Sagittarius A star is a supermassive black hole. A black hole itself emits no light. What astronomers detect comes from the material around it, gas, dust, and occasionally entire stars that venture too close. As matter falls toward the event horizon, it accelerates and heats up, glowing intensely in X-rays and infrared radiation. This glowing region, known as the accretion disk, marks the boundary between the observable universe and the domain of gravity so strong that space and time fold inward. In the case of Sagittarius A star, the accretion disk is faint compared with those of more active black holes in distant galaxies. The Milky Way's central black hole is considered quiescent, feeding only sporadically on the trickle of gas and dust that drifts into its vicinity. Despite its quiet nature, Sagittarius A star occasionally flares. Infrared and X-ray observatories such as Chandra and the Very Large Telescope have recorded sudden bursts of radiation, brief but powerful flashes that last for minutes to hours. These are thought to occur when clumps of matter are caught in the black hole's gravitational whirlpool and heated to millions of degrees before disappearing beyond the event horizon. Though these flares reveal only fleeting glimpses of activity, they confirm that the black hole remains a living, dynamic engine at the heart of the galaxy. The region surrounding Sagittarius A star is a unique laboratory for studying the extreme conditions of physics. Within a few light years of the black hole lies a dense cluster of stars, many of them massive and short-lived. Their presence is somewhat paradoxical. Conditions near a black hole should be hostile to star formation, yet evidence suggests that stars continue to form there, possibly in dense rings of gas orbiting just beyond the reach of destruction. These stellar populations, along with the intricate orbits mapped by missions like Gaia and the Keck Observatory, allow scientists to test the predictions of general relativity in the most extreme gravitational environment accessible to observation. In 2019, the Event Horizon Telescope, a network of radio observatories spread across the Earth, captured the first direct image of a black hole's shadow in the galaxy Messier 87. 3 years later, the same collaboration produced an image of Sagittarius A star. The image showed a bright, ring-like structure of light surrounding a dark central region, the shadow of the event horizon, distorted by the intense warping of space-time. It was not a photograph in the conventional sense, but rather a reconstruction derived from global interferometry, translating faint radio signals into an image of what lies at the center of our galaxy. That ring, only about 60 million kilometers across, represents the final surface from which light can still escape before plunging into the black hole itself. What lies beyond the event horizon remains unknown. According to general relativity, the matter that falls into a black hole collapses to an infinitely dense point called a singularity, where the laws of physics as we know them cease to apply. Quantum theory, however, suggests that this picture is incomplete, that information and energy cannot be lost entirely. Reconciling these two frameworks is one of the deepest challenges in modern physics. Sagittarius A star, though small on cosmic scales, sits at the crossroads of these mysteries. It is a reminder that our understanding of the universe remains unfinished, even in the heart of our own galaxy. The black hole's influence extends far beyond its immediate surroundings. Although its gravitational pull dominates only the inner few light years, it shapes the dynamics of the entire galactic bulge and may help regulate star formation in the central regions. Evidence from other galaxies shows that supermassive black holes and their host galaxies evolved together, their masses growing in proportion over cosmic time. This suggests a profound connection. The processes that feed black holes also drive the formation of stars and the distribution of gas in galaxies. In this sense, Sagittarius A star is not merely a passive anchor, but an active participant in the Milky Way's evolution. Astronomers studying high-energy phenomena have also discovered vast structures extending from the galactic center, the so-called Fermi bubbles, enormous lobes of energetic gas, stretching tens of thousands of light-years above and below the galactic plane. These bubbles are believed to be relics of a past episode of intense activity, when Sagittarius A star may have accreted large amounts of matter and released powerful jets of radiation. Though dormant now, the black hole once blazed brightly, influencing the galaxy on scales far beyond its immediate reach. Despite its reputation as a cosmic monster, Sagittarius A star is not a threat to us. The solar system lies nearly 26,000 light-years away, safely beyond its gravitational influence. The light and radiation it emits are too faint to affect our planet. What it represents, rather than danger, is a window into the extreme nature of the universe, a living example of the balance between gravity, energy, and the limits of physical law. From a scientific perspective, the study of Sagittarius A star is a triumph of observation and theory. From the first radio detections to the detailed tracking of stellar orbits, each step has confirmed predictions of Einstein's equations with remarkable precision. The black hole's measured properties, its mass, spin, and event horizon match the theoretical expectations for a rotating Kerr black hole. Yet the closer we look, the more profound the questions become. What happens to information that crosses the horizon? Can gravity and quantum mechanics ever be unified into a single description? Could the singularity itself be something more complex than an infinitesimal point? While physicists debate these questions, Sagittarius A star continues its silent existence, shaping space and time without a sound. It is an object of perfect stillness and ultimate energy, where the geometry of the universe folds back upon itself. Around it, stars continue to orbit like dancers circling an unseen partner, each motion a testament to the invisible mass at the center. To contemplate this heart of darkness is to glimpse both the power and the humility of nature. Our galaxy, with all its spiral arms, stars, and planets, revolves around a point of nothingness, an emptiness that defines the whole. The Milky Way's beauty and stability arise paradoxically from a region where matter ceases to exist as we understand it. It is a reminder that creation and destruction are not opposites, but two faces of the same cosmic process. And perhaps that realization offers a kind of peace. The same gravity that holds the stars together also holds us, weaving everything into a single story that began long before we existed. Sagittarius A star, silent and invisible, is not only the heart of the galaxy, but a symbol of continuity. The balance between what can be known and what forever remains beyond the horizon. As you think of it, far away in the darkness, you might feel that quiet gravity too, drawing all things toward unity, reminding us that even in the vastness of space, we are part of something whole. Chapter 4. The Stars of the Milky Way, From Newborns to Dying Giants. The Milky Way is not merely a collection of stars scattered through space. It is a vast, living system where stars are constantly being born, aging, and dying. Within its disk and halo exist hundreds of billions of suns, each at a different point in its life cycle, each a luminous thread in the great tapestry of our galaxy. From cool red dwarfs that burn slowly for trillions of years to colossal blue giants that exhaust their fuel in only a few million, the stars of the Milky Way form the structure, chemistry, and destiny of our cosmic home. The story of every star begins in darkness. Deep within cold molecular clouds, enormous regions of gas and dust scattered through the galactic disk, gravity slowly draws matter together. Over thousands of years, the densest knots of gas collapse under their own weight, forming protostars surrounded by disks of dust. These regions are invisible in visible light, but glow in infrared, where observatories like the James Webb Space Telescope can peer through the obscuring dust. The Orion Nebula and the Eagle Nebula are famous examples. Stellar nurseries where young suns ignite and sculpt their surroundings with intense radiation. When the temperature at the core of a forming star becomes high enough, hydrogen nuclei begin to fuse into helium. This process releases vast amounts of energy, halting further collapse and creating a delicate balance between gravity pulling inward and radiation pushing outward. A true star is born. The newborn star settles onto what astronomers call the main sequence, a stable phase of life that can last millions to billions of years, depending on its mass. Most of the Milky Way's stars are small, dim red dwarfs. These low-mass stars burn hydrogen slowly and efficiently, their lifetimes measured not in billions but in trillions of years, far longer than the current age of the universe. They make up the quiet majority of our galaxy, unseen to the naked eye, but dominating by sheer number. Their faint light fills the galactic disk like a low, constant hum, sustaining the structure of the Milky Way through their collective gravity. At the other extreme are the massive blue and white stars, giants several tens of times heavier than the Sun. They live fast and die violently. Their cores burn at immense temperatures, fusing heavier and heavier elements in rapid succession. In just a few million years, these giants exhaust their fuel, collapse under their own weight, and explode as supernovae. Such explosions briefly outshine entire galaxies, dispersing the elements forged in their cores, carbon, oxygen, calcium, and iron, into the surrounding interstellar medium. Every atom of iron in your blood was once released by a supernova like these. Between these two extremes lie the sun-like stars, medium in mass and longevity. They spend most of their lives fusing hydrogen into helium in a steady rhythm. When their central hydrogen runs low, the balance between gravity and pressure falters. The core contracts while the outer layers expand, transforming the star into a red giant. In this stage, the star's outer atmosphere swells to enormous size, sometimes engulfing nearby planets. The sun will follow this path in about 5 billion years, eventually shedding its outer layers into space to form a glowing planetary nebula. The remaining core will cool into a white dwarf. The dense remnant, roughly the size of Earth, but containing half the sun's mass, glowing faintly as it radiates away its stored heat over billions of years. The diversity of stars within the Milky Way reflects the galaxy's long and complex history. The oldest stars, found in the halo and globular clusters, are poor in heavy elements. These ancient suns formed soon after the galaxy itself was born, before successive generations of supernovae enriched the interstellar medium with metals. They are fossils of the early universe, their composition a record of the Milky Way's first epoch of star formation. In contrast, stars in the thin disk, including the Sun, are metal-rich, having formed from gas already seeded with the products of countless previous stars. This gradient in metallicity allows astronomers to trace the timeline of galactic evolution, reading it like tree rings written in starlight. Star clusters are another window into the structure and history of the Milky Way. Open clusters, such as the Pleiades, contain hundreds of young stars born from the same cloud. Their ages can be measured precisely, making them invaluable for calibrating models of stellar evolution. Globular clusters, by contrast, are densely packed spheres of hundreds of thousands of very old stars, orbiting far above and below the galactic disk. They are among the oldest surviving structures in the galaxy, remnants of the Milky Way's early assembly. Stars are not evenly distributed throughout the Milky Way. They are concentrated in the spiral arms, where density waves compress gas clouds and trigger bursts of star formation. Within these regions, massive stars form in clusters, light up the surrounding nebulae, and then die young, often before they have drifted far from their birthplaces. Their deaths enrich the nearby gas, and the cycle begins anew. Meanwhile, the older stars gradually drift out of the arms into the more diffuse background of the disk. The entire galaxy is thus engaged in a constant process of renewal, recycling its material through countless stellar generations. The physics of a star's life and death is governed by its mass. Mass determines the balance of gravity and pressure, the rate of nuclear fusion, the lifetime, and the manner of death. Low-mass stars end quietly as white dwarfs. Massive ones collapse to neutron stars or black holes. Neutron stars, the remnants of particularly massive explosions, are among the densest objects in the universe, composed almost entirely of neutrons packed into a sphere barely 20 kilometers across. Some of them spin rapidly, emitting beams of radiation like cosmic lighthouses known as pulsars. Others merge in cataclysmic collisions that generate gravitational waves and forge the heaviest elements, such as gold and platinum. The interplay between stellar birth and death defines the Milky Way's evolution. Each generation of stars alters the chemical and physical state of the interstellar medium, setting the conditions for the next. The galaxy's current star formation rate is estimated at about 1 or 2 solar masses per year, a steady pace that maintains its luminous population without exhausting its gas too quickly. This balance between consumption and renewal has persisted for billions of years, giving rise to the rich and varied stellar ecosystem we observe today. Advances in observational astronomy have deepened our understanding of this process. Space telescopes such as Hubble and James Webb allow astronomers to observe stellar nurseries in exquisite detail, revealing how dust grains clump into protostellar disks and how jets of plasma erupt from newborn stars. Meanwhile, surveys from missions like Gaia have mapped the motions of stars across the galaxy, uncovering streams and clusters that hint at past mergers and migrations. Through these data, the Milky Way emerges not as a static collection of stars, but as a dynamic, self-renewing organism on cosmic scales. Stars also serve as cosmic clocks. By analyzing their light, its color, brightness, and spectral lines, scientists can determine their age, composition, and distance. The Hertzsprung-Russell diagram, which plots stars by temperature and luminosity, provides a universal framework for understanding stellar evolution. It shows that the life of every star follows predictable paths dictated by physics, from the moment of ignition to the final fade into darkness. The same laws apply to all stars, from the smallest red dwarfs to the brightest supergiants, linking the Milky Way's billions of suns through a single underlying order. Yet for all this order, there remains something deeply human about the light of the stars. Every photon that reaches us carries information about its source, the temperature, motion, and history of the star that emitted it. When that light enters your eyes, you are, in a sense, touching the past. The glow of Vega left that star more than 2 decades ago. The shimmer of Deneb began its journey more than 1,000 years earlier. The night sky is not a fixed dome, but a time machine, showing us the Milky Way as it was across different epochs of history. Beyond their physical properties, stars have also been mirrors for human thought. For ancient civilizations, they served as calendars and guides. For modern science, they are laboratories of matter and energy. But their deeper significance lies in what they reveal about our origins. Every element essential for life, carbon, nitrogen, oxygen, and iron, was born in stars and scattered across space. When you look at the Milky Way, you are seeing not only distant suns, but also the source of your own existence. The same nuclear reactions that burn in those stars once forged the materials of your body, and in the grand cycle of time, those materials will one day return to the galaxy. The atoms that compose you will be dispersed again, perhaps drawn into new clouds, new stars, new worlds. The Milky Way is a vast, continuous act of creation, in which every ending feeds another beginning. Its stars are the rhythm of that cosmic heartbeat, pulsing in light and silence across the ages. So as you look at the sky, at the faint shimmer that stretches from horizon to horizon, remember that you are part of it. The same forces that ignite stars also shape you. The same elements that glow in their hearts flow in your veins. The stars of the Milky Way are not distant strangers but ancient relatives, bound to you through time and matter. Their births and deaths are your story, written on a scale too large to imagine, yet close enough to feel in every breath. The galaxy's stars remind us that existence is a cycle, not a line. Every atom that shines, burns, or fades is part of a greater pattern. The endless transformation of energy into form and form back into energy. The Milky Way itself, for all its grandeur, is just one chapter in that ongoing story. and within it you are a brief flicker of awareness, a momentary spark reflecting the light of billions of suns. To understand the stars is to glimpse that quiet truth, that you, too, are a way for the universe to look back at itself and see that it shines. Chapter 5. The Galactic Ecosystem, Gas, Dust, and the Birth of New Stars. Between the stars of the Milky Way lies an ocean of invisible material, a delicate mixture of gas, dust, and plasma known as the interstellar medium. Though tenuous by earthly standards, this medium is the raw material from which stars and planets form, and it is the thread that connects every generation of celestial bodies. The Milky Way is not simply a static collection of stars. It is an evolving ecosystem, where the death of old stars enriches the medium and the birth of new ones continues the cycle of creation. The interstellar medium is composed primarily of hydrogen and helium, the simplest and most abundant elements in the universe. But mixed within this gas are traces of heavier elements, carbon, oxygen, silicon, and iron, forged in the hearts of dying stars and distributed through space by supernova explosions. These elements condense into microscopic dust grains that drift through the galactic disk, absorbing and scattering light. It is this dust that gives the Milky Way its dark lanes and obscuring clouds, shaping what we can and cannot see. Although the average density of the interstellar medium is far lower than the best vacuum on Earth, its vast volume means it contains a tremendous amount of mass, roughly 15% of the visible matter in the galaxy. It is structured not as a uniform mist, but as a complex network of clouds, filaments, and bubbles, all in motion. These structures form, dissipate, and reform over millions of years under the influence of gravity, magnetic fields, and stellar feedback. The most important regions of this galactic ecosystem are the molecular clouds. These are cold, dense concentrations of gas and dust, where temperatures fall to just a few tens of degrees above absolute zero. Under such conditions, hydrogen atoms bind together to form molecular hydrogen, the most basic building block of star formation. Within these clouds, gravity begins its quiet work. Tiny fluctuations in density cause certain regions to collapse, drawing in more material as they do. Eventually, these collapsing pockets become protostars, the seeds of future suns. Astronomers map these molecular clouds using radio telescopes, since visible light cannot penetrate their thick dust. The emission from carbon monoxide molecules, in particular, provides a reliable tracer of their structure. Observations of regions such as the Orion molecular cloud reveal a dynamic environment where turbulent gas streams and shock waves from nearby stars sculpt the clouds into intricate shapes. These regions are often several light-years across and contain enough material to form thousands of stars. The process of star formation is slow and inefficient. Most of the gas in a molecular cloud never becomes a star. Instead, stellar winds, radiation pressure, and supernova explosions from nearby massive stars disrupt the cloud before it can fully collapse. Yet these same forces also play a creative role, compressing other regions of gas and triggering new waves of star formation. In this way, the death of one generation of stars can give birth to the next. The Milky Way continually recycles its material, maintaining a delicate balance between destruction and renewal. This balance can be seen in the life cycle of the interstellar medium itself. Hot ionized gas from supernova remnants expands into the surrounding space, creating vast bubbles that sweep up cooler material into dense shells. Over time, these shells cool and fragment into molecular clouds, where new stars ignite, releasing radiation that heats and stirs the surrounding gas once again. The result is a galactic web of feedback loops, where every phase of matter influences the others. The galaxy is, in essence, a self-regulating ecosystem, operating on scales of light years and millions of years. Dust, though it makes up only a tiny fraction of the mass, plays an essential role in this ecosystem. It provides the surfaces on which molecules can form, shields the interiors of clouds from destructive ultraviolet radiation, and determines how starlight is absorbed and re-emitted across the spectrum. Infrared observations have revealed vast networks of dust filaments tracing the magnetic fields of the galaxy, showing that even the smallest particles contribute to the Milky Way's structure and energy balance. Without dust, the chemistry that leads to complex molecules and eventually to life could not occur. The Milky Way's spiral arms act as engines driving this cycle. As density waves sweep through the galactic disk, they compress gas clouds, initiating new rounds of star formation. In these regions, bright clusters of young, massive stars illuminate nearby nebulae, such as the Carina and Eagle nebulae, turning cold gas into radiant clouds of ionized hydrogen. The light from these stellar nurseries can travel thousands of light years, marking the spiral arms as bands of blue and pink that define the galaxy's graceful form. Not all interstellar gas remains within the plane of the disk. Powerful supernovae and stellar winds can push material into the galactic halo, forming what astronomers call galactic fountains. The hot gas rises far above the disk, cools as it radiates energy, and eventually falls back, raining fresh material onto the galaxy. This circulation helps maintain the Milky Way's supply of star-forming gas over cosmic timescales, linking the visible disk with the more diffuse environment that surrounds it. At larger scales, the Milky Way also interacts with the intergalactic medium, the thin gas that fills the space between galaxies. Observations from the Hubble Space Telescope and other observatories have revealed extended halos of gas around the Milky Way and its neighbors, stretching for hundreds of thousands of light years. These halos serve as both reservoirs and regulators, storing gas that may one day cool and return to the disk. The boundaries between the Milky Way and its environment are therefore porous, blurring the distinction between galaxy and cosmos. The chemical evolution of this galactic ecosystem is equally fascinating. Each generation of stars enriches the interstellar medium with new elements. The first stars, massive, short-lived giants formed shortly after the Big Bang, contained almost no metals. Their violent deaths seeded the early universe with carbon, oxygen, and other elements, enabling subsequent generations of stars to form planets and eventually life. In the Milky Way today, the metallicity of the gas varies from one region to another, reflecting the history of enrichment and mixing across billions of years. This distribution allows astronomers to trace how the galaxy has grown and evolved through mergers and accretion events. Understanding the interstellar medium is also essential for understanding the conditions that lead to habitable worlds. Planets form within the dusty disks surrounding young stars, and the composition of that dust determines what materials are available for building solid worlds and organic molecules. The carbon-to-oxygen ratio in the gas, the abundance of water and silicates, and the prevalence of heavy elements all influence the types of planets that emerge. Thus, the chemistry of the galaxy's gas and dust sets the stage for the potential of life itself. Modern astronomy continues to refine this picture with unprecedented detail. Radio arrays such as ALMA in Chile reveal the fine structure of molecular clouds and the earliest stages of star formation. Infrared and submillimeter observations trace the distribution of dust and the glow of warm gas, while X-ray telescopes detect the hot plasma left by supernova explosions. Together, these instruments show that the Milky Way is an interconnected system where energy flows from stars into space and back again in endless cycles. Despite its vastness, the interstellar medium operates under universal physical laws. The same processes that shape the Milky Way occur in countless other galaxies across the universe. Yet from our position within this one, we can observe the details of how those processes work, how gravity, turbulence, and radiation interact to turn chaos into order, darkness into light. Every nebula, every glowing cloud, every faint wisp of dust is part of this grand transformation. To grasp the galactic ecosystem is to recognize that the Milky Way is alive in a metaphorical sense. It breathes through cycles of creation and destruction, nourishes itself through the recycling of matter, and evolves as its components exchange energy and mass. The light of the stars, the coldness of the clouds, and the silence between them are all part of one continuous process, unfolding on a time scale that dwarfs human existence. And yet, within that vast process, there is intimacy. The oxygen in your lungs and the carbon in your cells were once part of the interstellar medium, atoms that drifted through the galaxy for billions of years before becoming part of you. When you exhale, those same atoms will return to the air and eventually to the cosmos. The cycle continues, unbroken. You are part of the Milky Way's ecosystem as surely as the stars and clouds are. Perhaps that is the quiet lesson of the galaxy's dust and gas, that life itself is not separate from the universe, but a natural extension of it. The same physical laws that govern the birth of stars also govern the chemistry of your body. The same hydrogen that collapses to form suns flows through your veins as water. You are, in a very real sense, the galaxy made conscious, a fleeting awareness within a process that has no beginning or end. The Milky Way's ecosystem is therefore more than an astronomical phenomenon. It is a reflection of continuity, of connection across scales so vast that they dissolve the boundaries between the cosmic and the personal. To study the gas and dust between the stars is to study the origin of everything familiar, the atoms of our planet, our breath, our thoughts. When you look up at the hazy glow of the Milky Way, remember that its light and your life are drawn from the same source, woven from the same ancient matter. And in that realization, there is a kind of peace, the knowledge that nothing in the universe is truly isolated, that all things, even we, are part of one continuous exchange of energy, endlessly returning to the stars. Chapter 6. Our Place in the Galaxy, the Solar System's Journey Through Space. The solar system is not fixed in the cosmos. It moves, carried through the Milky Way as part of a vast gravitational dance. Every star you see in the night sky, every cloud of gas or trace of dust is taking part in this same motion, orbiting the galactic center in a rhythm that has endured for billions of years. Our sun, with its family of planets, is one of hundreds of billions of travelers following ancient, curved paths through space. The sun resides in a quiet region of the Milky Way known as the Orion Spur, a minor branch located between two major spiral arms, the Sagittarius arm and the Perseus arm. From this position, about halfway between the center of the galaxy and its outer edge, the Sun orbits around the Milky Way's core. The distance is immense, and one complete orbit takes roughly 230 million years, what astronomers call a galactic year. Since its formation, the Sun has made only about 20 such revolutions. This orbit is not a perfect circle, nor does it lie flat. The solar system moves in a gentle wave, bobbing above and below the galactic plane over tens of millions of years. These oscillations are caused by the gravitational pull of the Milky Way's disk, made up of stars, gas, and dark matter. Like a pebble rolling in a shallow bowl, the Sun is continually drawn back toward the galactic midplane. This motion, subtle and slow, is part of the broader gravitational choreography that gives the Milky Way its balance and shape. As it travels, the Sun carries with it all of its planets, comets, and asteroids, an entourage bound together by the same gravity that keeps Earth in orbit. Together, we race through space at hundreds of kilometers per second, though from our vantage point on Earth, that motion is imperceptible. The stars appear still because of their great distances, but they too are moving, each following its own orbit around the galactic center. Over the course of millions of years, constellations change shape, and familiar patterns in the sky fade and reform as the galaxy slowly turns. Our solar system is currently embedded in a region of space known as the local bubble, a cavity of thin, hot gas that stretches for roughly 1,000 light years. This bubble was carved by a chain of ancient supernova explosions that swept away denser interstellar gas. Within this zone, the solar system drifts through a relatively calm environment, protected by the Sun's own magnetic field and the solar wind, a steady stream of charged particles that creates the heliosphere. The heliosphere acts as a vast shield, deflecting much of the cosmic radiation that flows through the galaxy. At its farthest edge lies the heliopause, the true boundary where the Sun's influence ends and interstellar space begins. The Voyager spacecraft have crossed that frontier, becoming humanity's first emissaries beyond the Sun's protective bubble. The path the solar system follows through the Milky Way is not constant. As it orbits the galactic center, it occasionally passes through regions of higher stellar density, spiral arms filled with young stars and gas clouds, and then emerges into quieter interarm zones. These encounters can have subtle but lasting effects. When the Sun moves through dense molecular clouds or passes near supernova remnants, the increase in cosmic rays could influence the solar system's outer regions or even the Earth's atmosphere. Though such events occur over immense timescales, they are reminders that our planetary system is part of a larger, dynamic environment. The Sun's current neighborhood consists of stars that share similar galactic orbits. This region is called the local stellar neighborhood, containing familiar systems like Alpha Centauri, Sirius, and Barnard Star. But these companions are temporary. Over millions of years, as each star moves along its own orbit, our neighbors will change. The Sun's path through the galaxy continually reshapes its surroundings, ensuring that the sky above Earth is never truly the same from one cosmic epoch to the next. At the center of our journey lies Sagittarius A star, the supermassive black hole that anchors the Milky Way. Though its gravity exerts little direct pull on the Sun compared to nearby stars, it defines the structure of the entire galaxy. The Sun's orbit, like those of all other stars, is ultimately a response to the deep gravitational well at the galactic core. Every turn we make through the galaxy is part of the same vast rotation governed by that invisible center, where gravity bends space and time into harmony. From our vantage point, we cannot see the full spiral of the Milky Way, only a cross-section of its disk stretching across the night sky. Yet our position is a fortunate one. Closer to the center, the environment is far more hazardous, crowded with stars and intense radiation. Farther out, there would be fewer heavy elements, the materials needed for rocky planets and life. The Sun's orbit through this relatively calm and metal-rich region has likely provided the stability necessary for life to emerge and endure on Earth. The motion of the solar system also reveals itself through the cosmic microwave background, the faint afterglow of the Big Bang that fills the universe. By measuring slight shifts in that radiation, astronomers can determine our velocity relative to the rest of the cosmos. These observations confirm that not only are we orbiting within the Milky Way, but the galaxy itself is in motion, drawn toward neighboring galaxies in the local group and, on even larger scales, flowing toward clusters of galaxies that shape the structure of the universe. Every object, from the smallest moon to the largest supercluster, participates in this grand movement, all bound by gravity's unbroken web. The solar system's galactic journey has unfolded for billions of years and will continue for billions more. Long after the human species has passed, long after the sun expands into a red giant and then cools into a white dwarf, the remnants of our system will keep circling the Milky Way, completing orbit after orbit in silence. Even as the galaxy itself evolves, merging one day with Andromeda to form a new, larger galaxy, the fragments of our home will still be moving through the same gravitational dance that began when the Milky Way was young. To recognize our motion through the galaxy is to change how we see ourselves. We live our daily lives on a planet that spins around its axis and orbits the sun. But those motions are nested within even greater ones, the solar system orbiting the galactic center, the galaxy itself flowing through the cosmic web. Every moment of stillness we feel is an illusion created by scale. Beneath that calm, we are always moving, carried by currents of space and time too vast to perceive directly. The knowledge that we are travelers within the Milky Way can feel both humbling and profound. Our lives, measured in years, unfold within a galactic orbit measured in hundreds of millions. Yet within that brief instant, consciousness has arisen, capable of understanding the motion of its own home, of mapping the invisible paths of stars, of looking outward and realizing that it too belongs to the great rotation. When you look up at the Milky Way on a clear night, you are seeing the trail of your journey, the luminous band that marks the disk through which you travel. Each point of light is a fellow voyager, another sun caught in the same flow. The galaxy turns slowly, steadily, with a grace that feels eternal. And though your time within it is brief, you are part of that movement, bound to the stars by the same force that shapes them. In that thought, there is a quiet comfort. You are not still, not separate, but part of an endless voyage that began long before you and will continue long after. The earth beneath you spins, the sun carries you through the Milky Way, the galaxy itself drifts through the universe. All motion, all time, all existence are one continuous current. And somewhere within that current, small, luminous, and aware, you are moving too. Chapter 7. The Hidden Halo, Dark Matter and the Galaxy's Invisible Mass. The Milky Way, for all its luminous beauty, is not what it seems. The glowing spiral of stars that we see in the night sky represents only a small fraction of what truly exists. Surrounding our galaxy is an enormous invisible structure known as the dark matter halo, a vast, roughly spherical region of unseen mass that extends far beyond the visible disk. It is this halo, rather than the stars or gas, that provides most of the galaxy's gravitational strength. Without it, the Milky Way would not hold together. Its stars would drift apart into the emptiness of intergalactic space. Dark matter is one of the deepest mysteries in modern astrophysics. It neither emits nor absorbs light, making it undetectable through ordinary telescopes. Yet its presence is revealed through its gravitational effects. The first hints of this hidden mass appeared nearly a century ago, when astronomers began to measure how galaxies rotate. In the 1930s, Fritz Zwicky studied the Coma cluster of galaxies and found that the galaxies within it were moving too fast to be held together by the gravity of their visible stars. He concluded that some unseen material must provide additional mass, dunkle materie, or dark matter. Decades later, astronomer Vera Rubin and her collaborator Kent Ford extended this discovery to individual galaxies. By measuring how quickly stars and gas clouds orbited in the outer regions of spiral galaxies, Rubin found something astonishing. Instead of slowing down with distance from the center, as expected if most of the mass were concentrated in the visible stars, the rotation speeds remained nearly constant. The outer regions were moving far too fast to be explained by visible matter alone. The logical conclusion was that each galaxy was embedded in a massive halo of invisible material, extending far beyond its luminous disk. The Milky Way follows this same pattern. Observations of stellar motions, globular clusters, and satellite galaxies all indicate that the visible mass, the stars, planets, gas, and dust, accounts for only a small portion of the galaxy's total weight. The rest, perhaps more than 80%, is dark matter. This invisible halo stretches out to at least several 100,000 light-years, enveloping not only the disk, but also the Milky Way satellite galaxies, such as the Magellanic Clouds. Though unseen, it defines the very shape and stability of our galaxy. The evidence for dark matter comes from several independent sources. The motions of stars in the Milky Way's halo and of satellite galaxies orbiting the Milky Way can be measured with precision using instruments like the Gaia spacecraft. These measurements show that the outermost stars move at speeds that cannot be sustained unless a vast amount of mass lies beyond what we can see. Gravitational lensing, the bending of light from distant objects by the gravity of intervening matter, provides further confirmation. When astronomers measure the distortion of light from background galaxies, they can map the distribution of mass along the line of sight. These maps consistently reveal far more mass than is visible, both in our own galaxy and throughout the universe. Despite the strength of this evidence, the nature of dark matter remains unknown. It is not made of ordinary atoms, which interact with light and other forms of electromagnetic radiation. Instead, dark matter interacts primarily through gravity and possibly through the weak nuclear force. The leading candidates are hypothetical particles such as WIMPs, weakly interacting massive particles, or axions, ultralight particles predicted by some extensions of quantum field theory. Other possibilities include sterile neutrinos or even more exotic constructs like primordial black holes formed in the early universe. Yet, despite decades of experiments, no direct detection of dark matter has been confirmed. Physicists have built sensitive detectors buried deep underground, shielded from cosmic rays, in hopes of capturing the faintest interactions between dark matter particles and ordinary matter. They have searched for telltale signals in space, such as gamma rays produced by dark matter annihilations. So far, the results remain tantalizing but inconclusive. Dark matter continues to elude direct observation, hiding in the vast spaces between stars, shaping the cosmos from the shadows. In the Milky Way, the dark matter halo determines much of the galaxy's large-scale structure and evolution. It provides the gravitational framework in which the visible components, stars, gas, and dust, reside. The spiral disk, the bulge, the satellite galaxies, even the paths of intergalactic streams of gas, all move within the deeper gravitational field of the halo. Computer simulations of galaxy formation show that dark matter was the first ingredient to collapse after the Big Bang. As the universe cooled, tiny fluctuations in density grew under gravity, forming halos of dark matter that acted as gravitational wells. Into these wells, ordinary matter fell, forming the first stars and galaxies. In this way, dark matter shaped the cosmic architecture itself. Without it, the universe would look very different, diffuse, structureless, unable to form the rich web of galaxies we see today. In the case of the Milky Way, its halo likely began forming more than 13 billion years ago, gathering gas and smaller halos through mergers and accretion. The visible galaxy we now inhabit, the disk with its spiral arms, the central bulge, and the bright clusters, condensed later within that pre-existing halo of invisible matter. Even today, the Milky Way continues to grow by consuming smaller galaxies, their stars and dark matter streams merging seamlessly into the greater whole. One of the most fascinating aspects of the halo is its possible substructure. Simulations predict that it should contain thousands of smaller clumps, or subhalos, relics of the galaxy's assembly history. Some of these subhalos may host the Milky Way's dwarf satellite galaxies, while others remain completely dark, containing no stars at all. Astronomers search for their gravitational fingerprints by looking for tiny distortions in stellar streams, trails of stars left behind by disrupted clusters or galaxies. These subtle patterns provide clues to the otherwise invisible scaffolding of dark matter that surrounds us. The shape of the Milky Way's dark matter halo is another subject of ongoing research. While early models assumed it to be spherical, more recent studies suggest it may be elongated or slightly flattened, reflecting the complex interactions between the halo and the rotating disk of the galaxy. Understanding its exact shape and density profile is crucial, not only for mapping the Milky Way's mass, but also for refining models of dark matter behavior and the nature of gravity itself. Although dark matter does not emit light, it indirectly influences the luminous parts of the galaxy. Its gravity governs the rotation speed of stars, stabilizes the disk against disruption, and shapes the orbits of satellite galaxies. It even affects the distribution of interstellar gas, helping to maintain the spiral structure by providing an underlying gravitational anchor. In this sense, dark matter is not just a background component. It is the silent framework that makes the Milky Way possible. And yet, despite its dominance, we are effectively blind to it. We live inside the halo, but cannot perceive it. It surrounds us like an invisible ocean, extending hundreds of thousands of light years in every direction. Every atom on Earth, every photon of sunlight, every visible star, all exist within this unseen realm. It is a humbling reminder that what we can observe directly represents only a small fraction of reality. For cosmologists, the dark matter problem is both scientific and philosophical. It challenges our understanding of what the universe is made of. We can describe its gravitational influence with precision, but we do not yet know what it is. It could consist of particles beyond the standard model of physics, or it could hint at a deeper modification to the laws of gravity themselves. Whatever the answer, solving the mystery of dark matter will reshape our understanding of both the universe and our place within it. From an existential perspective, the dark matter halo invites reflection on the limits of perception. Most of the matter that shapes our galaxy is invisible and perhaps forever beyond direct detection. Yet, without it, we would not exist. The sun's orbit, Earth's stability, even the structure of the night sky depend on this unseen mass. The fact that so much of reality is hidden from our senses is not a flaw in our understanding, but an inherent feature of existence. The universe has depth far beyond what light alone can reveal. Perhaps there is something poetic in that. We live inside a galaxy illuminated by billions of stars, yet most of its substance is dark. We are creatures of light, built from the luminous matter of stars, but we are sustained within a framework of shadow. The visible and the invisible coexist, each giving the other meaning. The Milky Way's shining disk floats within an unseen halo, just as consciousness itself floats within the vast unknown of the universe. When you look up at the night sky, every glimmer you see is surrounded by a darkness that is not emptiness but structure. An invisible architecture holding everything together. The stars, like thoughts, are only the visible expression of something deeper and unseen. To understand the Milky Way's halo is to realize that the cosmos is built as much from mystery as from matter. And in that mystery, there is a quiet reassurance. We are part of a universe that is far larger, richer, and more intricate than our senses can grasp. The same unseen gravity that binds the stars also holds us, keeping our fragile world in orbit within an invisible sea. The dark matter halo reminds us that even when we cannot see the forces shaping our path, they are there, silent, enduring, and vast. Chapter 8. Companions and Neighbors, the Local Group and Satellite Galaxies. The Milky Way, magnificent as it appears in isolation, does not exist alone in the universe. Like every great structure in the cosmos, it is part of a community, a small cluster of galaxies bound together by gravity, known as the local group. This family of galaxies, though modest compared to the immense clusters scattered across the universe, defines our cosmic neighborhood. It shapes the Milky Way's motion, its evolution, and its future. To understand our galaxy fully, one must see it as part of this wider network, where interactions between galaxies are as vital to their growth as the stars within them. The local group contains more than 50 galaxies, though only a handful are large enough to be easily visible through telescopes. At its core are three dominant members: the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. These three spiral systems hold most of the group's mass, while the rest are smaller dwarf galaxies, faint, irregular, or spheroidal systems that orbit the larger ones like moons around planets. The entire local group spans roughly 10 million light-years across and is held together by mutual gravitational attraction, drifting as a unit through the larger cosmic web. The most significant of our galactic companions is the Andromeda Galaxy, also known as Messier 31. It lies about 2.5 million light-years from us and is the closest spiral galaxy comparable in size to the Milky Way. Andromeda is slightly more massive, containing hundreds of billions of stars, a similar spiral structure, and its own family of satellites. Observations show that it is moving toward us at a speed of several hundred kilometers per second. Far from being a static neighbor, Andromeda and the Milky Way are on a collision course, a slow cosmic dance that will culminate in their merger several billion years from now. When these two galaxies finally meet, their stars will not collide directly, as the spaces between them are vast. Instead, their mutual gravity will warp and stretch their disks, flinging long tidal streams of stars into space. Over time, they will merge into a single, larger elliptical galaxy, sometimes referred to as Milky Way by astronomers. The central black holes of both galaxies will spiral toward one another and eventually coalesce, releasing enormous amounts of energy in gravitational waves. This future merger, though far beyond human timescales, is a natural part of galactic evolution and a reminder that even on cosmic scales, nothing remains unchanged forever. The third major member of the local group, the Triangulum Galaxy, is smaller and less massive than the Milky Way and Andromeda, but still an impressive system of its own. It appears to be gravitationally linked to Andromeda and may be orbiting it in a loose association. The interactions between these three galaxies, Milky Way, Andromeda, and Triangulum, define the local group's central gravitational structure, influencing the motions of the many smaller galaxies that surround them. Orbiting the Milky Way itself is a retinue of dwarf galaxies, our immediate companions. The most prominent of these are the Large and Small Magellanic Clouds, visible to the naked eye from the southern hemisphere. These irregular dwarf galaxies are located about 160,000 and 200,000 light-years away, respectively, and are bound to the Milky Way by gravity. They are not static satellites, but are actively interacting with our galaxy, leaving behind a long stream of gas known as the Magellanic Stream, which stretches across much of the southern sky. This stream, composed of hydrogen gas, stripped from the dwarfs by gravitational forces, and the Milky Way's halo, may one day provide raw material for new star formation in our galaxy. The Magellanic Clouds are also notable for their internal activity. They contain vigorous regions of star formation, particularly the Tarantula Nebula in the Large Magellanic Cloud, one of the most active stellar nurseries in the local group. These galaxies are reminders that smaller systems can be dynamic and creative, not mere appendages to larger ones. Their ongoing interaction with the Milky Way provides astronomers with a real-time laboratory for studying how galaxies exchange gas and stars, and how larger galaxies grow by consuming smaller ones. Beyond the Magellanic Clouds lie other, fainter satellites, such as the Sagittarius dwarf spheroidal galaxy, currently being torn apart by the Milky Way's gravity. Its stars form a long, looping stream encircling our galaxy, evidence of a merger already in progress. Several other small dwarf spheroidals, including the Sculptor, Draco, and Fornax galaxies, follow similar fates. They orbit our galaxy at varying distances, gradually losing stars and gas as they spiral inward. These interactions are a normal part of galactic evolution. The Milky Way's halo, the vast, faint sphere surrounding the visible disk, is partly built from the remains of such ancient mergers. Every large galaxy bears these scars, remnants of smaller systems that were absorbed over billions of years. The local group itself is part of a larger structure known as the local sheet, which in turn belongs to the Virgo supercluster, a vast assembly of galaxy groups and clusters bound by gravity on an even greater scale. Yet, despite these immense surroundings, the local group maintains its distinct identity. Within its boundaries, the gravitational pull of its major galaxies dominates, shaping the motions of all its members. The Milky Way and Andromeda sit at the group's center of mass, pulling their smaller companions into orbits that trace the slow, intricate choreography of the group's collective motion. Astronomers have learned much about the local group through careful observation and measurement. Using the Hubble Space Telescope and more recently the Gaia mission, they have tracked the motions of individual stars and galaxies with unprecedented precision. These measurements reveal that the local group is not static, but gradually collapsing under its own gravity. Eventually, the Milky Way and Andromeda will merge to form the core of a new, larger galaxy, while many of the smaller dwarfs will either be absorbed or flung outward into intergalactic space. The local group, like everything else in the universe, is a dynamic system evolving over cosmic time. The study of dwarf galaxies within the local group has also shed light on one of the great mysteries of modern cosmology, the nature of dark matter. Dwarf spheroidal galaxies, though faint and small, appear to contain enormous amounts of dark matter relative to their visible stars. Their slow rotation speeds and gravitational binding require far more mass than what can be accounted for by luminous matter alone. These small galaxies thus serve as natural laboratories for understanding how dark matter behaves on small scales and how it influences the formation of galaxies. Interactions between galaxies also play a crucial role in the exchange of gas and the creation of new stars. Tidal forces can strip gas from dwarf galaxies, feeding the halos and disks of larger galaxies like the Milky Way. In turn, gravitational encounters can trigger bursts of star formation as gas clouds are compressed. Such processes are not rare or violent exceptions, but continuous acts of galactic recycling. Through these interactions, the local group remains alive and evolving, each galaxy influencing the others in subtle ways. Seen as a whole, the local group represents a microcosm of the universe's larger structure. Galaxies forming, merging, and reshaping each other under gravity's guidance. It is a reminder that galaxies are not isolated islands, but participants in a vast cosmic web, connected across space by invisible filaments of matter. The motions of the Milky Way, Andromeda, and their satellites reflect the same fundamental forces that sculpt clusters and superclusters across the cosmos. From a human perspective, this interconnectedness is both humbling and profound. The light that reaches our telescopes from Andromeda began its journey over 2 million years ago when early humans were first walking the Earth. The interactions that will one day unite our two galaxies are already written in their motions. We are witnessing the universe not as something frozen in time, but as an unfolding story. One chapter in an infinite sequence of creation and transformation. When you look at the night sky, some of the faintest smudges of light, the Magellanic clouds from the southern hemisphere, or the distant blur of Andromeda, are more than celestial ornaments. They are our neighbors, part of the same gravitational family that carries us through space. The distances between galaxies are enormous, but gravity binds them as firmly as the atoms within our bodies are bound by electromagnetic forces. Everything that exists is connected, from the stars in your sky to the galaxies beyond them. And in that realization lies something timeless. The Milky Way, the Andromeda Galaxy, and all their companions are engaged in an endless dance, moving, merging, and reshaping each other in slow cosmic rhythm. We are part of that dance, bound within the same web of gravity that holds the galaxies together. Though our lives occupy only a brief moment of this grand choreography, the motion continues, quiet and certain, carrying us forward through the universe. To understand our galactic neighbors is to glimpse our own future, and to see, perhaps, that even in the boundless dark, we are never truly alone. Chapter 9. The History and Evolution of the Milky Way. The Milky Way, like every galaxy in the universe, has not always existed in the form we see today. It is the result of more than 13 billion years of cosmic evolution, an immense story of gravity shaping matter, of stars forming and dying, and of countless collisions and mergers that gradually built the vast spiral we now call home. To understand the Milky Way's history is to trace the slow unfolding of cosmic structure from the aftermath of the Big Bang to the present moment, and to glimpse the processes that will continue shaping it long after we are gone. In the beginning, the universe was almost perfectly uniform. About 380,000 years after the Big Bang, matter and radiation decoupled, allowing light to travel freely through space. Tiny fluctuations in the density of matter, imprinted in that early radiation, served as the seeds of all future structure. Over time, under the influence of gravity, these slight irregularities grew, attracting more matter and forming the first dark matter halos. These invisible gravitational wells became the scaffolding for the first galaxies. The earliest stages of the Milky Way's formation began within one of these primordial halos. Cosmological simulations and observations suggest that small proto-galaxies, clumps of gas and dark matter, began to merge together around 13 billion years ago, just a few 100 million years after the first stars ignited. These small systems formed the first generation of stars, known as population 3 stars, made almost entirely of hydrogen and helium. They burned hot and lived briefly, exploding as supernovae that enriched their surroundings with heavier elements. Out of these enriched remnants, new generations of stars formed, creating the first building blocks of what would become the Milky Way. As these protogalaxies merged, they built a larger and more massive structure. The earliest core of the Milky Way likely resembled an irregular blob of gas and stars rather than a disk. Collisions between smaller systems were frequent and chaotic. Over time, as angular momentum accumulated from these interactions, the gas began to settle into a rotating disk, forming the foundation of the galaxy's current shape. The oldest stars we observe today in the halo and in globular clusters are relics from this early epoch. Their chemical compositions, poor in heavy elements, preserve the record of the galaxy's infancy. The Milky Way's growth did not stop once it acquired its basic form. Throughout its history, it has continued to merge with and absorb smaller galaxies. Astronomers can still see the remnants of these mergers today, long streams of stars stretched across the sky, the fossilized trails of ancient collisions. One of the most prominent of these is the Sagittarius stream, the remains of a dwarf galaxy currently being torn apart and assimilated by the Milky Way's gravity. Other faint stellar streams trace similar histories, each one a chapter in the ongoing story of galactic accretion. From about 10 billion years ago onward, the Milky Way entered a relatively stable phase. Its disk thickened as new stars formed, and its spiral structure began to emerge. This period saw intense star formation, fueled by abundant gas drawn in from the surrounding intergalactic medium. The galaxy's chemical composition grew richer with each generation of stars, as supernovae seeded the interstellar medium with carbon, oxygen, and iron. These elements would later become the building blocks for planets and eventually for life itself. The central bulge of the Milky Way, a dense concentration of older stars near the galactic core, also formed during this time. It likely arose through a combination of early mergers and internal evolution, as gas and stars were funneled inward by gravitational instabilities in the young disk. At its center, the supermassive black hole Sagittarius A star grew alongside the bulge, feeding intermittently on gas and smaller objects. The connection between black holes and galactic bulges is a pattern observed across the universe, an indication that the growth of galaxies and their central black holes are intimately linked. Over the next several billion years, the Milky Way's spiral arms became more pronounced. These arms are not fixed structures but density waves, regions where stars and gas bunch together as they orbit the galactic center. They act as engines of renewal, compressing interstellar clouds and triggering new bursts of star formation. The Orion Spur, where the Sun resides, is one such feature. The Sun itself formed about 4.5 billion years ago from a molecular cloud enriched by generations of previous stars. It was born in the midlife of the galaxy, inheriting a stable orbit in the disk and a chemical composition that reflects the Milky Way's long history of cosmic recycling. The present-day Milky Way is still evolving. Observations from the Gaia spacecraft reveal ripples and waves in the stellar disk, evidence of past interactions with satellite galaxies. These perturbations show that even now, the galaxy is not in perfect equilibrium. Streams of stars continue to flow into the halo, and the gravitational tug of the large and small Magellanic Clouds subtly distorts the Milky Way's outer regions. The galaxy remains an active participant in its cosmic environment, not a finished structure, but a living, changing system. Looking into the future, astronomers predict that the Milky Way's most dramatic transformation lies ahead. The Andromeda Galaxy, currently about 2.5 million light-years away, is moving toward us. In roughly 4 billion years, the two galaxies will collide. Their mutual gravity will tear apart their spiral arms, scattering stars and gas into vast tidal tails. Over the next several billion years, they will merge into a single, larger elliptical galaxy. The Sun, by then nearing the end of its life, will drift into a new orbit within that combined system. This merger will mark the next great chapter in the Milky Way's story, one written on timescales that dwarf the entire history of life on Earth. The Milky Way's evolution is not unique. It follows the same cosmic principles that govern all galaxies: formation through collapse and accretion, enrichment through stellar evolution, and transformation through interaction. Yet, because we live within it, we can study its structure and history in far greater detail than any other. Through observations of ancient stars, stellar streams, and the motions of gas, we can reconstruct the invisible steps of its growth. The Gaia mission, for instance, has allowed astronomers to map the precise orbits of more than 1 billion stars, revealing the fossil record of long-vanished galaxies absorbed by our own. Each star's chemistry and motion tell part of the story: where it was born, how it moved, and what it has endured. Some of the oldest known stars in the Milky Way are more than 13 billion years old, nearly as ancient as the universe itself. Their compositions show almost no heavy elements, suggesting they formed from the pristine gas left after the first supernova enriched the cosmos. These stars serve as time capsules from an era when the Milky Way was still assembling its first components. Their continued existence in the halo is a testament to the galaxy's longevity and the stability of its gravitational structure. Even the dark matter halo surrounding the Milky Way tells a story of history and evolution. It was the first part of the galaxy to take shape and remains the framework within which all visible matter resides. The halo's growth through mergers mirrors the assembly of the visible disk and bulge. In many ways, the Milky Way is the luminous face of a much larger invisible system that has evolved in parallel since the dawn of time. From the perspective of cosmic history, the Milky Way is now middle-aged. It has formed most of its stars, and its overall rate of star formation is declining. Over the next tens of billions of years, as gas supplies dwindle and stellar birth slows, the galaxy will gradually fade. Eventually, the remaining stars will age into white dwarfs, neutron stars, and black holes. The Milky Way will become a quiet, dim system, its bright spiral arms long gone. Yet even then, its structure will persist, a fossil of light in a universe growing ever colder and darker. To think of this timeline is to confront both immensity and intimacy. Our planet, our species, and everything we know occupy only a heartbeat of the Milky Way's existence. The atoms that make up your body were forged in stars that lived and died billions of years before the sun was born. You are part of a story that began long before human memory and will continue long after. When you look at the night sky, you are witnessing the latest frame of an ancient film still in motion. The light that reaches you tonight began its journey before our species existed, before civilization, before language. It carries within it the record of the Milky Way's evolution, of countless stars that lived and perished to make your world possible. And in that understanding lies both humility and wonder. The Milky Way's history is not merely the history of a distant structure, but the foundation of everything familiar. Its collisions, its stars, its invisible halo, all of it converge to create the conditions for life and consciousness to emerge. We are, in a sense, the galaxy reflecting on its own past. The same gravity that shaped its spiral arms also holds you here, beneath its starlit disk, thinking about where you came from. The Milky Way story is your story, a reminder that in the grand history of the universe, you have always been home. Chapter 10. The Meaning of Home. The Milky Way as a Mirror of Existence. When we speak of home, we usually mean something close, something familiar, a room, a city, a planet. Yet, on a cosmic scale, our true home extends far beyond the boundaries of Earth. The Milky Way is not just the galaxy that contains us. It is the context that gives our existence shape and meaning. Every atom in our bodies, every element that forms our world, and every beam of light that warms us belongs to this single, vast structure. To understand the Milky Way scientifically is to uncover the deep continuity between ourselves and the universe, to see that we are not merely living in the galaxy, but are of it. From a physical perspective, the Milky Way is a dynamic system, a rotating disk of hundreds of billions of stars, gas, and dust, all embedded within an even larger halo of dark matter. It is one of trillions of galaxies in the observable universe, and yet to us, it is unique, the galaxy through which we view all others. It has existed for more than 13 billion years, growing and changing as it merged with smaller systems and formed new generations of stars. In its present form, it stretches across more than 100,000 light years, a spiral of light and shadow turning endlessly in the dark. This structure is both ancient and alive, shaped by the same fundamental forces that govern the behavior of matter everywhere. The concept of home in this cosmic sense is not sentimental but structural. The Milky Way provides the gravitational environment that sustains our solar system's orbit. Without it, the Sun and its planets would not move in a coherent path. Earth would not experience the stable conditions necessary for life. The galaxy's dark matter halo holds the stars together, while its spiral arms continue to recycle gas and dust into new suns and worlds. Our planet is one of countless possible outcomes of this ongoing galactic metabolism. The light from the Milky Way that reaches our eyes on a clear night is a cross-section of this immense structure. It is the collective glow of stars scattered across tens of thousands of light years, their light blending into a silvery band that encircles the sky. What we see as a tranquil ribbon of light is, in fact, a momentary glimpse into a vast rotating system, a panorama of motion, birth, and decay. The serenity we perceive is the illusion of scale, the calm that comes from watching a process so immense that its movement unfolds over eons. Science allows us to see beyond this illusion. The Milky Way is not static, it is constantly changing. Stars form within cold molecular clouds, live their lives for millions or billions of years, and then die, enriching the galaxy with heavy elements. Supernovae blast shockwaves through interstellar space, compressing gas into new star-forming regions. Stellar winds carve bubbles in the surrounding medium, and gravitational tides draw streams of stars from nearby dwarf galaxies. Even the spiral arms are not fixed structures, but patterns of density waves, moving through the disk like ripples across a pond. The Milky Way is not a place but a process, a continuous flow of energy and matter through time. Humanity's understanding of this process has evolved dramatically in just a few centuries. For most of our history, the Milky Way was an enigma. Ancient civilizations saw it as a pathway for spirits or gods, a celestial river, or the spine of the night. Only in the early modern era did telescopes reveal that the faint glow was composed of countless stars. In the 20th century, astronomers discovered that the Milky Way itself was only one of many galaxies, and that all are receding from one another as the universe expands. With the advent of radio and infrared astronomy, we learned to peer through the dust, mapping the galaxy's spiral arms, its central bar, and the dense molecular clouds that give rise to new stars. Missions like Gaia now chart the precise motions of billions of stars, transforming our understanding of the Milky Way from a static picture into a dynamic, living model. From these observations, we know that the Sun and its planets are relatively young participants in the galaxy's long history. Our solar system formed about 4.5 billion years ago from a cloud of gas enriched by earlier generations of stars. The heavy elements that make up Earth's crust, oceans, and living creatures were forged in the hearts of those long-dead stars. Carbon, oxygen, iron, all were created in nuclear reactions that occurred billions of years before the solar system existed. In this sense, the Milky Way is our ancestor. Its cycles of creation and destruction are the direct cause of our existence. The Milky Way is also our frame of reference in space. When astronomers measure the position of any celestial object, they do so relative to the galactic plane. The galaxy provides the coordinates that define our orientation in the universe. Even our perception of the night sky, the constellations we draw, and the myths we create is shaped by our position within the disk. The stars that seem close together in constellations are, in reality, scattered across thousands of light years, their apparent patterns defined only by our viewpoint within this single galaxy. Yet the Milky Way is not permanent. Astronomical evidence shows that galaxies are transient entities constantly evolving. In a few billion years, the Milky Way will merge with the Andromeda Galaxy, forming a new, larger system. The spiral arms will be torn apart, the central black holes will merge, and the resulting galaxy will shine for trillions of years before its stars grow dim. Long after our sun has faded, the atoms that once formed Earth, and perhaps the remnants of whatever follows humanity, will still orbit within that future system. Even as forms change, the matter remains part of the unbroken continuum of the galaxy's existence. To call the Milky Way home is therefore not merely a statement of location but of identity. It defines the scale at which we belong to the universe. We are not separate from it, nor passengers within it. We are expressions of its ongoing processes. The iron in our blood was once in a star's core. The calcium in our bones was forged in a supernova. The atoms of our bodies have traveled through time and space, from the birth of the galaxy to the formation of the Earth, and will continue their journey long after we are gone. The Milky Way is both the cradle and the grave of matter, the setting in which consciousness, for a brief moment, became aware of itself. The notion of home also carries emotional weight, even in scientific terms. In astronomy, the Milky Way serves as a baseline for understanding other galaxies. Every observation of distant systems, spiral, elliptical, or irregular, is interpreted through comparison to our own. By studying the Milky Way, we calibrate our understanding of the universe. The patterns we find here, of star formation, chemical evolution, and gravitational interaction, echo throughout the cosmos. Our home galaxy is both unique in its details and universal in its principles. It is a mirror in which the universe reflects its own structure and history. In philosophical terms, the Milky Way embodies the paradox of existence. We are tiny and temporary, yet made of the same materials and governed by the same laws as the stars. The distances that separate us from other systems are immense, but the physics that connects us is universal. The galaxy's light stretching across the sky is a visible symbol of that unity. Countless suns bound together by gravity, moving in harmony through the darkness.